AWS Redshift Migration Failures and Fixes. Part 2. The Point of No Return.
By the time a migration reaches this phase, rollback is no longer a technical discussion. It is a historical fact. Part 2 focuses on incidents where the rollback contract has already been broken, sometimes quietly, sometimes legally, sometimes irreversibly. These failures occur after authority has leaked beyond engineering control, external systems have consumed corrupted state, or system history can no longer be reconstructed. At this stage, teams are no longer choosing between rollback and forward fix. They are choosing how to contain damage, restore trust, and survive the aftermath.
Part 2. Categories and Scenarios.
Part 1 covered the illusion of safety. Part 2 covers the reality of failure. The following categories document incidents where rollback is provably dead, and only containment and forward fix remain.
Part 2. Roadmap. Categories 6 to 15.
We begin with the structural and mechanical failures that prevent recovery. Category 6, rollback execution incidents, 12 scenarios. Category 7, no rollback point of no return incidents, 7 scenarios. Category 8, schema, contract, and identity transition incidents, 7 scenarios. Category 9, downstream materialization and cache incidents, 5 scenarios. Category 10, physical storage and execution semantics incidents, 5 scenarios. Category 11, Redshift transaction semantics and copy edge cases, 3 scenarios. Category 12, late consumer and shadow access incidents, 3 scenarios. Category 13, observability and state reconstruction failures, 3 scenarios. Category 14, semantic drift and business meaning incidents, 3 scenarios. Category 15, Redshift lakehouse and spectrum dependencies, 5 scenarios.
Part 2. Roadmap. Categories 16 to 24.
We conclude with the advanced data integrity, security, and next-gen architecture failures. Category 16, identity, surrogate key, and sequence failures, 4 scenarios. Category 17, Redshift serverless and auto-scaling edge cases, 6 scenarios. Category 18, collation and string sensitivity incidents, 5 scenarios. Category 19, write-ahead logging / commit visibility drift, 4 scenarios. Category 20, reprocessing idempotency failures, 4 scenarios. Category 21, cross-system referential integrity breaks, 4 scenarios. Category 22, human-initiated emergency fixes, 4 scenarios. Category 23, security and access rollback drift incidents, 4 scenarios. Category 24, modern Redshift architecture and native integration failures, 4 scenarios. Let's dive into Category 6, rollback execution incidents, by doing Category 5 wrap-up.
Part 2. Promise.
Part 2 is not about how to migrate. It is about what happens after rollback is gone, and why pretending otherwise causes more damage than admitting the truth and fixing forward.
Category 5. Wrap-up. When validation lies.
Validation blind spot incidents are dangerous because they do not look like failures. Systems appear healthy, dashboards show expected numbers, and confidence grows at exactly the wrong time. These incidents push teams past rollback boundaries silently because validation success is mistaken for system correctness.
Transition from false safety to failed rollbacks.
Once validation gives false confidence, teams act on that belief. Rollback plans are delayed, shortcuts are taken, and boundaries are crossed without being acknowledged. In the next category, we examine incidents where rollback still exists in theory, but fails in practice due to state changes, pressure, or missed execution details.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs in a single zip file, containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, system design. Required for your data engineer interviews jobs like data quality analyst jobs, data governance analyst jobs, AWS Python data engineer jobs, AWS Redshift database administrator DBA jobs, AWS Glue ETL developer jobs, AWS data engineer jobs, cloud data engineer jobs, data architect jobs, DataOps engineer jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based questions and answers, real-world problem solving. Interview questions and answers where almost 80% of the people are failing to answer. System design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section. These questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people also for your interviews. You people can download all 6 PDFs in a single zip file from below given links.
Category 6. Rollback Execution Incidents.
This category focuses on failures where rollback is technically defined but operationally impossible. Snapshots exist but are unusable, pipelines are corrupted mid-rollback, or organizational constraints block execution. These incidents show that rollback is not a button, but a fragile system operation that can fail under real-world conditions.
Rollback Execution Scenarios.
The following incidents demonstrate how rollback boundaries are crossed silently during Redshift migration. 1. No clean restore point available. 2. Source data changed after cutover. 3. Redshift already accepted writes. 4. Downstream systems already consuming Redshift. 5. Partial rollback only at domain level. 6. CDC streams corrupted during rollback. 7. No automated rollback process. 8. Rollback violates audit or compliance rules. 9. Business refuses downtime. 10. Silent resize or upgrade failures during rollback. 11. WLM queue starvation blocks rollback scripts. 12. Auto WLM rebalancing interferes with rollback execution. Rollback fails not when it is designed, but when it is executed under pressure.
Real-world incident during source to Redshift migration 41. No clean restore point available after cutover.
During an AWS Redshift migration, teams assumed rollback safety based on the existence of snapshots. However, no snapshot existed that aligned with the actual cutover boundary. By the time rollback was considered, all available snapshots already contained post-cutover changes, making rollback theoretically possible but practically meaningless. Failure class, rollback execution incidents.
System state before failure, very important.
At the moment rollback was needed, the system state was 1. Source system writes enabled and continuing to mutate business state. 2. Redshift cluster live and actively queried after cutover. 3. Snapshot strategy automated snapshots enabled but not aligned to cutover. 4. CDC pipeline either paused or already advanced beyond cutover boundary. 5. BI tools actively publishing Redshift-derived results. 6. Declared source of truth, implicitly Redshift after cutover. 7. Authority status, assumed recoverable without validating restore boundaries. Snapshots without cutover alignment are operational backups, not rollback points.
Incident analysis and root cause.
This failure resulted from a false rollback assumption. 1. Triggering action proceeding with cutover without taking a dedicated labeled rollback snapshot. 2. Why it appeared safe, automated snapshots existed and gave a false sense of recoverability. 3. What teams noticed first, rollback planning revealed no snapshot representing pre-cutover state. 4. What teams did not notice that every snapshot already included post-cutover mutations. 5. How divergence accumulated, business activity continued while snapshot history silently moved forward. 6. Missing invariant, a rollback snapshot must be explicitly captured at the authority transition point.
Why this failure is dangerous, hidden risk.
This failure is dangerous because rollback appears available on paper. Snapshots exist, restore operations succeed, and tooling reports success. The danger is semantic. Restoring any snapshot reproduces an already corrupted authority state. Detection latency is often hours or days, discovered only when rollback is attempted under pressure.
What exactly broke? Consistency breakdown.
Authority and temporal consistency are broken. There is no snapshot that represents the last known good authoritative state. If we roll back only data, this inconsistency remains because authority already shifted before any recoverable snapshot was taken.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate 1. Is there a snapshot taken immediately before cutover? No boundary missing. 2. Do existing snapshots predate authority transfer? No, all include post-cutover state. 3. Has Redshift already served authoritative reads? Yes, trust impact exists. 4. Has source data changed since cutover? Yes, divergence ongoing. 5. Can authority be restored cleanly? No, no clean restore point. Rollback without a clean boundary only recreates the same failure.
Decision point, rollback versus forward fix.
Rollback is not viable because no snapshot represents a clean pre-cut over authority state. Forward fix becomes the only option, focused on accepting the new authority, reconciling inconsistencies, and rebuilding trust explicitly rather than pretending rollback exists.
Rollback architecture, if executed.
A true rollback would have required restoring a snapshot captured immediately before cutover, discarding all post-cutover CDC state, repointing BI systems back to the source, invalidating downstream artifacts, and obtaining governance approval. In this incident, none of these steps are possible because the required snapshot does not exist.
Code illustration and Redshift artifacts.
In this section, we will show 1. How snapshot timelines prove no clean restore point exists. 2. Why restoring any available snapshot recreates post-cutover state. Snapshots must align with authority transitions to be meaningful. Here is Redshift SQL showing snapshot timelines relative to cutover. Disclaimer: always test code in a non-production environment. Comparing snapshot times with the cutover timestamp proves that no snapshot exists representing the last authoritative pre-cutover state.
Containment and forward fix strategy.
Once rollback is ruled out, containment must precede repair. 1. Formally declare Redshift authoritative to stop ambiguity. 2. Invalidate or annotate all early post-cutover reports. 3. Reconcile critical datasets against the source where possible. 4. Document the irreversible boundary for audit and governance. 5. Establish mandatory rollback snapshot policies for future migrations. Forward fix begins with authority clarity, not data repair.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Explain that rollback safety depends on snapshot timing, not snapshot existence. 2. Describe how authority transitions must be explicitly guarded by restore points. 3. Clarify why restoring a snapshot can succeed technically but fail semantically. 4. Emphasize that rollback boundaries must be validated before cutover, not after. A rollback snapshot is not a backup. It is an explicit authority checkpoint, and without it, rollback never truly existed.
Follow-up 1. Why didn't snapshots protect rollback here?
Answer: because snapshots were taken after authority had already shifted. They preserved data state but not the authoritative boundary. Rollback requires restoring both data and authority, not just bytes on disk.
Follow-up 2. When did rollback stop being possible?
Answer: rollback stopped being possible the moment cutover occurred without a dedicated pre-cutover snapshot. From that point onward, every snapshot encoded the new authority state.
Follow-up 3. What single control would have prevented this?
Answer: a mandatory, labeled rollback snapshot captured immediately before cutover, with cutover blocked if snapshot verification failed.
Pro insider tip.
If you cannot point to the exact snapshot that represents the last authoritative moment before cutover, rollback is already fiction, regardless of how many snapshots exist.
Real-world incident during source to Redshift migration 42. Source data changed after cutover.
During an AWS Redshift migration, a cutover decision was executed assuming the source system would remain quiescent. However, after BI and downstream systems were repointed to Redshift, the source system continued to accept writes. This caused the source and Redshift to diverge immediately, making rollback incapable of restoring a single authoritative truth. Failure class: rollback execution incidents.
System state before failure, very important.
At the moment divergence occurred, the system state was 1. Source system write enabled and continuing to process business transactions. 2. Redshift cluster declared authoritative for analytics after cutover. 3. CDC pipeline paused, lagging, or no longer considered authoritative. 4. BI tools fully repointed to Redshift and publishing results. 5. Downstream systems consuming Redshift-derived data. 6. Declared source of truth. Redshift after cutover. 7. Authority status violated by continued source writes. A cutover without enforcing write freeze is not a cutover.
Incident analysis and root cause.
This failure resulted from a broken authority assumption. 1. Triggering action executing cutover while leaving the source system writes enabled. 2. Why it appeared safe, teams assumed operational writes had ceased or were irrelevant post-cutover. 3. What teams noticed first, mismatches between operational records and Redshift analytics. 4. What teams did not notice, that source mutations immediately invalidated Redshift authority. 5. How divergence accumulated, each new source write created business facts absent from Redshift. 6. Missing invariant after cutover, exactly one system must be allowed to accept writes.
Why this failure is dangerous, hidden risk.
This failure is dangerous because both systems remain operational and appear healthy. No alarms fire, and CDC metrics may look irrelevant or green. The damage is semantic. Business truth splits instantly. Detection latency is often days, discovered only during reconciliation or customer impact investigations.
What exactly broke? Consistency breakdown.
Authoritative and domain-level consistency are broken. Redshift and the source describe different versions of reality. If we roll back only data, this inconsistency remains because business events occurred exclusively in the source after authority had already shifted.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Did the source accept writes after cutover? Yes, divergence exists. 2. Are post-cutover source changes present in Redshift? No missing facts. 3. Can those changes be deterministically replayed? No, authority unclear. 4. Have downstream systems consumed Redshift data? Yes, trust already shifted. 5. Can authority be restored cleanly? No, competing truths exist. Rollback cannot reconcile two independently evolving realities.
Decision point, rollback versus forward fix.
Rollback is not viable because restoring any snapshot only reproduces one side of the divergence. Forward fix is required, starting with authority enforcement, reconciliation planning, and explicit acknowledgement of the divergence window.
Rollback architecture, if executed.
A theoretical rollback would require restoring a pre-cutover snapshot, replaying all post-cutover source writes with perfect ordering, repointing BI systems, invalidating downstream data, and obtaining governance approval. In this scenario, rollback is not executed because post-cutover source writes cannot be replayed without reintroducing authority ambiguity.
Code illustration and Redshift artifacts.
In this section, we will show 1. How source and Redshift divergence is proven via record comparison. One proof of divergence is sufficient to invalidate rollback. Here is Redshift SQL showing divergence after cutover compared to source. Disclaimer: always test code in a non-production environment. Comparing this timestamp with the source system proves that newer business events exist only in the source, confirming post-cutover divergence.
Containment and forward fix strategy.
Once post-cutover source writes are confirmed, containment must precede repair. 1. Immediately freeze source writes or formally deprecate the source. 2. Declare Redshift authoritative and document the divergence window. 3. Assess business impact of missing post-cutover source events. 4. Manually reconcile or re-ingest critical records where possible. 5. Enforce hard write invariants before any future cutover. Authority must be enforced before data can be trusted.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Explain that cutover without a write freeze creates immediate split brain. 2. Describe why rollback cannot reconcile independently written facts. 3. Clarify that authority loss is instantaneous once dual writers exist. 4. Emphasize governance and invariance over tooling. After cutover, write authority must be exclusive or truth fragments immediately.
Follow-up 1. Why can't rollback fix this divergence?
Answer: because rollback can restore data state but not reassign authority retroactively. Business events that occurred only in the source cannot be reconciled without creating another split brain.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe the moment the first post-cutover write landed in the source system. From that point on, two conflicting truths existed.
Follow-up 3. What single control would have prevented this?
Answer: a hard write freeze or enforced single writer invariant at the exact moment of cutover.
Pro insider tip.
If you allow even one post cut over write in the old system, rollback is no longer a recovery option. It becomes a historical rewrite attempt.
Real-world incident during source to Redshift migration 43. Redshift accepted writes after cutover.
During an AWS Redshift migration, the target cluster began accepting direct application or downstream writes after cutover. This occurred before rollback viability was fully assessed. Once Redshift accepted writes, restoring any prior snapshot would discard valid business events, permanently breaking clean rollback semantics. Failure class, rollback execution incidents.
System state before failure, very important.
At the moment rollback safety was lost, the system state was 1. Source system still available but no longer authoritative post-cutover. 2. Redshift cluster write enabled and accepting application or downstream writes. 3. CDC pipeline paused, repurposed, or irrelevant after write enablement. 4. BI tools reading and publishing data from Redshift. 5. Downstream systems persisting Redshift-derived data. 6. Declared source of truth. Redshift. 7. Authority status locked to Redshift by write acceptance. The first accepted write defines the point of no return.
Incident analysis and root cause.
This failure occurred due to an irreversible authority transition. 1. Triggering action enabling writes on Redshift before rollback boundaries were finalized. 2. Why it appeared safe, writes were perceived as low volume or compensatable. 3. What teams noticed first, concerns about snapshot restores discarding recent data. 4. What teams did not notice, that write acceptance alone invalidates rollback guarantees. 5. How divergence accumulated. New business facts existed only in Redshift post-write enablement. 6. Missing invariant, rollback must be evaluated and approved before the target accepts writes.
Why this failure is dangerous, hidden risk.
This failure is dangerous because systems continue operating normally. No replication errors occur, dashboards remain green, and performance may even improve. The damage is contractual. Rollback semantics are broken the instant Redshift accepts writes. Detection latency is often short, but recovery options vanish immediately.
What exactly broke? Consistency breakdown.
Authoritative and transactional consistency are broken. Redshift now contains original business events that do not exist in any prior snapshot. If we roll back only data, this inconsistency remains because valid post-cutover writes would be discarded, destroying business truth.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Has Redshift accepted writes? Yes, rollback semantics broken. 2. Are post-write Redshift records present elsewhere? No single copy. 3. Would snapshot restore discard valid data? Yes, data loss guaranteed. 4. Have downstream systems consumed these writes? Likely. 5. Can authority be reverted cleanly? No, target already authoritative. Once the target accepts writes, rollback becomes destructive by definition.
Decision point, rollback versus forward fix.
Rollback is no longer viable because it would destroy valid business data written directly to Redshift. Forward fix is mandatory, focused on stabilizing authority, reconciling any pre-write inconsistencies, and enforcing strict write governance going forward.
Rollback architecture, if executed.
A theoretical rollback would require snapshot restoration, discarding all post-cutover Redshift writes, repointing BI systems, invalidating downstream data, and obtaining governance approval for data loss. In this scenario, rollback is not executed because it would irreversibly delete authoritative business events.
Code illustration and Redshift artifacts.
In this section, we will show 1. How post-cutover writes in Redshift can be detected via system metadata. Write detection alone is sufficient to invalidate rollback. Here is Redshift SQL showing post-cut over write activity in the target. Disclaimer: always test code in a non-production environment. This snippet proves that new records were written directly into Redshift after cutover. Any snapshot restore would delete these records, making rollback unsafe.
Containment and forward fix strategy.
Once Redshift write acceptance is confirmed, containment must precede repair. 1. Immediately freeze further schema or write path changes. 2. Declare Redshift permanently authoritative. 3. Audit and reconcile any data written during the transition window. 4. Invalidate any pre-write validation assumptions. 5. Enforce strict preconditions before allowing writes in future migrations. Write authority must follow governance, not convenience.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Explain that accepting writes is the irreversible cutover event. 2. Describe why rollback becomes destructive after write enablement. 3. Clarify that snapshots protect data, not authority. 4. Emphasize governance gates before enabling writes. Write enablement defines authority and permanently closes the rollback window.
Follow-up 1. Why is a single write enough to block rollback?
Answer: because that write represents a business event that exists only in the target. Restoring a snapshot would delete it, violating data integrity and trust.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe at the exact moment the first write was committed in Redshift. From that point on, rollback implies data loss.
Follow-up 3. What single control would have prevented this?
Answer: a hard rule that Redshift must remain read-only until rollback viability is formally signed off.
Pro insider tip.
If Redshift has accepted even one real business write, stop discussing rollback. You are already in forward fix territory.
Real-world incident during source to Redshift migration 44. Downstream systems already consuming Redshift.
During an AWS Redshift migration, downstream systems such as reporting services, data products, or external consumers began consuming Redshift data before rollback viability was formally closed. Although Redshift itself had not accepted application rights, the act of downstream materialization irreversibly propagated Redshift state, silently crossing the rollback boundary. Failure class: rollback execution incidents.
System state before failure, very important.
At the moment rollback safety was lost, the system state was: 1. Source system still intact but no longer the sole consumer-facing system. 2. Redshift cluster read-only for applications actively queried by consumers. 3. CDC pipeline running or paused no longer decisive for rollback safety. 4. Downstream systems persisting Redshift-derived data into their own stores. 5. BI and analytics, publishing results externally based on Redshift. 6. Declared source of truth, implicitly Redshift for consumers. 7. Authority status, leaked through downstream consumption. Authority is lost when data leaves the system boundary.
Incident analysis and root cause.
This failure occurred due to an ungoverned consumption boundary. 1. Triggering action allowing downstream systems to consume Redshift data during validation. 2. Why it appeared safe, Redshift itself was read-only and no errors were observed. 3. What teams noticed first, difficulty explaining why rollback would invalidate downstream outputs. 4. What teams did not notice, that consumption itself creates irreversible state outside Redshift. 5. How divergence accumulated, downstream systems cached, transformed, or persisted Redshift data. 6. Missing invariant, no downstream system may consume target data before rollback is closed.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it is invisible inside Redshift. No writes occur, no replication breaks, and validation appears controlled. The damage happens externally, where Redshift-derived data becomes embedded into other systems. Detection latency is often days or weeks, discovered only when rollback is proposed.
What exactly broke? Consistency breakdown.
Authoritative and domain-level consistency are broken. Multiple systems now hold versions of Redshift-derived truth. If we roll back only data, this inconsistency remains because downstream systems will continue to reflect a state that no longer exists.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Have downstream systems persisted Redshift data? Yes, authority leaked. 2. Can downstream state be fully invalidated? Rarely, high coordination cost. 3. Are consumers aware of rollback semantics? Often no. 4. Would rollback create conflicting truths across systems? Yes, guaranteed. 5. Can authority be re-established cleanly? No, consumption already occurred. Once data is consumed downstream, rollback becomes organizationally impossible.
Decision point, rollback versus forward fix.
Rollback is no longer viable because downstream systems have already materialized Redshift state. Forward fix is mandatory, focused on stabilizing Redshift as authoritative and reconciling downstream dependencies. rather than attempting reversal.
Rollback architecture, if executed.
A theoretical rollback would require restoring a prior snapshot, invalidating all downstream datasets, forcing coordinated consumer resets, and obtaining governance approval for widespread data invalidation. In practice, rollback is not executed because downstream state cannot be reliably or fully unwound.
Containment and forward fix strategy.
Once downstream consumption is confirmed, containment must precede repair. 1. Formally declare Redshift authoritative for all consumers. 2. Freeze further schema or semantic changes during stabilization. 3. Inventory all downstream systems consuming Redshift data. 4. Reconcile or rebaseline downstream datasets explicitly. 5. Introduce strict consumption gates for future migrations. Consumption must be governed as strictly as writes.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Explain that rollback boundaries include consumers, not just databases. 2. Describe how downstream persistence makes rollback unsafe even without writes. 3. Emphasize that authority leaks when data leaves system control. 4. Highlight governance failures as the root cause. Rollback safety depends on controlling both data mutation and data consumption.
Follow-up 1. Why doesn't read-only Redshift guarantee rollback safety?
Answer: because rollback safety is broken when downstream systems persist what they read. Even without writes, data leaving Redshift creates irreversible state elsewhere.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe the moment the first downstream system persisted Redshift-derived data. From that point on, multiple truths existed.
Follow-up 3. What single control would have prevented this?
Answer: a hard rule that no downstream consumption is allowed until rollback is formally closed and authority is declared.
Pro insider tip.
If another system has copied your data, you no longer control rollback. You only control damage.
Real-world incident during source to Redshift migration 45. Partial rollback executed at domain level only.
During an AWS Redshift migration, rollback was attempted only for a subset of domains after inconsistencies were detected. Other domains were left untouched because they appeared stable or were already consumed downstream. This created a fragmented rollback state where parts of the system reflected pre-cut over truth while others reflected post-cut over reality. Failure class: rollback execution incidents.
System state before failure, very important.
At the moment the rollback boundary was crossed, the system state was: 1. Source system still available but no longer uniformly authoritative. 2. Redshift cluster partially restored using domain-scoped rollback. 3. Affected domains restored to pre-cut over snapshot state. 4. Unaffected domains continued operating on post-cut over data. 5. CDC pipeline paused or inconsistently reconfigured per domain. 6. BI and downstream systems consuming mixed domain state. 7. Authority status fragmented by domain. Rollback applied selectively creates multiple competing truths.
Incident analysis and root cause.
This failure resulted from an invalid rollback assumption. 1. Triggering action rolling back only selected domains that showed visible corruption. 2. Why it appeared safe affected domains were logically isolated and easier to restore. 3. What teams noticed first cross-domain reports began producing inconsistent results. 4. What teams did not notice that interdomain dependencies invalidate partial rollback. 5. How divergence accumulated. Restored domains rejoined with non-restored domains. 6. Missing invariant, rollback scope must match authority scope.
Why this failure is dangerous, hidden risk.
This failure is dangerous because each domain appears internally consistent. Validation passes within domains, masking the fact that joins across domains now combine incompatible timelines. Detection latency is often days, surfacing only when ecosystem-level analytics are reviewed.
What exactly broke? Consistency breakdown.
Domain-level and referential consistency are broken. Some domains reflect pre-cut over truth, while others reflect post-cut over truth. If we roll back only data, this inconsistency remains because authority was restored selectively rather than globally.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Was rollback applied uniformly across all domains? No partial rollback. 2. Do domains participate in cross-domain joins? Yes, inconsistency guaranteed. 3. Can non-rollback domains be safely restored? Often no. 4. Have consumers already seen mixed domain outputs? Likely. 5. Can authority be re-established cleanly? No, fragmented state persists. Partial rollback creates permanent analytical ambiguity.
Decision point, rollback versus forward fix.
Rollback is no longer viable because it was already executed partially. Forward fix becomes mandatory, focusing on reconciling domain timelines and reasserting a single authoritative state rather than attempting further rollback.
Rollback architecture, if executed.
A correct rollback would have required restoring the entire Redshift cluster from a single snapshot, discarding all post-cutover data uniformly, rewinding or discarding CDC offsets globally, repointing all BI and downstream systems, and obtaining governance approval for full data invalidation. Domain-scoped rollback violates the requirement that rollback must be fully destructive or fully reversible.
Code illustration and Redshift artifacts.
In this section, we will show 1. How row counts differ between rolled back and non-rolled back domains. 2. How cross-domain joins expose incompatible timelines. Domain isolation must be proven before domain-level rollback. Here is Redshift SQL showing inconsistent timelines across partially rolled back domains. Disclaimer: always test code in a non-production environment. This condition proves that one domain reflects a newer timeline than another. The mismatch is direct evidence that rollback was applied unevenly across domains.
Containment and forward fix strategy.
Once partial rollback is detected, containment must precede repair. 1. Immediately declare Redshift authoritative despite known inconsistencies. 2. Freeze further rollback or domain-level restores. 3. Inventory cross-domain dependencies explicitly. 4. Reconcile domains to a single agreed timeline. 5. Revalidate all cross-domain analytics before restoring trust. Authority must be restored globally or not at all.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Explain why rollback scope must match system authority scope. 2. Describe how partial rollback creates incompatible timelines. 3. Highlight cross-domain joins as the failure amplifier. 4. Emphasize governance decisions over technical execution. Rollback must be atomic at the authority boundary, not convenient at the domain boundary.
Follow-up 1. Why did partial rollback appear attractive?
Answer: because restoring fewer domains felt faster and safer. However, this ignored the fact that domains are not independent once joined in analytics, making partial rollback structurally unsafe.
Follow-up 2. When did rollback stop being viable?
Answer: rollback stopped being viable the moment only some domains were restored. From that point on, no single snapshot could represent system truth.
Follow-up 3. What single rule would have prevented this?
Answer: enforcing a rule that rollback must always be cluster-wide, unless strict domain isolation is formally proven.
Pro insider tip.
If rollback is scoped smaller than authority, you have not rolled back, you have forked reality.
Real-world incident during source to Redshift migration 46. CDC streams corrupted during rollback execution.
During an AWS Redshift migration, rollback was initiated after data inconsistencies were detected. While the Redshift cluster was restored from snapshot, CDC replication tasks were restarted without fully resetting or discarding their prior state. This caused CDC streams to apply changes against a rolled-back target using contaminated offsets, silently reintroducing corruption. Failure class: rollback execution incidents.
System state before failure, very important.
At the moment rollback was attempted, the system state was 1. Source system write-enabled and continuing to generate changes. 2. Redshift cluster restored from a pre-cutover snapshot. 3. CDC pipeline restarted using pre-rollback task state. 4. CDC offsets advanced beyond snapshot restore point. 5. BI and downstream systems temporarily disabled or repointed. 6. Declared source of truth, intended to revert to source. 7. Authority status, assumed reset without validating CDC state. Rollback of data without rollback of CDC state creates replay contamination.
Incident analysis and root cause.
This failure resulted from a partial rollback of migration state. 1. triggering action, restoring Redshift from snapshot while reusing existing CDC tasks. 2. Why it appeared safe, the snapshot restore completed successfully and CDC restarted cleanly. 3. What teams noticed first, re-emergence of previously corrected data anomalies. 4. What teams did not notice that CDC offsets no longer aligned with restored target state. 5. How divergence accumulated, CDC applied changes assuming a later target timeline. 6. Missing invariant, CDC offsets must be reset or discarded whenever the target is restored.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it invalidates rollback silently. The system appears restored, CDC appears healthy, and replication resumes. In reality, CDC is replaying changes relative to a state that no longer exists. Detection latency is often days, surfacing only when inconsistencies reappear after rollback.
What exactly broke? Consistency breakdown.
Transactional and temporal consistency are broken. CDC reintroduces post-cutover changes into a pre-cutover snapshot. If we roll back only data, this inconsistency remains because CDC state still encodes the post-rollback timeline.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Was the Redshift cluster restored from snapshot? Yes, data reset. 2. Were CDC offsets reset or discarded? No, state reused. 3. Do CDC offsets predate the restored snapshot? No, misaligned. 4. Can CDC replay be trusted after restore? No, contaminated. 5. Can authority be restored cleanly? No, CDC state invalid. CDC state is part of system truth, not an implementation detail.
Decision point, rollback versus forward fix.
Rollback is no longer clean because CDC has already reintroduced corrupted state into the restored cluster. Forward fix must focus on discarding CDC history, rebaselining replication, and reasserting authority explicitly.
Rollback architecture, if executed.
A correct rollback would have required restoring the Redshift cluster from snapshot, discarding all CDC tasks, recreating replication from a new baseline, invalidating downstream caches, and obtaining governance approval for full data reset. Reusing CDC state after restore violates the requirement that rollback must reset all stateful components.
Code illustration and Redshift artifacts.
In this section, we will show 1. How CDC task state exposes advanced offsets after rollback. 2. How misaligned offsets prove rollback contamination. CDC offsets must align with the restored target timeline. Here is Bodo 3 showing CDC task state after rollback revealing offset contamination. Disclaimer: always test code in a non-production environment. This output exposes CDC offsets that advance beyond the restored snapshot boundary. This proves that CDC state was not reset and is incompatible with the rolled back target.
Containment and forward fix strategy.
Once CDC contamination is confirmed, containment must proceed repair. 1. Immediately stop all CDC replication tasks. 2. Discard existing CDC state and replication history. 3. Rebaseline replication from a known good snapshot. 4. Re-enable CDC only after offset alignment is verified. 5. Revalidate downstream systems before restoring access. Replication state must be rebuilt whenever data state is rebuilt.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Explain why CDC state is part of rollback scope. 2. Describe how restoring data without resetting CDC corrupts rollback. 3. Highlight offset alignment as a hard invariant. 4. Emphasize that rollback resets systems, not just databases. Stateful replication components must be rolled back together with data to preserve authority.
Follow-up 1. Why did CDC restart appear successful?
Answer: because from the tool's perspective, the task resumed normally. The failure is logical, not operational, so no errors or alarms were triggered even though offsets were invalid.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe the moment CDC was restarted without resetting offsets. From that point on, restored data was immediately contaminated again.
Follow-up 3. What single rule would have prevented this?
Answer: enforcing a rule that any data restore requires CDC tasks to be destroyed, and recreated from a clean baseline.
Pro insider tip.
If CDC survives a rollback, the rollback didn't actually happen. Only the database did.
Real-world incident during source to Redshift migration 47. No automated rollback process available.
During an AWS Redshift migration, a critical data inconsistency was detected shortly after cutover. Although a theoretical rollback plan existed, no automated or rehearsed rollback process was available. Manual steps were debated, delayed, and partially executed, allowing the system to drift further while decisions were pending. Failure class, rollback execution incidents.
System state before failure, very important.
At the moment rollback was discussed, the system state was 1. Source system write-enabled and continuing normal operations. 2. Redshift cluster live and serving analytical workload. 3. CDC pipeline actively replicating post-cutover changes. 4. Rollback tooling manual undocumented and untested. 5. BI and downstream systems consuming Redshift outputs. 6. Declared source of truth Redshift by default, not by decision. 7. Authority status ambiguous due to rollback indecision. Rollback without automation becomes a debate, not an action.
Incident analysis and root cause.
This failure was caused by the absence of executable rollback capability. 1. Triggering action, detecting a post-cutover data inconsistency without a runnable rollback plan. 2. Why it appeared safe, teams assumed rollback could be assembled manually if needed. 3. What teams noticed first, escalating confusion about who could approve and execute rollback. 4. What teams did not notice, that each hour of delay materially reduced rollback viability. 5. How divergence accumulated, CDC continued applying changes while rollback discussions stalled. 6. Missing invariant, rollback must be executable within a bounded time window, not just documented.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it converts rollback from a safety mechanism into a theoretical comfort. As time passes, downstream consumption grows, CDC advances, and authority silently shifts. Detection latency is measured not in errors, but in indecision.
What exactly broke? Consistency breakdown.
Authority and rollback consistency are broken. There is no longer a clear moment at which the system can be safely reset. If we roll back only data, this inconsistency remains because authority has already shifted through continued use and reliance.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Is there an automated rollback runbook? No, manual only. 2. Can rollback be executed within minutes or hours? No, unclear. 3. Has CDC continued advancing? Yes, boundary shifting. 4. Have downstream systems consumed Redshift data? Yes, ongoing. 5. Can authority be restored cleanly? No, delay-induced erosion. Rollback delayed is rollback denied.
Decision point, rollback versus forward fix.
Rollback is theoretically possible but practically unsafe due to delay, ambiguity, and ongoing consumption. Forward fix becomes the only viable path once rollback execution time exceeds the authority tolerance window.
Rollback architecture, if executed.
A valid rollback architecture would have required a pre-approved snapshot restore procedure, immediate CDC shutdown, downstream access revocation, cache invalidation, and governance sign-off within a defined SLA. Without automation, these steps could not be executed cohesively or safely.
Containment and forward fix strategy.
Once rollback delay is confirmed, containment must precede repair. 1. Formally declare rollback no longer viable. 2. Freeze further scope expansion and ad hoc fixes. 3. Declare a single authoritative system explicitly. 4. Repair data inconsistencies through controlled forward fix. 5. Implement automated rollback for future migrations. Forward fix is safer than a delayed rollback.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Rollback must be executable, not aspirational. 2. Automation defines rollback viability, not intent. 3. Delay is a form of silent cutover. 4. Authority shifts while teams debate. Rollback must be automated and rehearsed or it does not exist.
Follow-up 1. Why didn't teams just roll back manually?
Answer: because manual rollback requires coordination across systems, approvals, and timing. By the time alignment was achieved, Rollback conditions were already violated.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe once CDC continued running while decisions were pending. At that point, authority and data state diverged irreversibly.
Follow-up 3. What single change would have prevented this?
Answer: a fully automated rollback pipeline with a defined execution SLA and pre-approved governance.
Pro insider tip.
If rollback cannot be executed faster than data is consumed, it is already obsolete.
Real-world incident during source to Redshift migration 48. Rollback violates audit or compliance rules.
During an AWS Redshift migration, a critical data issue was identified after cutover. While a technical rollback path existed via snapshot restore, compliance and audit teams determined that restoring historical snapshots would violate regulatory requirements, audit immutability guarantees, or data retention laws. As a result, rollback was legally blocked. Failure class: rollback execution incidents.
System state before failure, very important.
At the moment rollback was evaluated, the system state was: 1. Source system rights-enabled and continuing regulated operations. 2. Redshift cluster serving analytics and compliance-relevant reporting. 3. CDC pipeline actively replicating post-cutover changes. 4. Snapshots available but not legally restorable. 5. BI and downstream systems using Redshift data for decision-making. 6. Declared source of truth: Redshift by regulatory designation. 7. Authority status: legally enforced, not technically reversible. Compliance constraints override technical rollback capability.
Incident analysis and root cause.
This failure resulted from a mismatch between technical rollback plans and regulatory reality. 1. Triggering action discovering post-cutover data issues that would normally warrant rollback. 2. Why it appeared safe, engineers assumed snapshot restore was always an option. 3. What teams noticed first, audit and compliance teams immediately blocked rollback execution. 4. What teams did not notice, that regulatory immutability rules applied the moment cutover occurred. 5. How divergence accumulated, systems continued operating while rollback discussions stalled. 6. Missing invariant, rollback must be legally permissible, not just technically feasible.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it creates a false sense of safety around rollback. Engineering teams believe they have an escape hatch, but legal and regulatory constraints silently remove it. Detection latency is immediate only if compliance is consulted early. Otherwise, it surfaces too late.
What exactly broke? Consistency breakdown.
Governance and authority consistency are broken. The system cannot be reverted without violating compliance guarantees. If we roll back only data, this inconsistency remains because the audit trail and regulatory record would no longer be trustworthy.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Does rollback alter regulated historical records? Yes, prohibited. 2. Are snapshots compliant with audit immutability rules? No. 3. Would rollback invalidate submitted reports? Likely. 4. Can compliance approve rollback execution? No. 5. Can authority be restored legally? No, compliance blocks. A rollback that breaks audit is not a rollback, it is a violation.
Decision point, rollback versus forward fix.
Rollback is categorically impossible due to legal and regulatory constraints. Forward fix is the only permissible path, even if it is more complex or costly. Technical correctness is subordinate to compliance correctness.
Rollback architecture, if executed.
A compliant rollback architecture would have required regulatory pre-approval, immutable audit preservation, downstream notification, and potentially parallel corrective adjustments instead of state reversal. In this incident, such an architecture did not exist, making rollback non-executable.
Containment and forward fix strategy.
Once rollback is legally blocked, containment must precede repair. 1. Formally declare rollback prohibited by compliance. 2. Freeze scope and prevent further ungoverned changes. 3. Design a forward fix that preserves audit trails. 4. Apply corrective adjustments with full lineage tracking. 5. Engage compliance in validation and sign-off. Compliance-safe repair is slower but mandatory.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Rollback must satisfy legal and audit constraints, not just technical ones. 2. Compliance can silently eliminate rollback options at cutover. 3. Authority shifts the moment regulated reporting begins. 4. Forward fix is often the only lawful recovery mechanism. A rollback that violates compliance destroys trust permanently.
Follow-up 1. Why wasn't rollback approved even though snapshots existed?
Answer: because restoring snapshots would rewrite regulated historical records. Compliance rules prioritize immutability over technical convenience, making rollback illegal.
Follow-up 2. When did rollback become impossible?
Answer: rollback became impossible the moment Redshift outputs were considered part of an auditable or regulated record, regardless of technical capability.
Follow-up 3. What should architects do differently next time?
Answer: involve compliance early and design migrations assuming rollback may be legally blocked. Forward fix paths must be planned from day one.
Pro insider tip.
If compliance has not approved rollback explicitly, assume it is forbidden, even if every snapshot is green.
Real-world incident during source to Redshift migration 49. Business refuses downtime during rollback window.
During an AWS Redshift migration, a data integrity issue was detected that technically required rollback to a prior snapshot. However, business leadership refused any downtime due to revenue impact, SLAs, or executive commitments. As a result, rollback was blocked despite being technically feasible, forcing the system to continue operating in a compromised state. Failure class: rollback execution incidents.
System state before failure, very important.
At the moment rollback was evaluated, the system state was: 1. Source system still operational and write-enabled. 2. Redshift cluster serving analytics and business-critical dashboards. 3. CDC pipeline actively applying ongoing changes. 4. Rollback mechanism technically available via snapshot restore. 5. BI and downstream systems actively consumed by business users. 6. Declared source of truth Redshift for analytics. 7. Authority status, business enforced, not technically enforced. Rollback feasibility exists only if downtime is permitted.
Incident analysis and root cause.
This failure emerged from organizational constraints overriding technical recovery. 1. Triggering action identifying a data integrity issue that required rollback. 2. Why it appeared safe, teams assumed downtime could be negotiated if needed. 3. What teams noticed first, business leadership immediately rejected rollback due to downtime. 4. What teams did not notice, that refusing downtime permanently removed rollback as an option. 5. How divergence accumulated, the system continued operating while known corruption persisted. 6. Missing invariant, rollback requires explicit business approval for downtime.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it creates a false belief that rollback remains available. In reality, once the business refuses downtime, rollback becomes politically and operationally impossible. Detection latency is immediate, but acceptance of risk becomes normalized over time.
What exactly broke? Consistency breakdown.
Authority and recovery consistency are broken. The system cannot be reset without violating business constraints. If we roll back only data, this inconsistency remains because business operations would be disrupted beyond acceptable limits.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Is technical rollback possible? Yes, snapshots exist. 2. Is downtime approved by business? No, explicitly refused. 3. Can rollback be executed without service interruption? No. 4. Have downstream consumers accepted current state? Yes. 5. Can authority be restored cleanly? No business blocks. Rollback without downtime approval is theoretical only.
Decision point, rollback versus forward fix.
Rollback is technically possible but operationally forbidden. Forward fix becomes the only viable path, even if it carries higher long-term risk. The decision is driven by organizational constraints, not system design.
Rollback architecture, if executed.
A rollback architecture would require full service suspension, coordinated snapshot restore, CDC reseeding, BI cache invalidation, and executive approval. Because downtime was refused, none of these steps could be executed, rendering rollback architecture moot.
Containment and forward fix strategy.
When rollback is blocked by downtime refusal, containment must proceed. 1. Formally document rollback rejection by business leadership. 2. Freeze further risky changes to prevent compounding issues. 3. Design forward fix with zero downtime constraints. 4. Communicate known data limitations transparently. 5. Plan a future controlled correction window if business priorities change. Operational continuity often wins over technical correctness.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Rollback requires business approval for downtime, not just snapshots. 2. Refusing downtime silently converts rollback into forward fix only. 3. Authority shifts to business constraints once systems go live. 4. Architects must negotiate rollback terms before migration begins. Rollback viability is as much organizational as it is technical.
Follow-up 1. Why couldn't engineers force a rollback?
Answer: because rollback would interrupt critical business operations. Engineering authority ends where business risk tolerance begins.
Follow-up 2. When did rollback stop being viable?
Answer: rollback stopped being viable the moment business leadership refused downtime, regardless of technical readiness.
Follow-up 3. What should be agreed before future migrations?
Answer: downtime windows and rollback authority must be contractually agreed before cutover, not negotiated during incidents.
Pro insider tip.
If downtime is not pre-approved, assume rollback does not exist and design migrations accordingly.
Real-world incident during source to Redshift migration 50. Silent resize or upgrade failure masquerades as successful rollback.
During an AWS Redshift migration, a classic resize or engine upgrade was initiated as part of rollback or remediation. The operation auto-canceled or partially failed, yet surfaced a misleading success message such as rollback completed or resize finished. Engineers assumed the cluster had reverted cleanly, while in reality the physical state, data layout, or metadata remained partially mutated. Failure class: rollback execution incidents.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system stable and unchanged during the resize or upgrade attempt. 2. Redshift cluster undergoing classic resize, elastic resize, or version upgrade. 3. Cluster events reported completion without explicit failure. 4. Snapshots present but not validated post-operation. 5. CDC pipeline paused or resumed based on assumed rollback success. 6. BI tools gradually re-enabled based on rollback confirmation. 7. Declared source of truth assumed restored Redshift state. 8. Authority status incorrectly re-established without verification. A successful message does not guarantee a successful state.
Incident analysis and root cause.
This failure resulted from trusting control plane signals over data plane verification. 1. Triggering action, initiating a Redshift resize or upgrade as part of rollback or recovery. 2. Why it appeared safe, the console or API returned a completion or rollback message. 3. What teams noticed first, performance anomalies, skew, or missing data days later. 4. What teams did not notice that the resize or rollback auto-canceled mid-operation. 5. How divergence accumulated, queries and CDC resumed against a partially mutated cluster. 6. Missing invariant, rollback completion must be validated at the data and system table level.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it creates a false sense of safety. Control plane messages indicate success, while physical storage, distribution, or metadata remain inconsistent. Detection latency is often weeks, surfacing only under load or during deep performance analysis.
What exactly broke? Consistency breakdown.
Physical and execution consistency are broken. The cluster is neither fully rolled back nor fully upgraded. If we roll back only data, this inconsistency remains because the underlying cluster state and metadata were never fully restored.
Rollback viability checklist, go or no go.
Before trusting rollback completion, the architect must evaluate 1. Did the resize or upgrade complete without auto-cancel? Unknown requires verification. 2. Do system tables reflect expected node slice and distribution state? Often no. 3. Are post-rollback snapshots validated? Rarely. 4. Has CDC resumed based on assumption alone? Yes. Risk introduced. 5. Can authority be re-established with confidence? No. State uncertain. Unverified rollback is indistinguishable from silent corruption.
Decision point. Rollback versus forward fix.
Rollback cannot be trusted because the cluster state is indeterminate. Forward fix must begin from a known good snapshot or a fresh cluster, not from an assumed rollback state.
Rollback architecture, if executed.
A correct rollback would require restoring from a verified pre-resized snapshot into a new cluster, discarding the partially resized environment, reseeding CDC offsets, repointing BI tools, invalidating caches, and obtaining governance approval. Reusing the mutated cluster is unsafe.
Code illustration and Redshift artifacts.
In this section, we will show 1. How cluster events reveal auto-canceled resize or upgrade operations. 2. How system tables expose incomplete physical state after successful rollback. Control plane success does not imply data plane correctness. Here is Redshift system table, SQL showing incomplete resize or upgrade state via cluster events. Disclaimer: always test code in a non-production environment. This snippet exposes rollback or resize messages that may indicate auto-cancellation or partial completion. These messages often appear benign but hide incomplete execution. Here is Redshift SQL showing physical inconsistencies after a silent resize or upgrade failure. Disclaimer: always test code in a non-production environment. This condition proves that distribution or sort skew persists after an assumed rollback, confirming that the physical layout was not restored correctly.
Containment and forward fix strategy.
Once a silent failure is detected, containment must be immediate. 1. Stop CDC and BI access to the affected cluster. 2. Provision a new cluster from a verified snapshot. 3. Discard the partially resized or upgraded cluster entirely. 4. Revalidate physical layout and performance baselines. 5. Resume CDC and analytics only after full verification. When state is uncertain, replacement is safer than repair.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Redshift resize and upgrade operations can auto-cancel silently. 2. Console success messages must never be trusted alone. 3. Rollback requires validating physical and metadata state. 4. The safest fix is often cluster replacement, not reuse. Rollback must be proven at the data plane, not assumed from control plane signals.
Follow-up 1. Why didn't monitoring alert on this failure?
Answer: because the control plane reported success and the cluster remained available. The failure was physical and semantic, not operational, so standard alarms stayed green.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe the moment the partially resized cluster was reused as authoritative, without validating its physical and metadata state.
Follow-up 3. What single practice would have prevented this?
Answer: mandating post-rollback validation, using system tables and snapshots before re-enabling CDC or BI access.
Pro insider tip.
If a Redshift resize or upgrade touches rollback paths, always assume failure until system tables prove otherwise.
Real-world incident during source to Redshift migration 51. WLM queue starvation blocks rollback scripts.
During an AWS Redshift migration rollback attempt, validation and rollback scripts were executed under production load. Due to misconfigured or saturated workload management, WLM queues, critical rollback queries were queued, throttled, or timed out. Engineers assumed rollback had executed fully, while in reality only a subset of rollback steps completed. Failure class: rollback execution incidents.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system stable and unchanged during rollback execution. 2. Redshift cluster under heavy analytical and CDC-driven load. 3. WLM configuration shared queues with no reserved capacity for rollback tasks. 4. Rollback scripts executed manually or via automation without queue isolation. 5. CDC pipeline paused or partially paused during rollback. 6. BI tools still connected and generating concurrent workload. 7. Declared source of truth assumed to be reverting to pre-cutover state. 8. Authority status incorrectly assumed restored. Rollback scripts compete for resources unless explicitly protected.
Incident analysis and root cause.
This failure resulted from treating rollback as a low-priority workload. 1. Triggering action executing rollback and validation queries during peak cluster load. 2. Why it appeared safe, scripts started successfully and some steps completed. 3. What teams noticed first, rollback appeared slow or partially completed. 4. What teams did not notice that critical rollback queries never executed due to queue starvation. 5. How divergence accumulated, partial rollback created a mixed state with no clear authority. 6. Missing invariant, rollback execution must be isolated and guaranteed cluster resources.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it produces the illusion of rollback. Some steps complete, logs show progress, and no explicit errors occur. Detection latency is high, often discovered only when downstream inconsistencies or missing data appear days later.
What exactly broke? Consistency breakdown.
Authoritative and transactional consistency are broken. The system is neither fully rolled back nor fully cut over. If we roll back only data, this inconsistency remains because execution order and completeness were never guaranteed.
Rollback viability checklist, go or no go.
Before trusting rollback completion, the architect must evaluate. 1. Were rollback queries queued or timed out? Yes, partial execution. 2. Did any rollback step fail silently due to WLM limits? Likely. 3. Was rollback executed in an isolated queue? No. 4. Did CDC resume based on assumed rollback completion? Yes, risk introduced. 5. Can authority be re-established cleanly? No, execution incomplete. A rollback that cannot execute fully is not a rollback.
Decision point, rollback versus forward fix.
Rollback cannot be trusted once rollback scripts are starved or partially executed. Forward fix must assume rollback failure and re-establish authority from a verified clean state.
Rollback architecture, if executed.
A safe rollback requires dedicating isolated WLM queues for rollback and validation, pausing BI and CDC workloads, restoring from verified snapshots if needed, reseeding CDC offsets, invalidating downstream caches, and obtaining governance approval before resuming access.
Code illustration and Redshift artifacts.
In this section, we will show 1. How WLM queue starvation can be detected using Redshift system tables. 2. How query timeouts prove rollback execution was incomplete. Rollback must have guaranteed execution, not best effort scheduling. Here is Redshift SQL showing rollback queries blocked by WLM queue starvation. Disclaimer: always test code in a non-production environment. This condition proves that rollback or validation queries spent time waiting in WLM queues. Excessive queue time indicates rollback steps may not have executed within required windows. Here is Redshift SQL showing rollback queries that timed out or were aborted. Disclaimer: always test code in a non-production environment. This snippet exposes rollback-related queries that were aborted due to timeouts or resource pressure, proving that rollback execution was incomplete.
Containment and forward fix strategy.
Once rollback starvation is detected, containment must be immediate. 1. Pause all BI and CDC workloads immediately. 2. Declare rollback incomplete and authority undefined. 3. Provision isolated WLM queues for recovery operations. 4. Re-execute rollback or restore from a verified snapshot. 5. Resume access only after rollback completeness is proven. Rollback must be isolated, not contended.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Rollback is a production-critical workload that must be isolated. 2. WLM queue starvation can silently block rollback execution. 3. Partial rollback is worse than no rollback. 4. System tables must be used to prove rollback completeness. Rollback execution requires guaranteed resources, not shared capacity.
Follow-up 1. Why didn't rollback fail loudly here?
Answer: because queries were queued or aborted due to WLM limits, not due to syntax or logic errors. From the system's perspective, nothing crashed, but critical steps never executed.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe the moment rollback scripts began competing with production workloads, and execution completeness was no longer guaranteed.
Follow-up 3. What single control would have prevented this?
Answer: a dedicated WLM queue with reserved slots for rollback and validation. combined with enforced suspension of BI and CDC workloads.
Pro Insider Tip.
If rollback queries wait in a queue, rollback is already failing, even if nothing errors out.
Real-world incident during source to Redshift migration 52. Auto WLM rebalancing interferes with rollback execution.
During an AWS Redshift migration rollback, Auto WLM and concurrency scaling dynamically rebalanced workloads in response to cluster pressure. While intended to optimize performance, this behavior interfered with long-running rollback and validation queries, causing execution reordering, intermittent throttling, and partial completion. Engineers believed rollback had completed successfully, but system state proved otherwise. Failure class, rollback execution incidents.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system stable and unchanged during rollback window. 2. Redshift cluster under variable analytical load with Auto WLM enabled. 3. WLM mode Auto WLM actively rebalancing queues. 4. Concurrency scaling enabled and triggered intermittently. 5. Rollback scripts executed assuming stable execution ordering. 6. CDC pipeline paused or partially paused during rollback. 7. BI tools still connected contributing background load. 8. Declared source of truth assumed to be reverting to source. 9. Authority status assumed restored without verification. Auto WLM optimizes throughput, not rollback determinism.
Incident analysis and root cause.
This failure resulted from relying on adaptive scheduling during a critical rollback. 1. Triggering action, executing rollback under Auto WLM and concurrency scaling. 2. Why it appeared safe, queries executed successfully at different times with no hard failures. 3. What teams noticed first, rollback steps completing out of expected order or slower than planned. 4. What teams did not notice? That Auto WLM dynamically reshuffled execution priorities mid-rollback. 5. How divergence accumulated, some rollback steps completed while others were delayed or preempted. 6. Missing invariant, rollback execution must be deterministic and isolated from adaptive scheduling.
Why this failure is dangerous, hidden risk.
This failure is dangerous because Auto WLM masks rollback instability. Queries eventually complete, dashboards remain responsive, and no alerts fire. Detection latency is high, often discovered only when post-rollback validation reveals partial state or missing reversals.
What exactly broke? Consistency breakdown.
Authoritative and transactional consistency are broken. Rollback steps executed in a non-deterministic order, producing a mixed system state. If we roll back only data, this inconsistency remains because execution order and completeness were never guaranteed.
Rollback viability checklist, go or no go.
Before trusting rollback completion, the architect must evaluate. 1. Was Auto WLM enabled during rollback? Yes, execution non-deterministic. 2. Did concurrency scaling activate mid-rollback? Likely load-dependent. 3. Were rollback steps verified for completion order? No. 4. Did any rollback queries experience requeuing or delay? Yes. 5. Can authority be re-established with confidence? No. Execution unstable. Rollback cannot rely on adaptive scheduling.
Decision point, rollback versus forward fix.
Rollback cannot be trusted once Auto WLM interferes with execution order. Forward fix must assume rollback instability and restore authority from a verified clean baseline.
Rollback architecture, if executed.
A safe rollback requires disabling Auto WLM and concurrency scaling, allocating fixed WLM queues for rollback and validation, pausing BI workloads, restoring from verified snapshots if required, reseeding CDC offsets, invalidating downstream caches, and obtaining governance approval before resuming access.
Code illustration and Redshift artifacts.
In this section, we will show 1. How concurrency scaling activity can be detected during rollback windows. 2. How Auto WLM behavior proves rollback execution instability. Adaptive scheduling and rollback are incompatible. Here is Redshift SQL showing concurrency scaling activity during rollback execution. Disclaimer: always test code in a non-production environment. This snippet proves that rollback or validation queries executed on concurrency scaling clusters. Execution on scaled clusters indicates non-deterministic scheduling during rollback. Here is Redshift SQL showing WLM service class shifts caused by auto WLM. Disclaimer: always test code in a non-production environment. Changes in service class across rollback queries indicate auto WLM rebalancing, proving that rollback execution priority was not stable.
Containment and forward fix strategy.
Once auto WLM interference is detected, containment must be immediate. 1. Disable auto WLM and concurrency scaling for recovery windows. 2. Pause all non-essential workloads. 3. Rerun rollback or restore from snapshot under fixed WLM queues. 4. Validate rollback completeness using system tables. 5. Re-enable adaptive features only after authority is restored. Rollback requires predictability, not optimization.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Rollback must execute under deterministic scheduling conditions. 2. Auto WLM and concurrency scaling optimize throughput, not correctness. 3. Partial rollback caused by scheduling drift is worse than no rollback. 4. Adaptive features must be disabled during recovery operations. Rollback execution must be deterministic to restore authority.
Follow-up 1. Why didn't this cause visible errors?
Answer: because queries still executed successfully, just under different scheduling contexts. The failure was in execution ordering and completeness, not in query correctness.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe the moment auto WLM and concurrency scaling altered execution order, making rollback completion unverifiable.
Follow-up 3. What single control would have prevented this?
Answer: disabling auto WLM and concurrency scaling during rollback and running recovery under fixed, isolated WLM queues.
Pro insider tip.
If auto WLM is enabled during rollback, you are recovering on shifting ground.
Category 6 wrap-up. When rollback exists only on paper.
Across these incidents, rollback appeared theoretically possible but failed in execution. Missing restore points, CDC corruption, downstream consumption, operational pressure, and system-level interference quietly pushed the system past safe recovery boundaries. These failures demonstrate a hard truth. Rollback is not a button. It is a narrow window that closes silently under real-world conditions. Transition from failed rollback to no rollback at all.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs in a single zip file, containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, system design. Required for your data engineer interviews jobs like data quality analyst jobs, data governance analyst jobs, AWS Python data engineer jobs, AWS Redshift Database Administrator DBA jobs, AWS Glue ETL Developer jobs, AWS Data Engineer jobs, Cloud Data Engineer jobs, Data Architect jobs, DataOps Engineer jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based questions and answers, real-world problem-solving, interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people also for your interviews. You people can download all 6 PDFs in a single zip file from below given links.
Category 7. No rollback point of no return incidents.
This category covers incidents where rollback is no longer an option, not because of tooling limitations, but because irreversible external commitments have already occurred. Regulatory filings, external consumers, machine learning models, and cache systems have absorbed corrupted state. At this point, Any attempt to roll back data would only amplify damage rather than restore trust.
Category 7 scenarios. Forward fix is the only path.
The following incidents represent true points of no return. 1. Regulatory reports already submitted based on inconsistent or partial data. 2. Machine learning models trained on corrupted or mixed-source datasets. 3. External consumers accessed and persisted incorrect data. 4. Feature stores refreshed using mixed authoritative states. 5. Search indexes built during partial cut over Windows. 6. APIs cached inconsistent state and served it externally. 7. Cost of rollback exceeds cost of repair and trust rebuilding. Once external reality diverges from internal state, rollback becomes a liability, not a solution.
Real-world incident. During source-to-Redshift migration 53, regulatory reports submitted before migration integrity was proven.
During an AWS Redshift migration, finance and compliance teams submitted regulatory reports based on data sourced from Redshift before migration validation and authority declaration were complete. Weeks later, inconsistencies were discovered between source and target systems, but the reports had already been formally filed with regulators. Failure class, no rollback / point of no return incident.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system, write-enabled and continuing to process live transactions. 2. Redshift cluster, receiving replicated data and being used for analytical reporting. 3. CDC pipeline, running with acceptable lag but without full end-to-end reconciliation. 4. BI and reporting tools pointed to Redshift for official financial and compliance reporting. 5. Declared source of truth, implicitly assumed to be Redshift for reporting purposes. 6. Authority status, never formally declared before regulatory submission. Submitting reports before authority is declared converts migration risk into legal fact.
Incident analysis and root cause.
This failure resulted from an authority decision made too early. 1. Triggering action, generating and submitting regulatory filings using Redshift-derived data before migration validation was finalized. 2. Why it appeared safe, high-level aggregates and row counts matched expectations, and no operational errors were visible. 3. What teams noticed first, post-submission reconciliation revealed metric discrepancies between source and Redshift. 4. What teams did not notice, that regulatory submission permanently externalized the data state. 5. How divergence accumulated, any subsequent correction could not change the already filed reports. 6. Missing invariant, no data may be used for regulatory reporting until authoritative truth is explicitly declared.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it feels successful until it is too late. Reports are accepted, dashboards look correct, and no alarms fire. The risk materializes only after submission, when discrepancies are discovered but cannot be retroactively corrected. Detection latency is typically weeks or months, often during audit or regulator inquiry.
What exactly broke? Consistency breakdown.
Authoritative and legal consistency are broken. The organization now has two conflicting versions of truth, one embedded in regulatory filings and another in internal systems. The blast radius is unbounded, impacting compliance, audits, and executive accountability. If we roll back only data, this inconsistency remains because the external regulatory record cannot be altered.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Have regulatory reports already been submitted? Yes, external commitment made. 2. Can submitted filings be withdrawn or amended cleanly? No legal process required. 3. Would restoring snapshots change regulator-held records? No external state persists. 4. Have auditors or regulators access the data? Likely audit trail established. 5. Can authority be restored internally without legal contradiction? No, conflict persists. Once compliance consumes data, rollback ceases to exist as a technical option.
Decision point, rollback versus forward fix.
Rollback is impossible because it cannot change the external legal record. Any attempt to restore earlier data states would only increase internal inconsistency. The only viable path forward is a forward fix strategy focused on disclosure, reconciliation, and governance correction.
Rollback architecture, state of rollback.
Rollback is explicitly not executable in this scenario. Snapshot restores, CDC rewinds, or BI repointing cannot alter data already submitted to regulators. Any partial rollback would create internal divergence without resolving external truth. Governance approval would be required even to attempt remediation, but rollback mechanics provide no corrective value here.
Containment and forward fix strategy.
Once regulatory submission is confirmed, containment must focus on trust repair. 1. Immediately freeze further regulatory reporting from Redshift until reconciliation completes. 2. Perform a full reconciliation between submitted reports and source of record data. 3. Document discrepancies and engage compliance and legal teams proactively. 4. Issue amended filings if legally permitted with full audit disclosure. 5. Establish hard governance gates preventing future pre-authority submissions. Forward fix is about credibility restoration, not data correction.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Regulatory submission externalizes data authority beyond technical control. 2. Migration validation must complete before any compliance use. 3. Rollback is meaningless once legal truth is established externally. Authority must be declared before data leaves the organization.
Follow-up 1. Why can't rollback fix this scenario?
Answer: rollback can restore internal data state, but it cannot alter reports already filed with regulators. Once data is externalized into a legal record, technical recovery loses relevance. The system boundary has been crossed permanently.
Follow-up 2. When exactly did rollback stop being safe?
Answer: rollback stopped being safe the moment the regulatory report was formally submitted. From that point on, any internal correction would create a contradiction between internal systems and external legal truth.
Follow-up 3. Curveball. What if the data error is later proven immaterial?
Answer: even immaterial errors require formal documentation and disclosure. The existence of an incorrect filing still creates audit risk. Architects must assume that any submission, regardless of impact, permanently constrains rollback options.
Pro insider tip.
If a dataset is good enough for regulators, it is already beyond rollback. Treat compliance consumption as the final authority boundary in any migration.
Real-world incident during source to Redshift migration 54. Machine learning models trained on inconsistent migration data.
During an AWS Redshift migration, data science teams trained and deployed machine learning models using data sourced from Redshift before migration validation and authority declaration were complete. Later reconciliation revealed inconsistencies between the source system and Redshift, but the models had already been trained, validated, and put into production. Failure class: no rollback / point of no return incident.
System state before failure, very important.
At the moment the failure was introduced, the system state was: 1. Source system write-enabled and continuing to evolve transactional data. 2. Redshift cluster serving analytical queries and feature extraction workloads. 3. CDC pipeline active but not fully reconciled against the source system. 4. ML pipelines reading features directly from Redshift tables. 5. Declared source of truth implicitly assumed to be Redshift for analytics. 6. Authority status not formally declared prior to model training. Training models before authority is declared embeds inconsistency into learned behavior.
Incident analysis and root cause.
This failure stemmed from premature analytical adoption. 1. Triggering action, training and validating ML models using Redshift data during an incomplete migration. 2. Why it appeared safe, model metrics and offline validation scores met expected thresholds. 3. What teams noticed first, model predictions began diverging from business expectations post-deployment. 4. What teams did not notice, that training data itself was inconsistent with the source system. 5. How divergence accumulated, models learned patterns from corrupted or incomplete historical data. 6. Missing invariant training data must be sourced only from an authoritative and validated system.
Why this failure is dangerous, hidden risk.
This failure is dangerous because models can perform well while being fundamentally wrong. Offline validation masks data inconsistency, and errors surface only in production decisions. Detection latency is often weeks or months, discovered through business impact rather than technical alerts.
What exactly broke? Consistency breakdown.
Semantic and temporal consistency are broken. The model encodes a version of reality that never truly existed in the authoritative source system. The blast radius is unbounded, affecting automated decisions, downstream systems, and customer outcomes. If we roll back only data, this inconsistency remains because the model's learned parameters cannot be retroactively corrected.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate 1. Have models already been trained on inconsistent data? Yes, learned state persists. 2. Can model predictions be reverted by data rollback alone? No, models must be retrained. 3. Have model outputs influenced business decisions? Likely impact already externalized. 4. Is the original clean training dataset preserved? Often no. 5. Can authority be restored without retraining? No, model state invalid. Model training converts data inconsistency into irreversible behavior.
Decision point, rollback versus forward fix.
Rollback is not sufficient because restoring data does not undo trained model state. Forward fix requires retraining models using authoritative data and revalidating all downstream decisions influenced by prior predictions.
Rollback architecture, state of rollback.
Rollback is explicitly non-viable in this scenario. Snapshot restores and CDC rewinds do not affect deployed models or historical predictions. Any partial rollback would leave models operating on invalid assumptions. Governance approval is required to deprecate models, but rollback mechanics offer no remediation.
Containment and forward fix strategy.
Once model contamination is confirmed, containment must focus on decision safety. 1. Immediately halt use of affected models in production workflows. 2. Identify all decisions influenced by the contaminated model outputs. 3. Reconstruct authoritative training datasets from validated sources. 4. Retrain and revalidate models with explicit data lineage controls. 5. Introduce governance gates preventing model training during migrations. Models must be treated as data products with their own rollback boundaries.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Machine learning models persist data errors beyond data rollback. 2. Training data authority is as critical as serving data authority. 3. Model retraining is the only valid recovery path after contamination. Learned state is irreversible once deployed.
Follow-up 1. Why can't we just fix the data and keep the model?
Answer: because the model parameters were optimized on incorrect patterns. Even if the data is fixed, the learned relationships remain wrong. The model would continue making decisions based on a corrupted view of reality.
Follow-up 2. When exactly did rollback stop being safe?
Answer: rollback stopped being safe the moment the model completed training on inconsistent data. At that point, the error was embedded into model behavior, not just stored data.
Follow-up 3. Curveball. What if the model was only used for internal experimentation?
Answer: even experimental models influence future feature design and thresholds. Unless their outputs were fully isolated and discarded, contamination still exists. Architects must assume experimentation leaks unless explicitly sandboxed.
Pro insider tip.
If a model trains during migration, assume it is wrong until proven otherwise. Data lineage gaps compound faster in ML than in analytics.
Real-world incident during source to Redshift migration 55. External consumers accessed incorrect data during partial cut-over.
During an AWS Redshift migration, external consumers were granted access to Redshift endpoints before migration validation and authority declaration were complete. These consumers ingested, cached, or acted upon incorrect analytical data. Even after the inconsistency was discovered internally, the data had already propagated beyond organizational control. Failure class: no rollback / point of no return incident.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system write-enabled and continuing normal operations. 2. Redshift cluster exposed to external consumers for early access. 3. CDC pipeline active but not fully reconciled or validated. 4. External consumers querying or exporting data from Redshift. 5. declared source of truth not formally declared for external use. 6. Authority status, implicitly assumed, never contractually enforced. Once data leaves the system boundary, rollback authority is lost.
Incident analysis and root cause.
This failure resulted from premature external exposure. 1. Triggering action granting external access to Redshift during an incomplete migration. 2. Why it appeared safe, internal validation showed acceptable metrics and no errors. 3. What teams noticed first, external partners reporting discrepancies against prior numbers. 4. What teams did not notice, that external systems had already persisted the incorrect data. 5. How divergence accumulated, consumers cached, transformed, and redistributed inconsistent data. 6. Missing invariant, external access must only be granted after authority is formally declared.
Why this failure is dangerous, hidden risk.
This failure is dangerous because internal fixes cannot retract external truth. Even if Redshift data is corrected, external consumers may never refresh or may have already acted on incorrect information. Detection latency is high and often initiated by third parties, not monitoring.
What exactly broke? Consistency breakdown.
Authoritative and semantic consistency are broken. Multiple external systems now hold conflicting versions of analytical truth. The blast radius is unbounded because the data has escaped organizational control. If we roll back only data, this inconsistency remains because external copies cannot be recalled or corrected reliably.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Have external consumers accessed Redshift data? Yes, data already propagated. 2. Can external systems be forced to refresh or delete data? No, no control. 3. Have decisions or reports been generated externally? Likely impact persists. 4. Would snapshot restore change external state? No, only internal. 5. Can authority be re-established retroactively? No, trust already fractured. Rollback cannot retract data once it leaves organizational boundaries.
Decision point, rollback versus forward fix.
Rollback is ineffective because it only restores internal state. Forward fix must focus on communication, reissuance, and coordinated correction with external consumers, acknowledging that some impact may be irreversible.
Rollback architecture, state of rollback.
Rollback is explicitly non-viable in this scenario. Snapshot restores and CDC rewinds affect only internal systems and do not invalidate externally cached or persisted data. Any partial rollback creates a false sense of correction, while external inconsistencies remain unresolved. Governance approval is required to manage disclosure and remediation, not technical rollback.
Containment and forward fix strategy.
Once external exposure is confirmed, containment must prioritize trust repair. 1. Immediately freeze further external data access. 2. Notify all external consumers of the inconsistency window. 3. Provide corrected datasets with explicit versioning. 4. Require acknowledgments of correction from key consumers. 5. Introduce contractual and technical gates for future access. External trust recovery is a coordination problem, not a SQL problem.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. External consumption defines the true rollback boundary. 2. Data authority must be contractually enforced, not assumed. 3. Once data exits the system, rollback becomes a governance problem. Authority ends where control ends.
Follow-up 1. Why doesn't restoring Redshift fix this issue?
Answer: because the incorrect data already exists outside Redshift. External systems may have cached, transformed, or acted on it. Internal restoration does not affect external state or decisions already made.
Follow-up 2. When exactly did rollback stop being safe?
Answer: rollback stopped being safe the moment the first external consumer accessed and persisted the data. From that point on, the system no longer had exclusive authority over the truth.
Follow-up 3. Curveball. What if the external consumer promises to delete the data?
Answer: promises are not guarantees. Unless deletion is provable and comprehensive, architects must assume the data still exists. System design must treat external exposure as irreversible.
Pro insider tip.
The fastest way to lose rollback is to expose data early. External access is not a feature flag you can turn off after the fact.
Real-world incident during source to Redshift migration 56. Feature stores refreshed from mixed sources during partial cut-over.
During an AWS Redshift migration, machine learning feature stores were refreshed while the system was in a partial cut-over state. Some features were sourced from Redshift, while others were still derived from the legacy system. This created inconsistent feature vectors that were persisted and later used for model training and inference. Failure class, no rollback / point of no return incident.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system write-enabled and producing operational data. 2. Redshift cluster partially populated and used for analytics. 3. CDC pipeline running with known lag and unresolved validation gaps. 4. Feature store pipelines actively refreshing features from both systems. 5. ML models consuming refreshed feature sets without migration awareness. 6. Declared source of truth not formally defined for feature generation. 7. Authority status fragmented across systems at feature level. Mixed feature inputs create permanent semantic corruption.
Incident analysis and root cause.
This failure emerged from uncontrolled feature refresh timing. 1. Triggering action refreshing feature stores during a partial migration state. 2. Why it appeared safe both systems individually passed validation checks. 3. What teams noticed first model performance drift and unexplained prediction variance. 4. What teams did not notice that feature vectors combined incompatible system states. 5. How divergence accumulated. Feature snapshots were persisted and reused downstream. 6. Missing invariant, all features must be derived from a single authoritative system.
Why this failure is dangerous, hidden risk.
This failure is dangerous because feature stores persist corruption silently. Once features are materialized and consumed by models, downstream behavior diverges without obvious data errors. Detection latency is high and often surfaces only through degraded model outcomes.
What exactly broke? Consistency breakdown.
Semantic and temporal consistency are broken. Feature vectors no longer represent a coherent business state. The blast radius is unbounded because models trained on these features propagate incorrect logic into production. If we roll back only data, this inconsistency remains because trained models encode the corruption.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Have feature stores been refreshed from mixed sources? Yes, semantic corruption. 2. Have models been trained on these features? Likely embedded inconsistency. 3. Can feature snapshots be invalidated globally? No copies exist. 4. Would snapshot restore fixed model behavior? No, models persist. 5. Can authority be re-established retroactively? No, training already occurred. Model training marks the true rollback boundary.
Decision point, rollback versus forward fix.
Rollback is ineffective because restoring data does not undo trained models or feature snapshots. Forward fix must focus on retraining models with clean, authoritative features and explicitly deprecating corrupted artifacts.
Rollback architecture, state of rollback.
Rollback is not viable once mixed source features are consumed. Snapshot restores and CDC rewinds do not affect feature stores or trained models. Any attempt at partial rollback worsens divergence by masking model-level corruption. Governance approval is required to retire models and reissue corrected feature pipelines.
Containment and forward fix strategy.
Containment must focus on halting propagation of corrupted features. 1. Freeze all feature store refreshes immediately. 2. Identify models trained during the mixed source window. 3. Invalidate and deprecate corrupted feature versions. 4. Retrain models using a single authoritative data source. 5. Enforce source of truth contracts for all feature pipelines. Feature integrity is more important than model uptime.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Feature stores persist semantic corruption beyond data rollback. 2. Model training creates irreversible dependency on feature correctness. 3. Migration authority must extend to ML pipelines, not just databases. Models are data consumers that cannot be rolled back.
Follow-up 1. Why can't we just retrain models later?
Answer: retraining is possible, but only if corrupted features are fully identified and removed. Until then, predictions continue to rely on inconsistent logic. Retraining also requires business acceptance of model downtime and behavior changes.
Follow-up 2. When exactly did rollback stop being safe?
Answer: rollback stopped being safe the moment feature snapshots were consumed by training jobs. From that point forward, the inconsistency was embedded into model parameters, not just data tables.
Follow-up 3. Curveball. What if the models are only used for internal experimentation?
Answer: even experimental models influence decisions and future designs. Treating them as disposable underestimates their impact. Architects must assume any trained model can leak into production workflows.
Pro insider tip.
If feature stores refresh during migration, assume your models are already wrong, even if accuracy metrics look stable.
Real-world incident during source-to-Redshift migration 57. Search indexes built during partial cut-over.
During an AWS Redshift migration, downstream search indexes were rebuilt while the system was in a partial cut-over state. Indexing jobs consumed data from Redshift for some entities and from the source system for others. These indexes were later promoted to production, permanently persisting inconsistent business state outside the database. Failure class: no rollback/point of no return incident.
System state before failure, very important.
At the moment the failure was introduced, the system state was: 1. Source system write enabled and serving operational reads. 2. Redshift cluster partially populated and used for analytics. 3. CDC pipeline running with unresolved validation gaps. 4. Search indexing jobs actively rebuilding indexes from mixed sources. 5. Search consumers using rebuilt indexes for production queries. 6. Declared source of truth, not defined for search materialization. 7. Authority status, fragmented across database and index layers. Indexes persist data truth outside database control.
Incident analysis and root cause.
This failure was caused by materializing search state during authority ambiguity. 1. Triggering action rebuilding search indexes during a partial cut-over window. 2. Why it appeared safe both systems returned valid-looking records. 3. What teams noticed first inconsistent search results compared to reports. 4. What teams did not notice that index documents combined incompatible system states. 5. How divergence accumulated. Index snapshots were promoted and cached downstream. 6. Missing invariant search indexes must be built from a single authoritative system.
Why this failure is dangerous, hidden risk.
This failure is dangerous because search systems act as external sources of truth. Once indexed, incorrect documents are served independently of database corrections. Detection latency is high and often surfaces only through user complaints or trust erosion.
What exactly broke? Consistency breakdown.
Authoritative and semantic consistency are broken. Search results no longer represent any single point-in-time business truth. The blast radius is unbounded because search indexes feed APIs, UIs, and downstream systems. If we roll back only data, this inconsistency remains because indexes persist independently.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Have search indexes been rebuilt during partial cutover? Yes, externalized corruption. 2. Can all index replicas be invalidated? Often no, cached globally. 3. Would database snapshot restore fixed search state? No, indexes detached. 4. Have consumers relied on indexed results? Yes, trust impact. 5. Can authority be restored retroactively? No, state already leaked. Search promotion marks a point of no return.
Decision point, rollback versus forward fix.
Rollback is ineffective because restoring database state does not affect deployed search indexes. Forward fix must focus on rebuilding indexes from a single authoritative source and explicitly invalidating corrupted ones.
Rollback architecture, state of rollback.
Rollback cannot restore search correctness once mixed source indexes are promoted. Database snapshot restores and CDC rewinds do not propagate to search layers. Governance approval is required to decommission affected indexes and trigger controlled reindexing from a clean authority.
Containment and forward fix strategy.
Containment focuses on stopping further propagation of corrupted search state. 1. Freeze all search index rebuilds immediately. 2. Identify indexes built during the partial cutover window. 3. Invalidate and decommission corrupted indexes. 4. Rebuild indexes from a single authoritative data source. 5. Enforce authority checks before future index promotions. Search correctness depends on authority, not freshness.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Search systems externalize data truth beyond rollback reach. 2. Index rebuild timing is an authority decision, not a performance task. 3. Once indexes are promoted, rollback boundaries are crossed. Materialization outside the database creates irreversible state.
Follow-up 1. Why can't database rollback fix search results?
Answer: search indexes persist independently and are not transactionally linked to the database. Rolling back tables does not alter index documents already deployed. Users continue seeing incorrect results even after data correction.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe the moment the mixed source indexes were promoted to production. At that point, corrupted state escaped the database boundary and became externally authoritative.
Follow-up 3. Curveball. What if search indexes are rebuilt frequently?
Answer: frequent rebuilds increase risk if authority is unclear. Without strict gating, each rebuild can propagate new inconsistencies. High rebuild frequency amplifies damage, not safety.
Pro insider tip.
If search indexes rebuild during migration, assume rollback is already gone, even if the database still looks clean.
Real-world incident during source to Redshift migration 58. APIs cached inconsistent state during partial cut.
During an AWS Redshift migration, application APIs continued serving responses while the system was in a partial cutover state. API layer caches stored responses derived from Redshift for some requests and from the source system for others. These cached responses were later reused and served to clients, permanently externalizing inconsistent business state. Failure class: no rollback / point of no return incident.
System state before failure, very important.
At the moment the failure was introduced, the system state was: 1. Source system write enabled and serving operational reads. 2. Redshift cluster partially validated and serving analytical reads. 3. CDC pipeline running with unresolved consistency gaps. 4. API layer actively serving traffic with response caching enabled. 5. Cache layer persisting API responses without authority awareness. 6. Declared source of truth, not defined for API responses. 7. Authority status fragmented across database and cache layers. Caches persist truth outside database control.
Incident analysis and root cause.
This failure was caused by caching during authority ambiguity. 1. Triggering action continuing API traffic with caching enabled during partial cutover. 2. Why it appeared safe API responses were valid-looking and low latency. 3. What teams noticed first users receiving inconsistent results for identical requests. 4. What teams did not notice that cached responses mixed incompatible system states. 5. How divergence accumulated. Cached entries were reused long after authority shifted. 6. Missing invariant API responses must be derived from a single authoritative system.
Why this failure is dangerous, hidden risk.
This failure is dangerous because caches externalize incorrect state beyond database visibility. Even after backend fixes, clients continue receiving stale or incorrect responses. Detection latency is high and often surfaces only through user complaints or reconciliation efforts.
What exactly broke? Consistency breakdown.
Authoritative and temporal consistency are broken. API responses no longer reflect a single point-in-time business truth. The blast radius is unbounded because cached responses propagate across clients, regions, and sessions. If we roll back only data, this inconsistency remains because cached responses persist independently of database state.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Have API responses been cached during partial cutover? Yes, externalized corruption. 2. Can all cache entries be invalidated globally? Often no, distributed caches. 3. Would database snapshot restore fix API behavior? No, cache detached. 4. Have clients already consumed cached responses? Yes, trust impact. 5. Can authority be restored retroactively? No, state already leaked. Cached responses define a hard rollback boundary.
Decision point, rollback versus forward fix.
Rollback is ineffective because restoring database state does not retract cached API responses already served to clients. Forward fix must focus on cache invalidation, authority redeclaration, and controlled rehydration of a PI state.
Rollback architecture, state of rollback.
Rollback cannot restore correctness once inconsistent API responses are cached. Database snapshot restores and CDC rewinds do not propagate to cache layers. Governance approval is required to flush caches, communicate trust resets, and accept irreversible exposure of incorrect responses.
Code illustration and Redshift artifacts.
In this section, we will show 1. How API responses diverge from authoritative source data. 2. How cached values persist after backend state changes. Cache comparison exposes irreversible divergence. Here is Redshift SQL showing authoritative state, used to compare against cached API responses. Disclaimer: always test code in a non-production environment. This snippet retrieves the authoritative database state for a specific business entity. Comparing this result to cached API responses proves that clients received data that no longer matches any authoritative source.
Containment and forward fix strategy.
Containment focuses on stopping further propagation of corrupted API state. 1. Immediately disable API response caching. 2. Flush all existing cache entries across regions. 3. Declare a single authoritative backend for API responses. 4. Rehydrate caches only after authority is re-established. 5. Communicate trust reset explicitly to downstream consumers. API correctness depends on authority, not cache hit rate.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. API caches externalize data beyond rollback reach. 2. Caching during partial cutover permanently leaks inconsistent state. 3. Rollback boundaries are crossed when responses leave the system. Never cache without a declared authority.
Follow-up 1. Why can't rollback fix cached API responses?
Answer: rollback restores backend data, not responses already served to clients. Cached entries persist independently and continue to be reused. Once clients consume those responses, trust cannot be retroactively restored.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe the moment API responses were cached and served during partial cutover. At that point, inconsistent state escaped system boundaries and became client visible.
Follow-up 3. Curveball. What if cache TTLs are very short?
Answer: short TTLs reduce duration, not impact. Even a single incorrect response can trigger downstream actions, retries, or client-side caching. Authority loss is instantaneous, not time-based.
Pro insider tip.
If APIs cache during migration, assume rollback is already compromised the moment responses reach clients.
Real-world incident. During source to Redshift migration 59, cost of rollback exceeds cost of repair.
During an AWS Redshift migration, data inconsistencies were detected after partial cutover. While rollback was still technically possible, analysis showed that the operational, financial, and trust costs of rollback exceeded the cost of accepting the inconsistency and performing a controlled forward fix. At this point, rollback ceased to be a viable option due to business impact rather than technical feasibility. Failure class. No rollback / point of no return incident.
System state before failure. Very important.
At the moment rollback viability was evaluated, the system state was 1. Source system write enabled but already operationally deprioritized. 2. Redshift cluster actively used for analytics and decision making. 3. CDC pipeline running with known inconsistencies. 4. BI and downstream systems fully consuming Redshift outputs. 5. External consumers already relying on Redshift-derived data. 6. Declared source of truth, de facto Redshift. 7. Authority status shifted irreversibly due to adoption and dependency. Authority shifted before cost was fully understood.
Incident analysis and root cause.
This incident emerged from delayed authority decisions. 1. Triggering condition discovery of data issues after Redshift adoption reached critical mass. 2. Why it appeared manageable, rollback was still technically possible in isolation. 3. What teams noticed first, business disruption estimates exceeded acceptable thresholds. 4. What teams did not notice, that rollback cost itself defines a hard irreversibility boundary. 5. How divergence accumulated. Organizational dependency on Redshift increased faster than validation rigor. 6. Missing invariant. Rollback cost must remain lower than forward fix cost until cutover is finalized.
Why this failure is dangerous, hidden risk.
This failure is dangerous because systems appear recoverable while the organization is not. Technical teams may still see rollback paths, but business impact, downtime, and trust loss make those paths unusable. Detection latency is high and usually occurs only during executive-level risk assessment.
What exactly broke? Consistency breakdown.
Authoritative consistency is broken at the organizational level. Redshift becomes authoritative by adoption, not correctness. If we roll back only data, this inconsistency remains because authority has already shifted through usage, not system state.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Is rollback technically possible? Yes, in isolation. 2. Would rollback cause unacceptable downtime? Yes, business impact. 3. Have users adapted workflows to Redshift? Yes, behavioral lock-in. 4. Would rollback invalidate decisions already made? Yes, trust erosion. 5. Is forward fix cheaper than rollback? Yes, decisive factor. Cost can invalidate rollback even when mechanics allow it.
Decision point, rollback versus forward fix.
Rollback was rejected not because it was impossible, but because it was more damaging than repair. Forward fix became the only rational path once business cost exceeded recovery value.
Rollback architecture, state of rollback.
Rollback was intentionally not executed. Although snapshot restore and CDC rewind paths existed, governance and leadership determined that operational disruption, user retraining, and trust loss outweighed technical recovery benefits. Rollback viability ended at the cost boundary, not the data boundary.
Containment and forward fix strategy.
Containment focused on stabilizing authority and minimizing further damage. 1. Formally declare Redshift as the permanent system of record. 2. Document known inconsistencies and affected domains. 3. Apply targeted forward fix with full audit visibility. 4. Communicate transparently with stakeholders about limitations. 5. Reinforce stricter cutover and rollback thresholds for future migrations. Forward fix is justified only when rollback cost exceeds trust value.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Rollback feasibility is constrained by business cost, not just data state. 2. Authority can shift irreversibly through adoption and dependency. 3. The true rollback boundary is often economic, not technical. Rollback must remain cheaper than repair to stay viable.
Follow-up 1. Why wasn't rollback chosen if it was technically possible?
Answer: because rollback would have caused greater business disruption than fixing forward. At that point, authority had already shifted to Redshift through usage, making rollback more damaging than corrective repair.
Follow-up 2. When exactly did rollback stop being safe?
Answer: rollback stopped being safe when business dependency and operational cost exceeded recovery benefit. That moment defines the true point of no return, regardless of technical restore capability.
Follow-up 3. Curveball. Could this have been prevented?
Answer: yes, by enforcing rollback cost thresholds and authority gates earlier. If rollback cost is tracked as a first-class metric, teams can force decisions before economic irreversibility sets in.
Pro insider tip.
If rollback costs more than repair, rollback is already gone, even if the snapshot still exists.
Category 7 outro. The point of no return is not a technical line.
Category 7 incidents represent the moment where rollback ceases to be a technical option and becomes an illusion. In these scenarios, data has already escaped the system boundary into regulators, customers, models, caches, or external contracts. At this stage, restoring a snapshot may restore tables, but it cannot restore trust, legality, or business reality. The only viable response is containment, disclosure, and forward fix.
Transition from rollback failure to contract failure.
If Category 7 showed us when rollback is no longer possible, the next category explains why migrations fail even earlier than that. Category 8 focuses on contract breakage, schemas, identities, permissions, and assumptions changing while systems overlap. These failures are subtle, migration-specific, and often invisible until they permanently invalidate correctness.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs in a single zip file, containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, system design. Required for your data engineer interviews jobs like data quality analyst jobs, data governance analyst jobs, AWS Python data engineer jobs, AWS Redshift database administrator DBA jobs, AWS Glue ETL developer jobs, AWS data engineer jobs, cloud data engineer jobs, data architect jobs, DataOps engineer jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based questions and answers, real-world problem-solving, interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people also for your interviews. You people can download all 6 PDFs in a single zip file from below given links.
Category 8 Introduction. Schema, Contract and Identity Transition Incidents.
Category 8 incidents occur when data contracts change while multiple systems are live. Unlike pure data corruption, these failures alter meaning, visibility, or identity itself. Even when data appears present and pipelines are green, the contract between producers, consumers, and the warehouse is already broken. These are advanced migration failures that almost never appear in steady-state systems.
Category 8 Scenarios, Schema, Contract and Identity Transition Incidents.
The following incidents describe contract-level failures that occur only during overlapping system states. 60. Column added in source during dual-write window. 61. Encoding or compression change alters data semantics. 62. Backward incompatible view logic deployed mid-cutover. 63. BI semantic model updated before data consistency is established. 64. IAM role differences cause selective data invisibility. 65. Row-level security policies differ between source and Redshift. 66. Service accounts rotated during migration freeze. Core failure, contracts change while systems overlap.
Real-world incident during source to Redshift migration. 60. Column added in source during dual-write window.
During an AWS Redshift migration operating in a dual-write state, application teams deployed a schema change by adding a new column to the source system. The change was applied only to the source and not propagated to Redshift. CDC continued without errors, but the new business attribute was silently dropped, creating a contract mismatch between systems. Failure class, schema, contract and identity transition incident.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system write-enabled with active schema deployments. 2. Redshift cluster write-enabled under dual-write schema frozen for stability. 3. CDC pipeline running successfully without schema enforcement. 4. BI tools reading from Redshift and assuming schema completeness. 5. Declared source of truth ambiguous during dual-write window. 6. Authority status, split between source for writes and Redshift for analytics. Dual write without schema invariance creates silent contract drift.
Incident analysis and root cause.
This incident resulted from a broken schema governance assumption. 1. Triggering action deploying a new column in the source system during an active dual write phase. 2. Why it appeared safe, CDC pipelines remained green and no load failures occurred. 3. What teams noticed first, missing or null values for newly introduced business attributes in Redshift. 4. What teams did not notice that the new column never existed in the Redshift contract? 5. How divergence accumulated. New source data was written and consumed upstream but silently discarded downstream. 6. Missing invariant schema parity must be enforced across all writers during dual write.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it does not break pipelines or raise alarms. CDC succeeds, row counts match, and validations pass. The corruption is semantic. Business meaning is lost without visibility. Detection latency is often weeks, discovered only when downstream logic depends on the missing attribute.
What exactly broke? Consistency breakdown.
Domain level and semantic consistency are broken. The source system and Redshift no longer share the same data contract. Redshift becomes analytically incomplete for the affected domain. If we roll back only data, this inconsistency remains because schema divergence is not corrected by snapshot restoration.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Has Redshift accepted writes? Yes, dual write active. 2. Has the source schema changed post-cutover? Yes, new column added. 3. Can schema changes be replayed automatically? No, manual contract change. 4. Have downstream systems used incomplete data? Likely. 5. Can authority be restored cleanly? No, contract already consumed. Schema drift weakens rollback, even when data restore is possible.
Decision point, rollback versus forward fix.
Rollback is not sufficient because restoring snapshots does not restore the missing column or its business meaning. Forward fix is required to re-establish schema parity and reprocess affected data under an explicit contract.
Rollback architecture, state of rollback.
Rollback was not executed. Although cluster snapshots could restore data, they would not restore the missing schema element or downstream interpretations. CDC offsets would still replay data under the wrong contract, making rollback ineffective for restoring correctness.
Code illustration and Redshift artifacts.
In this section, we will show 1. How schema mismatch is detected between source and Redshift. 2. Why CDC success does not guarantee schema completeness. Schema drift is invisible to CDC unless explicitly enforced. Here is Redshift SQL showing missing columns that expose schema drift during dual write. Disclaimer: always test code in a non-production environment. This snippet proves the Redshift table schema. Comparing this output to the source schema reveals missing columns, confirming contract divergence even when CDC is healthy.
Containment and forward fix strategy.
Once schema drift is confirmed, containment must precede repair. 1. Immediately freeze further schema changes on the source. 2. Formally declare the schema contract version in effect. 3. Apply missing DDL changes to Redshift explicitly. 4. Backfill affected data ranges under the corrected schema. 5. Revalidate downstream logic and metrics before restoring trust. Data repair without schema repair only deepens semantic corruption.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Dual write requires strict schema invariance across systems. 2. CDC guarantees movement, not contract correctness. 3. Schema drift creates silent semantic data loss. Schema parity is a first-class invariant during migration.
Follow-up 1. Why didn't CDC fail when the column was added?
Answer: CDC focuses on row movement, not schema completeness. As long as existing columns map successfully, replication continues even if new business attributes are silently dropped. This makes the failure logical rather than operational.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe once data containing the new column was written and consumed upstream without ever existing in Redshift. At that point, restoring snapshots could not reconstruct lost business meaning.
Follow-up 3. Curveball. Could adding the column later fully fix this?
Answer: only partially. While the schema can be aligned going forward, historical rows that lost the attribute must be reprocessed from source. Without that, analytical truth remains permanently incomplete.
Pro insider tip.
If schemas are allowed to evolve during dual write, you are no longer migrating data. You are migrating broken contracts.
Real-world incident during source to Redshift migration 61. Encoding or compression change alters data semantics.
During an AWS Redshift migration, table encoding and compression strategies were modified to optimize storage and performance. Although the data loaded successfully and CDC reported no errors, subtle changes in numeric precision and string handling altered business semantics. These changes were not detected during initial validation and surfaced only after analytical discrepancies appeared. Failure class, schema, contract, and identity transition incident.
System state before failure, very important.
At the moment semantic drift was introduced, the system state was 1. Source system write-enabled with original data types and precision. 2. Redshift cluster write-enabled with modified encodings and compression applied. 3. CDC pipeline running successfully without data type validation. 4. BI tools reading from Redshift and assuming semantic equivalence. 5. Declared source of truth implicitly Redshift for analytics. 6. Authority status, assumed preserved without semantic verification. Physical optimizations can change meaning without changing shape.
Incident analysis and root cause.
This incident resulted from an optimization-first migration decision. 1. Triggering action changing column encodings or compression during migration to improve performance. 2. Why it appeared safe, data loaded cleanly and row counts matched across systems. 3. What teams noticed first, minor but persistent discrepancies in financial totals and ratios. 4. What teams did not notice, that rounding and truncation had already altered stored values. 5. How divergence accumulated, aggregations amplified small per row precision differences over time. 6. Missing invariant, semantic equivalence must be preserved across physical storage changes.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it passes all structural and volumetric validations. Data types appear compatible, pipelines remain green, and performance may even improve. The damage is semantic and cumulative, often detected only after significant business impact. Detection latency is typically weeks.
What exactly broke? Consistency breakdown.
Semantic and domain-level consistency are broken. Values stored in Redshift no longer represent the same business facts as the source, even though rows and columns align. If we roll back only data, this inconsistency remains because the altered encoding has already changed stored values.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Has Redshift applied new encodings or compression? Yes, semantics changed. 2. Can original precision be reconstructed from Redshift? No, information lost. 3. Would snapshot restore revert encoding only if taken before change? 4. Have aggregates been consumed externally? Likely. 5. Can authority be restored without reprocessing? No. Semantic loss is often irreversible without full reprocessing.
Decision point, rollback versus forward fix.
Rollback is only meaningful if a pre-encoding snapshot exists and downstream usage can be invalidated. In most cases, forward fix is required by reprocessing data from the source under strict semantic validation.
Rollback architecture, state of rollback.
Rollback was not executed. Although a cluster restore could revert physical storage, it would not address downstream consumption or semantic drift already embedded in reports. Restoring authority requires reprocessing, not just restoring blocks.
Code illustration and Redshift artifacts.
In this section, we will show 1. How precision drift is detected through value comparison. 2. Why compression and encoding changes alter business meaning. Physical storage decisions directly affect analytical truth. Here is Redshift SQL showing precision drift caused by encoding or compression changes. Disclaimer: always test code in a non-production environment. This aggregate amplifies small per row rounding differences. Comparing this result to the source total proves that encoding or compression has altered stored values, not just performance.
Containment and forward fix strategy.
Once semantic drift is confirmed, containment must precede repair. 1. Freeze further physical optimizations until semantics are validated. 2. Declare affected metrics unreliable for the impacted period. 3. Reprocess data from source using verified data types and precision. 4. Rebuild aggregates and dependent datasets. 5. Revalidate business metrics before restoring trust. Performance gains are meaningless if meaning is lost.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Encoding and compression are semantic decisions, not just performance tweaks. 2. Row counts and CDC health do not guarantee business correctness. 3. Semantic validation must precede optimization during migration. Semantic equivalence must be preserved before performance is optimized.
Follow-up 1. Why didn't validation catch this early?
Answer: validation focused on row counts and schema shape, not value-level equivalence. Small precision differences passed unnoticed until aggregates magnified them. This is a semantic failure, not a structural one.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe once aggregates built on altered values were consumed externally. At that point, restoring older snapshots would not undo decisions already made using corrupted semantics.
Follow-up 3. Curveball. Is this ever acceptable?
Answer: only if the semantic change is explicitly approved and communicated as a contract change. Silent semantic drift is never acceptable in a migration context.
Pro insider tip.
Treat encoding and compression changes as business contract changes. If you cannot explain their impact to finance or operations, you should not apply them during migration.
Real-world incident during source to Redshift migration 62. Backward incompatible view logic deployed mid-cut.
During an AWS Redshift migration, a backward incompatible change was deployed to one or more analytical views while systems were still in a partial cutover state. The new view logic assumed post-migration semantics and data availability, while downstream consumers were still relying on pre-migration contracts. This caused silent semantic breakage across reports and dependent queries. Failure class, schema, contract, and identity transition incident.
System state before failure, very important.
At the moment the incompatible view logic was introduced, the system state was 1. Source system write-enabled and still serving some analytical dependencies. 2. Redshift cluster partially authoritative for analytics during cutover. 3. CDC pipeline running and keeping tables structurally in sync. 4. Views actively used by BI tools and downstream consumers. 5. Declared source of truth ambiguous during migration window. 6. Authority status split between legacy semantics and new analytical logic. Views are contracts, not just query shortcuts.
Incident analysis and root cause.
This incident was caused by a contract violation during overlap. 1. Triggering action deploying a backward incompatible change to a shared view during cutover. 2. Why it appeared safe underlying tables existed and queries continued to run without errors. 3. What teams noticed first reports returning unexpected results or missing categories. 4. What teams did not notice that dependent consumers were still assuming the old view semantics. 5. How divergence accumulated. Different consumers interpreted the same view output differently over time. 6. Missing invariant. View logic must remain backward compatible while multiple systems depend on it.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it does not break pipelines or queries. All SQL executes successfully, dashboards refresh, and row counts may even look reasonable. The damage is contractual, business meaning changes silently. Detection latency is often days or weeks when users compare results across systems or time periods.
What exactly broke? Consistency breakdown.
Domain level and semantic consistency are broken. The same view name now represents different business logic than consumers expect. If we roll back only data, this inconsistency remains because dependent consumers have already adapted or misinterpreted the new logic.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Was the view logic changed in a backward incompatible way? Yes, contract broken. 2. Have downstream reports or queries adapted to the new logic? Likely. 3. Would restoring the old view logic break current consumers? Yes. 4. Is there a single authoritative definition of the metric? No. 5. Can authority be restored without coordinated consumer changes? No. View contract changes propagate faster than rollback can contain.
Decision point. Rollback versus forward fix.
Rollback of view logic alone is unsafe because consumers may already rely on the new semantics. Forward fix requires explicit versioning, consumer coordination, and a controlled transition to a single authoritative definition.
Rollback architecture, state of rollback.
Rollback was not executed. Although view definitions could technically be reverted, doing so would reintroduce inconsistency across dependent systems. Restoring authority requires contract reconciliation, not schema reversal.
Code illustration and Redshift artifacts.
In this section, we will show 1. How incompatible view definitions are detected via DDL comparison. 2. Why view logic changes represent contract violations during migration. Views encode business meaning, not just joins. Here is Redshift SQL showing how backward incompatible view logic is detected. Disclaimer: always test code in a non-production environment. Comparing this definition to the pre-migration version exposes removed columns, changed filters, or altered calculations. This proves that the view contract changed even though the view name remained the same.
Containment and forward fix strategy.
Once a view contract break is confirmed, containment must precede repair. 1. Freeze further view logic changes during cutover. 2. Version views explicitly instead of modifying them in place. 3. Declare one authoritative semantic definition. 4. Migrate consumers in a controlled, audited manner. 5. Retire legacy logic only after all consumers are aligned. Contracts must transition, not mutate.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Views are shared contracts, not implementation details. 2. Backward incompatible changes during cutover create semantic split brain. 3. Rollback cannot automatically realign dependent consumers. Semantic contracts must remain stable while authority overlaps.
Follow-up 1. Why didn't validation catch this immediately?
Answer: validation focused on query success and row counts, not semantic equivalence. Since the view still returned data, automated checks passed while business meaning had already changed.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe once downstream consumers adapted to or depended on the new view logic. At that point, reverting the view would break consumers rather than restore trust.
Follow-up 3. Curveball. How could this be avoided without freezing all changes?
Answer: by versioning views and migrating consumers explicitly. This preserves backward compatibility while allowing evolution without semantic ambiguity.
Pro insider tip.
If you change a view during migration, assume you are changing a business contract. Treat it with the same rigor as an API version change.
Real-world incident during source to Redshift migration 63. BI semantic model updated before data was consistent.
During an AWS Redshift migration, the BI semantic model was updated to align with the target Redshift schema before data consistency was fully established. Measures, dimensions, and calculated fields were redefined, while the underlying data was still incomplete or inconsistent. This caused dashboards to present internally consistent but fundamentally incorrect business narratives. Failure class, schema, contract, and identity transition incident.
System state before failure, very important.
At the moment the semantic model was updated, the system state was 1. Source system still authoritative for some domains and historical corrections. 2. Redshift cluster partially populated and under active validation. 3. CDC pipeline running with known gaps and lag. 4. BI semantic layer actively modified to match target schema and naming. 5. Declared source of truth not formally declared. 6. Authority status split between evolving BI logic and incomplete data. Semantic layers amplify errors faster than raw tables.
Incident analysis and root cause.
This incident was driven by premature contract alignment. 1. Triggering action updating BI semantic models before data consistency was proven. 2. Why it appeared safe, dashboards rendered successfully and metrics looked reasonable. 3. What teams noticed first, conflicting KPI interpretations across teams. 4. What teams did not notice, that the same metric now represented different data completeness levels. 5. How divergence accumulated, BI definitions masked missing or duplicated data over time. 6. Missing invariant, semantic models must not change until data authority is finalized.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it creates polished misinformation. BI tools show clean dashboards, consistent trends, and stable aggregates. The issue surfaces late, often during executive reviews, when numbers cannot be reconciled back to source reality.
What exactly broke? Consistency breakdown.
Domain level and semantic consistency are broken. The same business metric now encodes assumptions about data completeness that are no longer true. If we roll back only data, this inconsistency remains because the semantic layer has already redefined business meaning.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate: 1. Has the BI semantic model diverged from source definitions? Yes, contract drift. 2. Have dashboards been used for decisions? Likely. 3. Would restoring old data fix semantic assumptions? No. 4. Is there a single authoritative metric definition? No. 5. Can authority be restored without BI refactoring? No. Semantic drift survives data rollback.
Decision point, rollback versus forward fix.
Rollback of data alone is insufficient because BI logic has already diverged. Forward fix requires freezing semantic changes, reconciling metric definitions, and revalidating dashboards against a declared authoritative source.
Rollback architecture, state of rollback.
Rollback was not executed. Although data snapshots could be restored, semantic inconsistencies in BI models would persist. Restoring trust requires coordinated rollback of contracts, not just storage state.
Code illustration and Redshift artifacts.
In this section, we will show: 1. How metric definitions differ before and after semantic model changes. 2. Why data correctness cannot be inferred from BI outputs alone. BI layers hide inconsistency better than they reveal it. Here is Redshift SQL showing base data totals compared to BI exposed aggregates. Disclaimer: always test code in a non-production environment. Comparing this raw aggregate to BI reported totals exposes discrepancies introduced by semantic filters, joins, or assumptions applied before data was consistent.
Containment and forward fix strategy.
Once semantic drift is confirmed, containment must precede repair. 1. Freeze all BI semantic model changes. 2. Redeclare authoritative data sources and completeness criteria. 3. Align metric definitions with verified data state. 4. Rebuild dashboards after semantic reconciliation. 5. Audit and communicate corrected metrics explicitly. Semantic trust must be rebuilt explicitly.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Semantic layers are contracts layered on top of data authority. 2. Changing BI logic before data consistency creates polished misinformation. 3. Rollback cannot fix semantics once business meaning shifts. Business meaning must lag data authority, never lead it.
Follow-up 1. Why didn't validation catch this earlier?
Answer: validation focused on table-level checks, not semantic alignment. Since dashboards rendered successfully, teams assumed correctness while meaning had already drifted.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe once BI definitions were trusted and used for decisions. At that point, restoring data alone could not restore the original business meaning.
Follow-up 3. Curveball. What is the safest migration rule for BI teams?
Answer: never change semantic models until data authority and completeness are formally declared. BI must adapt after data stabilizes, not during uncertainty.
Pro insider tip.
If dashboards look clean during migration, be suspicious. BI tools are extremely good at hiding incomplete or inconsistent data.
Real-world incident during source to Redshift migration 64. IAM role differences cause selective data invisibility.
During an AWS Redshift migration, different IAM roles were used for validation, BI access, and operational queries. Although the underlying data was fully present in Redshift, permission differences caused some users and services to see incomplete datasets. This led teams to believe data was missing or corrupted when, in reality, access was selectively restricted. Failure class, schema, contract, and identity transition incident.
System state before failure, very important.
At the moment selective invisibility was introduced, the system state was: 1. Source system fully accessible to application and analytics roles. 2. Redshift cluster fully loaded with expected datasets. 3. IAM roles, multiple roles with different table, schema, or row-level permissions. 4. BI tools using a restricted IAM role or database user. 5. Declared source of truth, Redshift for analytics. 6. Authority status, fragmented by identity and access boundaries. Invisible data is indistinguishable from missing data to consumers.
Incident analysis and root cause.
This failure was caused by identity-level divergence rather than data corruption. 1. Triggering action, introducing new IAM roles or database users during migration without permission parity. 2. Why it appeared safe, queries succeeded and returned results without errors. 3. What teams noticed first, inconsistent row counts between different users and tools. 4. What teams did not notice, that permissions, not data, differed across access paths. 5. How divergence accumulated. Teams debugged data pipelines while the issue lived entirely in IAM. 6. Missing invariant. All migration validation must run under a single, authoritative access role.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it mimics real data loss. Validation queries pass for some roles and fail for others, creating contradictory evidence. Detection latency is high because access control is rarely included in data reconciliation checklists.
What exactly broke? Consistency breakdown.
Authority and domain-level consistency are broken. There is no single observable truth because different identities see different realities. If we roll back only data, this inconsistency remains because IAM state, not storage state, caused the divergence.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Is the underlying data actually missing? No data present. 2. Are discrepancies role-dependent? Yes, permission-based. 3. Would snapshot restore change visibility? No, IAM unchanged. 4. Have business users already distrusted Redshift outputs? Likely. 5. Can authority be restored without access unification? No. Rollback cannot fix identity-level inconsistency.
Decision point, rollback versus forward fix.
Rollback is ineffective because restoring data does not alter IAM permissions. Forward fix requires reconciling roles, grants, and access paths so that all consumers observe the same authoritative dataset.
Rollback architecture, state of rollback.
Rollback was not executed. Even a full cluster restore would reproduce the same IAM configuration. Authority recovery depends on identity alignment, not data reversion.
Code illustration and Redshift artifacts.
In this section, we will show 1. How permission differences cause the same query to return different results. 2. How system views expose role-based access discrepancies. Access control defines visibility, not data correctness. Here is Redshift SQL showing table visibility differences across users. Disclaimer: always test code in a non-production environment. Running this query under different roles reveals which tables are visible. Missing tables for certain users prove selective invisibility caused by permissions. Here is Redshift SQL showing role-based privilege differences. Disclaimer: always test code in a non-production environment. This output proves that access to the same table varies by role. Data discrepancies originate from identity configuration, not ingestion failure.
Containment and forward fix strategy.
Once permission-based divergence is confirmed, containment must precede repair. 1. Freeze IAM and database grant changes during migration. 2. Designate a single authoritative validation role. 3. Align all BI and consumer access to that role. 4. Audit and reconcile grants across environments. 5. Rerun validation under unified identity. Identity consistency is a prerequisite for data trust.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Data can be fully correct yet invisible due to IAM differences. 2. Validation without identity control produces false corruption signals. 3. Rollback cannot restore trust if access boundaries remain fractured. Authority requires both data correctness and identity alignment.
Follow-up 1. Why did teams assume data was missing?
Answer: because restricted roles returned fewer rows without errors. From the user perspective, invisibility is indistinguishable from data loss unless permissions are audited explicitly.
Follow-up 2. When did rollback stop being useful?
Answer: rollback was never useful in this scenario. The moment discrepancies were role-dependent, the issue moved out of data state and into identity state.
Follow-up 3, curveball. What single rule prevents this class of failure?
Answer: all migration validation and early BI access must run under one canonical role. Multiple identities during cut over guarantee contradictory truths.
Pro insider tip.
If two users see different row counts from the same table, stop debugging pipelines. Debug IAM first.
Real-world incident during source to Redshift migration. 65. Row-level security differs post-migration.
During an AWS Redshift migration, row-level security (RLS) policies were reimplemented or modified in the target environment. Although table-level data was fully migrated, differences in RLS predicates caused users to see filtered or incomplete result sets compared to the source system. This led to perceived data loss and conflicting analytical results across roles. Failure class, schema, contract, and identity transition incident.
System state before failure, very important.
At the moment RLS divergence was introduced, the system state was 1. Source system enforcing established row-level security rules. 2. Redshift cluster loaded with full datasets but using newly defined RLS policies. 3. CDC pipeline running successfully and replicating all rows. 4. BI tools accessing Redshift through roles subject to RLS filters. 5. Declared source of truth Redshift for analytics. 6. Authority status, fragmented by policy differences rather than data state. Row-level filters change truth without changing data.
Incident analysis and root cause.
This failure originated from policy-level mismatch rather than ingestion error. 1. Triggering action, recreating or adjusting row-level security rules during migration. 2. Why it appeared safe, queries executed successfully and returned plausible results. 3. What teams noticed first, certain users consistently saw fewer records than expected. 4. What teams did not notice, that filtering logic differed from the source system. 5. How divergence accumulated, different teams validated data under different RLS scopes. 6. Missing invariant, authorization predicates must be semantically identical across systems.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it produces believable but incomplete answers. Dashboards appear correct within a role's scope, masking the fact that global truth differs. Detection latency is high because row-level filtering is expected behavior and rarely audited during migration validation.
What exactly broke? Consistency breakdown.
Authoritative and domain-level consistency are broken. Different users observe different realities from the same tables. If we roll back only data, this inconsistency remains because the divergence is enforced by policy, not by stored rows.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Is the underlying data complete in Redshift? Yes, rows exist. 2. Do different roles return different row counts? Yes, policy-based. 3. Would snapshot restore change RLS behavior? No, policies persist. 4. Have consumers already trusted filtered results? Likely. 5. Can authority be restored without policy alignment? No. Rollback restores rows, not authorization semantics.
Decision point, rollback versus forward fix.
Rollback is ineffective because restoring snapshots does not reconcile row-level security logic. Forward fix requires explicit comparison, validation, and alignment of authorization rules to re-establish a single analytical truth.
Rollback architecture, state of rollback.
Rollback was not executed. Even a full cluster restore would reproduce the same row-level security definitions. Authority recovery depends on governance and policy parity, not data reversion.
Code illustration and Redshift artifacts.
In this section, we will show 1. How row counts differ across roles due to RLS filters. 2. How policy definitions reveal semantic divergence. Security predicates define visible truth. Here is Redshift SQL showing row count differences caused by row-level security. Disclaimer: always test code in a non-production environment. Running this query under different roles yields different counts, proving that RLS filters are altering observable truth without changing stored data. Here is Redshift SQL showing row-level security policy definitions. Disclaimer: Always test code in a non-production environment. Comparing these policy expressions against source system rules exposes semantic mismatches that caused post-migration divergence.
Containment and forward fix strategy.
Once RLS divergence is confirmed, containment must precede repair. 1. Freeze all authorization and RLS changes during migration. 2. Designate a canonical policy definition as authoritative. 3. Align Redshift RLS predicates with source semantics. 4. Revalidate analytics under a controlled representative role. 5. Document security assumptions as part of migration sign-off. Security is part of the data contract.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Row-level security can create the illusion of data loss. 2. Validation without policy parity produces false discrepancies. 3. Rollback cannot restore trust if authorization semantics differ. Authorization rules must preserve semantic equivalence.
Follow-up 1. Why was this mistaken for data corruption?
Answer: because users saw fewer rows without errors. From their perspective, filtered visibility looked identical to missing data, especially without cross-role validation.
Follow-up 2. When did rollback stop being a viable option?
Answer: rollback was never viable. The moment divergence was caused by row-level policies rather than storage state. Restoring snapshots could not recover a single authoritative view.
Follow-up 3. Curveball. What single control prevents this failure class?
Answer: enforcing policy parity checks as part of migration validation. If authorization logic is not validated alongside data, trust will fracture silently.
Pro insider tip.
If dashboards differ by role after migration, assume policy drift before assuming data loss.
Real-world incident during source to Redshift migration. 66. Service accounts rotated during migration freeze.
During an AWS Redshift migration, a planned cutover freeze was in effect while validation was ongoing. During this window, security teams rotated service account credentials and IAM roles as part of routine security hygiene. Migration pipelines and downstream consumers were not updated consistently, causing selective authentication failures and silent data access gaps. Failure class, schema, contract and identity transition incident.
System state before failure. Very important.
At the moment identity drift was introduced, the system state was 1. Source system operating normally with newly rotated service credentials. 2. Redshift cluster accessible only via pre-rotation IAM roles and secrets. 3. CDC pipeline running intermittently or failing authentication. 4. BI tools, some dashboards failing, others showing stale cached results. 5. Declared source of truth, Redshift for analytics. 6. Authority status, fragmented by identity and access inconsistencies. Identity drift creates invisible access fractures.
Incident analysis and root cause.
This failure was caused by uncoordinated identity lifecycle changes. 1. Triggering action, rotation of service accounts and IAM roles during the migration freeze. 2. Why it appeared safe, credential rotation is a routine security operation. 3. What teams noticed first, intermittent authentication failures and missing updates. 4. What teams did not notice, that different systems were operating under different identity assumptions. 5. How divergence accumulated. Some pipelines failed silently while cached data masked gaps. 6. Missing invariant, identity and access state must remain stable during migration freezes.
Why this failure is dangerous. Hidden risk.
This failure is dangerous because it looks like transient instability rather than structural drift. Some consumers continue working with cached or partial data, while others lose access entirely. Detection latency is high because failures are intermittent and often attributed to networking or transient auth issues.
What exactly broke? Consistency breakdown.
Authoritative and operational consistency are broken. Access to the same data depends on which credentials or roles a consumer is using. If we roll back only data, this inconsistency remains because the failure is rooted in identity state, not stored records.
Rollback viability checklist. Go or no go.
Before rollback is considered, the architect must evaluate. 1. Were service credentials rotated during freeze? Yes, identity drift introduced. 2. Can old credentials be safely restored? No security policy violation. 3. Did consumers observe access failures or stale data? Yes, trust impacted. 4. Would snapshot restore fix access gaps? No, IAM state unchanged. 5. Can authority be restored without identity alignment? No. Rollback cannot resurrect expired credentials.
Decision point: rollback versus forward fix.
Rollback is ineffective because restoring data does not restore expired credentials, rotated roles, or broken trust chains. Forward fix must focus on re-establishing a single, authoritative identity model and revalidating all access paths.
Rollback architecture, state of rollback.
Rollback was not executed. Identity state cannot be rolled back without violating security controls. Any attempt to restore prior credentials would introduce greater risk than proceeding with a controlled forward fix.
Code illustration and Redshift artifacts.
In this section, we will show 1. Authentication failures caused by expired or rotated service credentials. 2. Access gaps that prove identity-based divergence rather than data loss. Identity defines reachability, not data correctness. Here is Redshift SQL showing access failure under rotated service accounts. Disclaimer: always test code in a non-production environment. Comparing roles across failing and succeeding sessions exposes that different credentials are in use, proving identity drift rather than data corruption.
Containment and forward fix strategy.
Once identity drift is confirmed, containment must precede repair. 1. Freeze all credential and IAM changes during migration windows. 2. Designate a single authoritative set of service accounts. 3. Reissue and validate credentials across all pipelines and consumers. 4. Invalidate caches populated under partial access. 5. Rerun validation only after identity parity is restored. Identity stability is a migration invariant.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Identity changes can silently break migrations without touching data. 2. Rollback cannot restore expired credentials or trust chains. 3. Access parity is as critical as data parity during cutover. 4. Migration freezes must include security and IAM state. Identity invariants must be enforced alongside data invariants.
Follow-up 1. Why was this not immediately flagged as a migration failure?
Answer: because failures were intermittent and role-dependent. Some consumers continued working with cached data, masking the systemic identity break.
Follow-up 2. When did rollback stop being safe?
Answer: rollback was never safe. The moment credentials were rotated, the system entered an irreversible identity state that snapshots cannot undo.
Follow-up 3. Curveball. What single rule prevents this class of failure?
Answer: treat IAM, service accounts, and secrets as part of the migration freeze scope. If identity changes, migration authority is already broken.
Pro insider tip.
If authentication errors appear during migration, assume identity drift first, not network or data issues.
Category 8 wrap-up. When contracts shift, rollback stops being about data.
Schema, identity, and contract changes during migration expose a critical truth. Once systems disagree on structure, meaning, or access, data correctness alone cannot restore trust. At this stage, rollback failures are rarely technical. They are contractual and organizational.
Transition from broken contracts to persistent contamination.
The next class of incidents shows what happens when inconsistent data does not just exist temporarily, but is materialized, cached, or propagated into downstream systems. At that point, corruption no longer lives in one place, it spreads.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs in a single zip file, containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, system design. Required for your data engineer interviews jobs like data quality analyst jobs, data governance analyst jobs, AWS Python data engineer jobs, AWS Redshift database administrator DBA jobs, AWS Glue ETL developer jobs, AWS data engineer jobs, cloud data engineer jobs, data architect jobs, DataOps engineer jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based questions and answers, real-world problem solving. Interview questions and answers where almost 80% of the people are failing to answer. System design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section. These questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people also for your interviews. You people can download all 6 PDFs in a single zip file from below given links.
Category 9. Downstream materialization and cache incidents.
Downstream materialization and cache incidents occur when incorrect or partial data is baked into derived systems such as aggregates, materialized views, feature stores, or caches. Even if the source or Redshift is later corrected, these downstream artifacts often persist, making rollback incomplete or meaningless.
Category 9 Scenarios. Downstream materialization and cache incidents.
These scenarios illustrate how bad state becomes durable beyond the primary data store. 1. Pre-aggregated tables rebuilt on Redshift with bad historical data. 2. Materialized views refreshed from mixed or inconsistent sources. 3. Feature stores capturing snapshots during partial cut over windows. 4. Caches warmed while authority and consistency were not yet established. 5. Downstream APIs persisting corrupted or partial state. Core failure. Bad data becomes persistent elsewhere.
Real-world incident during source to Redshift migration 67. Pre-aggregated tables, rebuilt on Redshift with corrupted history.
During an AWS Redshift migration, base fact tables were partially inconsistent due to an earlier cutover issue. Before the inconsistency was detected or resolved, downstream pre-aggregated tables were rebuilt directly on Redshift. These aggregates baked incorrect historical state into durable tables, making later rollback of base data insufficient to restore analytical correctness. Failure class. Downstream materialization and cache incident.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system write-enabled and continuing to evolve business facts. 2. Redshift cluster hosting partially inconsistent base tables post-cutover. 3. CDC pipeline running but previously affected by upstream inconsistencies. 4. Pre-aggregated tables dropped and rebuilt on Redshift for performance. 5. BI and downstream systems, reading primarily from pre-aggregated tables. 6. Declared source of truth, implicitly assumed Redshift aggregates. 7. Authority status, shifted to derived tables without validating base truth. Derived tables inherited corruption from their inputs.
Incident analysis and root cause.
This incident occurred due to a misplaced optimization decision. 1. Triggering action, rebuilding pre-aggregated tables before base data correctness was formally re-established. 2. Why it appeared safe, aggregate rebuilds completed successfully and performance improved immediately. 3. What teams noticed first, KPIs stabilized but differed from historical benchmarks and source reports. 4. What teams did not notice, aggregates permanently encoded earlier base stable inconsistencies. 5. How divergence accumulated silently, downstream systems trusted aggregates, masking base-level corruption. 6. Missing invariant, aggregates must only be rebuilt after base tables are authoritative and stable.
Why this failure is dangerous, hidden risk.
This failure is dangerous because aggregates appear clean, fast, and stable. Once rebuilt, they stop reflecting base-stable corrections. Detection latency is often weeks, surfacing only when deep historical reconciliation is attempted.
What exactly broke? Consistency breakdown.
Domain level and temporal consistency are broken. Aggregated truth diverges from corrected base truth. If we roll back only base data, this inconsistency remains because derived tables retain the corrupted historical computation.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Were aggregates rebuilt after inconsistency occurred? Yes, corruption baked in. 2. Can aggregate rebuilds be safely rerun only after base authority restored? 3. Have downstream systems consumed aggregate outputs? Likely trust impact. 4. Is aggregate lineage and rebuild window documented? Often no. 5. Can authority be restored without aggregate rebuild? No. Rollback of base tables alone does not restore derived truth.
Decision point, rollback versus forward fix.
Rollback of base tables without rebuilding aggregates is ineffective. A forward fix that reestablishes base authority, followed by controlled aggregate invalidation and rebuild, is the only viable recovery path.
Rollback architecture.
Rollback requires discarding both base tables and all derived aggregates built after the corruption window. This includes restoring Redshift from a clean snapshot, disabling aggregate rebuild jobs, repointing BI tools to raw tables temporarily, invalidating caches, and obtaining governance approval before any rematerialization occurs.
Code illustration and Redshift artifacts.
In this section, we will show 1. How aggregate totals diverge from corrected base facts. 2. How rebuild timing proves aggregates encoded corrupted history. Derived data must be invalidated explicitly. Here is Redshift SQL showing aggregate totals diverging from base table truth. Disclaimer: always test code in a non-production environment. This snippet proves that the aggregate reflects a historical computation. Comparing this result with a recomputed SUM from corrected base tables exposes permanent divergence.
Containment and forward fix strategy.
Once aggregate contamination is confirmed, containment must precede repair. 1. Freeze all aggregate rebuild jobs immediately. 2. Redeclare base tables as the only provisional source of truth. 3. Invalidate all downstream reports using affected aggregates. 4. Rebuild aggregates only after base tables are revalidated. 5. Reintroduce aggregates under controlled governance approval. Never rebuild aggregates on untrusted foundations.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. Aggregates inherit all upstream mistakes and make them durable. Rollback must include derived data, not just raw tables. Performance optimizations must never precede correctness validation. Derived data must never become authoritative before base truth is established.
Follow-up 1. Why didn't row counts reveal this issue?
Answer: row counts validate table size, not semantic correctness. Aggregates can have perfectly stable row counts while encoding incorrect historical sums, masking corruption until reconciliation occurs.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe the moment aggregates were rebuilt on top of inconsistent base data. From that point onward, derived truth diverged permanently from raw truth.
Follow-up 3. What is the safest prevention control?
Answer: enforcing a hard rule that no derived or aggregated data may be rebuilt until base tables are explicitly declared authoritative and validated under governance control.
Pro insider tip.
If aggregates are rebuilt before correctness is proven, you have converted a temporary data issue into a permanent analytical lie.
Real-world incident during source to Redshift migration 68. Materialized views refreshed from mixed sources.
During an AWS Redshift migration, materialized views were automatically refreshed, while some underlying tables were already migrated to Redshift, and others were still being served from the source system. As a result, the materialized views captured a mixed authority snapshot, embedding inconsistent business state into a durable structure that survived later corrections. Failure class: downstream materialization and cache incident.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system write-enabled and serving some base tables. 2. Redshift cluster hosting a subset of migrated tables. 3. Materialized views enabled with automatic refresh. 4. CDC pipeline running with acceptable lag. 5. BI tools querying materialized views for performance. 6. Declared source of truth never formally defined during partial cutover. 7. Authority status implicitly delegated to materialized views. Materialized views snapshot whatever authority exists at refresh time.
Incident analysis and root cause.
This incident resulted from an unsafe interaction between automation and partial cutover. 1. Triggering action, allowing materialized views to refresh during a mixed source migration state. 2. Why it appeared safe, view refreshes completed successfully with no errors. 3. What teams noticed first, stable dashboards that disagreed with operational reports. 4. What teams did not notice that different base tables feeding the view came from different systems? 5. How divergence accumulated silently. Each refresh rematerialized mixed authority as durable truth. 6. Missing invariant. All inputs to a materialized view must share the same authoritative source.
Why this failure is dangerous, hidden risk.
This failure is dangerous because materialized views look deterministic and trustworthy. Once refreshed, they decouple analytics from later corrections in base tables. Detection latency is often long, surfacing only during deep audits or reconciliation.
What exactly broke? Consistency breakdown.
Domain level and authority consistency are broken. The materialized view encodes a state that never existed in any single system. If we roll back only data, this inconsistency remains because the view persists a mixed authority snapshot.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate 1. Were materialized views refreshed during partial cutover? Yes, mixed authority captured. 2. Can view refresh windows be precisely identified? Sometimes often unclear. 3. Have downstream systems consumed view outputs? Likely. 4. Can rollback invalidate materialized views automatically? No. 5. Can authority be restored without view rebuild? No. Materialized views must be explicitly invalidated.
Decision point, rollback versus forward fix.
Rollback of base tables alone is insufficient because materialized views persist independently. Recovery requires a forward fix that disables refresh, restores authoritative base state, and then rebuilds views under controlled conditions.
Rollback architecture.
Rollback requires restoring Redshift to a clean snapshot taken before any mixed source refresh, dropping or disabling all affected materialized views, invalidating BI caches, and re-establishing a single authoritative source before re-enabling view refresh under governance approval.
Code illustration and Redshift artifacts.
In this section, we will show 1. How materialized view definitions reference multiple base tables. 2. How refresh timing overlaps partial cut over windows. Automation amplifies authority mistakes. Here is Redshift SQL showing materialized view dependencies across mixed authority tables. Disclaimer: always test code in a non-production environment. This system view proves which base tables feed the materialized view. If these tables originate from different authoritative systems, the view encodes mixed truth.
Containment and forward fix strategy.
Once mixed source refresh is confirmed, containment must precede repair. 1. Disable automatic refresh on all affected materialized views. 2. Declare base tables as the only provisional source of truth. 3. Invalidate all BI outputs using affected views. 4. Restore base tables to a clean authoritative state. 5. Rebuild materialized views only after governance approval. Never refresh materialized views during partial cutover.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. Materialized views persist whatever authority exists at refresh time. Rollback must include invalidation of derived objects. Automation increases blast radius when authority is unclear. Derived automation must never outrun governance.
Follow-up 1. Why didn't CDC health metrics catch this?
Answer: CDC metrics track data movement, not how that data is combined downstream. Materialized views can refresh successfully while encoding logically inconsistent state.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe the moment the materialized view refreshed using mixed authority inputs. From that point, derived truth diverged permanently.
Follow-up 3. What is the single safest control?
Answer: disabling all automated materialization until a single authoritative source is formally declared and validated.
Pro insider tip.
If a materialized view refreshes during partial cutover, assume you have permanently poisoned derived truth.
Real-world incident during source to Redshift migration 69. Feature stores captured inconsistent snapshots during partial cutover.
During an AWS Redshift migration, downstream feature stores ingested data from Redshift while the migration was still in a partial cutover state. Some features were derived from Redshift tables, while others still depended on source-backed datasets. This caused machine learning and real-time systems to persist inconsistent feature snapshots that outlived the migration itself. Failure class, downstream materialization and cache incident.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system write-enabled and still authoritative for some domains. 2. Redshift cluster serving partially migrated datasets. 3. Feature store pipelines actively ingesting from Redshift. 4. CDC pipeline running with acceptable lag but incomplete authority. 5. ML and downstream services consuming feature snapshots. 6. Declared source of truth never formally established. 7. Authority status implicitly transferred to feature store outputs. Feature stores persist state long after migrations end.
Incident analysis and root cause.
This incident resulted from premature downstream consumption. 1. Triggering action allowing feature stores to ingest from Redshift before full cutover. 2. Why it appeared safe, feature pipelines ran successfully and produced stable outputs. 3. What teams noticed first, model behavior drift and inconsistent predictions. 4. What teams did not notice, that features were derived from mixed authority inputs. 5. How divergence accumulated silently. Each ingestion cycle reinforced inconsistent snapshots. 6. Missing invariant, feature stores must ingest only from a single authoritative source.
Why this failure is dangerous, hidden risk.
This failure is dangerous because feature stores decouple models and services from the original data systems. Once captured, inconsistent features propagate into models, caches, and decision systems. Detection latency is high and often surfaces only as degraded business outcomes.
What exactly broke? Consistency breakdown.
Domain level, temporal, and authority consistency are broken. The feature store encodes a snapshot that never existed in any single system. If we roll back only data, this inconsistency remains because features have already been materialized and consumed externally.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Have feature snapshots been materialized? Yes, persisted externally. 2. Can feature ingestion windows be precisely isolated? Rarely. 3. Have models or services consume the features? Yes. 4. Can rollback retract feature usage? No. 5. Can authority be restored retroactively? No. Once features are consumed, rollback is theoretical.
Decision point, rollback versus forward fix.
Rollback is no longer meaningful because feature stores and downstream systems have persisted inconsistent state. Forward fix must focus on freezing feature ingestion, rebaselining features from a single authoritative source, and retraining or revalidating dependent models.
Rollback architecture.
Rollback would require discarding all affected feature snapshots, invalidating downstream models, restoring Redshift to a pre-ingestion snapshot, and rerunning feature pipelines only after authority is formally declared. In practice, this level of destruction is rarely acceptable.
Code illustration and Redshift artifacts.
In this section, we will show 1. How feature ingestion timestamps align with partial cut over windows. Downstream persistence amplifies upstream ambiguity. Here is Redshift SQL showing feature ingestion occurring during partial cut. Disclaimer: always test code in a non-production environment. This snippet proves that feature ingestion occurred while Redshift was not yet authoritative, confirming that persisted features encode mixed truth.
Containment and forward fix strategy.
Once feature contamination is confirmed, containment must precede repair. 1. Immediately stop feature ingestion from Redshift. 2. Declare feature outputs invalid for the affected window. 3. Recompute features from a single authoritative source. 4. Retrain or revalidate dependent models. 5. Re-enable ingestion only after full cut over governance. Feature correctness is inseparable from authority correctness.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. Feature stores persist inconsistencies beyond migration. Rollback must consider downstream ML and decision systems. Authority must be enforced before feature ingestion. Features must be derived from declared truth.
Follow-up 1. Why is rollback ineffective once features are consumed?
Answer: because feature snapshots are copied into independent systems and models. Restoring Redshift does not retract already used features or undo decisions made from them.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe at the first successful feature ingestion from a non-authoritative Redshift state. From that point onward, inconsistency became persistent.
Follow-up 3. What is the safest preventive control?
Answer: hard gating all downstream ingestion until a single authoritative source is formally declared and validated.
Pro insider tip.
If feature stores ingest during partial cutover, assume every downstream model is now suspect.
Real-world incident during source to Redshift migration 70. Caches warmed during partial cut.
During an AWS Redshift migration, application and BI caches were proactively warmed using Redshift query results while the migration was still in a partial cutover state. Some cached responses were derived from Redshift, while others were still sourced from the legacy system. This caused stale and mixed authority data to persist long after the migration phase ended. Failure class: downstream materialization and cache incident.
System state before failure. Very important.
At the moment the failure was introduced, the system state was: 1. Source system write-enabled and authoritative for ongoing transactions. 2. Redshift cluster queried for analytics and application reads. 3. Cache layer actively warming responses from Redshift. 4. CDC pipeline running but not yet authority safe. 5. Applications and BI tools reading from caches instead of live systems. 6. Declared source of truth, not formally declared. 7. Authority status indirectly transferred to cached results. Caches persist answers long after authority changes.
Incident analysis and root cause.
This incident was caused by premature optimization during migration. 1. Triggering action, warming application and BI caches using Redshift before full cutover. 2. Why it appeared safe, cached queries returned fast and consistent results. 3. What teams noticed first, users saw different answers depending on cache hit or miss. 4. What teams did not notice that cached values were derived from a non-authoritative state. 5. How divergence accumulated silently. Cached TTLs extended the lifetime of bad answers. 6. Missing invariant. Caches must only be populated from an authoritative source.
Why this failure is dangerous. Hidden risk.
This failure is dangerous because caches decouple consumers from live data systems. Even after authority is corrected, cached answers continue to circulate. Detection latency is high because cache hits mask the underlying inconsistency.
What exactly broke? Consistency breakdown.
Authoritative and temporal consistency are broken. Cached responses represent a state that was never globally true. If we roll back only data, this inconsistency remains because caches continue serving previously materialized answers.
Rollback viability checklist. Go or no go.
Before rollback is considered, the architect must evaluate. 1. Have caches been populated from Redshift? Yes, mixed authority persisted. 2. Can all cache entries be invalidated globally? Rarely. 3. Have users consumed cached responses? Yes. 4. Can rollback retract served responses? No. 5. Can authority be restored without cache purge? No. Cached truth outlives database truth.
Decision point. Rollback versus forward fix.
Rollback of Redshift alone is ineffective because cached answers continue to circulate. Forward fix must focus on cache invalidation, authority declaration, and controlled rewarming after migration completion.
Rollback architecture.
A theoretical rollback would require invalidating all caches, restoring Redshift to a pre-warmed snapshot, repointing applications to a single authoritative source, and rewarming caches only after governance approval. In practice, cache reach often makes this infeasible.
Containment and forward fix strategy.
Once cache contamination is confirmed, containment must precede repair. 1. Immediately disable cache warming jobs. 2. Force cache invalidation across all layers. 3. Declare a single authoritative data source. 4. Rewarm caches only after authority is restored. 5. Add migration-aware cache guards for future cutovers. Caches must never decide authority.
Interview framing. Extremely important.
How would you explain this in an interview? Here are the key talking points. Caches can persist incorrect answers beyond migration windows. Rollback must account for non-database state like caches. Authority must be established before any cache warming. Authoritative truth must precede performance optimization.
Follow-up 1. Why don't cache metrics reveal this issue?
Answer: cache hit rates and latency only measure performance, not correctness. A cache can be perfectly healthy while serving incorrect or mixed authority data for long periods.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe the moment caches were warmed from a non-authoritative Redshift state. From that point on, incorrect answers were already externalized.
Follow-up 3. What single control prevents this?
Answer: hard blocking cache warming until a single authoritative source is formally declared and validated.
Pro insider tip.
If you warm caches during partial cutover, assume you have extended the blast radius of inconsistency far beyond the database.
Real-world incident during source to Redshift migration 71. Downstream APIs persisting corrupted state.
During an AWS Redshift migration, downstream APIs began persisting responses derived from Redshift into their own storage layers, while the migration was still in a partial cutover state. These APIs treated Redshift responses as authoritative and wrote them into application databases and object stores. When inconsistencies were later discovered, corrupted state had already been permanently materialized outside Redshift. Failure class, downstream materialization and cache incident.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system rights enabled and authoritative for operational truth. 2. Redshift cluster queried by downstream APIs for read-heavy workflows. 3. CDC pipeline running with lag and without final authority declaration. 4. Downstream APIs persisting Redshift-derived responses into their own databases. 5. Caches and storage layers, treating API outputs as durable truth. 6. Declared source of truth not formally established. 7. Authority status implicitly transferred to downstream services. Once APIs persist data, authority permanently shifts outward.
Incident analysis and root cause.
This incident resulted from ungoverned downstream rights during migration. 1. Triggering action, allowing downstream APIs to persist Redshift query results during partial cutover. 2. Why it appeared safe, API responses looked correct and passed functional tests. 3. What teams noticed first, inconsistent behavior between API-backed features and source-driven systems. 4. What teams did not notice, that APIs had already stored corrupted state independently. 5. How divergence accumulated silently, each API call reinforced and expanded the corrupted dataset. 6. Missing invariant downstream systems must not persist data until authority is final.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it multiplies the blast radius. Corrupted data is no longer confined to Redshift, but embedded in multiple downstream systems. Detection latency is high because API correctness is assumed once responses are stored.
What exactly broke? Consistency breakdown.
Authoritative and referential consistency are broken. Downstream systems now contain data that does not correspond to any single authoritative timeline. If we roll back only data, this inconsistency remains because downstream stores have already persisted corrupted state.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Have downstream APIs persisted Redshift-derived data? Yes, externalized corruption. 2. Can all downstream stores be identified? Often no. 3. Can persisted API data be fully invalidated? Rarely. 4. Have consumers acted on API outputs? Yes. 5. Can authority be restored without downstream rewrites? No. Persisted API state outlives any database rollback.
Decision point. Rollback versus forward fix.
Rollback of Redshift does not restore correctness because downstream systems retain corrupted state. Forward fix must focus on identifying affected systems, invalidating persisted data, and rehydrating from a single authoritative source.
Rollback architecture.
A theoretical rollback would require restoring Redshift to a clean snapshot, halting all downstream writes, invalidating or purging API-backed stores, repointing APIs to the authoritative source, and reprocessing all persisted data. In practice, this is rarely feasible once external systems are involved.
Containment and forward fix strategy.
Once downstream persistence is confirmed, containment must precede repair. 1. Immediately block downstream APIs from persisting Redshift-derived data. 2. Inventory all systems that stored API outputs. 3. Declare a temporary authoritative source for rehydration. 4. Purge or quarantine corrupted downstream datasets. 5. Rebuild downstream state only after authority is restored. Downstream writes must be explicitly gated during migration.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. Downstream systems can permanently persist migration mistakes. Rollback must account for every system that materialized data. Authority cannot be implicit when APIs write state. Authority must be declared before data is allowed to escape.
Follow-up 1. Why is this worse than cache contamination?
Answer: caches can be invalidated, but persisted API data becomes part of business state. Once written, it must be explicitly identified and repaired across multiple systems.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe the moment downstream APIs persisted Redshift-derived responses. At that point, corrupted data escaped the database boundary.
Follow-up 3. What single rule would have prevented this?
Answer: a hard rule that no downstream system may persist data until a single authoritative source is formally declared and enforced.
Pro insider tip.
If an API writes data during migration, treat it as a database with its own rollback problem.
Category 9. Wrap-up. Why downstream propagation is a point of no return.
Category 9 incidents demonstrate that once corrupted data is materialized outside Redshift, the database is no longer the containment boundary. Pre-aggregations, caches, feature stores, and APIs turn transient migration mistakes into durable business state. At that point, rollback becomes a multi-system recovery problem rather than a database operation.
Transition from propagated data to physical truth.
If Category 9 shows how bad data escapes Redshift, the next category shows something more subtle and more dangerous. Even when data is correct, Redshift's physical execution semantics can change its meaning. Here, rollback restores rows but not behavior.
Category 10. Physical storage and execution semantics incidents.
These incidents are Redshift-specific and often misunderstood. Data loads succeed, counts match, and validation passes, yet analytical results drift because physical layout, execution plans, and storage characteristics differ from expectations. Rollback restores data, not how Redshift executes queries against it.
Category 10 scenarios.
The following incidents illustrate how physical design choices silently alter analytical truth. 1. Copy succeeded but distribution skew differs from source. 2. Vacuum or analyze changes query plans mid-migration. 3. Sort key mismatch causes windowing and ranking inconsistencies. 4. Compression encoding change causes rounding or precision drift. 5. Encryption enablement failures during snapshot restore cause selective invisibility or restore failure. Core failure. Physical layout affects analytical truth.
Real-world incident during source to Redshift migration 72. Copy succeeded, but distribution skew differs from source.
During an AWS Redshift migration, data was loaded successfully using copy from the source system. Row counts matched and no load errors were reported. However, the physical data distribution in Redshift differed significantly from the source, creating severe skew. This skew altered join behavior, execution plans, and query correctness under load, even though validation initially passed. Failure class, physical storage and execution semantics incident.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system evenly distributed data with stable query performance. 2. Redshift cluster newly loaded via copy with default or incorrect distribution keys. 3. Data load method bulk copy completed without errors. 4. CDC pipeline not yet started or lagging behind snapshot. 5. BI tools pointed to Redshift for validation and early reporting. 6. Declared source of truth implicitly assumed Redshift post load. 7. Authority status assumed valid based on row count and load success. Physical layout differences are invisible to logical validation.
Incident analysis and root cause.
This failure originated from a physical design assumption. 1. triggering action performing copy without explicitly aligning distribution keys to source access patterns. 2. Why it appeared safe, copy completed successfully and row counts matched expected values. 3. What teams noticed first, queries became slower and produced inconsistent results under concurrent load. 4. What teams did not notice, that data was unevenly distributed across Redshift slices. 5. How divergence accumulated, query planners changed join strategies due to skew, altering execution semantics. 6. Missing invariant physical data distribution must preserve access symmetry to maintain analytical correctness.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it passes all early validation checks. Copy succeeds, counts match, and queries return results. The corruption appears only under realistic workloads, where skewed slices dominate execution, causing timeouts, partial joins, or inconsistent aggregations. Detection latency is often weeks, surfacing only after production load.
What exactly broke? Consistency breakdown.
Execution and analytical consistency are broken. Identical logical queries no longer behave equivalently to the source due to skew-driven plan changes. If we roll back only data, this inconsistency remains because physical distribution and execution behavior are not restored by logical reloads alone.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Did copy complete without errors? Yes, logical load succeeded. 2. Is distribution skew present? Yes, slice imbalance detected. 3. Can snapshot restore fixed skew? No, skew is encoded in table design. 4. Have BI queries relied on current execution plans? Likely. 5. Can authority be restored without physical redesign? No. Rollback restores data, not execution semantics.
Decision point, rollback versus forward fix.
Rollback does not resolve this failure because restoring snapshots reproduces the same skewed distribution. Forward fix is required to redesign physical layout, rebalance data, and revalidate execution behavior before authority can be reestablished.
Rollback architecture, if executed.
A rollback would require discarding the skewed Redshift cluster entirely and restoring a snapshot only as a staging point. Tables would need to be unloaded to S3, recreated with corrected distribution keys, and reloaded. BI access must be revoked during this process, downstream extracts invalidated, and governance approval obtained before any recut over. Partial or table-level rollback is unsafe unless full domain isolation is guaranteed.
Code illustration and Redshift artifacts.
In this section, we will show 1. How distribution skew is detected using Redshift system tables. 2. How query plans change due to skewed data placement. 3. Why rollback cannot restore correct execution behavior. 4. How forward fix rebalances data to restore correctness. Physical skew directly alters analytical truth. Here is Redshift SQL showing distribution skew via svv_table_info. Disclaimer: always test code in a non-production environment. This metric exposes uneven row distribution across slices. High skew proves that copy loaded data in a way that concentrates workload on a subset of nodes, breaking execution balance. Here is explain output showing skew-driven join plan changes. Disclaimer: always test code in a non-production environment. This plan reveals broadcast or redistributed joins caused by skew. The change in join strategy proves that physical layout, not data correctness, is altering query behavior. Here is SQL illustrating why snapshot rollback reproduces the same skew. Disclaimer: always test code in a non-production environment. Persistent slice concentration after restore confirms that snapshots preserve skew. Rolling back data does not restore balanced execution. Here is Redshift SQL showing forward fix via table, rebuild with corrected distribution. Disclaimer: always test code in a non-production environment. Rebuilding the table with an appropriate distribution key redistributes data evenly. This is the only way to restore execution correctness and analytical trust.
Containment and forward fix strategy.
Once skew is confirmed, containment must precede repair. 1. Suspend BI workloads that depend on skewed tables. 2. Declare Redshift analytically unreliable until physical layout is corrected. 3. Rebuild affected tables with correct distribution and sort keys. 4. Run vacuum and analyze to stabilize execution plans. 5. Revalidate queries under production-like concurrency before restoring trust. Physical correctness must precede analytical authority.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Copy success does not guarantee correct physical data distribution. 2. Distribution skew alters join strategies and query semantics. 3. Rollback restores data but not execution behavior. 4. Physical design is part of data correctness in Redshift. Analytical truth depends on physical layout, not just logical data.
Follow-up 1. Why didn't validation catch the skew?
Answer: validation focused on row counts and sample queries, which do not stress execution paths. Skew manifests only under distributed joins and concurrent workloads, where slice imbalance dominates performance and correctness.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe once BI workloads relied on Redshift execution behavior. At that point, restoring snapshots would reproduce the same skew and reintroduce the same analytical failures.
Follow-up 3. Curveball, can concurrency scaling hide skew?
Answer: temporarily, yes. Concurrency scaling can mask skew by adding capacity, but it does not fix distribution. Once scaling limits are hit, the same failures reappear with greater severity.
Pro insider tip.
If SVV_table_info shows skew before cutover, stop the migration. Fixing skew after authority is declared is exponentially more expensive than rebuilding early.
Real-world incident during source to Redshift migration 73. Vacuum or analyze changed query plans mid-migration.
During an AWS Redshift migration, routine maintenance operations such as vacuum and analyze were executed mid-migration to improve performance. Although no data changed and row counts remained identical, query execution plans shifted significantly. This altered join order, distribution behavior, and execution timing, causing analytical results and performance characteristics to diverge from pre-migration expectations. Failure class, physical storage, and execution semantics incident.
System state before failure, very important.
At the moment the failure was introduced, the system state was: 1. Source system stable execution plans and predictable query behavior. 2. Redshift cluster data fully loaded and undergoing validation. 3. Maintenance activity vacuum and analyze executed during migration window. 4. CDC pipeline running or paused independently of maintenance. 5. BI tools actively querying Redshift and comparing results. 6. Declared source of truth not formally declared, assumed stable. 7. Authority status assumed safe due to unchanged data. Execution behavior can change without data changing.
Incident analysis and root cause.
This failure resulted from a hidden execution assumption. 1. Triggering action running vacuum or analyze during active migration validation. 2. Why it appeared safe. These operations are considered non-functional and data-preserving. 3. What teams noticed first. Queries became faster or slower and returned different execution characteristics. 4. What teams did not notice. That optimizer statistics and sort order had materially changed. 5. How divergence accumulated. New execution plans altered join order and data access paths. 6. Missing invariant. Execution plans must remain stable during validation windows.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it produces behavioral drift without data drift. Validation queries still return results, but the meaning of performance baselines and execution assumptions is lost. Detection latency is often high, discovered only when production workloads behave differently than validated workloads.
What exactly broke? Consistency breakdown.
Execution and performance consistency are broken. Identical queries no longer execute with the same semantics or guarantees. If we roll back only data, this inconsistency remains because optimizer state and statistics are not reverted with data alone.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Has data content changed? No data identical. 2. Have optimizer statistics changed? Yes, analyze executed. 3. Can snapshot restore revert optimizer state partially not deterministic? 4. Have BI workloads relied on new plans likely? 5. Can execution behavior be made identical via rollback alone? No, execution state is not fully rollbackable.
Decision point, rollback versus forward fix.
Rollback does not guarantee restoration of prior execution behavior. Forward fix is required to explicitly control maintenance timing, lock validation windows, and rebaseline performance expectations before declaring authority.
Rollback architecture, if executed.
A rollback would require restoring a pre-maintenance snapshot and blocking any automated vacuum or analyze jobs. BI access must be disabled during restore, downstream extracts invalidated, and execution baselines revalidated. Partial rollback is unsafe because optimizer drift can reoccur immediately after restore.
Code illustration and Redshift artifacts.
In this section, we will show 1. How execution plans change before and after analyze. 2. How optimizer statistics differ despite identical data. 3. Why rollback cannot guarantee plan stability. 4. How forward fix controls execution behavior. Optimizer state directly affects analytical behavior. Here is explain output before vacuum or analyze execution. Disclaimer: always test code in a non-production environment. This plan represents the baseline execution behavior used during initial validation. It establishes the expected join order and distribution strategy. Here is explain output after vacuum or analyze execution. Disclaimer: always test code in a non-production environment. Running analyze updates optimizer statistics. The subsequent plan change proves that execution behavior can shift even when data is unchanged. Here is Redshift system, view SQL showing statistics changes. Disclaimer: always test code in a non-production environment. Changes in statistics freshness confirm why the optimizer recalculated execution plans, altering query behavior. Here is SQL illustrating forward fix via controlled maintenance windows. Disclaimer: always test code in a non-production environment. Disabling automatic statistics updates during migration prevents unplanned execution drift and preserves validation integrity.
Containment and forward fix strategy.
Once execution drift is confirmed, containment must precede repair. 1. Freeze vacuum and analyze during migration validation. 2. Rebaseline execution plans explicitly. 3. Communicate performance expectation changes to stakeholders. 4. Re-enable maintenance only after authority is declared. 5. Revalidate under production-like concurrency. Execution stability is part of data correctness.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Vacuum and analyze can change query behavior without changing data. 2. Validation assumes execution stability, which must be enforced. 3. Rollback restores data, not optimizer state. 4. Maintenance timing is a migration-critical control. Execution semantics are as important as data correctness.
Follow-up 1. Why didn't data validation catch this?
Answer: validation focused on result correctness, not execution behavior. As long as queries returned results, plan drift went unnoticed until performance and concurrency changed under load.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe once BI teams accepted new performance baselines. At that point, restoring older plans would invalidate validated expectations and trust.
Follow-up 3. Curveball. Can snapshots preserve optimizer state?
Answer: only partially. While snapshots restore data and metadata, optimizer decisions are recalculated dynamically. You cannot rely on snapshots to guarantee identical execution plans.
Pro insider tip.
If you allow analyze during validation, you are validating a moving target. Freeze optimizer state before you trust any performance comparison.
Real-world incident during source to Redshift migration 74. Sort key mismatch caused windowing inconsistencies.
During an AWS Redshift migration, tables were created with sort keys that differed from the source system's effective ordering. While row counts and values matched, analytical queries using window functions began producing inconsistent results. Pagination, ranking, and running aggregates behaved differently across executions, undermining analytical correctness. Failure class, physical storage and execution semantics incident.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system tables ordered implicitly by clustered index or primary key. 2. Redshift cluster tables created with default or mismatched sort keys. 3. Data state fully loaded with matching row counts. 4. CDC pipeline not contributing to ordering differences. 5. BI tools executing window functions for ranking, pagination, and trends. 6. Declared source of truth, assumed Redshift after validation. 7. Authority status, assumed safe due to identical data values. Ordering assumptions are part of analytical truth.
Incident analysis and root cause.
This failure resulted from a physical layout assumption. 1. Triggering action creating Redshift tables without aligning sort keys to source ordering semantics. 2. Why it appeared safe aggregates and row-level comparisons matched during validation. 3. What teams noticed first window functions return different ranks in pagination order across runs. 4. What teams did not notice that Redshift does not guarantee order without explicit sort keys. 5. How divergence accumulated. Parallel execution and redistribution changed row ordering deterministically but unexpectedly. 6. Missing invariant window function ordering must be explicitly preserved via physical sort keys.
Why this failure is dangerous, hidden risk.
This failure is dangerous because results look correct in isolation, but differ across executions. Queries succeed, numbers appear plausible, yet ordering-dependent logic becomes unstable. Detection latency is high, often surfacing only when users notice pagination shifts or inconsistent rankings.
What exactly broke? Consistency breakdown.
Execution and temporal ordering consistency are broken. Analytical queries relying on deterministic order no longer produce stable results. If we roll back only data, this inconsistency remains because physical sort order is not restored by data rollback alone.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Has data content changed? No values identical. 2. Are sort keys misaligned with query semantics? Yes, root cause persists. 3. Would snapshot restore fix ordering? No same table definitions. 4. Have downstream systems relied on unstable ordering? Likely. 5. Can authority be restored via rollback alone? No physical layout unchanged. Rollback does not restore ordering guarantees.
Decision point, rollback versus forward fix.
Rollback is ineffective because it preserves the same physical table layout. Forward fix is required to redefine sort keys, rebuild tables, and revalidate all ordering-dependent analytics.
Rollback architecture, if executed.
A rollback would restore data but reintroduce the same sort key mismatch. BI queries would remain unstable. Therefore, rollback must be paired with table rebuilds using corrected sort keys, full data reloads, cache invalidation, and governance approval before re-enabling analytics.
Code illustration and Redshift artifacts.
In this section, we will show 1. How window functions behave without aligned sort keys. 2. How repeated executions produce different ordering. 3. Why rollback cannot stabilize window results. 4. How forward fix restores deterministic ordering. Physical sort order defines analytical determinism. Here is Redshift SQL showing unstable window function, ordering without aligned sort keys. Disclaimer: always test code in a non-production environment. This snippet relies on deterministic ordering. Without a matching sort key on order_date, parallel execution can yield inconsistent row numbering across runs. Here is Redshift system, view SQL showing sort key definition. Disclaimer: always test code in a non-production environment. This exposes the actual physical sort key. A mismatch between this and window order by columns explains the instability. Here is Redshift SQL showing that snapshot restore preserves sort key mismatch after rollback. Disclaimer: always test code in a non-production environment. This proves that restoring a snapshot does not change physical table design. The sort key remains misaligned, confirming that rollback restores data but not execution semantics. Here is SQL illustrating forward fix via table rebuild with correct sort key. Disclaimer: always test code in a non-production environment. Rebuilding the table with an aligned sort key restores deterministic execution for window functions and pagination.
Containment and forward fix strategy.
Once ordering instability is confirmed, containment must precede repair. 1. Disable ordering-dependent analytics temporarily. 2. Rebuild affected tables with correct sort keys. 3. Revalidate window functions under concurrency. 4. Invalidate cached results in downstream extracts. 5. Redeclare Redshift authoritative only after stability is proven. Ordering correctness must be engineered, not assumed.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Window functions require deterministic physical ordering. 2. Redshift does not guarantee order without explicit sort keys. 3. Rollback restores data, not execution semantics. 4. Physical design choices directly affect analytical correctness. Execution semantics are part of data correctness.
Follow-up 1. Why didn't validation catch this issue?
Answer: validation focused on aggregates and row counts, which are order-insensitive. Ordering-dependent logic only failed under repeated execution and concurrency, which was not tested.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe once downstream systems relied on unstable ordering. At that point, restoring prior data without fixing sort keys would perpetuate incorrect behavior.
Follow-up 3. Curveball. Can order by inquiries fix this permanently?
Answer: no. Order by inquiries enforces presentation order, not execution determinism. Without aligned sort keys, parallel processing can still introduce instability.
Pro insider tip.
If a query depends on order, the table must too. Window functions expose physical design flaws faster than any validation report.
Real-world incident during source to Redshift migration 75. Compression encoding change causes rounding or precision drift.
During an AWS Redshift migration, tables were recreated using Redshift-recommended compression encodings to optimize storage and performance. While the data loaded successfully and row counts matched, subtle rounding and precision differences appeared in numeric columns compared to the source system. These differences accumulated in aggregates and financial reports, creating silent semantic drift that rollback could not correct. Failure class, physical storage, and execution semantics incident.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system, write-enabled relational database storing high-precision numeric values. 2. Redshift cluster, newly created tables using automatic or recommended compression encodings. 3. Data load mechanism, copy from S3 snapshots completed successfully. 4. CDC pipeline, either not yet started or already caught up. 5. BI and downstream systems, pointed to Redshift for validation and reporting. 6. Declared source of truth, implicitly Redshift after data load. 7. Authority status, assumed preserved without validating numeric semantics. Physical optimization was applied without validating semantic equivalence.
Incident analysis and root cause.
This failure originated from a storage-level assumption. 1. Triggering action, recreating tables in Redshift with different compression encodings than the source system. 2. Why it appeared safe, data loaded cleanly, row counts matched, and no load errors were reported. 3. What teams noticed first, small but persistent differences in financial totals and ratio-based KPIs. 4. What teams did not notice, that numeric values were being stored with different precision characteristics. 5. How divergence accumulated, minor rounding differences compounded across aggregations and time. 6. Missing invariant, numeric precision and scale must be preserved end-to-end during migration.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it produces believable numbers that are subtly wrong. Monitoring shows healthy pipelines, validations pass at row level, and discrepancies are small enough to evade early detection. Detection latency is typically weeks or months, often discovered during audits or financial reconciliation.
What exactly broke? Consistency breakdown.
Semantic and numerical consistency are broken. The same business facts are represented with different precision, causing aggregates to diverge over time. Redshift is no longer trustworthy for metrics dependent on exact numeric fidelity. If we roll back only data, this inconsistency remains because compression encoding defines how values are physically stored and interpreted.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate 1. Were tables recreated with different encodings? Yes, physical drift present. 2. Would snapshot restore change encodings? No encodings are preserved. 3. Have aggregates already been published, likely trust impacted? 4. Can original precision be reconstructed only by rebuild? 5. Can authority be restored without rebuild? No. Rollback restores data state, not physical encoding semantics.
Decision point, rollback versus forward fix.
Rollback is not sufficient because restoring a snapshot preserves the same compression encodings. Forward fix requires explicit table rebuilds with correct precision guarantees and full revalidation of all affected metrics.
Rollback architecture.
Rollback would involve restoring the cluster snapshot, but this does not correct encoding-induced drift. CDC offsets would remain valid, BI tools would still point to Redshift, and downstream consumers would continue seeing semantically altered values. Rollback is therefore destructive without benefit and should not be executed.
Code illustration and Redshift artifacts.
In this section, we will show 1. How numeric precision differences are detected in Redshift results. 2. How compression encodings differ at the system catalog level. 3. Why snapshot rollback preserves the same encoding. 4. How forward fix restores semantic precision. Encoding defines meaning, not just storage efficiency. Here is Redshift SQL showing numeric precision drift in aggregated results. Disclaimer: always test code in a non-production environment. This aggregate exposes small but consistent differences compared to the source system, proving that numeric precision has drifted despite identical row counts. Here is Redshift system table, SQL showing compression encoding, applied to numeric columns. Disclaimer: always test code in a non-production environment. This confirms that the numeric column uses a compression encoding that alters how values are stored and reconstructed, explaining the observed rounding behavior. Here is Redshift SQL showing that snapshot rollback preserves compression encoding. Disclaimer: always test code in a non-production environment. Running this after a snapshot restore shows identical encodings, proving rollback does not restore original numeric semantics. Here is Redshift SQL showing forward fix via table rebuild with controlled precision. Disclaimer: always test code in a non-production environment. This rebuild enforces explicit precision and scale, restoring semantic equivalence with the source system and preventing further rounding drift.
Containment and forward fix strategy.
Once encoding-induced drift is confirmed, containment must precede repair. 1. Pause publication of affected metrics. 2. Declare existing aggregates semantically unreliable. 3. Rebuild affected tables with explicit precision definitions. 4. Recompute all dependent aggregates. 5. Revalidate against source before restoring trust. Physical rebuild is the only safe repair.
Interview framing.
How would you explain this in an interview? Here are the key talking points. 1. Compression is a semantic decision for numeric data, not just a performance one. 2. Row counts and CDC health do not guarantee numeric correctness. 3. Rollback restores state, not physical representation. 4. Explicit precision is a migration invariant, not an optimization. Numeric semantics must be preserved before performance is optimized.
Follow-up 1. Why didn't validation catch this earlier?
Answer: early validation focused on row counts and spot checks, which do not reveal small numeric drift. Because the differences were within expected ranges, alarms never fired. The failure surfaced only when aggregates accumulated error over time.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe once tables were recreated with new encodings. From that moment, every snapshot preserved altered numeric semantics, making rollback incapable of restoring original meaning.
Follow-up 3. What is the single control that would have prevented this?
Answer: mandating explicit precision and scale definitions for all numeric columns before enabling compression. Performance tuning must always follow semantic preservation, never precede it.
Pro insider tip.
If financial totals differ by cents after migration, inspect compression encodings before blaming data. Precision drift is usually physical, not logical.
Real-world incident. During source to Redshift migration 76, encryption enablement failures cause selective data invisibility.
During an AWS Redshift migration, encryption was enabled as part of a security hardening step. The process required snapshot restore operations and KMS key associations. Although the restore operation reported success, Subsequent queries failed or returned partial results due to KMS permission mismatches and key rotation issues. Some data became selectively invisible, creating a false sense of successful rollback. Failure class, physical storage, and execution semantics incident.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system stable and write-enabled. 2. Redshift cluster restored from snapshot into an encrypted configuration. 3. Snapshot restore completed without fatal errors. 4. KMS configuration new or rotated customer-managed keys applied. 5. BI and downstream systems reconnected post-restore. 6. Declared source of truth Redshift after restore. 7. Authority status assumed intact without validating encryption access paths. Encryption was treated as transparent rather than authoritative.
Incident analysis and root cause.
This failure resulted from a security boundary assumption. 1. Triggering action restoring an unencrypted snapshot into an encrypted Redshift cluster. 2. Why it appeared safe snapshot restore completed successfully with no blocking errors. 3. What teams noticed first certain tables or queries failing with permission-related errors. 4. What teams did not notice that some data was silently inaccessible due to KMS grants. 5. How divergence accumulated. Consumers saw partial datasets and cached incomplete results. 6. Missing invariant, encryption keys and grants must be validated as part of rollback authority.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it masquerades as a successful restore. The cluster is online, queries run, and dashboards load, but portions of the data are unreadable or invisible. Detection latency is high because failures appear intermittent and role-dependent.
What exactly broke? Consistency breakdown.
Authority and access consistency are broken. Data exists physically but cannot be read uniformly by authorized consumers. Redshift is no longer a trustworthy system of record. If we roll back only data, this inconsistency remains because encryption and access state are external to the snapshot contents.
Rollback viability checklist, go or no go.
For rollback is considered, the architect must evaluate. 1. Did snapshot restore succeed technically? Yes, but misleading. 2. Are correct KMS keys and grants applied? No. Access fragmented. 3. Can restore fix missing permissions? No. Requires governance action. 4. Have downstream systems cache partial data? Likely. 5. Can authority be restored without security changes? No. Rollback without access parity restores illusion, not truth.
Decision point, rollback versus forward fix.
Rollback is ineffective because restoring snapshots does not restore KMS grants or IAM trust relationships. Forward fix requires coordinated security remediation and explicit revalidation of data visibility across roles.
Rollback architecture.
A rollback would involve restoring the cluster snapshot again, but this repeats the same encryption boundary. CDC offsets and data state remain correct, yet access remains broken. Rollback is therefore non-destructive but non-restorative and should not be executed.
Code illustration and Redshift artifacts.
In this section, we will show 1. Snapshot restore success without access validation. 2. KMS permission errors proving selective invisibility. Encryption failures break authority without breaking availability. Here is Redshift SQL showing selective table access failures post-encryption restore. Disclaimer: always test code in a non-production environment. This query fails or returns inconsistent results depending on IAM role, proving that data exists but is not uniformly accessible. Here is an example KMS-related error observed during post-restore access. Disclaimer: always test code in a non-production environment. This error confirms that encryption key permissions, not data corruption, are preventing access to restored data.
Containment and forward fix strategy.
Once encryption-induced invisibility is confirmed, containment must precede repair. 1. Pause downstream consumption immediately. 2. Audit KMS keys, grants, and IAM role mappings. 3. Restore uniform access across all required roles. 4. Invalidate caches populated during partial visibility. 5. Revalidate full data access before reasserting authority. Security state must be validated as part of data correctness.
Interview framing.
How would you explain this in an interview? Here are the key talking points. 1. Snapshot restore success does not imply access correctness. 2. Encryption introduces an external authority boundary. 3. Rollback restores data blocks, not security state. 4. Access parity is a first-class migration invariant. Security boundaries define truth as much as data does.
Follow-up 1. Why did monitoring not catch this immediately?
Answer: cluster health checks and snapshot status focus on availability, not access parity. Because some roles could still read data, the system appeared healthy. The failure was role-dependent and therefore invisible to standard monitoring.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe the moment encryption was enabled without validated KMS grants. From that point onward, every restore preserved the same access asymmetry.
Follow-up 3. Curveball. Could this happen even if no data was queried after restore?
Answer: yes. Even without queries, downstream systems may establish connections, warm metadata caches, or pre-compute access paths. Once those processes run under partial visibility, trust boundaries are already fractured.
Pro insider tip.
After encrypted restores, always validate data visibility using every production IAM role. A green restore status means nothing if half your data is unreadable.
Category 10 wrap-up. Physical layout is not just performance.
The previous category demonstrated that restoring data does not restore behavior. Distribution style, sort keys, encoding, and encryption alter how Redshift executes queries and exposes data. Once these physical semantics diverge, Rollback can recreate the same data with fundamentally different behavior, silently changing analytical truth.
Transition from physical semantics to transactional illusions.
If physical layout breaks the assumption that identical data behaves the same, transactional semantics break a deeper assumption that operations either fully succeed or fully fail. The next category focuses on how Redshift copy and transaction behavior violate traditional ACID expectations during migration and rollback.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs in a single zip file, containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, system design. Required for your data engineer interviews jobs like data quality analyst jobs, data governance analyst jobs, AWS Python data engineer jobs, AWS Redshift Database Administrator DBA jobs, AWS Glue ETL Developer jobs, AWS Data Engineer jobs, Cloud Data Engineer jobs, Data Architect jobs, DataOps Engineer jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based questions and answers, real-world problem-solving, interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people also for your interviews. You people can download all 6 PDFs in a single zip file from below given links.
Category 11. Redshift transaction semantics and copy edge cases.
These incidents expose a critical but often misunderstood reality. Redshift does not provide traditional transactional guarantees for bulk ingestion and parallel execution. During migration, copy operations and concurrent writes can partially commit, interleave, or behave in ways that make rollback logically unsafe, even when it appears technically possible.
Category 11 scenarios.
This category covers the following Redshift-specific transactional edge cases. 77. Copy partially commits across slices. 78. Concurrent copy jobs interleave partitions. 79. Copy plus DML in the same transaction behaves non-intuitively. Core failure, transactional assumptions are false.
Real-world incident during source-to-Redshift migration 77. Copy partially commits across slices.
During an AWS Redshift migration, a large copy operation was executed to ingest historical data during cutover. The copy command appeared to fail partway through due to data errors on specific slices. However, other slices committed their data successfully, resulting in a partially loaded table. This created a false sense of rollback safety, where operators assumed the failed copy was fully reverted. Failure class, Redshift transaction semantics, and copy edge cases.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system stable and read-only during historical backfill. 2. Redshift cluster write-enabled and actively ingesting data via copy. 3. Copy execution parallel load across multiple slices. 4. Transaction context copy assumed to be atomic by operators. 5. BI tools disabled or running validation queries only. 6. Declared source of truth. Redshift assumed authoritative post-load. 7. Authority status assumed intact based on copy failure signal. Copy failure does not imply global rollback across slices.
Incident analysis and root cause.
This failure occurred due to a misunderstanding of Redshift execution semantics. 1. Triggering action, executing a large copy operation that encountered data errors on a subset of slices. 2. Why it appeared safe, the copy command surfaced an error, leading operators to assume no data was committed. 3. What teams noticed first, row counts lower than expected but non-zero after the failed copy. 4. What teams did not notice, that some slices had already committed their partitions successfully. 5. How divergence accumulated, subsequent retries and validations operated on a partially populated table. 6. Missing invariant bulk ingestion must be either provably atomic or explicitly verified for partial commit.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it violates the mental model of transactional safety. Operators trust that a failed copy leaves the table unchanged. In reality, Redshift may commit data slice by slice. Detection latency is high because partial data looks like a truncated load rather than corruption, and standard error handling does not signal partial success.
What exactly broke? Consistency breakdown.
Transactional and domain-level consistency are broken. The table contains a non-deterministic subset of the intended dataset. If we roll back only data, this inconsistency remains because there is no authoritative boundary indicating which slices committed and which did not.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate 1. Did copy partially commit across slices? Yes, partial state exists. 2. Is there a reliable marker of committed versus uncommitted rows? No. 3. Can copy be rerun idempotently? No. Risk of duplication. 4. Have validations already used partial data? Likely. 5. Can authority be restored without table rebuild? No. Partial copy commits invalidate transactional rollback assumptions.
Decision point, rollback versus forward fix.
Rollback at the transaction level is impossible because the copy operation did not fail atomically. The only safe rollback is a destructive table-level reset or cluster restore. Forward fix is not viable without first re-establishing a clean baseline.
Rollback architecture.
Rollback requires a full reset of the affected table or cluster. Partial deletion is unsafe because slice boundaries are opaque. The only valid rollback options are restoring from a snapshot taken before the copy or dropping and recreating the table, followed by a verified reload. CDC offsets and downstream validations must be discarded and re-established.
Code illustration and Redshift artifacts.
In this section we will show 1. How partial copy commits are detected via slice-level inspection. 2. How load errors confirm non-atomic behavior. 3. What rollback would require at the system level. 4. How a forward fix rebuild restores consistency. Only execution evidence proves copy is not atomic. Detection, inspecting slice-level row distribution after failed copy. Disclaimer, always test code in a non-production environment. Uneven or unexpected row counts across slices after a failed copy prove that some slices committed data while others did not. Failure proof, Identifying copy errors that did not trigger full rollback. Disclaimer: always test code in a non-production environment. This table shows that load errors occurred, but does not imply that previously loaded slices were rolled back. Rollback mechanics: dropping and recreating the affected table. Disclaimer: always test code in a non-production environment. Dropping the table is the only safe rollback because partial slice commits cannot be surgically undone. Forward fix: verified reload after destructive rollback. Disclaimer: always test code in a non-production environment. A clean reload after destructive rollback reestablishes a single authoritative baseline.
Containment and forward fix strategy.
After partial copy commit is confirmed: 1. Immediately stop downstream validation or consumption. 2. Destroy partial data state via table drop or snapshot restore. 3. Reload data with strict error thresholds. 4. Validate slice-level distribution post-load. 5. Re-enable downstream systems only after full verification. Partial success is worse than visible failure.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Redshift copy is not guaranteed to be atomic across slices. 2. A failed copy can still commit partial data. 3. Transactional rollback assumptions do not hold for bulk ingestion. 4. Safe rollback requires destructive reset, not row-level cleanup. Bulk ingestion systems must be treated as non-atomic unless proven otherwise.
Follow-up 1. Why doesn't copy failure guarantee rollback?
Answer: because copy executes in parallel across slices, and Redshift commits data incrementally. An error on one slice does not retroactively undo commits on others. This breaks traditional ACID expectations.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe the moment the first slice committed data successfully. From that point on, there was no clean transactional boundary to revert.
Follow-up 3. Curveball. Could higher max error settings prevent this?
Answer: no. Max error only controls tolerance, not atomicity. Increasing it can actually worsen corruption by allowing more partial commits without clear failure signals.
Pro insider tip.
If you cannot prove a copy was atomic, assume it was not. Always validate slice-level state before trusting a bulk load.
Real-world incident during source to Redshift migration 78. Concurrent copy jobs interleave partitions.
During an AWS Redshift migration, multiple copy jobs were executed concurrently to accelerate ingestion of large historical datasets. Although each copy targeted the same table, they were assumed to operate on independent file partitions. In reality, Redshift interleaved data application across slices and partitions, creating non-deterministic overlaps. This resulted in duplicated, missing, and partially ordered data that could not be cleanly rolled back. Failure class: Redshift transaction semantics and copy edge cases.
System state before failure, very important.
At the moment the failure was introduced, the system state was: 1. Source system read-only for historical extraction. 2. Redshift cluster write-enabled and under heavy ingestion load. 3. Copy execution model multiple concurrent copy commands targeting the same table. 4. Partitioning assumption operators assumed file-level isolation. 5. BI tools disabled or running spot validation queries. 6. Declared source of truth. Redshift assumed authoritative post-load. 7. Authority status assumed intact based on successful copy completion signals. Concurrency without isolation creates invisible write overlap.
Incident analysis and root cause.
This failure resulted from unsafe concurrency assumptions. 1. Triggering action launching multiple copy jobs in parallel against the same target table. 2. Why it appeared safe, each copy completed successfully with no explicit errors. 3. What teams noticed first: inconsistent row counts and duplicate business keys. 4. What teams did not notice: that copy jobs interleaved writes across slices and partitions. 5. How divergence accumulated. Overlapping data ranges were applied multiple times or partially. 6. Missing invariant, bulk ingestion must enforce single writer or explicit partition isolation.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it produces valid-looking but corrupted data. Each copy reports success, monitoring remains green, and validations often focus on aggregate volume. The corruption is ordering and duplication-based. surfacing only under reconciliation or downstream inconsistencies. Detection latency is typically days.
What exactly broke? Consistency breakdown.
Transactional and temporal consistency are broken. The same logical partitions are applied multiple times in non-deterministic order. If we roll back only data, this inconsistency remains because there is no authoritative execution order to reconstruct.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate 1. Were multiple copy jobs writing concurrently? Yes, interleaving occurred. 2. Is there a deterministic mapping of files to committed rows? No. 3. Can duplicates be reliably identified post facto, sometimes business key dependent? 4. Have downstream systems consumed corrupted data? Likely. 5. Can authority be restored without destructive reset? No. Concurrency destroys rollback determinism.
Decision point, rollback versus forward fix.
Rollback at the transaction level is unsafe because concurrent copy execution destroyed ordering guarantees. The only safe rollback is a destructive table or cluster restore. Forward fix without reset risks compounding duplication and ordering errors.
Rollback architecture.
Rollback requires discarding the entire affected dataset. Valid options include restoring a pre-ingestion snapshot or dropping and recreating the table. CDC offsets, validation artifacts, and downstream caches must all be invalidated. Partial rollback or selective deletes are unsafe due to non-deterministic interleaving.
Code illustration and Redshift artifacts.
In this section, we will show 1. How concurrent copy execution can be identified via system tables. 2. How overlapping load windows prove interleaving. 3. What rollback requires at the system level. 4. How forward fix restores a single writer baseline. Only execution evidence reveals copy interleaving. Detection, identifying overlapping copy executions. Disclaimer, always test code in a non-production environment. Overlapping start and end times for copy queries prove concurrent execution against the same table. Failure proof, detecting duplicate business keys after concurrent copy. Disclaimer, always test code in a non-production environment. Duplicate keys, confirm that overlapping partitions were applied multiple times. Rollback mechanics, destructive reset of corrupted table. Disclaimer, always test code in a non-production environment. Dropping the table is required because interleaving prevents safe row-level cleanup. Forward fix, single writer copy with enforced serialization. Disclaimer, always test code in a non-production environment. Rerunning copy in a strictly serialized manner restores deterministic ingestion.
Containment and forward fix strategy.
After concurrent copy interleaving is confirmed. 1. Immediately halt all parallel ingestion jobs. 2. Invalidate partially loaded data via destructive reset. 3. Enforce single writer ingestion guarantees. 4. Reload data with explicit ordering and isolation. 5. Revalidate using business key uniqueness checks. Parallel ingestion without isolation is corruption, not optimization.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Redshift copy jobs are not isolated by default. 2. Concurrent copy can interleave data non-deterministically. 3. Success signals do not imply correctness under concurrency. 4. Rollback requires destructive reset, not replay. Concurrency must be explicitly serialized during bulk ingestion.
Follow-up 1. Why can't Redshift prevent concurrent copy overlap automatically?
Answer, Redshift optimizes for throughput, not ingestion isolation. Copy jobs execute independently across slices. Without explicit coordination, the engine does not enforce single writer semantics, leading to overlap.
Follow-up 2. When did rollback stop being safe in this scenario?
Answer, rollback stopped being safe the moment the second copy began committing rows. From that point, execution order and overlap were no longer reconstructible.
Follow-up 3. Curveball. Would splitting data into more files prevent this?
Answer, no. File granularity does not guarantee isolation. Without enforced serialization, Redshift can still interleave partitions across concurrent copy jobs.
Pro insider tip.
If 2 copy jobs can run at the same time, assume they will corrupt each other unless you prove isolation.
Real-world incident during source to Redshift migration 79. Copy and DML, in the same transaction behave non-intuitively.
During an AWS Redshift migration, engineers attempted to wrap a bulk copy operation and subsequent DML statements inside a single transaction to preserve atomicity. Although this pattern is valid in many relational databases, Redshift applies copy semantics differently. As a result, rows loaded by copy became visible and persisted even when the surrounding transaction was rolled back. This shattered ACID assumptions and made rollback behavior fundamentally unsafe. Failure class, Redshift transaction semantics and copy edge cases.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system read-only snapshot used for bulk load. 2. Redshift cluster write-enabled and executing migration SQL. 3. Transaction model explicit begin/commit blocks used by engineers. 4. Copy usage executed inside an open transaction with follow-up DML. 5. BI tools disabled or running validation queries. 6. Declared source of truth expected to become Redshift after transaction commit. 7. Authority status assumed transactional atomicity. Copy does not obey transactional intuition in Redshift.
Incident analysis and root cause.
This failure was caused by incorrect assumptions about transactional guarantees. 1. Triggering action executing copy and DML within the same explicit transaction block. 2. Why it appeared safe standard ACID databases treat bulk loads as transactional. 3. What teams noticed first rows persisted after an explicit rollback. 4. What teams did not notice that copy commits data outside normal transaction boundaries. 5. How divergence accumulated. Subsequent retries reapplied data assumed to be rolled back. 6. Missing invariant. Copy operations in Redshift must never be assumed to be fully transactional.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it creates a false sense of safety. Engineers believe they can test, rollback, and retry safely within a transaction. In Redshift, copy can partially or fully commit data regardless of transaction outcome. Detection latency is immediate only if rollback is tested. Otherwise, corruption propagates silently through retries.
What exactly broke? Consistency breakdown.
Transactional consistency is broken. Copy-loaded rows can survive transaction rollback, while subsequent DML obeys rollback semantics. If we roll back only data, this inconsistency remains because copy visibility is decoupled from transaction control.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Was copy executed inside a transaction? Yes, non-atomic behavior. 2. Did copy-loaded rows persist after rollback? Yes. 3. Can persisted rows be deterministically identified, sometimes file or timestamp dependent? 4. Have retries already occurred? Likely. 5. Can rollback restore a clean pre-copy state? No. Transactional rollback does not undo copy side effects.
Decision point, rollback versus forward fix.
Rollback at the transaction level is invalid because copy escaped transactional control. Safe rollback requires destructive reset of the affected table or restoring a snapshot from before copy execution. Forward fix without reset risks compounding duplicate or partial data.
Rollback architecture.
Rollback requires discarding all data loaded by copy regardless of transaction state. Options include restoring a pre-copy cluster snapshot or dropping and recreating affected tables. CDC offsets, validation artifacts, and downstream caches must be invalidated. Partial deletes or transactional retries are unsafe.
Code illustration and Redshift artifacts.
In this section, we will show 1. How copy behaves inside a transaction. 2. How rollback fails to remove copy-loaded rows. 3. What rollback requires at the system level. 4. How forward fix avoids transactional illusions. Copy breaks the illusion of atomic rollback. Failure demonstration. Copy and DML inside a single transaction. Disclaimer: always test code in a non-production environment. This snippet shows copy executed inside an explicit transaction. In Redshift, copy does not fully participate in transaction rollback semantics. Detection: verifying copy-loaded rows survived rollback. Disclaimer: always test code in a non-production environment. The presence of rows after rollback proves that copy-loaded data persisted, Despite transaction rollback. Rollback mechanics, destructive reset of affected table. Disclaimer, always test code in a non-production environment. Dropping the table is required because transactional rollback cannot undo copy side effects. Forward fix, separating copy from transactional DML. Disclaimer, always test code in a non-production environment. Separating copy from transactional DML avoids, assuming eremicity that Redshift does not provide.
Containment and forward fix strategy.
After non-transactional copy behavior is confirmed. 1. Prohibit copy execution inside transactions. 2. Assume copy is immediately persistent. 3. Use snapshots or table recreation for rollback. 4. Serialize retries to avoid duplicate application. 5. Re-educate teams on Redshift-specific semantics. Copy is bulk ingestion, not transactional DML.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Redshift copy does not obey full ACID semantics. 2. Rollback cannot be trusted to undo copy. 3. Retries amplify corruption after copy rollback. 4. Safe rollback requires destructive reset. Never assume transactional atomicity for copy in Redshift.
Follow-up 1. Why does Redshift allow copy inside a transaction at all?
Answer, Redshift permits the syntax for compatibility, but the engine optimizes copy as a bulk load operation. It prioritizes throughput over transactional isolation, leading to non-intuitive behavior.
Follow-up 2. When did rollback stop being safe in this scenario?
Answer, rollback stopped being safe the moment copy committed rose outside transactional control. From that point onward, transaction boundaries no longer represented a recoverable state.
Follow-up 3. Curveball. Would wrapping copy in a stored procedure fix this?
Answer, no. Stored procedures do not change copy execution semantics. Copy remains non-atomic regardless of procedural wrapping.
Pro insider tip.
If you rely on rollback to undo a copy in Redshift, you are already corrupting data without knowing it.
Category 11 wrap-up. When correctness is undermined by access.
The previous category demonstrated how transactional assumptions break inside Redshift itself. In contrast, the next category shows failures that occur even when data pipelines and execution mechanics are technically sound. These incidents originate outside the migration plan, through ungoverned access paths that bypass approval and validation.
Transition from execution semantics to organizational leakage.
At this stage of a migration, the primary risk is no longer how data is loaded or committed, but who can see and use it. Once unauthorized consumers access Redshift before correctness is proven, rollback boundaries are crossed silently and irreversibly.
Category 12. Late consumer and shadow access incidents.
This category covers failures caused by premature or unauthorized access to Redshift during migration. These are not technical pipeline errors, but governance and access control failures that allow data to escape before it is validated. Once this happens, correctness becomes secondary to trust loss.
Scenarios in this category.
The following incidents represent common shadow access failure modes. 1. Shadow BI tools reading Redshift before cutover approval. 2. Analysts running ad hoc SQL that mutates session state through temp tables or UDFs. 3. External partners or third parties granted early Redshift access. Core failure, data leaked before correctness was proven.
Real-world incident during source to Redshift migration 80. Shadow BI tools access Redshift before cutover approval.
During an AWS Redshift migration, the cluster became reachable to internal BI tools before formal cutover approval. Analysts and teams began querying Redshift informally for exploration and early insights, despite the data still being under validation. This resulted in ungoverned consumption of unverified data and permanently crossed the rollback boundary. Failure class, late consumer and shadow access incident.
System state before failure, very important.
At the moment shadow access occurred, the system state was 1. Source system write enabled and still considered operationally authoritative. 2. Redshift cluster loaded with migrated data but still under validation. 3. CDC pipeline running or recently completed, correctness not yet certified. 4. BI tools not officially repointed but technically able to connect. 5. Declared source of truth, source system by policy, Redshift by perception. 6. Authority status, implicitly breached through unapproved access. Technical accessibility without governance equals authority leakage.
Incident analysis and root cause.
This incident was caused by a breakdown in access governance. 1. Triggering action, network access and credentials allowed BI tools to connect to Redshift before cutover approval. 2. Why it appeared safe, data looked complete, queries succeeded, and no errors were visible to users. 3. What teams noticed first, numbers being discussed from Redshift that did not match officially sanctioned reports. 4. What teams did not notice, that any access prior to authority declaration permanently weakens rollback. 5. How divergence accumulated, informal insights, screenshots, and exports spread before validation completed. 6. Missing invariant, no system may be queried before it is formally declared authoritative.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it leaves no technical trace. Queries succeed, logs look normal, and no alarms fire. The damage is social and organizational. Once people see data, they trust it. Detection latency is effectively infinite because access itself is not treated as an error.
What exactly broke? Consistency breakdown.
Authoritative consistency is broken. Redshift data was consumed before being declared correct, while the source system was still officially authoritative. If we roll back only data, this inconsistency remains because human trust and external usage cannot be rolled back.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Has Redshift been queried by unauthorized consumers? Yes, trust already leaked. 2. Were results shared, exported, or discussed? Likely informal propagation. 3. Can all consumers be identified and corrected? No, shadow access by definition. 4. Would restoring a snapshot remove prior exposure? No, knowledge persists. 5. Can authority be re-established cleanly? No, human boundary crossed. Rollback restores systems, not memory or trust.
Decision point, rollback versus forward fix.
Rollback is no longer meaningful once shadow consumers have accessed Redshift. Even if data is restored perfectly, prior exposure invalidates authority. The only viable path is forward fix with explicit trust reset and recertification.
Rollback architecture.
A formal rollback would require snapshot restore, CDC discard, BI repointing, and cache invalidation. However, in this scenario, rollback is intentionally not executed because it cannot undo prior access or re-establish authority. Governance approval must acknowledge rollback infeasibility explicitly.
Containment and forward fix strategy.
Containment focuses on stopping further trust erosion. 1. Immediately revoke all non-approved access to Redshift. 2. Declare all pre-approval insights invalid and non-authoritative. 3. Rerun validation from a clean governance-approved baseline. 4. Re-announce a formal cut-over moment with executive backing. 5. Audit access logs to understand blast radius, not to assign blame. Authority must be declared explicitly, not inferred from access.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Explain that technical correctness is meaningless without authority control. 2. Highlight that early access permanently weakens rollback guarantees. 3. Emphasize that access governance is part of migration architecture. 4. State that preventing shadow access is cheaper than repairing trust. Authority must be established before access, not after.
Follow-up 1. Why is early BI access worse than a failed query?
Answer: a failed query creates a visible error and stops usage. Early access creates invisible trust. Once users see results, they form mental models and decisions, even if the data later changes. That trust cannot be rolled back.
Follow-up 2. When did rollback stop being safe in this scenario?
Answer: rollback stopped being safe the moment the first unauthorized query returned results. From that instant, data left the system boundary and entered human workflows, making technical rollback insufficient.
Follow-up 3. Curveball. What if leadership says informal access is harmless?
Answer: informal access is exactly how authority leaks. The architect must explain that migrations fail socially before they fail technically. Treating early access as harmless guarantees long-term distrust and audit risk.
Pro insider tip.
If you cannot point to the exact minute Redshift became authoritative, you have already allowed shadow access. even if no one admits it.
Real-world incident during source-to-Redshift migration 81. Analysts run ad hoc SQL that mutates session state.
During an AWS Redshift migration, analysts were granted exploratory access to validate data. Several users executed ad hoc SQL that created temporary tables, session-level UDFs, and session-scoped assumptions. These actions mutated session state without auditability, creating analysis results that could not be reproduced or rolled back. Failure class, late consumer and shadow access incident.
System state before failure, very important.
At the moment session state was mutated, the system state was 1. Source system still authoritative for production decisions. 2. Redshift cluster accessible for validation but not yet approved for use. 3. CDC pipeline running or recently completed with no certification. 4. Analyst access enabled with broad SQL permissions. 5. Session behavior, temporary tables and UDFs allowed per connection. 6. Declared source of truth, undeclared during validation window. 7. Authority status, implicitly weakened by uncontrolled session mutation. Session-level mutations bypass migration auditability.
Incident analysis and root cause.
This incident resulted from uncontrolled exploratory access. 1. Triggering action, analysts creating temp tables and UDFs during validation. 2. Why it appeared safe, session changes disappear on disconnect and leave no persistent trace. 3. What teams noticed first, conflicting numbers produced by different analysts. 4. What teams did not notice that session-level logic was never governed or replayable. 5. How divergence accumulated, decisions and narratives formed from non-reproducible sessions. 6. Missing invariant, validation queries must be immutable and replayable.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it produces untraceable conclusions. Session state disappears, but decisions remain. No logs capture the derived logic, and no rollback can recreate or invalidate the analysis. Detection latency is effectively infinite.
What exactly broke? Consistency breakdown.
Authoritative and semantic consistency are broken. Analytical truth varies by session rather than system state. If we roll back only data, this inconsistency remains because session-derived logic cannot be reconstructed or invalidated.
Rollback viability checklist, go or no-go.
Before rollback is considered, the architect must evaluate 1. Were temp tables or session UDFs used? Yes, non-replayable logic. 2. Are analytical results reproducible? No, session-dependent. 3. Can session logic be audited? No, ephemeral state. 4. Would snapshot restore invalidate conclusions? No, human trust persists. 5. Can authority be restored cleanly? No, interpretations already diverged. Ephemeral logic creates permanent trust damage.
Decision point, rollback versus forward fix.
Rollback is ineffective because it cannot erase conclusions derived from session-scoped logic. Forward fix must focus on rerunning validation under controlled, immutable query sets and explicitly invalidating prior exploratory results.
Rollback architecture.
A rollback would involve snapshot restore, CDC discard, and BI repointing. However, rollback is not executed because it cannot undo analyst-generated session logic or derived interpretations. Governance approval must document rollback in feasibility.
Containment and forward fix strategy.
Containment must eliminate non-replayable analysis. 1. Revoke ad hoc SQL permissions during validation. 2. Require all validation logic to be version controlled. 3. Invalidate conclusions derived from session state. 4. Rerun validation using approved immutable queries. 5. Introduce read-only roles with no temp object privileges. Validation must be replayable to be trustworthy.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Session state is invisible to migration governance. 2. Temp tables and UDFs create non-reproducible truth. 3. Rollback cannot invalidate session-derived conclusions. 4. Controlled validation requires immutable query contracts. Replayability is a prerequisite for authority.
Follow-up 1. Why are temp tables dangerous during migration validation?
Answer: temp tables allow analysts to reshape data outside any governed pipeline. The logic disappears, but the conclusions persist. This breaks replayability, which is essential for rollback confidence and auditability.
Follow-up 2. When did rollback stop being safe in this scenario?
Answer: rollback stopped being safe the moment analytical conclusions were formed from session-only logic. At that point, restoring data cannot invalidate or reproduce the reasoning that drove decisions.
Follow-up 3. Curveball. What if analysts insist temp tables are only for exploration?
Answer: exploration without governance is indistinguishable from production usage and impact. The architect must enforce that any logic influencing decisions must be replayable, versioned, and auditable.
Pro insider tip.
If validation logic cannot be rerun verbatim after rollback, it should never influence a migration decision.
Real-world incident during source to Redshift migration 82. External partners given early Redshift access.
During an AWS Redshift migration, external partners were granted early access to the Redshift cluster for integration testing before cutover approval. These partners consumed data, generated reports, and persisted results outside the organization, while validation was still ongoing. This permanently crossed the rollback boundary, even though no data corruption was detected internally. Failure class: late consumer and shadow access incident.
System state before failure, very important.
At the moment external access was granted, the system state was: 1. Source system still authoritative for business operations. 2. Redshift cluster populated and exposed for validation only. 3. CDC pipeline running or recently completed without certification. 4. External partners granted credentials or network access. 5. Data usage query is executed and results exported externally. 6. Declared source of truth, not formally switched. 7. Authority status implicitly breached by external consumption. External access converts validation data into published data.
Incident analysis and root cause.
This incident was caused by premature trust delegation. 1. Triggering action granting Redshift access to external partners before cutover approval. 2. Why it appeared safe data was marked as for testing only and no internal consumers relied on it. 3. What teams noticed first partner feedback referencing Redshift-derived results. 4. What teams did not notice that partners persisted and reused the data externally. 5. How divergence accumulated. External systems integrated Redshift data into their own workflows. 6. Missing invariant. No external consumer may access data before authority is formally declared.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it creates irreversible trust leakage. External consumers treat access data as real, regardless of disclaimers. Detection latency is high, often discovered only when rollback is proposed and partner dependencies are revealed.
What exactly broke? Consistency breakdown.
Authority consistency is broken. Redshift data becomes externally authoritative before internal validation completes. If we roll back only data, this inconsistency remains because external systems have already accepted and persisted the information.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Have external partners consumed Redshift data? Yes, authority leaked. 2. Can external systems retract or invalidate data? No, outside control. 3. Was access contractually restricted to testing? Often no, ambiguous. 4. Have integrations been built on this data? Likely. 5. Can authority be re-established cleanly? No, external trust persists. External consumption permanently crosses the rollback boundary.
Decision point, rollback versus forward fix.
Rollback is not viable because it cannot undo external reliance. Forward fix must focus on certifying Redshift as authoritative, correcting inconsistencies, and formally communicating data validity to partners.
Rollback architecture.
Rollback would require snapshot restore, CDC discard, credential revocation, and external notification. Rollback is not executed because partner systems cannot be forced to forget or retract consumed data, making authority restoration impossible.
Containment and forward fix strategy.
Containment must address external trust leakage. 1. Immediately freeze schema and data changes. 2. Audit all external access and data exports. 3. Communicate data validity status explicitly to partners. 4. Correct inconsistencies and republish certified datasets. 5. Introduce contractual cut over gates for future migrations. External trust must be governed as strictly as internal usage.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. External access instantly confers authority. 2. Disclaimers do not prevent trust propagation. 3. Rollback cannot retract data already consumed externally. 4. Cutover gates must include partner access controls. Authority is defined by consumption, not intent.
Follow-up 1. Why is external access more dangerous than internal validation?
Answer: external consumers operate outside organizational control. Once they ingest data, there is no guarantee of retraction or correction. This makes rollback ineffective regardless of internal system state.
Follow-up 2. When did rollback stop being safe in this scenario?
Answer: rollback stopped being safe the moment external partners consumed and persisted Redshift data. From that point, authority shifted beyond the organization's control.
Follow-up 3. Curveball. What if partners promise to delete the data?
Answer: promises do not restore authority. Without enforceable guarantees and verification, the system must assume the data still exists and has influenced downstream decisions.
Pro insider tip.
The fastest way to kill rollback is to let someone outside your org see the data.
Category 12 wrap-up. Why shadow access is a rollback killer.
Late consumer and shadow access incidents mark a hard end to technical rollback. Once data is accessed, cached, or acted upon outside approved boundaries, rollback stops being a system operation and becomes a trust problem. At that point, correctness is no longer controlled by engineers, but by uncontrolled external state.
Transition from data leakage to state blindness.
If late consumers destroy rollback by leaking authority outward, observability failures destroy rollback by removing memory inward. The next category focuses on incidents where teams cannot even agree on what happened, making rollback impossible not because of policy, but because of missing facts.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs in a single zip file, containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, system design. Required for your data engineer interviews jobs like data quality analyst jobs, data governance analyst jobs, AWS Python data engineer jobs, AWS Redshift Database Administrator DBA jobs, AWS Glue ETL Developer jobs, AWS Data Engineer jobs, Cloud Data Engineer jobs, Data Architect jobs, DataOps Engineer jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based questions and answers, real-world problem-solving, interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section. These questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people also for your interviews. You people can download all 6 PDFs in a single zip file from below given links.
Category 13. Observability and state reconstruction failures.
Observability and state reconstruction failures occur when migrations progress without durable, replayable records of actions taken, validations performed, and checkpoints crossed. In these incidents, rollback fails not due to data corruption, but because no one can reliably reconstruct the system state at any point in time. Failure class: observability and state reconstruction failures.
Category 13 scenarios.
This category includes the following failure scenarios: 83. Migration steps not replayable from logs. 84. Validation artifacts not versioned. 85. CDC offsets not checkpointed with migration ID. Core failure: system state cannot be reconstructed.
Category 12 wrap-up. Why shadow access is a rollback killer.
Late consumer and shadow access incidents mark a hard end to technical rollback. Once data is accessed, cached, or acted upon outside approved boundaries, rollback stops being a system operation and becomes a trust problem. At that point, correctness is no longer controlled by engineers, but by uncontrolled external state.
Transition from data leakage to state blindness.
If late consumers destroy rollback by leaking authority outward, observability failures destroy rollback by removing memory inward. The next category focuses on incidents where teams cannot even agree on what happened, making rollback impossible not because of policy, but because of missing facts.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs in a single zip file, containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, system design. Required for your data engineer interviews jobs like data quality analyst jobs, data governance analyst jobs, AWS Python data engineer jobs, AWS Redshift Database Administrator DBA jobs, AWS Glue ETL Developer jobs, AWS Data Engineer jobs, Cloud Data Engineer jobs, Data Architect jobs, DataOps Engineer jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based questions and answers, real-world problem-solving, interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people also for your interviews. You people can download all 6 PDFs in a single zip file from below given links.
Category 13. Observability and state reconstruction failures.
Observability and state reconstruction failures occur when migrations progress without durable, replayable records of actions taken, validations performed, and checkpoints crossed. In these incidents, rollback fails not due to data corruption, but because no one can reliably reconstruct the system state at any point in time. Failure class: Observability and state reconstruction failures.
Category 13. Scenarios.
This category includes the following failure scenarios: 83. Migration steps not replayable from logs. 84. Validation artifacts not versioned. 85. CDC offsets not checkpointed with migration ID. Core failure: system state cannot be reconstructed.
Real-world incident during source to Redshift migration. 83. Migration steps not replayable from logs.
During an AWS Redshift migration, multiple operational steps were executed manually and via ad hoc scripts during snapshot, CDC pause, validation, and resume phases. These actions were not consistently logged, versioned, or correlated with a migration identifier. When data inconsistencies were later discovered, the team was unable to reconstruct the exact sequence of events, making rollback analysis and recovery decisions unreliable. Failure class: Observability and state reconstruction failure.
System state before failure. Very important.
At the moment irreversibility was introduced, the system state was 1. Source system write enabled with normal transactional activity. 2. Redshift cluster actively receiving data via snapshot and CDC phases. 3. Migration execution combination of scripted, manual, and console-driven actions. 4. Logging state partial logs across tools with no unified execution timeline. 5. CDC status started, stopped, and resumed multiple times without correlated identifiers. 6. BI and downstream systems access intermittently enabled for validation. 7. Declared source of truth assumed but never formally recorded per phase. 8. Authority status implicit and undocumented. If actions cannot be replayed, system state cannot be proven.
Incident analysis and root cause.
This failure resulted from an observability and process breakdown. 1. Triggering action, executing migration steps without deterministic replayable logging. 2. Why it appeared safe, each individual step completed successfully with no immediate errors. 3. What teams noticed first, inability to explain how and when inconsistencies were introduced. 4. What teams did not notice that no authoritative execution timeline existed. 5. How divergence accumulated. Multiple state transitions occurred without durable evidence. 6. Missing invariant. Every migration state transition must be logged, replayable, and correlated to a migration ID.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it destroys rollback confidence without breaking any systems. Data may still exist, CDC may still run, and dashboards may still load. However, without a replayable history of actions, it is impossible to prove correctness, identify the rollback boundary, or defend decisions during audit or incident review. Detection latency is typically weeks, discovered only when teams attempt forensic reconstruction.
What exactly broke? Consistency breakdown.
Authority and audit consistency are broken. There is no longer a provable mapping between migration actions and resulting data state. Redshift data cannot be trusted because its lineage is unverifiable. If we roll back only data, this inconsistency remains because the historical execution context that defines correctness no longer exists.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Are all migration steps logged and replayable? No execution history incomplete. 2. Can CDC start or stop boundaries be reconstructed? No missing correlation. 3. Can snapshot timing be proven relative to source rights? No evidence missing. 4. Can rollback restore both data and authority? No authority unverifiable. 5. Can rollback be defended during audit or post-mortem? No evidence trail. Rollback without evidence creates new risk rather than removing it.
Decision point, rollback versus forward fix.
Rollback is not safe because there is no trustworthy reference point to roll back to. Any restored state would be arbitrary and indefensible. Forward fix must focus on freezing further changes, re-establishing observability, and rebuilding trust through controlled revalidation, rather than attempting historical correction.
Rollback architecture.
A true rollback cannot be executed in this scenario. Snapshot restore would recreate data without restoring the missing execution history. CDC rewind or discard cannot be scoped because offsets are not correlated to logged actions. BI repointing and downstream invalidation would occur without a provable justification. Governance and audit approval cannot be obtained without evidence. Any rollback attempt here would be destructive and irreversible rather than corrective.
Containment and forward fix strategy.
Containment must prioritize restoring observability before correctness. 1. Immediately freeze migration actions and prevent further state changes. 2. Declare the current state provisional and non-authoritative. 3. Introduce mandatory migration IDs and structured logging for all future steps. 4. Rerun validation end-to-end with version artifacts. 5. Proceed with forward fix only after state reconstruction controls are in place. You cannot repair what you cannot explain.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Rollback failed not due to data corruption but due to missing execution evidence. 2. Observability is a prerequisite for rollback, not an optional enhancement. 3. Migration steps must be deterministic, logged, and replayable. 4. Without an authoritative timeline, correctness cannot be proven. Rollback requires evidence before it requires tools.
Follow-up 1. Why can't we reconstruct the state using system tables?
Answer: system tables show outcomes, not intent or sequencing. They cannot explain why a state exists or which migration step caused it. Without logged execution context, outcomes alone are insufficient to reconstruct authority or rollback boundaries.
Follow-up 2. When did rollback stop being safe in this scenario?
Answer: rollback stopped being safe the moment migration steps were executed without durable, correlated logs. From that point forward, no authoritative reference state existed to restore with confidence.
Follow-up 3. Curveball. Would adding logs now make rollback possible?
Answer: no. Logging is not retroactive. Adding observability after the fact cannot reconstruct missing history. It only prevents future failures, not past irreversibility.
Pro insider tip.
If you cannot replay a migration from logs in a dry run, you should assume rollback is already impossible in production.
Real-world incident during source to Redshift migration 84. Validation artifacts not versioned.
During an AWS Redshift migration, multiple validation queries, reconciliation scripts, and comparison reports were executed to build confidence before cutover. However, these validation artifacts were not versioned, timestamped, or tied to a specific migration phase. When discrepancies were later discovered, teams could not determine which validations applied to which system state, rendering rollback decisions unreliable. Failure class, observability, and state reconstruction failure.
System state before failure, very important.
At the moment rollback confidence was lost, the system state was 1. Source system writes enabled with ongoing transactional changes. 2. Redshift cluster receiving snapshot data and incremental CDC updates. 3. Validation process manual and semi-automated queries run repeatedly. 4. Validation artifacts stored informally without versioning or phase tagging. 5. CDC state advanced between validation runs. 6. BI tools gradually enabled for confidence building. 7. Declared source of truth assumed Redshift post-validation. 8. Authority status based on unverifiable validation evidence. Unversioned validation is indistinguishable from no validation.
Incident analysis and root cause.
This failure emerged from a validation governance gap. 1. Triggering action treating validation outputs as disposable rather than authoritative artifacts. 2. Why it appeared safe, validation results were repeatedly positive at the time they were run. 3. What teams noticed first, conflicting validation numbers during later investigations. 4. What teams did not notice, that no validation result could be tied to a specific system state. 5. How divergence accumulated, CDC progress and schema changes invalidated earlier validations. 6. Missing invariant, validation artifacts must be versioned and bound to an immutable system snapshot.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it creates false confidence. Validation appears thorough, yet provides no durable evidence. When incidents occur, teams cannot prove whether data was ever correct. Detection latency is high, surfacing only when rollback or audit requires historical proof.
What exactly broke? Consistency breakdown.
Audit and authority consistency are broken. There is no verifiable link between validation results and the data they supposedly validated. Redshift data cannot be trusted because correctness claims cannot be substantiated. If we roll back only data, this inconsistency remains because validation authority was never anchored to a reproducible state.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate 1. Are validation results versioned and timestamped? No evidence unverifiable. 2. Can validations be replayed against the same data state? No state moved. 3. Can rollback restore both data and validation authority? No authority missing. 4. Can rollback decisions be defended during audit? No proof trail. 5. Is there a trusted baseline to roll back to? No validation ambiguous. Rollback without trusted validation evidence is indefensible.
Decision point, rollback versus forward fix.
Rollback is unsafe because no validated reference state exists. Forward fix must focus on freezing state, rerunning validation with strict versioning, and rebuilding authority before any further migration actions are taken.
Rollback architecture.
Rollback cannot be executed with confidence. Snapshot restore would recreate data without restoring validation authority. CDC rewind cannot be justified without knowing which validations apply to which offsets. BI repointing and downstream invalidation would occur without defensible evidence. Governance approval cannot be obtained without version validation artifacts.
Containment and forward fix strategy.
Containment must restore validation discipline. 1. Immediately freeze migration and CDC advancement. 2. Invalidate all prior unversioned validation results. 3. Rerun validation against a fixed snapshot with versioned outputs. 4. Bind each validation artifact to a migration phase and offset. 5. Proceed only after validation authority is formally re-established. Validation without versioning is narrative, not evidence.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Validation failed as evidence, not as execution. 2. Correctness claims must be replayable and provable. 3. Rollback depends on trusted validation baselines. 4. Versioning is a prerequisite for migration authority. Validation must be as auditable as the data itself.
Follow-up 1. Why can't we trust validations that passed earlier?
Answer: because validations were not bound to a fixed system state. As CDC advanced and schemas evolved, earlier results lost relevance. Without versioning, a passing result has no durable meaning.
Follow-up 2. When did rollback stop being safe here?
Answer: rollback stopped being safe when validation results were used to justify decisions without being preserved as authoritative artifacts. From that moment, no trustworthy baseline existed.
Follow-up 3. Curveball. Would automating validation alone prevent this?
Answer: no. Automation without versioning still produces ephemeral results. The critical requirement is binding validation outputs to immutable system states with traceable lineage.
Pro insider tip.
If validation results cannot be reproduced byte for byte against the same snapshot, they should never be used to justify cutover or rollback decisions.
Real-world incident during source to Redshift migration 85. CDC offsets, not checkpointed with migration ID.
During an AWS Redshift migration, CDC replication tasks were stopped, started, and modified multiple times across snapshot loads, validation retries, and partial rollbacks. However, CDC offsets were not checkpointed with a unique migration identifier or phase marker. When issues surfaced, teams could not reconstruct which offsets corresponded to which migration attempt, making rollback and replay decisions unreliable. Failure class: observability and state reconstruction failure.
System state before failure, very important.
At the moment state reconstruction failed, the system state was: 1. Source system write-enabled with continuous transactional changes. 2. Redshift cluster loaded via snapshot and receiving CDC intermittently. 3. CDC pipeline stopped and restarted multiple times across migration phases. 4. CDC offsets advanced but not tagged to a specific migration run. 5. Migration attempts, multiple retries without unique identifiers. 6. BI tools enabled intermittently based on perceived stability. 7. Declared source of truth assumed Redshift after each restart. 8. Authority status undocumented and impossible to reconstruct. Offsets without context are indistinguishable from corruption.
Incident analysis and root cause.
This failure resulted from missing state attribution. 1. Triggering action restarting CDC tasks across multiple migration attempts without binding offsets to a migration ID. 2. Why it appeared safe, CDC tasks reported healthy status and advancing positions. 3. What teams noticed first, inability to explain data gaps or duplicates after rollback attempts. 4. What teams did not notice, that CDC offsets no longer map to a single linear migration timeline. 5. How divergence accumulated, offsets advanced across retries, overriding historical context. 6. Missing invariant, CDC offsets must be checkpointed with an immutable migration phase identifier.
Why this failure is dangerous, hidden risk.
This failure is dangerous because CDC continues to function operationally while destroying historical traceability. Offsets advance, lag appears healthy, and replication looks correct. Detection latency is high, often discovered only when rollback or audit requires exact reconstruction of past states.
What exactly broke? Consistency breakdown.
State and authority consistency are broken. There is no longer a trustworthy mapping between source changes, CDC offsets, and Redshift state. If we roll back only data, this inconsistency remains because the historical offset context cannot be reconstructed.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate: 1. Are CDC offsets tied to a specific migration ID? No context lost. 2. Can offsets be mapped to snapshot boundaries? No ambiguous. 3. Can CDC replay be proven safe? No replay may duplicate or skip changes. 4. Can rollback restore authority over data state? No history unclear. 5. Can rollback decisions be defended during audit? No. Offset lineage missing. Rollback without offset lineage is guesswork.
Decision point: rollback versus forward fix.
Rollback is unsafe because there is no authoritative offset baseline to return to. Forward fix must focus on freezing the current state, declaring prior attempts invalid, and re-establishing CDC with strict offset lineage before any further migration work.
Rollback architecture.
Rollback cannot be executed cleanly. Snapshot restore would recreate data without restoring CDC context. CDC rewind or discard cannot be justified because offsets are not attributable to a specific migration phase. BI repointing and downstream invalidation would occur without defensible evidence. Governance approval cannot be obtained without offset lineage.
Containment and forward fix strategy.
Containment must restore state traceability. 1. Immediately freeze CDC and migration retries. 2. Invalidate all prior migration attempts lacking offset lineage. 3. Reseed CDC from a fresh snapshot with a unique migration ID. 4. Persist offsets alongside migration metadata at every phase. 5. Proceed only after offset-to-state traceability is enforced. Offsets without lineage destroy rollback authority.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. CDC offsets are part of system state, not just replication progress. 2. Restarting CDC without migration IDs destroys historical traceability. 3. Rollback depends on knowing exactly which offsets produced which data. 4. Offset lineage is a prerequisite for defensible migration decisions. State must be identifiable before it can be reversible.
Follow-up 1. Why isn't CDC health enough to guarantee safety?
Answer: CDC health metrics show progress, not correctness. Without knowing which migration phase an offset belongs to, progress cannot be interpreted. Healthy replication can still destroy rollback viability.
Follow-up 2. When did rollback stop being safe in this case?
Answer: rollback stopped being safe the moment CDC was restarted without recording a migration-specific offset checkpoint. From that point forward, no authoritative baseline existed.
Follow-up 3. Curveball. Would storing offsets alone fix this?
Answer: no. Offsets without context are meaningless. They must be bound to migration IDs, snapshots, and validation artifacts to be actionable during rollback or audit.
Pro insider tip.
Treat CDC offsets like financial ledgers. Every movement must be attributable to a specific event, phase, and authority decision, or rollback becomes impossible.
Category 13 wrap-up. When observability fails, rollback becomes guesswork.
The previous category showed that rollback is not only a data problem but a reconstruction problem. When logs, offsets, and validation artifacts cannot be replayed or correlated, teams lose the ability to explain what happened. At that point, rollback decisions are no longer technical. They are speculative and indefensible.
Transition from state reconstruction failure to semantic corruption.
Even when every action is logged and every state can be reconstructed, migrations can still fail in a more subtle way. The data may be technically correct, complete, and consistent, yet still wrong in meaning. This next category focuses on failures where correctness exists, but truth does not.
Category 14. Semantic drift and business meaning incidents.
Semantic drift incidents occur when data values migrate successfully, but their interpretation changes. Metrics, flags, and null semantics evolve during migration windows, causing analytics to silently diverge from business reality. These failures are rarely caught by validation queries because the data still looks valid at a structural level.
Semantic drift and business meaning incident scenarios.
The following incidents illustrate how business meaning can change even when data migration appears successful. 1. Metric definitions change during migration window. 2. Null handling differences affect KPIs. 3. Boolean or enum mapping differences across systems. Core failure, semantic equivalence is not preserved across systems.
Real-world incident during source to Redshift migration 86. Metric definitions changed during migration window.
During an AWS Redshift migration, business stakeholders modified the definition of a key metric, while data was still being validated and compared between the source system and Redshift. Although the underlying data remained structurally correct in both systems, the meaning of the metric diverged mid-migration. As a result, validation results became misleading, and rollback could no longer restore analytical trust. Failure class, semantic drift, and business meaning incident.
System state before failure, very important.
At the moment semantic drift was introduced, the system state was 1. Source system writes-enabled and continuing normal business operations. 2. Redshift cluster loaded with migrated data and actively used for validation. 3. Metric logic defined in BI or semantic layer not enforced in storage. 4. CDC pipeline running normally with no data movement errors. 5. BI tools, comparing source and Redshift metrics during validation. 6. Declared source of truth, temporarily ambiguous during validation. 7. Authority status, implicitly assumed stable without locking metric definitions. Semantic stability was assumed, not enforced.
Incident analysis and root cause.
This incident was triggered by a semantic contract violation. 1. Triggering action changing metric definitions during the migration validation window. 2. Why it appeared safe underlying tables and row counts remained unchanged and valid. 3. What teams noticed first, KPI mismatches between historical reports and new dashboards. 4. What teams did not notice that validation comparisons were using different metric logic. 5. How divergence accumulated, reports validated against shifting definitions lost meaning over time. 6. Missing invariant, metric definitions must remain immutable during migration validation.
Why this failure is dangerous, hidden risk.
This failure is dangerous because all technical checks pass. Data loads succeed, row counts match, and CDC remains healthy. The corruption exists entirely in meaning, not mechanics. Detection latency is often weeks, surfacing only when business decisions, conflict, or historical trends appear to shift inexplicably.
What exactly broke? Consistency breakdown.
Semantic consistency is broken. The same data now answers different business questions depending on when and where it is queried. No single authoritative interpretation exists. If we roll back only data, this inconsistency remains because the definition change lives outside the data itself.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Has the metric definition changed during migration? Yes, semantic drift. 2. Can the old definition be reconstructed unambiguously? Often no. 3. Would a snapshot restore fixed semantic meaning? No, data unchanged. 4. Have business decisions used the new definition? Likely. 5. Can authority over metric meaning be re-established cleanly? Only via governance. Rollback restores data, not meaning.
Decision point, rollback versus forward fix.
Rollback is ineffective because no data corruption occurred. Forward fix requires explicitly rebaselining metric definitions, communicating changes, and revalidating historical interpretations under a single, frozen semantic contract.
Rollback architecture.
Rollback cannot be executed meaningfully in this scenario. Restoring snapshots or replaying CDC would reproduce identical data with the same semantic ambiguity. The only viable action is to formally declare which metric definition is authoritative and invalidate all analyses produced under the conflicting definition.
Containment and forward fix strategy.
Once semantic drift is identified, containment must be immediate. 1. Freeze all metric definitions until migration completes. 2. Declare a single authoritative definition retroactively. 3. Invalidate or annotate reports built during the drift window. 4. Rerun validations using the frozen definition. 5. Introduce governance controls for metric changes. Meaning must be stabilized before data can be trusted.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Data correctness does not guarantee semantic correctness. 2. Metric definitions are contracts and must be versioned and frozen during migration. 3. Validation is meaningless if the question being asked changes midstream. 4. Rollback cannot fix failures that live outside the data layer. Semantic contracts must be immutable during migration windows.
Follow-up 1. Why can't SQL detect this failure?
Answer: because SQL only validates data shape and values, not business meaning. The same query can be technically correct while answering a different question after a definition change. This makes the failure invisible to traditional validation.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe the moment the metric definition changed and new reports were produced. At that point, restoring data would not restore the business interpretation already communicated.
Follow-up 3. Curveball. What if leadership wants to keep both definitions?
Answer: that creates permanent analytical ambiguity. The architect must force a single canonical definition and treat the alternative as a new metric, not a migration artifact.
Pro insider tip.
If metric definitions are not frozen during migration, validation results are fiction. You may migrate data perfectly and still migrate the wrong business reality.
Real-world incident during source to Redshift migration 87. Null handling differences affect KPIs.
During an AWS Redshift migration, key performance indicators began to drift even though row counts and base data appeared identical between the source system and Redshift. The root cause was a difference in null handling semantics between the source database, the transformation logic, and Redshift SQL behavior. This caused aggregates and ratios to compute differently post-migration. Failure class: semantic drift and business meaning incident.
System state before failure, very important.
At the moment KPI drift was introduced, the system state was 1. Source system, writes enabled with established null handling behavior in queries and views. 2. Redshift cluster loaded with migrated data and executing equivalent analytical queries. 3. Transformation logic partially rewritten or revalidated during migration. 4. CDC pipeline running normally with no data loss or lag alerts. 5. BI tools pointed to Redshift and publishing KPI values. 6. Declared source of truth assumed Redshift for analytics. 7. Authority status implicitly transferred without semantic equivalence verification. Null semantics were assumed equivalent across systems.
Incident analysis and root cause.
This incident resulted from a silent semantic mismatch. 1. Triggering action, rerunning KPI queries in Redshift without enforcing identical null handling rules. 2. Why it appeared safe, base tables matched exactly and validation focused on row counts and totals. 3. What teams noticed first, KPI percentages and averages drifting subtly post-migration. 4. What teams did not notice, that null were being treated differently inside aggregates and expressions. 5. How divergence accumulated, every aggregation amplified small null handling differences over time. 6. Missing invariant, null handling semantics must be identical across source, transformation, and target.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it produces believable but incorrect metrics. All pipelines are green, validations pass, and dashboards remain stable. The corruption exists in interpretation, not data movement. Detection latency is typically weeks, surfacing only when business decisions conflict with historical expectations.
What exactly broke? Consistency breakdown.
Semantic and analytical consistency are broken. Identical datasets now yield different answers depending on how null are interpreted. No single authoritative KPI definition exists across systems. If we roll back only data, this inconsistency remains because the divergence lies in query semantics, not stored values.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Is the underlying data corrupted? No data is intact. 2. Are KPI results semantically equivalent? No null handling differs. 3. Would snapshot restore change KPI behavior? No same semantics apply. 4. Have business decisions used the drifted KPIs? Likely. 5. Can authority be restored by data rollback alone? No semantics unresolved. Rollback restores rows, not interpretation.
Decision point, rollback versus forward fix.
Rollback is ineffective because no data error occurred. Forward fix must focus on aligning null handling semantics explicitly, revalidating KPIs, and re-establishing trust through documented metric definitions.
Rollback architecture.
Rollback cannot resolve this failure. Snapshot restore, or CDC replay, reproduces identical data with the same semantic behavior. The only corrective action is to redefine KPI logic and enforce consistent null handling rules across all analytical layers.
Code illustration and Redshift artifacts.
In this section, we will show 1. How KPI values differ when null are treated differently in aggregates. 2. Why identical row counts still produce divergent analytical results. Null semantics directly influence analytical truth. Semantic drift, KPI discrepancy via null handling. Disclaimer: always test code in a non-production environment. This comparison illustrates the drift. Standard average excludes null, while coalesce treats them as zero. During migration, if your source and target systems default to different behaviors, your KPIs will diverge even though the raw data is identical.
Containment and forward fix strategy.
Once null handling drift is confirmed, containment must be immediate. 1. Freeze KPI publication until semantic alignment is complete. 2. Document and standardize null handling rules for all metrics. 3. Update queries, views, and BI logic to enforce consistency. 4. Recompute affected KPIs and annotate historical reports. 5. Introduce semantic validation into migration checklists. Semantic consistency must be enforced, not assumed.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Null handling differences can silently corrupt KPIs without changing data. 2. Validation focused on rows and totals misses semantic divergence. 3. Rollback cannot fix failures rooted in query semantics. 4. Metric definitions must explicitly specify null behavior. Semantic equivalence must be defined, not inferred.
Follow-up 1. Why do null handling differences evade standard validation?
Answer: because row counts, checksums, and even sums can match while averages, ratios, and percentages drift. Null semantics only surface at the aggregation layer, which is often validated last or not at all.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe once KPI values computed with new null semantics were consumed by the business. At that point, restoring data would not restore the interpretation already acted upon.
Follow-up 3. Curveball. What if null handling differs across BI tools too?
Answer: then the problem multiplies. The architect must centralize metric computation and enforce semantics at a single layer. Otherwise, each tool produces a different version of truth.
Pro insider tip.
If null semantics are not locked down during migration, KPI drift is guaranteed. Most teams only discover it after executives start asking why the same data tells different stories.
Real-world incident during source to Redshift migration 88. Boolean/enum mapping differences affect business meaning.
During an AWS Redshift migration, several KPIs and filters began producing inconsistent results even though the underlying data values appeared correct. The root cause was a mismatch in how Boolean and enum values were mapped between the source system, CDC pipeline, and Redshift. Values that were semantically equivalent in the source were interpreted differently in Redshift, leading to silent analytical drift. Failure class, semantic drift, and business meaning incident.
System state before failure, very important.
At the moment semantic drift was introduced, the system state was 1. Source system write enabled with Boolean or enum fields using source-specific encodings. 2. Redshift cluster loaded with migrated data using native Boolean or varchar mappings. 3. CDC pipeline actively replicating values without semantic normalization. 4. Transformation logic minimal or bypass to preserve raw values. 5. BI tools, applying filters and aggregations based on assumed semantics. 6. Declared source of truth, assumed Redshift for analytics. 7. Authority status, transferred without validating enum or Boolean equivalence. Value equality was assumed to imply semantic equality.
Incident analysis and root cause.
This incident resulted from a contract mismatch rather than data loss. 1. Triggering action, mapping source Booleans or enums directly into Redshift without enforcing canonical meaning. 2. Why it appeared safe, values loaded successfully and row counts matched across systems. 3. What teams noticed first, filters and breakdowns producing unexpected category distributions. 4. What teams did not notice, that identical literal values carried different business meaning. 5. How divergence accumulated, every query amplified misinterpreted enum or Boolean states. 6. Missing invariant, Enum and Boolean semantics must be explicitly normalized during migration.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it produces analytically consistent but semantically wrong results. Queries run correctly, dashboards look stable, and validations pass. The corruption exists in interpretation, not storage. Detection latency is often weeks, surfacing only when business outcomes conflict with operational reality.
What exactly broke? Consistency breakdown.
Semantic and domain-level consistency are broken. The same Boolean or enum values represent different states across systems. There is no single authoritative interpretation of business flags or statuses. If we roll back only data, this inconsistency remains because the meaning attached to values is already divergent.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Is the stored data corrupted? No values are present. 2. Are enum or Boolean meanings aligned? No semantic drift exists. 3. Would snapshot restore change interpretation? No same mappings apply. 4. Have business decisions used misinterpreted values? Likely. 5. Can authority be restored by rollback alone? No semantics unresolved. Rollback restores values, not their meaning.
Decision point, rollback versus forward fix.
Rollback is ineffective because no data loss occurred. Forward fix must re-establish a canonical mapping for Booleans and enums, update transformations and BI logic, and revalidate all dependent metrics.
Rollback architecture.
Rollback cannot correct this failure. Restoring snapshots or replaying CDC reproduces the same semantic mismatch. Corrective action requires redefining value contracts and enforcing them consistently across ingestion, storage, and consumption layers.
Code illustration and Redshift artifacts.
In this section, we will show 1. How Boolean or enum value distributions differ between expected and observed states. 2. Why identical stored values lead to divergent analytical interpretations. Semantic drift can be proven through distribution analysis. Here is Redshift SQL showing enum or Boolean mapping drift via value distribution. Disclaimer: always test code in a non-production environment. This distribution exposes how Boolean or enum values are populated in Redshift. Comparing expected versus actual categories proves that semantic meaning has shifted despite successful data load.
Containment and forward fix strategy.
Once mapping drift is confirmed, containment must be immediate. 1. Freeze analytics relying on affected enums or flags. 2. Define and document canonical Boolean and enum meanings. 3. Apply normalization logic during ingestion or transformation. 4. Recompute affected reports and annotate historical outputs. 5. Add semantic contract checks to migration validation. Value contracts must be enforced, not inferred.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Boolean and enum values can drift semantically without any data loss. 2. Standard validation misses meaning-level inconsistencies. 3. Rollback cannot fix interpretation errors. 4. Semantic contracts must be explicit during migration. Semantic meaning must be governed, not assumed.
Follow-up 1. Why do enum mapping issues evade detection?
Answer: because values load successfully and distributions may look reasonable in isolation. The failure appears only when those values are interpreted in business logic, where assumptions about meaning no longer hold.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe once analytics and decisions relied on the misinterpreted values. At that point, restoring data would not restore the meaning already applied by consumers.
Follow-up 3. Curveball. What if the source system also changes enum meaning later?
Answer: then the divergence compounds. The architect must version enum semantics explicitly and treat meaning changes as breaking contracts, not as routine data evolution.
Pro insider tip.
If enum or Boolean meaning is not explicitly versioned during migration, semantic drift is inevitable. The data will be correct, and the business conclusions will be wrong.
Category 14 wrap-up. When meaning breaks, correct data still lies.
The previous category demonstrated that migrations can fail even when data is structurally correct and complete. Once business meaning drifts, rollback restores bytes but not interpretation. At that point, trust is broken at the semantic layer, not the storage layer.
Transition from semantic drift to external dependency failures.
Even when semantics are well governed, Redshift rarely operates in isolation. Modern migrations depend on external tables, S3, glue, data sharing, and managed replication services. The next category focuses on failures where correctness breaks outside the Redshift cluster boundary.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs in a single zip file, containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, system design. Required for your data engineer interviews jobs like data quality analyst jobs, data governance analyst jobs, AWS Python data engineer jobs, AWS Redshift Database Administrator DBA jobs, AWS Glue ETL Developer jobs, AWS Data Engineer jobs, Cloud Data Engineer jobs, Data Architect jobs, DataOps Engineer jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based questions and answers, real-world problem-solving, interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people also for your interviews. You people can download all 6 PDFs in a single zip file from below given links.
Category 15. Redshift Lakehouse and Spectrum Dependency Incidents.
These incidents occur when Redshift depends on external systems whose state, metadata, or consistency guarantees differ from core database assumptions. Data may be correct at rest, but external dependencies introduce timing gaps, schema drift, or access inconsistencies that invalidate analytical trust.
Redshift Lakehouse and Spectrum Dependency Scenarios.
The following scenarios illustrate how external dependencies can silently break consistency during migration. 1. External table schema drift when source S3 par-K evolves while Redshift external DDL remains frozen. 2. Glue catalog metadata falling out of sync, causing Spectrum scan failures or partial reads. 3. Data share consumer breakage when producer clusters migrate or roll back independently. 4. S3 eventual consistency causing Redshift to read stale data immediately after successful writes. 5. Redshift maintenance window interruptions halting or duplicating DMS ongoing replication. Core failure. External dependencies break consistency guarantees beyond Redshift control.
Real-world incident during source to Redshift migration 89. External table schema drift while Spectrum DDL remains frozen.
During an AWS Redshift migration, external tables backed by S3 par-K files were used to validate and supplement data in Redshift. While the migration was in progress, upstream pipelines evolved the par-K schema by adding new columns and changing field structures. Redshift external table definitions were not updated, causing silent schema drift between S3 and Redshift Spectrum. Queries continued to run but returned incomplete or misleading results. Failure class, Redshift Lakehouse and Spectrum Dependency Incident.
System state before failure, very important.
At the moment schema drift was introduced, the system state was 1. Source data lake actively evolving par-K schemas in S3. 2. Redshift cluster querying data via Spectrum external tables. 3. External table DDL frozen to stabilize migration validation. 4. Glue catalog reflecting updated par-K schema from upstream jobs. 5. BI and analytics reading from Spectrum back tables. 6. Declared source of truth implicitly assumed to include external tables. 7. Authority status assumed stable without schema parity enforcement. External tables inherit schema risk from upstream storage.
Incident analysis and root cause.
This failure resulted from an invalid contract assumption. 1. Triggering action. Upstream jobs evolved PAR-K schemas during the migration window. 2. Why it appeared safe. Spectrum queries continued to succeed without runtime errors. 3. What teams noticed first. Missing or null values for newly introduced business attributes. 4. What teams did not notice that Redshift was silently ignoring fields not present in external table DDL. 5. How divergence accumulated. Analytics consumed incomplete rows while assuming full schema coverage. 6. Missing invariant. External table DDL must always remain schema compatible with underlying data.
Why this failure is dangerous. Hidden risk.
This failure is dangerous because it produces valid-looking but incomplete results. Spectrum does not fail when extra PAR-K columns exist. It simply ignores them. Validation checks pass, dashboards render, and no alerts fire. Detection latency is often weeks, discovered only when new fields are referenced by business logic.
What exactly broke? Consistency breakdown.
Domain level and semantic consistency are broken. The data lake contains richer records than Redshift can see. Redshift is no longer a trustworthy analytical surface for domains dependent on external tables. If we roll back only data, this inconsistency remains because schema evolution happened outside Redshift and cannot be reverted by snapshots.
Rollback viability checklist. Go or no go.
Before rollback is considered, the architect must evaluate. 1. Did external PAR-K schema change during migration? Yes, drift exists. 2. Can Redshift snapshots restore external table schemas? No external state. 3. Have downstream users consumed incomplete analytics? Likely. 4. Is original schema version recoverable in S3? Sometimes version dependent. 5. Can authority be restored cleanly? No contract already broken. Rollback cannot revert external schema evolution.
Decision point. Rollback versus forward fix.
Rollback is not meaningful because restoring Redshift state does not restore external table compatibility. Forward fix is required to realign schema contracts between S3, Glue, and Redshift before analytical trust can be restored.
Rollback architecture.
A true rollback cannot be executed in this scenario. Redshift snapshots do not capture external schemas or Glue catalog state. Any attempt to restore the cluster reproduces the same incompatibility unless external data and metadata are also versioned and reverted, which is rarely feasible.
Code illustration and Redshift artifacts.
In this section, we will show 1. How external table definitions differ from underlying PAR-K schema. 2. How Spectrum queries expose missing or ignored columns. Spectrum enforces DDL contracts, not PAR-K truth. Here is Redshift SQL showing external table column definitions, frozen during schema evolution. Disclaimer: always test code in a non-production environment. This snippet proves what Redshift believes the external table schema to be. Any PAR-K fields missing here are invisible to Spectrum queries, regardless of their presence in S3. Here is Redshift SQL showing null or missing values, caused by external schema drift. Disclaimer: always test code in a non-production environment. This snippet proves that a field present in PAR-K is not visible in Redshift. The discrepancy confirms silent schema drift rather than missing data.
Containment and forward fix strategy.
Once schema drift is confirmed, containment must precede repair. 1. Immediately pause analytical reliance on Spectrum-backed tables. 2. Reconcile PAR-K schemas against external table DDL definitions. 3. Update Glue catalog and Redshift external tables in a controlled change window. 4. Rerun validation queries explicitly covering newly introduced fields. 5. Establish schema freeze or dual deploy rules for future migrations. External schema contracts must be governed, not assumed.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. External tables do not automatically adapt to PAR-K schema evolution. 2. Spectrum can return valid results while silently ignoring new fields. 3. Rollback cannot restore schema compatibility when drift happens outside Redshift. 4. Schema contracts must be enforced across storage, catalog, and query layers. Schema authority must be centralized before analytics can be trusted.
Follow-up 1. Why didn't Spectrum fail when the Parquet schema changed?
Answer: Spectrum enforces the external table DDL, not the underlying file schema. Extra fields in Parquet are ignored rather than rejected. This makes the failure semantic instead of operational, allowing queries to succeed while silently returning incomplete data.
Follow-up 2. When did Rollback stop being safe in this scenario?
Answer: Rollback stopped being safe the moment Parquet schemas evolved without synchronized external table updates. From that point onward, no Redshift snapshot could restore full analytical truth because the missing fields were never visible to Redshift.
Follow-up 3. Curveball. What if only one downstream team used the new columns?
Answer: that still breaks global analytical trust. Once any consumer relies on fields invisible to Redshift, partial truth exists. The architect must either block those fields entirely or fast-track schema alignment to restore a single authoritative contract.
Pro insider tip.
If Spectrum queries look healthy but new fields are always null, assume schema drift first. External tables fail silently far more often than they fail loudly.
Real-world incident during source to Redshift migration 90. Glue catalog metadata out of sync causes Spectrum scan failures.
During an AWS Redshift migration, Amazon Redshift Spectrum was used to query data stored in S3 via the AWS Glue data catalog. While upstream ingestion jobs continued updating table schemas and partitions, Glue catalog updates intermittently failed or lagged. Redshift Spectrum queries began failing or returning inconsistent results because metadata no longer accurately represented the underlying S3 layout. Failure class: Redshift Lakehouse and Spectrum Dependency Incident.
System state before failure. Very important.
At the moment the failure was introduced, the system state was 1. Source data lake actively writing new partitions and evolving schemas in S3. 2. Glue data catalog partially updated with delayed or failed crawls. 3. Redshift cluster querying external tables through Spectrum. 4. External table definitions dependent on Glue metadata. 5. BI and analytics running validation queries against Spectrum-backed datasets. 6. Declared source of truth assumed to include external tables. 7. Authority status implicitly trusted Glue metadata without verification. Spectrum correctness depends entirely on Glue metadata accuracy.
Incident analysis and root cause.
This failure resulted from a broken metadata dependency. 1. Triggering action upstream pipelines modified S3 schemas and partitions without guaranteed Glue synchronization. 2. Why it appeared safe previous crawls had succeeded and Spectrum queries worked historically. 3. What teams noticed first, intermittent Spectrum scan errors or missing partitions. 4. What teams did not notice that Glue catalog state no longer matched actual S3 layout. 5. How divergence accumulated, queries alternated between partial success and failure as metadata drift widened. 6. Missing invariant Glue catalog metadata must be transactionally consistent with S3 data layout.
Why this failure is dangerous. Hidden risk.
This failure is dangerous because it produces non-deterministic behavior. The same query may succeed, partially succeed, or fail depending on which partitions Glue exposes at query time. Validation becomes unreliable, and analysts may trust incomplete results. Detection latency is often days, surfacing only under specific query patterns.
What exactly broke? Consistency breakdown.
Domain level and temporal consistency are broken. Redshift Spectrum no longer represents a complete or stable view of the data lake. If we roll back only data, this inconsistency remains because the failure lies in external metadata state, not in Redshift storage.
Rollback viability checklist. Go or no go.
Before rollback is considered, the architect must evaluate. 1. Is Glue metadata consistent with S3 data? No, drift exists. 2. Can Redshift snapshots restore Glue state? No, external service. 3. Have consumers queried incomplete data? Likely. 4. Is previous Glue state recoverable? Rarely, not versioned. 5. Can authority be restored cleanly? No, metadata trust broken. Rollback cannot repair external metadata drift.
Decision point. Rollback versus forward fix.
Rollback is not viable because restoring Redshift does not restore glue catalog correctness. Forward fix is required to resynchronize metadata, validate completeness, and explicitly reassert analytical authority.
Rollback architecture.
A true rollback cannot be executed in this scenario. Glue catalog state is external, mutable, and typically not versioned. Any rollback attempt would reproduce the same inconsistency unless metadata and data lake state are reverted together, which is rarely possible.
Code illustration and Redshift artifacts.
In this section, we will show 1. How glue catalog metadata differs from actual S3 partitions. 2. How Spectrum queries fail or skip partitions due to metadata drift. Metadata correctness is a prerequisite for analytical truth. Here is Redshift SQL showing Spectrum scan failures caused by missing glue partitions. Disclaimer: always test code in a non-production environment. This query highlights missing data when expected partitions are absent from the glue catalog. Comparing results against S3 contents proves metadata drift rather than data loss. Here is Redshift SQL inspecting external table partition visibility via system views. Disclaimer: always test code in a non-production environment. This view shows what Redshift believes exists externally. Any mismatch with actual S3 structure confirms glue synchronization failure.
Containment and forward fix strategy.
Once glue drift is confirmed, containment must precede repair. 1. Pause analytical reliance on Spectrum-backed datasets. 2. Force glue crawler reruns with validation checks. 3. Reconcile partition counts between S3 and glue explicitly. 4. Revalidate all time-bound analytics after metadata repair. 5. Introduce metadata drift alerts before resuming migration. Metadata drift must be treated as data corruption.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Redshift Spectrum correctness depends entirely on glue metadata. 2. Glue catalog lag can cause silent data loss in analytics. 3. Rollback cannot fix external metadata corruption. 4. Metadata synchronization must be an explicit migration invariant. External metadata is part of the data contract, not an implementation detail.
Follow-up 1. Why do Spectrum queries sometimes succeed and sometimes fail?
Answer: because Spectrum reads whatever glue exposes at query time. If partitions are partially registered, results vary. This makes the failure state-dependent and non-deterministic rather than a hard outage.
Follow-up 2. When did rollback stop being safe in this scenario?
Answer: rollback stopped being safe once glue metadata diverged from S3. From that moment, no Redshift restore could guarantee completeness because the authoritative catalog was already inconsistent.
Follow-up 3. Curveball. What if glue is fixed but analysts already exported reports?
Answer: then rollback of metadata alone is insufficient. External decisions were made using incomplete data. The architect must invalidate those reports and re-establish trust through explicit revalidation.
Pro insider tip.
If Spectrum behaves inconsistently, always validate glue partition counts against S3 first. Most Spectrum failures are metadata problems disguised as data issues.
Real-world incident during source to Redshift migration 91. Redshift data share consumer breakage after producer migration.
During an AWS Redshift migration, the producer cluster hosting shared datasets was modified as part of cutover and stabilization activities. Although the producer appeared healthy post-migration, downstream consumer clusters relying on Redshift data sharing experienced missing objects, permission errors, or stale data. The migration did not propagate shared state guarantees to consumers. Failure class: Redshift Lakehouse and Spectrum dependency incident.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Producer Redshift cluster undergoing migration-related changes. 2. Consumer Redshift clusters actively querying shared datasets. 3. Data sharing mechanism Redshift data share across clusters/accounts. 4. CDC and ingestion operating only on producer cluster. 5. BI and downstream consumers connected via consumer clusters. 6. Declared source of truth, assumed to be producer cluster. 7. Authority status, implicitly assumed to propagate to consumers. Data sharing introduces hidden downstream dependencies.
Incident analysis and root cause.
This incident resulted from an incomplete understanding of shared state propagation. 1. Triggering action, migrating or modifying the producer cluster during cutover. 2. Why it appeared safe, producer validation passed and internal queries succeeded. 3. What teams noticed first, consumer queries failing or returning incomplete data. 4. What teams did not notice, that data share objects and permissions are not fully migration transparent. 5. How divergence accumulated, consumers continued operating on broken or stale shared views. 6. Missing invariant, shared data consumers must be validated as first-class migration dependencies.
Why this failure is dangerous, hidden risk.
This failure is dangerous because producer-side validation gives false confidence. Consumers may silently receive partial data or fail selectively. Detection latency is often days, discovered only when consumer-specific dashboards or pipelines break.
What exactly broke? Consistency breakdown.
Authority and domain-level consistency are broken. The producer cluster no longer guarantees correctness for consumers. If we roll back only producer data, this inconsistency remains because consumer access state and shared object integrity are already fractured.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Are consumer clusters still fully functional? No errors observed. 2. Does producer rollback restore data share objects? No, not guaranteed. 3. Have consumers materialized shared data? Likely. 4. Are share permissions versioned? Often no. 5. Can authority be re-established cleanly? No, consumers already impacted. Rollback restores producer state, not consumer trust.
Decision point, rollback versus forward fix.
Rollback is insufficient because restoring the producer does not guarantee consumer recovery. Forward fix must focus on revalidating data shares, re-granting permissions, and explicitly re-onboarding consumers.
Rollback architecture.
A full rollback would require coordinated restoration of the producer cluster and all consumer clusters. Because consumer state and permissions are not transactionally bound to producer snapshots, rollback cannot be executed safely in isolation.
Code illustration and Redshift artifacts.
In this section, we will show 1. How data share objects appear inconsistent across producer and consumer clusters. 2. How consumer-side query failures prove shared state breakage. Shared data integrity must be validated end-to-end. Here is Redshift SQL showing missing shared objects on a consumer cluster. Disclaimer: always test code in a non-production environment. This query proves that expected shared tables are missing or inaccessible on the consumer cluster, even though they exist on the producer. Here is Redshift SQL showing consumer-side permission errors when querying shared data. Disclaimer: always test code in a non-production environment. Query failures or partial results here prove that producer correctness does not imply consumer correctness after migration.
Containment and forward fix strategy.
Once consumer breakage is confirmed, containment must precede repair. 1. Pause consumer analytics dependent on shared data. 2. Revalidate all data share objects post-migration. 3. Reapply grants and permissions explicitly. 4. Force consumer-side revalidation before resuming trust. 5. Document shared state dependencies for future migrations. Data sharing multiplies rollback complexity.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Redshift data sharing creates hidden downstream consumers. 2. Producer migration does not guarantee consumer continuity. 3. Rollback must consider shared state propagation. 4. Consumers must be treated as first-class migration participants. Shared data breaks the single system rollback assumption.
Follow-up 1. Why didn't producer-side validation catch this?
Answer: because producer validation does not exercise consumer permissions or object visibility. The failure exists only when data is accessed through the consumer cluster, outside the producer's scope.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe once consumer clusters began failing or materializing partial data. At that point, restoring the producer alone could not restore global consistency.
Follow-up 3. Curveball. What if only one consumer is affected?
Answer: even a single affected consumer breaks global trust. Migration authority must be restored across all consumers before declaring success. Otherwise, rollback boundaries are already crossed.
Pro insider tip.
Before migrating a producer cluster, inventory and validate every data share consumer. Unseen consumers are the fastest way to invalidate a rollback plan.
Real-world incident during source to Redshift migration 92. S3 eventual consistency causes stale reads after migration writes.
During an AWS Redshift migration, data was written to Amazon S3 as part of snapshot offload and CDC staging. Write operations returned success, and downstream steps proceeded assuming durability. However, immediate Redshift Spectrum queries read stale object versions due to S3 eventual consistency semantics, producing incorrect analytical results. Failure class, Redshift Lakehouse, and Spectrum dependency incident.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system successfully exporting data to S3. 2. Amazon S3 accepting writes with eventual consistency guarantees. 3. Redshift cluster querying S3 via Spectrum immediately after writes. 4. External tables defined correctly but pointing to recently written objects. 5. BI tools running validation queries shortly after data arrival. 6. Declared source of truth assumed S3-backed external tables. 7. Authority status implicitly granted without read-after-write validation. Write success does not imply immediate read correctness.
Incident analysis and root cause.
This incident resulted from an incorrect durability assumption. 1. Triggering action querying external tables immediately after S3 writes. 2. Why it appeared safe S3 returned success for all put operations. 3. What teams noticed first inconsistent query results across repeated runs. 4. What teams did not notice that S3 does not guarantee immediate read consistency for overwrites. 5. How divergence accumulated. Validation passed intermittently, masking stale reads. 6. Missing invariant read-after-write consistency must be explicitly validated for S3-backed queries.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it creates non-deterministic validation results. The same query may succeed or fail depending on timing. Detection latency is high, and engineers often misdiagnose the issue as query instability or caching.
What exactly broke? Consistency breakdown.
Temporal and authority consistency are broken. Data exists but is not uniformly visible. If we roll back only data, this inconsistency remains because S3 visibility timing is independent of Redshift rollback state.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Were writes acknowledged by S3? Yes, put success returned. 2. Were reads immediately consistent? No stale reads observed. 3. Does rollback change S3 consistency behavior? No. 4. Have downstream consumers use stale results? Likely. 5. Can authority be re-established cleanly? No. Timing-dependent visibility persists. Rollback cannot enforce read-after-write consistency.
Decision point. Rollback versus forward fix.
Rollback is not meaningful because restoring prior data does not address visibility timing. Forward fix must focus on enforcing read delays, object versioning, or explicit validation windows.
Rollback architecture.
A rollback would involve restoring Redshift state and repointing external tables. However, because S3 consistency semantics are unchanged by rollback, this does not restore correctness guarantees.
Code illustration and Redshift artifacts.
In this section, we will show 1. How repeated Spectrum queries return inconsistent results immediately after S3 writes. 2. How object timestamps differ from query visibility. Eventual consistency breaks deterministic validation. Here is Redshift SQL showing non-deterministic results from Spectrum immediately after S3 writes. Disclaimer: always test code in a non-production environment. Running this query repeatedly after S3 writes can yield different results, proving that data visibility is not yet stable.
Containment and forward fix strategy.
Once S3 consistency issues are confirmed, containment must precede repair. 1. Introduce mandatory delay between S3 writes and Spectrum reads. 2. Use object versioning to avoid overwrite semantics. 3. Validate object counts before enabling BI access. 4. Document S3 consistency assumptions explicitly. 5. Rerun validation only after visibility stabilization. Timing guarantees must be explicit in lakehouse designs.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. S3 write success does not imply immediate read consistency. 2. Spectrum queries inherit S3 consistency semantics. 3. Rollback cannot change object visibility timing. 4. Validation windows must respect storage guarantees. Read after write consistency must be proven, not assumed.
Follow-up 1. Why did validation pass sometimes?
Answer: because S3 consistency is timing dependent. Some reads occurred after visibility stabilized, while others did not. This creates false confidence during migration validation.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe once downstream consumers trusted Spectrum results. At that point, restoring data could not undo decisions made from stale reads.
Follow-up 3. Curveball. Would retries fix this?
Answer: retries may mask the issue but do not guarantee correctness. Without explicit stabilization logic, retries only make non-determinism less visible, not less dangerous.
Pro insider tip.
If your migration depends on Spectrum, treat S3 consistency as a first-class architectural constraint, not a storage footnote.
Real-world incident during source to Redshift migration 93. Maintenance window interruptions. Corrupt CDC state during ongoing replication.
During an AWS Redshift migration, an automated maintenance window interrupted ongoing CDC replication. The replication task failed mid-apply and was automatically retried after the cluster became available. This retry caused partial reapplication of changes and silent duplication, even though the CDC task reported a healthy running state. Failure class: Redshift Lakehouse and Spectrum Dependency Incident.
System state before failure. Very important.
At the moment the failure was introduced, the system state was: 1. Source system write enabled and continuing normal transactional activity. 2. Redshift cluster undergoing scheduled maintenance or patching. 3. CDC pipeline actively applying ongoing replication changes. 4. CDC task state interrupted mid-apply without clean transaction boundaries. 5. BI tools disabled or consuming Redshift post-maintenance. 6. Declared source of truth assumed Redshift after snapshot cutover. 7. Authority status assumed stable despite mid-flight interruption. Maintenance does not respect CDC transactional boundaries.
Incident analysis and root cause.
This failure resulted from an unsafe assumption about retry semantics. 1. Triggering action automated Redshift maintenance interrupted CDC apply operations. 2. Why it appeared safe, CDC tasks automatically resumed and reported healthy status. 3. What teams noticed first, gradual appearance of duplicate or inflated metrics. 4. What teams did not notice, that CDC retries reapplied partially committed changes. 5. How divergence accumulated, CDC advanced offsets without guaranteeing exactly once apply. 6. Missing invariant, CDC apply must be idempotent across infrastructure interruptions.
Why this failure is dangerous. Hidden risk.
This failure is dangerous because it hides behind infrastructure reliability features. Maintenance and retries are expected behaviors, yet they silently violate replication correctness. Detection latency is often weeks, discovered only through deep reconciliation.
What exactly broke? Consistency breakdown.
Transactional and temporal consistency are broken. The same logical change may be applied more than once. If we roll back only data, this inconsistency remains because the CDC state itself is already corrupted.
Rollback viability checklist. Go or no go.
Before rollback is considered, the architect must evaluate. 1. Did maintenance interrupt CDC mid-apply? Yes, partial state exists. 2. Are CDC offsets guaranteed exactly once? No, retry ambiguity. 3. Can duplicated changes be deterministically identified? Sometimes. 4. Have downstream systems consumed corrupted data? Likely. 5. Can authority be restored cleanly? No, CDC state untrusted. Once CDC state is corrupted, rollback is no longer clean.
Decision point. Rollback versus forward fix.
Rollback is unsafe because restoring snapshots without correcting CDC state risks reintroducing the same corruption. Forward fix with deduplication and CDC reseeding becomes the only viable path.
Rollback architecture.
A rollback would require full cluster snapshot restore, complete CDC task discard, and reseeding from a known good source snapshot. Partial rollback or CDC resume is explicitly unsafe in this state.
Code illustration and Redshift artifacts.
In this section, we will show 1. How CDC retries after maintenance create duplicate application. 2. How system tables expose interrupted apply behavior. Infrastructure retries can violate exactly once replication. Here is Redshift SQL showing duplicate application caused by CDC retries after maintenance. Disclaimer: always test code in a non-production environment. This snippet proves that identical business events were applied more than once, indicating CDC retry behavior without idempotency.
Containment and forward fix strategy.
Once maintenance-induced CDC corruption is confirmed, containment must precede repair. 1. Immediately pause CDC replication. 2. Declare Redshift non-authoritative until repaired. 3. Deduplicate affected tables using business keys and timestamps. 4. Discard and recreate CDC tasks with fresh checkpoints. 5. Resume replication only after state integrity is proven. CDC retries must never be trusted blindly.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Infrastructure maintenance can interrupt CDC mid-apply. 2. Automatic retries do not guarantee exactly once semantics. 3. CDC state corruption survives snapshot rollback. 4. Forward fix requires CDC reseeding, not resume. Exactly once replication must survive infrastructure failures.
Follow-up 1. Why didn't CDC fail loudly?
Answer: because retries are considered normal recovery behavior. From the system perspective, progress continued, but logical correctness was already violated.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe once CDC resumed after maintenance with corrupted state. At that moment, offsets could no longer be trusted.
Follow-up 3. Curveball. Would disabling maintenance prevent this?
Answer: it reduces risk but does not eliminate it. Any unplanned interruption can recreate this failure unless CDC apply is provably idempotent.
Pro insider tip.
If CDC correctness depends on uninterrupted uptime, your replication design is already unsafe.
Category 15 wrap-up. Why external dependencies make rollback fragile.
The previous category showed that Redshift migrations rarely operate in isolation. When external systems like S3, Glue, data sharing, or managed replication are involved, correctness depends on contracts outside the cluster. Once those contracts drift, rollback restores internal data but not external truth, leaving hidden inconsistencies intact.
Transition from external dependencies to identity collapse.
If external dependencies quietly undermine consistency, identity and key failures go one step further. They corrupt the fundamental guarantees that tie records together. These failures are especially dangerous because row counts and validations often pass while joins, references, and business meaning silently break.
Category 16. Identity, surrogate key, and sequence failures.
This category covers migration failures where identity, surrogate keys, or sequence behavior diverge between source and Redshift. These issues are the most common silent killers of referential integrity. Once keys collide, regenerate differently, or fill gaps inconsistently, rollback may restore data but cannot restore correct relationships.
Scenarios in this category.
The following incidents demonstrate how identity and key semantics break during migration. 1. Identity column reset target resets counters, causing new inserts to collide with existing source IDs. 2. Surrogate key regeneration hash or surrogate logic differs between source and Redshift, especially with null handling. 3. Gap management failure. Source preserves gaps while Redshift fills them during copy or insert, breaking external references. 4. Federated or external table key collisions. Sequences or keys regenerate differently across systems, causing cross-system collisions. Core failure. Referential integrity is silently lost even though the data appears complete.
Real-world incident during source to Redshift migration 94. Identity column reset causes silent primary key collisions.
During an AWS Redshift migration, Historical data was bulk loaded using copy into tables with identity columns. After the load, new inserts began generating identity values that overlap with existing primary keys originating from the source system. This created silent key collisions that broke referential integrity across fact and dimension tables. Failure class, identity, surrogate key, and sequence failures.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system write enabled with monotonically increasing primary keys. 2. Redshift cluster loaded via copy into tables with identity columns. 3. Identity behavior Redshift auto-generated new values post-load. 4. CDC pipeline either paused or resumed without identity alignment. 5. BI tools reading exclusively from Redshift. 6. Declared source of truth, implicitly Redshift for analytics. 7. Authority status, assumed intact without validating key continuity. Identity columns reset silently unless explicitly reseeded.
Incident analysis and root cause.
This incident resulted from a broken identity continuity assumption. 1. Triggering action, bulk loading historical data into Redshift tables with identity columns. 2. Why it appeared safe, copy completed successfully and row counts matched the source. 3. What teams noticed first, fact-to-dimension joins returning incorrect or duplicate results. 4. What teams did not notice, new inserts were reusing identity values that already existed. 5. How divergence accumulated, downstream tables referenced newly generated IDs that collided with historical ones. 6. Missing invariant, identity sequences must be globally continuous across migration boundaries.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it produces structurally valid data that is logically incorrect. No errors are thrown, inserts succeed, and dashboards populate. Detection latency is often weeks, surfacing only when reconciliation reveals impossible joins or duplicated business entities.
What exactly broke? Consistency breakdown.
Referential and transactional consistency are broken. Multiple logical entities now share the same surrogate key. Redshift can no longer be trusted to preserve entity identity. If we roll back only data, this inconsistency remains because the identity counter state is not restored by data rollback alone.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Has Redshift generated new identity values post-load? Yes, collisions exist. 2. Can identity counters be deterministically reconstructed? No, state lost. 3. Have downstream tables consumed collided keys? Likely. 4. Would snapshot restore reset identity states safely? Only if taken pre-insert. 5. Can authority be restored without rekeying? No. Once identity collisions propagate, rollback becomes destructive.
Decision point, rollback versus forward fix.
Rollback is only viable if a snapshot exists from before any new identity values were generated. Otherwise, forward fix with controlled rekeying and downstream reconciliation is required to restore integrity.
Rollback architecture, if executed.
Rollback requires restoring a pre-insert snapshot of the cluster to recover identity counter state. All downstream consumers must be invalidated, BI caches cleared, and CDC reseeded from a known safe offset. Partial rollback is forbidden because identity state is global, not table scoped.
Code illustration and Redshift artifacts.
In this section we will show 1. How identity counters reset after copy. 2. How new inserts collide with historical keys. 3. How joins break due to key collisions. 4. How forward fix requires controlled rekeying. Identity failures must be proven at execution level. Here is Redshift SQL showing identity counter state after bulk load. Disclaimer: always test code in a non-production environment. This snippet proves the current identity counter position. If it is lower than the maximum historical ID, future inserts will collide with existing keys. Here is Redshift SQL showing identity collision after new inserts. Disclaimer: always test code in a non-production environment. This snippet isolates duplicate primary keys. Their presence proves identity regeneration overlapped with historical data. Here is Redshift SQL showing downstream join corruption caused by key collisions. Disclaimer: always test code in a non-production environment. This join returns logically incorrect mappings because multiple entities now share the same surrogate key. Here is Redshift SQL illustrating forward fix, rekeying via controlled rebuild. Disclaimer: always test code in a non-production environment. This snippet demonstrates the necessity of rekeying. Forward fix requires generating a new, collision-free identity space and propagating it consistently.
Containment and forward fix strategy.
Once identity collision is confirmed, containment must precede repair. 1. Immediately halt inserts into affected tables. 2. Declare Redshift non-authoritative for identity-bearing domains. 3. Rebuild surrogate keys in a controlled staging environment. 4. Propagate new keys to all dependent tables. 5. Re-enable writes only after referential integrity is revalidated. Identity repair is always invasive and must be audited.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Identity columns do not preserve source sequence continuity by default. 2. Bulk loads can silently reset counters below historical maxima. 3. Referential integrity can be destroyed without any load errors. 4. Rollback must restore identity state, not just data. Identity continuity is a global invariant, not a table-level concern.
Follow-up 1. Why don't identity collisions trigger immediate errors?
Answer: Redshift does not enforce global uniqueness unless constrained. Inserts succeed because, from the engine's perspective, the values are valid. The failure is logical, not syntactic, and surfaces only through downstream joins.
Follow-up 2. When did rollback stop being safe in this incident?
Answer: rollback stopped being safe the moment new identity values were generated and consumed downstream. At that point, restoring data without restoring identity state would amplify corruption.
Follow-up 3. Could this have been avoided without changing tooling?
Answer: yes. Explicitly reseeding identity counters after copy or disabling identity generation during migration would have preserved key continuity. This is an architectural control, not a tool limitation.
Pro insider tip.
Never trust identity after a bulk load. Always compare max ID to the sequence state before allowing inserts, or you are guaranteed to corrupt referential integrity.
Real-world incident. During source to Redshift migration 95, surrogate key regeneration produces silent non-equivalent keys.
During an AWS Redshift migration, surrogate keys were regenerated in the target system using hashing logic that appeared equivalent to the source. However, subtle differences in null handling, string concatenation, and type casting caused the regenerated keys to diverge from source values. This silently broke fact dimension joins even though row counts and data volumes matched. Failure class, identity, surrogate key, and sequence failures.
System state before failure, very important.
At the moment the failure was introduced, the system state was: 1. Source system generated surrogate keys using application-defined hash logic. 2. Redshift cluster regenerated surrogate keys during load using SQL-based hashing. 3. CDC pipeline replicating data without surrogate key reconciliation. 4. Fact tables loaded using regenerated surrogate keys. 5. Dimension tables, partially rebuilt with new surrogate logic. 6. BI tools, reading exclusively from Redshift. 7. Authority status, assumed equivalence between source and target key logic. Hash equivalence is an assumption unless explicitly proven.
Incident analysis and root cause.
This incident resulted from a false equivalence assumption. 1. Triggering action regenerating surrogate keys in Redshift instead of preserving source keys. 2. Why it appeared safe hash formulas looked identical in documentation. 3. What teams noticed first fact records failing to join to dimensions. 4. What teams did not notice different null handling and string normalization between systems. 5. How divergence accumulated. Each load generated keys that were syntactically valid but semantically different. 6. Missing invariant surrogate key generation must be bit-for-bit identical across systems.
Why this failure is dangerous, hidden risk.
This failure is dangerous because all data appears present and valid in isolation. Row counts match, CDC succeeds, and no errors are raised. Detection latency is often long, surfacing only when aggregates drop or dimensions appear sparsely populated.
What exactly broke? Consistency breakdown.
Referential and semantic consistency are broken. Facts and dimensions no longer share a common identity space. Redshift cannot be trusted to answer joined analytical questions. If we roll back only data, this inconsistency remains because the regenerated keys are not reversible to source identities.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate 1. Were surrogate keys regenerated in Redshift? Yes, non-equivalent keys exist. 2. Are original source surrogate keys preserved anywhere? No, overwritten. 3. Have fact tables already been loaded with new keys? Yes. 4. Can joins be repaired without rekeying? No. 5. Can authority be restored without rebuilding dimensions and facts? No. Once surrogate equivalence is lost, rollback becomes destructive.
Decision point, rollback versus forward fix.
Rollback is only viable if a snapshot exists prior to surrogate regeneration. Otherwise, forward fix requires rebuilding all dependent tables using a single, authoritative key generation strategy.
Rollback architecture, if executed.
Rollback requires restoring a snapshot taken before surrogate key regeneration and disabling all loads that compute new keys. CDC must be reseeded, BI caches invalidated, and downstream datasets rebuilt. Partial rollback is forbidden because surrogate keys span the entire analytical model.
Code illustration and Redshift artifacts.
In this section, we will show 1. How source and Redshift surrogate keys differ for the same business attributes. 2. How null handling alters hash output. 3. How joins fail despite matching row counts. 4. How forward fix requires full rekeying. Surrogate key failures must be proven by execution, not assumption. Here is Redshift SQL showing regenerated surrogate keys. Disclaimer: always test code in a non-production environment. This snippet shows the regenerated surrogate key values used in Redshift for each business entity. Here is source equivalent SQL logic highlighting null handling differences. Disclaimer: always test code in a non-production environment. This snippet illustrates how null handling influences the hash. Any mismatch from source behavior guarantees non-equivalence. Here is Redshift SQL showing join failure caused by non-equivalent surrogate keys. Disclaimer: always test code in a non-production environment. This condition isolates facts that can no longer join to dimensions, proving referential breakage. Here is Redshift SQL illustrating forward fix via authoritative rekeying. Disclaimer: always test code in a non-production environment. This snippet demonstrates that forward fix requires preserving or reintroducing the authoritative surrogate key from the source.
Containment and forward fix strategy.
Once surrogate divergence is confirmed, containment must precede repair. 1. Freeze all loads that regenerate surrogate keys. 2. Declare the source key logic authoritative. 3. Rebuild all dimension tables using preserved source keys. 4. Reload fact tables with corrected foreign keys. 5. Revalidate joins before restoring analytical trust. Surrogate keys are contracts, not conveniences.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Hash logic must be identical across systems, including null semantics. 2. Regenerating surrogate keys breaks referential integrity silently. 3. Row counts and CDC success do not validate key equivalence. 4. Rollback must restore original identity space, not just data. Surrogate key equivalence is a hard invariant in analytics.
Follow-up 1. Why didn't checksum or row count validation catch this?
Answer: checksums and row counts validate data presence, not relational meaning. The rows exist, but their identities no longer align across tables, which only surfaces during joins.
Follow-up 2. When did rollback stop being safe in this incident?
Answer: rollback stopped being safe once regenerated surrogate keys were used to populate fact tables. From that moment, restoring data without restoring original keys would deepen corruption.
Follow-up 3. Could this have been prevented without changing platforms?
Answer: yes. Preserving source-generated surrogate keys or enforcing byte-for-byte equivalent hash logic across systems would have prevented divergence. This is an architectural discipline issue.
Pro insider tip:
never regenerate surrogate keys unless you can mathematically prove equivalence across every edge case. If you cannot prove it, preserve the original keys.
Real-world incident during source to Redshift migration 96. Gap management fills source key gaps and breaks external references.
During an AWS Redshift migration, tables were reloaded using copy and insert operations that implicitly reassigned surrogate keys. Unlike the source system, which preserved intentional gaps in identifiers, Redshift-generated sequences filled these gaps. This caused logical key collisions where previously unused identifiers now pointed to different records, silently breaking external references and application links. Failure class, identity, surrogate key and sequence failures.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system used surrogate keys with intentional gaps due to deletes and rollbacks. 2. Redshift cluster reloaded tables using identity columns during copy and insert. 3. Sequence behavior automatically reassigned contiguous values without preserving gaps. 4. CDC pipeline replicated data values, not original sequence semantics. 5. Downstream consumers relied on stable identifiers in URLs and API references. 6. Authority status assumed surrogate key values were interchangeable across systems. Surrogate key gaps are part of the contract, not an implementation detail.
Incident analysis and root cause.
This incident was caused by treating identifiers as ordinal rather than semantic. 1. Triggering action, reloading tables into Redshift with identity columns instead of preserving source keys. 2. Why it appeared safe, row counts matched and all primary keys were unique. 3. What teams noticed first, external links and API calls returning incorrect records. 4. What teams did not notice, that previously unused key values were now assigned to new rows. 5. How divergence accumulated, every reload reinforced incorrect key-to-entity mappings. 6. Missing invariant surrogate keys must preserve identity meaning, including gaps.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it produces internally consistent but externally incorrect systems. Redshift enforces uniqueness, masking the fact that identifiers now point to different business entities. Detection latency is often high, surfacing only when customers or partners report incorrect behavior.
What exactly broke? Consistency breakdown.
Referential and semantic consistency are broken. Identifiers no longer represent the same entities across systems. Redshift cannot be trusted for any workflow that depends on stable external references. If we roll back only data, this inconsistency remains because identifier semantics have already been altered.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Were surrogate keys regenerated in Redshift? Yes, gaps filled. 2. Are original source key values preserved? No, overwritten. 3. Have downstream systems consumed new identifiers? Yes. 4. Can identifier meaning be reconstructed from data alone? No. 5. Can authority be restored without full reload? No. Once identifier meaning changes, rollback becomes identity destructive.
Decision point, rollback versus forward fix.
Rollback is viable only if a snapshot exists before identifier regeneration. Otherwise, forward fix requires a full reload using preserved source identifiers and coordinated downstream correction.
Rollback architecture, if executed.
Rollback requires restoring a snapshot taken before any identity-based reload, disabling automatic key generation, reseeding CDC from preserved identifiers, invalidating downstream caches, and reloading all affected tables. Partial rollback is forbidden because identifier semantics span systems.
Code illustration and Redshift artifacts.
In this section we will show 1. How Redshift fills surrogate key gaps during reload. 2. How source gaps are preserved in the original system. 3. How external references break due to reassigned IDs. 4. Why forward fix requires full identifier preservation. Identifier gaps are semantic, not accidental. Here is Redshift SQL showing contiguous surrogate keys after reload. Disclaimer: always test code in a non-production environment. This snippet shows that Redshift reassigned contiguous identifiers, filling gaps that existed in the source system. Here is source system evidence showing intentional identifier gaps. Disclaimer: always test code in a non-production environment. This snippet proves that the source system preserved gaps, which were part of the identifier contract. Here is Redshift SQL showing external reference breakage. Disclaimer: Always test code in a non-production environment. This condition isolates cases where the same identifier now points to a different entity than before migration. Here is forward fix SQL, preserving authoritative source identifiers. Disclaimer: always test code in a non-production environment. This snippet demonstrates that forward fix requires explicitly preserving the source identifier values.
Containment and forward fix strategy.
Once identifier drift is confirmed, containment must precede repair. 1. Freeze all reloads that use identity or sequence reassignment. 2. Declare source identifiers authoritative. 3. Rebuild affected tables using preserved identifiers. 4. Coordinate downstream systems to refresh references. 5. Revalidate referential integrity end-to-end. Identifiers are contracts with the outside world.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Surrogate key gaps carry semantic meaning. 2. Filling gaps silently breaks external references. 3. Uniqueness does not imply correctness. 4. Rollback must restore identifier meaning, not just data. Identity semantics must be preserved across migrations.
Follow-up 1. Why didn't uniqueness constraints detect this?
Answer: uniqueness constraints ensure no duplicates, not that identifiers map to the same entities. The data is valid structurally, but incorrect semantically.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe once downstream systems began relying on reassigned identifiers. At that point, restoring data without restoring identity meaning would amplify damage.
Follow-up 3. How could this have been prevented?
Answer: by disabling identity regeneration during reloads and preserving source identifiers explicitly. Identifier semantics must be treated as immutable contracts.
Pro insider tip.
If an identifier ever appears in a URL, API, or external system, you are no longer allowed to treat it as an implementation detail.
Real-world incident during source to Redshift migration 97. Federated or external table key collisions after migration.
During an AWS Redshift migration, federated queries and external tables were used to join Redshift-managed data with source or S3-backed datasets. Although row counts and schemas appeared compatible, surrogate keys were regenerated differently across systems. This resulted in key collisions where identical identifiers referred to different business entities depending on the access path. Failure class, identity, surrogate key, and sequence failures.
System state before failure, very important.
At the moment the failure was introduced, the system state was: 1. Source system generated surrogate keys using its native sequence logic. 2. Redshift cluster rebuilt tables using identity columns during migration. 3. External tables queried S3 or federated source data with original key values. 4. Key generation not globally coordinated across systems. 5. BI tools executed joins across Redshift and external or federated datasets. 6. Declared source of truth, implicit and inconsistent by access path. Keys must be globally unique or globally meaningless.
Incident analysis and root cause.
This incident resulted from an implicit identity assumption. 1. Triggering action, joining Redshift-managed tables with federated or external tables using regenerated surrogate keys. 2. Why it appeared safe, keys were unique within each system and schemas aligned. 3. What teams noticed first, inconsistent query results depending on whether data was accessed via Redshift native or federated paths. 4. What teams did not notice, that the same numeric identifiers referred to different entities across systems. 5. How divergence accumulated, each federated query reinforced conflicting identity mappings. 6. Missing invariant surrogate keys must be globally consistent across all participating systems.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it produces believable but contradictory results. Queries execute successfully, joins return rows, and no errors surface. Detection latency is high, often discovered only when analysts compare results across access paths or when downstream consumers report inconsistencies.
What exactly broke? Consistency breakdown.
Referential and identity consistency are broken. The same key value represents different entities depending on the data source. Redshift cannot be trusted as an authoritative integration layer. If we roll back only data, this inconsistency remains because identity alignment across systems is still broken.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate 1. Were surrogate keys regenerated in Redshift? Yes, identity divergence exists. 2. Are external or federated systems still using original keys? Yes. 3. Can keys be deterministically remapped? Rarely requires domain logic. 4. Have downstream joins already used mixed identities? Likely. 5. Can authority be restored without full rekeying? No. Rollback cannot reconcile identities that were never aligned.
Decision point, rollback versus forward fix.
Rollback is ineffective because restoring snapshots does not resolve cross-system key collisions. Forward fix must focus on declaring a single authoritative key system and rebuilding integrations around that contract.
Rollback architecture, if considered.
Even if rollback is attempted, it would require restoring a pre-migration snapshot, disabling federated access, invalidating all mixed identity query results, and coordinating downstream systems. Partial rollback is forbidden because identity semantics span system boundaries.
Code illustration and Redshift artifacts.
In this section, we will show 1. How identical key values exist in Redshift and external tables. 2. How joins across access paths return contradictory entity mappings. Identity collisions are invisible without execution-level evidence. Here is Redshift SQL showing identical keys across native and external tables. Disclaimer: always test code in a non-production environment. This condition isolates cases where the same key value maps to different entities, proving identity collision across systems.
Containment and forward fix strategy.
Once identity collision is confirmed, containment must precede repair. 1. Disable federated joins that rely on surrogate keys. 2. Declare a single authoritative identity source. 3. Introduce explicit crosswalk or mapping tables. 4. Rebuild integrations using authoritative keys only. 5. Revalidate referential integrity end-to-end. Identity must be unified before data can be trusted.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Federated access amplifies identity mistakes. 2. Uniqueness is local, identity must be global. 3. Joins can succeed while truth diverges. 4. Rollback cannot fix identity contracts. Identity consistency must be enforced across all access paths.
Follow-up 1. Why didn't this surface during initial validation?
Answer: initial validation focused on row counts and schema alignment within Redshift. Federated joins were not exercised deeply, so identity collisions across systems remained invisible until real analytical queries were run.
Follow-up 2. When exactly did rollback stop being safe?
Answer: rollback stopped being safe once federated or external consumers executed joins using mixed identity spaces. At that moment, downstream interpretations diverged and restoring data alone could not restore meaning.
Follow-up 3. Curveball. What if the business insists on keeping federated queries for flexibility?
Answer: then identity governance must be elevated to a first-class contract. Without a globally enforced identity mapping, every flexible query increases the probability of silent corruption.
Pro insider tip.
If two systems can generate the same identifier independently, you do not have surrogate keys. You have future collisions.
Category 16 wrap-up. Identity and key failures mark the end of silent corruption.
Identity, surrogate key, and sequence failures represent a critical inflection point in migrations. Once identifiers diverge, referential integrity collapses silently, and neither rollback nor replay can restore correctness without rebuilding identity contracts end-to-end. These failures teach a hard lesson. Correctness is not only about data, but about how entities are named and referenced across systems.
Transition from logical integrity to platform-induced failure modes.
After identity contracts fail, the next class of incidents emerges not from data modeling or migration logic, but from the execution environment itself. As teams move to Redshift serverless and auto-scaling architectures, new failure modes appear that are driven by elasticity, cost controls, and background automation rather than explicit human actions.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs in a single zip file, containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, system design. Required for your data engineer interviews jobs like data quality analyst jobs, data governance analyst jobs, AWS Python data engineer jobs, AWS Redshift Database Administrator DBA jobs, AWS Glue ETL Developer jobs, AWS Data Engineer jobs, Cloud Data Engineer jobs, Data Architect jobs, DataOps Engineer jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based questions and answers, real-world problem solving, interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section. These questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people also for your interviews. You people can download all 6 PDFs in a single zip file from below given links.
Category 17. Redshift serverless and auto-scaling edge cases.
These incidents occur only in elastic or serverless Redshift environments. The system dynamically changes capacity, enforces cost controls, and performs background optimization. While these features improve efficiency, they also introduce timing, visibility, and partial execution risks that can silently corrupt migration workflows and invalidate rollback assumptions.
Category 17 scenarios. Redshift serverless and auto-scaling edge cases.
The following scenarios illustrate how elasticity and automation introduce new migration failure modes. 1. RPU limit hard stop. Transactions abort mid-flight due to strict cost controls. 2. Cold start latency timeout. Orchestrator validation queries timeout during cluster wake-up. 3. Background optimization race conditions. Resource stealing slows validation, creating false negative alerts. 4. Connection failures due to TLS enforcement changes, breaking older DMS, Glue, or JDBC clients. 5. Cost control alarms pausing Glue or DMS jobs mid-transaction, leaving partial state after restart. 6. Budget-driven pipeline interruptions that mimic spot failures, leading engineers to restart without detecting partial corruption. Core failure. Serverless elasticity introduces new timing and cost-driven traps that invalidate traditional rollback assumptions.
Real-world incident during source to Redshift migration 98. RPU limit hard stop. Aborts transactions mid-flight.
During an AWS Redshift serverless migration, strict RPU cost controls were enabled to limit spend during validation. Under peak validation load, the serverless workgroup hit its RPU hard limit, causing in-flight queries and transactions to be abruptly aborted. Some operations partially executed before termination, creating an inconsistent target state that appeared superficially healthy. Failure class. Redshift serverless and auto-scaling edge case.
System state before failure. Very important.
At the moment the failure occurred, the system state was 1. Source system write-enabled and continuing to accept production transactions. 2. Redshift serverless workgroup active with strict RPU usage limits enforced. 3. Data load pattern validation queries and batch copy operations running concurrently. 4. Cost controls hard RPU cap configured with immediate enforcement. 5. BI tools running validation queries against Redshift. 6. Declared source of truth temporarily assumed Redshift for analytics. 7. Authority status implicitly transferred without verifying serverless execution guarantees. Cost limits became an invisible execution boundary.
Incident analysis and root cause.
This incident resulted from a serverless execution assumption failure. 1. Triggering action, validation, and load workloads exceeded the configured RPU hard limit. 2. Why it appeared safe, queries were accepted and began execution normally. 3. What teams noticed first, sudden query failures and timeouts without clear data corruption alerts. 4. What teams did not notice, some operations partially executed before forced termination. 5. How divergence accumulated. Aborted transactions left partial state, while monitoring focused only on query success rates. 6. Missing invariant, serverless execution must guarantee atomic completion or explicit failure semantics under cost enforcement.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it masquerades as normal resource throttling. Queries fail loudly, but partial side effects may already exist. Validation retries often succeed later, masking the fact that earlier executions left behind incomplete or inconsistent state. Detection latency is typically hours or days.
What exactly broke? Consistency breakdown.
Transactional and execution consistency are broken. Some operations are neither fully committed nor fully rolled back. Redshift serverless enforces cost limits outside traditional transaction semantics. If we roll back only data, this inconsistency remains because execution atomicity was never guaranteed at the platform level.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Did transactions abort due to RPU hard stop? Yes, execution interrupted. 2. Can partial effects be deterministically identified? Often no, execution level ambiguity. 3. Was Redshift already queried by consumers post-abort? Likely. 4. Can snapshot restore remove partial execution safely? Only if taken before abort window. 5. Can authority be re-established cleanly? No, execution guarantees violated. Serverless hard stops blur the line between failure and partial success.
Decision point, rollback versus forward fix.
Rollback is risky because partial execution boundaries are unclear. Restoring a snapshot may reintroduce the same workload patterns unless cost controls are changed. Forward fix requires revalidating all affected operations under stable RPU conditions and reasserting authority only after execution guarantees are restored.
Rollback architecture.
Rollback, if attempted, must be treated as a full system reset. This includes restoring a snapshot taken before the RPU enforcement window, discarding any CDC or load progress during the abort period, repointing BI tools away from Redshift, invalidating cached results, and obtaining governance approval to temporarily lift cost controls during recovery. Partial or table-level rollback is unsafe because execution boundaries are not observable.
Code illustration and Redshift artifacts.
In this section, we will show 1. How RPU hard stop errors and aborted queries are detected in Redshift system views. 2. How execution timing proves that queries were terminated mid-flight rather than cleanly failed. Execution evidence proves that cost controls can violate transactional assumptions. Redshift system view showing aborted queries due to RPU enforcement. Disclaimer: always test code in a non-production environment. The aborted flag combined with RPU-related errors proves that queries were forcefully terminated by cost controls, not by application logic. Query timing analysis exposing mid-flight termination patterns. Disclaimer: always test code in a non-production environment. Long runtimes followed by aborts indicate execution was well underway before termination, confirming partial execution risk.
Containment and forward fix strategy.
Once RPU-induced aborts are confirmed, containment must be immediate. 1. Suspend validation and load workloads until RPU limits are adjusted. 2. Declare Redshift non-authoritative until execution stability is restored. 3. Rerun all aborted operations under controlled resource conditions. 4. Reintroduce cost controls only after validation completes. 5. Document RPU thresholds as part of migration invariants. Cost controls must never be stricter than correctness guarantees.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Serverless cost controls operate outside traditional transaction semantics. 2. RPU hard stops can abort execution after partial side effects have occurred. 3. Validation success does not imply execution atomicity in serverless systems. Execution guarantees must dominate cost optimization during migration.
Follow-up 1. Why didn't Redshift automatically roll back these aborted queries?
Answer: because the abort was triggered by resource governance, not transactional failure. The platform stops execution to enforce cost limits, but it does not guarantee that all intermediate effects are reversible. Transactional semantics are secondary to resource enforcement in this mode.
Follow-up 2. When exactly did rollback stop being safe?
Answer: rollback stopped being safe the moment the first query was aborted after partial execution. From that point onward, there was no reliable boundary separating committed, uncommitted, and partially applied work.
Follow-up 3. Curveball. What if cost controls cannot be relaxed due to budget policy?
Answer: then migration must pause. If execution correctness cannot be guaranteed under enforced limits, continuing validation only compounds risk. Budget policy cannot override data authority and correctness requirements.
Pro insider tip.
In Redshift serverless, cost controls are not just throttles, they are execution boundaries. Treat RPU limits as part of your transactional model, or they will silently redefine it.
Real-world incident during source to Redshift migration 99. Cold start latency causes validation timeouts during serverless wake-up.
During an AWS Redshift serverless migration, the work group was allowed to scale down to 0 during idle periods to reduce cost. When migration validation jobs resumed, the first wave of orchestration and validation queries timed out due to cold start latency. Automation marked these timeouts as transient failures and retried later, creating false confidence that validation had passed. Failure class: Redshift serverless and auto-scaling edge case.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system write-enabled and continuing normal production activity. 2. Redshift serverless workgroup scaled down to 0 RPUs due to inactivity. 3. Orchestration layer triggering validation queries immediately after wake-up. 4. Timeout configuration fixed assuming warm cluster behavior. 5. BI tools not yet repointed. Validation relied on automated checks. 6. Declared source of truth still assumed source during validation. 7. Authority status pending validation not formally transferred. Cold start latency was misinterpreted as query failure.
Incident analysis and root cause.
This incident resulted from an execution timing assumption. 1. Triggering action running validation queries immediately after serverless wake-up. 2. Why it appeared safe queries eventually succeeded on retry without code changes. 3. What teams noticed first intermittent validation failures that self-resolved. 4. What teams did not notice initial validations never actually ran against a fully initialized cluster. 5. How divergence accumulated, validation gaps were silently accepted as transient noise. 6. Missing invariant, validation must only run after execution environment readiness is confirmed.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it produces false negatives rather than visible corruption. Validation checks appear flaky, then green. Teams trust the later success without realizing that early critical validations never executed against a stable system. Detection latency can span days until inconsistencies surface downstream.
What exactly broke? Consistency breakdown.
Validation completeness and temporal authority are broken. Some checks never executed against the intended system state. If we roll back only data, this inconsistency remains because validation gaps are not tied to any data snapshot or replayable state.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Did validation queries fail due to cold start latency? Yes, execution never occurred. 2. Were failed validations retried automatically? Yes, masked gap. 3. Can we prove all required checks ran post-warmup? Often no. 4. Did authority transfer depend on these validations? Yes. 5. Can validation state be reconstructed? No, timing not logged. You cannot roll back a validation that never ran.
Decision point, rollback versus forward fix.
Rollback does not address the core failure because data itself may be correct. The failure lies in incomplete validation. Forward fix requires rerunning all validations after enforcing readiness checks and delaying authority transfer until execution guarantees are met.
Rollback architecture.
Rollback, if attempted, would require restoring any post-validation snapshots, discarding all validation results obtained during cold start windows, repointing orchestration to a warmed cluster, invalidating cached validation outcomes, and obtaining governance approval to rerun validation before authority transfer.
Code illustration and Redshift artifacts.
In this section, we will show 1. How cold start latency manifests as query timeouts in Redshift system views. 2. How execution timing proves validation never reached steady state. Execution timing evidence exposes validation gaps, not data errors. Redshift query log showing timeouts during serverless cold start. Disclaimer: always test code in a non-production environment. Timeout errors clustered immediately after wake-up prove that validation queries failed due to cold start latency, not data issues. Execution timing comparison, before and after warm-up. Disclaimer: always test code in a non-production environment. Short aborted runtimes followed by normal runtimes show that early validation never executed against a fully initialized environment.
Containment and forward fix strategy.
Once cold start validation gaps are confirmed, containment must proceed. 1. Block validation until serverless readiness is explicitly confirmed. 2. Rerun all validation checks after warm-up. 3. Invalidate any authority decisions made on partial validation. 4. Add warm-up detection to orchestration logic. 5. Document serverless readiness as a migration invariant. Validation must wait for execution readiness.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Serverless cold starts introduce execution gaps, not data corruption. 2. Retries can mask validation failures rather than fix them. 3. Authority transfer must depend on confirmed execution, not eventual success. Execution readiness is a prerequisite for trust.
Follow-up 1. Why didn't retries fix the validation problem?
Answer: retries only ensured that validation eventually succeeded. They did not guarantee that all required checks ran at the correct time or against the intended system state, leaving a blind spot in authority transfer.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being meaningful once authority decisions were made based on incomplete validation. At that point, restoring data does not restore trust in the validation process.
Follow-up 3. Curveball. What if cold starts cannot be avoided due to cost policy?
Answer: then validation must be redesigned to include explicit readiness checks and delayed execution. Cost policy cannot justify blind validation gaps during migration.
Pro insider tip.
In Redshift Serverless, a green validation dashboard does not mean validation actually ran. Always prove the cluster was awake before trusting the results.
Real-world incident during source to Redshift migration 100. Background optimization race conditions, steal resources during validation.
During an AWS Redshift serverless migration, background optimization tasks such as automatic vacuuming, table optimization, and metadata rebalancing ran concurrently with migration validation queries. These background processes temporarily consumed execution capacity, causing validation queries to slow down or time out. The resulting false negative alerts led teams to rerun validations later, masking the fact that some checks never completed under representative load. Failure class: Redshift Serverless and auto-scaling edge case.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system write-enabled and continuing production activity. 2. Redshift Serverless workgroup active and auto-scaling under mixed workload. 3. Background processes, automatic optimization and maintenance tasks running. 4. Validation jobs executed concurrently with background optimization. 5. Timeout thresholds tuned for steady state, not resource contention. 6. Declared source of truth pending validation completion. 7. Authority status not yet formally transferred. Background optimization competed with validation for execution resources.
Incident analysis and root cause.
This incident stemmed from an ungoverned execution race. 1. Triggering action allowing background optimization to run during migration validation. 2. Why it appeared safe, validation queries eventually completed when retried. 3. What teams noticed first, sporadic slow or failed validation checks. 4. What teams did not notice that validation failures correlated with optimization windows? 5. How divergence accumulated. Partial validation coverage was accepted as transient noise. 6. Missing invariant. Validation must run in isolation from resource-stealing background processes.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it undermines validation determinism. The same checks pass or fail depending on invisible background activity. Detection latency is high because the system appears healthy and data remains unchanged, while trust decisions are made on incomplete evidence.
What exactly broke? Consistency breakdown.
Validation completeness and authority timing are broken. Some validations never ran under uncontended conditions. If we roll back only data, this inconsistency remains because the validation gap is execution-based, not data-based.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Did background optimization overlap with validation? Yes, resource contention present. 2. Were failed validations retried without isolation? Yes, gaps masked. 3. Can we prove all checks ran without contention? Often no. 4. Did authority decisions rely on these validations? Yes. 5. Can validation state be reconstructed deterministically? No. Rollback cannot fix validation that was never isolated.
Decision point, rollback versus forward fix.
Rollback does not correct the core failure because data itself is not corrupted. Forward fix requires rerunning all validations in an isolated execution window and delaying authority transfer until resource contention is eliminated.
Rollback architecture.
Any rollback attempt would require discarding post-validation decisions, restoring pre-validation snapshots if taken, pausing background optimization tasks, rerunning validations in isolation, invalidating cached validation outcomes, and obtaining governance approval before re-evaluating authority transfer.
Code illustration and Redshift artifacts.
In this section, we will show 1. How validation query runtime spike during background optimization. 2. How system views correlate slow queries with maintenance activity. Execution contention explains non-deterministic validation outcomes. Redshift query, runtimes during background optimization, Windows. Disclaimer, always test code in a non-production environment. Sudden runtime inflation without data change indicates resource contention rather than data complexity. System view showing background maintenance activity. Disclaimer, always test code in a non-production environment. Maintenance and optimization events overlapping validation windows prove that background tasks were competing for resources.
Containment and forward fix strategy.
Once contention-driven validation gaps are confirmed, containment must proceed. 1. Disable or schedule background optimization outside validation windows. 2. Rerun all validations under isolated conditions. 3. Invalidate prior validation results obtained under contention. 4. Gate authority transfer on uncontended validation success. 5. Document isolation as a mandatory migration invariant. Validation must be isolated to be trustworthy.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Serverless background optimization can steal resources unpredictably. 2. Validation failures can be execution artifacts, not data issues. 3. Authority transfer must depend on isolated, deterministic validation. Isolation is a prerequisite for reliable validation.
Follow-up 1. Why are background optimizations risky during migration?
Answer, because they introduce non-deterministic resource contention. Validation results then depend on timing rather than data correctness, undermining trust in the outcome.
Follow-up 2. When did rollback stop being safe?
Answer, rollback stopped being safe once authority decisions were made based on validations that ran under contention. Data rollback cannot restore confidence in those decisions.
Follow-up 3. Curveball. What if optimization cannot be disabled in serverless?
Answer, then validation must be redesigned to detect and wait out contention. If isolation cannot be guaranteed, authority transfer must be delayed regardless of schedule pressure.
Pro insider tip.
In Redshift serverless, background optimization is invisible unless you look for it. If validation runtimes fluctuate wildly, Assume contention before blaming data.
Real-world incident during source-to-Redshift migration 101. Connection failures after TLS enforcement changes.
During an AWS Redshift migration, TLS 1.0 and 1.1 were deprecated as part of a security enforcement update. Several migration-era clients, including DMS tasks, glue jobs, and legacy JDBC-based BI tools, were not upgraded to support TLS 1.2+. As a result, connections failed abruptly mid-migration, halting replication and validation while leaving partial state in Redshift. Failure class, Redshift Serverless and auto-scaling edge case.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system write-enabled and continuing normal operations. 2. Redshift cluster or serverless workgroup enforced TLS 1.2+ connections. 3. Migration clients mixed versions with inconsistent TLS support. 4. CDC/ingestion pipelines running until enforcement cut over. 5. BI and validation tools, some using legacy JDBC drivers. 6. Declared source of truth pending migration completion. 7. Authority status not formally transferred. Security enforcement changed connection semantics mid-migration.
Incident analysis and root cause.
This incident resulted from an uncoordinated security boundary change. 1. Triggering action enforcing TLS 1.2+ on Redshift endpoints during migration. 2. Why it appeared safe security upgrades were assumed backward compatible. 3. What teams noticed first sudden connection failures in DMS, glue, or BI jobs. 4. What teams did not notice that partial replication and validation had already occurred. 5. How divergence accumulated, pipelines stopped mid-flight, leaving incomplete state. 6. Missing invariant, all migration clients must meet enforced security protocols before cutover.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it looks like a transient connectivity issue. In reality, it introduces partial ingestion, stalled CDC, and incomplete validation. Detection latency is high because teams focus on fixing connectivity, not on assessing the data boundary already crossed.
What exactly broke? Consistency breakdown.
Transactional and authority consistency are broken. Some data changes were applied, others were never ingested. If we roll back only data, this inconsistency remains because the interruption point is unknown and not transactionally bounded.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate 1. Did ingestion stop mid-flight due to TLS failures? Yes, partial state likely. 2. Is the exact interruption boundary known? Often no. 3. Have some consumers already queried partial data? Possibly. 4. Can all clients be upgraded and replay safely? Uncertain. 5. Can authority be restored without revalidation? No. Security-driven interruptions often create unbounded partial state.
Decision point, rollback versus forward fix.
Rollback may be technically possible but unsafe without a known ingestion boundary. Forward fix requires upgrading all clients, revalidating ingestion state, and explicitly re-establishing authority before resuming migration.
Rollback architecture.
A rollback would require restoring a pre-enforcement snapshot, discarding all partial ingestion, pausing CDC, upgrading all clients to compliant TLS versions, invalidating downstream caches, and obtaining governance approval before retrying migration under enforced security constraints.
Code illustration and Redshift artifacts.
In this section, we will show 1. How TLS-related connection failures appear in Redshift and client logs. 2. How partial ingestion can be inferred from system tables. Connectivity failures must be treated as data boundary events. Redshift system view showing aborted sessions due to connection failures. Disclaimer: always test code in a non-production environment. Aborted sessions around the enforcement window indicate abrupt client disconnects consistent with TLS incompatibility. Example: client-side TLS error indicating protocol mismatch. Disclaimer: always test code in a non-production environment. This error proves that the client cannot negotiate the enforced TLS version, explaining sudden pipeline failures.
Containment and forward fix strategy.
Once TLS incompatibility is confirmed, containment must proceed. 1. Pause all ingestion and CDC pipelines. 2. Upgrade all clients and drivers to support enforced TLS versions. 3. Rebaseline ingestion boundaries before restart. 4. Rerun validation after connectivity is restored. 5. Delay authority transfer until security invariants are met. Security invariants must be satisfied before data authority can exist.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Security enforcement can interrupt migrations mid-flight. 2. Connection failures must be treated as data boundary events. 3. Authority transfer requires security and data invariants to align. Security boundaries are also data boundaries.
Follow-up 1. Why are TLS changes dangerous during migration?
Answer: because they can halt pipelines without transactional guarantees. Partial ingestion may already have occurred, creating unclear boundaries and undermining rollback safety.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe once ingestion was interrupted mid-flight and the exact apply boundary became unknown. Data rollback cannot restore certainty.
Follow-up 3. Curveball. What if security mandates immediate enforcement?
Answer: then migration must pause entirely. Security compliance overrides timelines, and authority cannot be transferred until all clients are compliant and state is revalidated.
Pro insider tip.
Treat security changes like schema changes during migration. If clients are not compliant, assume partial state and stop immediately.
Real-world incident during source to Redshift migration 102. Cost control alarms pause glue or DMS jobs mid-transaction.
During an AWS Redshift migration, aggressive cost control alarms automatically paused glue and DMS jobs when budget thresholds were exceeded. The pause occurred mid-transaction during CDC apply, leaving Redshift in a partially updated state. When jobs were later resumed manually, replication continued without awareness of the interrupted transactional boundary. Failure class: Redshift serverless and auto-scaling edge case.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system write-enabled and continuing normal transactional activity. 2. Redshift serverless or cluster actively receiving CDC-applied changes. 3. Glue/DMS pipelines running under strict cost and budget alarms. 4. Cost control mechanism configured to pause jobs automatically. 5. CDC state mid-transaction at time of pause. 6. BI and validation tools either paused or querying partial state. 7. Declared source of truth not formally established. Cost controls interrupted data flow without transactional awareness.
Incident analysis and root cause.
This incident resulted from treating cost controls as operationally safe. 1. Triggering action automatic pausing of glue or DMS jobs due to budget alarms. 2. Why it appeared safe job pausing was assumed to be equivalent to a clean stop. 3. What teams noticed first replication lag and stalled pipelines. 4. What teams did not notice that the pause occurred mid-transaction. 5. How divergence accumulated. Partial changes were applied and then resumed without transactional context. 6. Missing invariant CDC pipelines must only stop at transaction boundaries.
Why this failure is dangerous, hidden risk.
This failure is dangerous because pausing appears reversible and controlled. In reality, it breaks atomicity guarantees. Detection latency is high because pipelines resume cleanly, masking the partial state left behind.
What exactly broke? Consistency breakdown.
Transactional consistency is broken. Some statements from a transaction were applied while others were not. If we roll back only data, this inconsistency remains because the original transaction boundary was already violated.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Was CDC paused mid-transaction? Yes, atomicity violated. 2. Is the exact interruption boundary known? No, job level pause only. 3. Can CDC safely replay from a known commit? Uncertain. 4. Have downstream consumers queried partial data? Possible. 5. Can authority be restored without revalidation? No. Automated pauses create transactional ambiguity.
Decision point, rollback versus forward fix.
Rollback is unsafe without a known commit boundary. Forward fix requires identifying and reconciling partial transactions, followed by re-establishing a clean CDC boundary before resuming replication.
Rollback architecture.
Rollback would require restoring a snapshot taken before the pause, discarding all CDC-applied changes after that point, disabling automated cost controls temporarily, invalidating downstream caches, and obtaining governance approval before restarting pipelines with enforced stop-at-commit behavior.
Code illustration and Redshift artifacts.
In this section, we will show 1. How paused glue or DMS jobs appear in service logs and metrics. 2. How partial CDC application can be inferred from Redshift system tables. Operational pauses must be treated as data boundary violations. Redshift query showing partially applied CDC changes around pause window. Disclaimer: always test code in a non-production environment. This condition highlights transactions where only a subset of statements were applied before the job was paused. Example: glue or DMS log, indicating automatic pause due to cost alarm. Disclaimer: always test code in a non-production environment. This log line proves that the interruption was external to the data pipeline logic and unaware of transaction boundaries.
Containment and forward fix strategy.
Once mid-transaction pausing is confirmed, containment must proceed. 1. Disable automatic pause mechanisms during active CDC apply. 2. Identify and reconcile partially applied transactions. 3. Re-establish a clean CDC boundary with explicit checkpoints. 4. Revalidate affected tables before resuming migration. 5. Reintroduce cost controls only after transactional safety is guaranteed. Cost efficiency must never override transactional safety.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Automated cost controls can interrupt data pipelines mid-transaction. 2. Pausing is not equivalent to a transactional stop. 3. Rollback safety depends on preserving commit boundaries. Operational controls must respect transactional invariance.
Follow-up 1. Why are cost-based pauses dangerous during CDC?
Answer: because they interrupt pipelines without awareness of transaction boundaries. This creates partial state that cannot be safely rolled back without full revalidation.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe the moment the job was paused mid-transaction. From that point, atomicity was already violated and the exact boundary was unknown.
Follow-up 3. Curveball. What if finance refuses to relax cost controls?
Answer: then migration must pause entirely. Transactional safety and authority must take precedence over cost optimization during critical state transitions.
Pro insider tip.
If a pipeline can be paused by cost alarms, assume it can break transactions. Design CDC controls to stop only at commit boundaries.
Real-world incident during source to Redshift migration 103. Budget-driven pipeline interruptions mimic spot failures.
During an AWS Redshift migration, budget-enforced pipeline interruptions caused glue and DMS jobs to stop and restart repeatedly. Engineers treated these interruptions as transient infrastructure failures and manually restarted jobs without validating intermediate state. This caused partial CDC application to accumulate silently, creating corruption that appeared operationally normal. Failure class: Redshift serverless and auto-scaling edge case.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system write-enabled with continuous transactional activity. 2. Redshift serverless or cluster actively receiving CDC data intermittently. 3. Glue/DMS pipeline subject to budget-driven stop or start behavior. 4. Restart mechanism manual job restarts without state validation. 5. CDC offsets advancing across restarts without commit boundary enforcement. 6. BI and downstream systems reading Redshift intermittently. 7. Declared source of truth assumed Redshift once pipelines appeared healthy. Repeated restarts hid partial corruption behind apparent recovery.
Incident analysis and root cause.
This incident emerged from misclassifying budget interruptions. 1. Triggering action automatic job termination triggered by budget limits. 2. Why it appeared safe restarts succeeded and pipelines resumed without errors. 3. What teams noticed first: inconsistent aggregates and occasional missing records. 4. What teams did not notice that CDC resumed from unsafe intermediate positions. 5. How divergence accumulated. Each restart advanced offsets without verifying transactional completeness. 6. Missing invariant. CDC restarts must be idempotent and replay safe across interruptions.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it normalizes corruption as infrastructure noise. Pipelines appear resilient, but each restart compounds partial state. Detection latency is long because symptoms surface only after enough drift accumulates.
What exactly broke? Consistency breakdown.
Transactional and temporal consistency are broken. CDC applied fragments of transactions across multiple restarts. If we roll back only data, this inconsistency remains because the replay boundary was already crossed multiple times.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Did pipelines restart multiple times mid-CDC? Yes, fragmentation risk. 2. Are restart boundaries recorded with transaction context? No. 3. Can CDC offsets be replayed deterministically? Uncertain. 4. Have downstream systems consumed partial data? Likely. 5. Can authority be re-established without reloading? No. Repeated restarts erase safe rollback boundaries.
Decision point, rollback versus forward fix.
Rollback is unsafe because no single restart represents a clean state. Forward fix requires identifying corrupted windows, reloading affected domains, and enforcing strict restart invariants before resuming.
Rollback architecture.
Rollback would require restoring a snapshot prior to the first budget interruption, discarding all CDC-applied changes since then, disabling budget-based auto-stops, invalidating downstream materializations, and obtaining explicit approval before resuming with guarded restart semantics.
Code illustration and Redshift artifacts.
In this section, we will show 1. How multiple pipeline restarts appear in service logs. 2. How offset advancement without commit validation can be detected. Restart frequency without state validation predicts corruption. Redshift query, detecting gaps caused by repeated CDC restarts. Disclaimer, always test code in a non-production environment. This highlights transactions whose application spanned multiple restarts, proving non-atomic CDC behavior. Example pipeline log, showing repeated budget-triggered restarts. Disclaimer, always test code in a non-production environment. These log entries prove interruptions were financial, not transient infrastructure failures.
Containment and forward fix strategy.
Once restart-driven corruption is confirmed, containment must proceed. 1. Freeze all pipelines until restart safety is enforced. 2. Identify corrupted time ranges via audit tables. 3. Reload affected domains from a clean snapshot. 4. Implement idempotent restart and checkpoint validation. 5. Resume migration only after restart drills succeed. Restarts must be safe by design, not by hope.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Budget controls can mimic infrastructure failures but have different data risks. 2. Repeated restarts without validation destroy rollback boundaries. 3. CDC pipelines must be restart idempotent. Restarts are data operations, not operational noise.
Follow-up 1. Why are repeated restarts worse than a single failure?
Answer, each restart advances offsets and applies partial state. Over time, these fragments compound, making it impossible to reconstruct a clean transactional boundary.
Follow-up 2. When did rollback stop being safe?
Answer, rollback stopped being safe after the first restart that resumed CDC without validating transactional completeness. From then on, every restart deepened ambiguity.
Follow-up 3. Curveball. What if finance insists budgets must stay strict?
Answer, then migration must halt entirely. Data correctness and authority must be guaranteed before cost efficiency can be reintroduced.
Pro insider tip.
If pipelines restart more than once during migration, assume corruption until proven otherwise. Restart count is a leading indicator of rollback failure.
Real-world incident during source-to-Redshift migration 104. Case sensitivity mismatch breaks application logic after cut.
During an AWS Redshift migration, Application queries that relied on case-insensitive string comparisons began returning empty or inconsistent results after cutover. The source database treated string equality as case-insensitive, while Redshift enforced case-sensitive semantics by default. Although data was fully replicated and validation passed, application behavior silently diverged. Failure class, collation and string sensitivity incident.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system case-insensitive collation for string equality and filtering. 2. Redshift cluster default case-sensitive string comparison semantics. 3. CDC pipeline fully synchronized with no lag or replication errors. 4. Application queries written assuming case-insensitive behavior. 5. BI and APIs repointed to Redshift immediately after cutover. 6. Declared source of truth, Redshift post-cutover. 7. Authority status formally transferred without validating string semantics. Semantic assumptions survived cutover without verification.
Incident analysis and root cause.
This incident resulted from an unvalidated semantic assumption. 1. Triggering action cutting over application read traffic to Redshift without testing predicate behavior. 2. Why it appeared safe row counts, checksums, and CDC validation all passed successfully. 3. What teams noticed first application filters and role-based access returning empty results. 4. What teams did not notice that Redshift applies case-sensitive equality by default. 5. How divergence accumulated, queries executed successfully but returned logically incorrect results. 6. Missing invariant, query predicate semantics must remain equivalent across source and target systems.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it produces silent functional corruption. Queries succeed, dashboards render, and no operational alarms fire. Detection latency is often days or weeks, surfacing only through user reports or business impact analysis rather than system metrics.
What exactly broke? Consistency breakdown.
Semantic and domain-level consistency are broken. Identical SQL predicates no longer represent the same business logic across systems. If we roll back only data, this inconsistency remains because the interpretation of string values has already changed.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Has Redshift served production query results? Yes, behavioral divergence observed. 2. Is the underlying data incorrect? No, values are present. 3. Can rollback restore original comparison semantics? No, engine behavior differs. 4. Have downstream systems cached incorrect results? Likely. 5. Can authority be re-established cleanly? No, semantics already diverged. Rollback restores rows, not meaning.
Decision point, rollback versus forward fix.
Rollback is not meaningful because returning to the source does not address the semantic mismatch that caused the failure. Forward fix is required to explicitly encode string comparison behavior and revalidate application logic.
Rollback architecture.
A rollback would require repointing applications back to the source system, invalidating caches, and retracting any decisions made using Redshift-derived results. However, this does not eliminate the risk, as the same semantic failure would recur upon recut over unless query behavior is explicitly corrected. Rollback cannot restore semantic equivalence.
Code illustration and Redshift artifacts.
In this section, we will show 1. Detection of case-sensitive predicate failure in Redshift. 2. Failure manifestation compared to source expectations. 3. Why rollback cannot fix semantic interpretation. 4. How forward fix restores consistent behavior. Execution-level evidence proves semantic drift, not data loss. Detection. Case-sensitive predicate returns empty results in Redshift. Disclaimer: always test code in a non-production environment. This query returns no rows in Redshift when values are stored as admin or admin, proving case-sensitive equality. Failure manifestation: source-style logic expected non-empty result. Disclaimer: always test code in a non-production environment. This represents the effective behavior of the source system, highlighting the semantic mismatch introduced by Redshift defaults. Rollback boundary proof: data presence versus semantic failure. Disclaimer: always test code in a non-production environment. This confirms that data exists and is complete. The failure is interpretive, proving rollback cannot fix the issue. Forward fix: explicit normalization to restore semantic equivalence. Disclaimer: always test code in a non-production environment. Explicit normalization restores consistent behavior across systems, demonstrating the correct forward fix approach.
Containment and forward fix strategy.
Once semantic drift is confirmed, containment must precede repair. 1. Audit all application predicates that rely on implicit case-insensitive behavior. 2. Introduce explicit normalization or collation handling in queries and models. 3. Invalidate cached results produced under incorrect semantics. 4. Rerun functional validation, not just data validation. 5. Document semantic invariants as mandatory migration gates. Defaults are never portable. Semantics must be explicit.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Data can be correct while behavior is wrong due to semantic differences. 2. Case sensitivity is a silent breaking change during migrations. 3. Validation must test real application predicates, not just row counts. Semantic equivalence must be explicitly enforced during migration.
Follow-up 1. Why didn't standard validation detect this issue?
Answer: validation focused on replication health and data completeness. Because queries executed successfully and rows existed, no alarms fired, even though business logic was broken.
Follow-up 2. When exactly did rollback stop being safe?
Answer: rollback stopped being safe once applications and users consumed Redshift query results. At that moment, behavior, not just data, diverged, permanently fracturing trust.
Follow-up 3. Curveball. Could this issue exist even if both systems use varchar?
Answer: yes. Varchar type equality does not guarantee identical comparison semantics. Collation, normalization, and engine behavior determine meaning, not the data type itself.
Pro insider tip.
If your migration validation does not execute real application predicates, you are validating storage correctness, not behavioral correctness.
Real-world incident during source to Redshift migration 105. Trailing space truncation causes silent join failures.
During an AWS Redshift migration, multiple joins that previously worked in the source system began returning incomplete results after cutover. The root cause was a difference in how trailing spaces were handled. The source database used char semantics with space batting, while Redshift stored values as varchar and treated trailing spaces as significant. Data was fully replicated and validation passed, but relational behavior silently diverged. Failure class: collation and string sensitivity incident.
System state before failure, very important.
At the moment the failure was introduced, the system state was: 1. Source system char-based columns with space-batted comparison semantics. 2. Redshift cluster varchar-based columns with trailing space-sensitive equality. 3. CDC pipeline fully synchronized with no lag or replication errors. 4. Fact and dimension tables migrated without explicit trimming or normalization. 5. BI queries relied on equality joins that worked historically in the source. 6. Declared source of truth Redshift post-cutover. 7. Authority status formally transferred without validating join semantics. String storage equivalence does not imply comparison equivalence.
Incident analysis and root cause.
This incident resulted from an implicit assumption about string equality. 1. Triggering action cutting over joins that compared identifier columns migrated from char to varchar. 2. Why it appeared safe, row counts matched and CDC replication completed successfully. 3. What teams noticed first, missing records in joined reports and dashboards. 4. What teams did not notice that values appeared visually identical but differed by trailing spaces. 5. How divergence accumulated, joins failed silently, producing partial datasets without errors. 6. Missing invariant, join key comparison semantics must be preserved across source and target systems.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it produces silent relational corruption. Queries execute successfully, counts appear reasonable, and no operational alarms fire. Detection latency is often weeks, discovered only when downstream aggregates or reconciliations reveal unexplained gaps.
What exactly broke? Consistency breakdown.
Referential and semantic consistency are broken. Keys that were equal in the source are no longer equal in Redshift due to trailing space sensitivity. If we roll back only data, this inconsistency remains because the comparison semantics of the target engine differ fundamentally.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Has Redshift already served joined results? Yes, partial joins consumed. 2. Is the underlying data missing? No, values exist. 3. Can rollback restore char padding semantics? No, engine behavior differs. 4. Have downstream aggregates been built on broken joins? Likely. 5. Can authority be re-established cleanly? No, semantics already diverged. Rollback restores tables, not relational meaning.
Decision point, rollback versus forward fix.
Rollback is not meaningful because the same join failures would recur after recut over. Forward fix is required to explicitly normalize join keys and revalidate all relational assumptions.
Rollback architecture.
A rollback would require repointing applications to the source, invalidating downstream materializations, and retracting reports built on incomplete joins. However, this does not eliminate the root cause, as the semantic mismatch would persist upon any future cutover. Rollback cannot restore relational equivalence.
Code illustration and Redshift artifacts.
In this section, we will show 1. Detection of join failures caused by trailing spaces. 2. Failure manifestation compared to source behavior. 3. Proof that data exists but does not join. 4. Forward fix using explicit normalization. Execution-level evidence proves relational drift, not data loss. Detection: join fails due to trailing space mismatch. Disclaimer: always test code in a non-production environment. This join returns fewer rows than expected because values differ only by trailing spaces, which Redshift treats as significant. Failure manifestation: visual equality but logical inequality. Disclaimer: always test code in a non-production environment. This exposes hidden trailing spaces that are not visible in standard query outputs, but break equality joins. Rollback boundary proof: data presence without joinability. Disclaimer: always test code in a non-production environment. This confirms that dimension data exists in full. The failure is relational, proving rollback cannot fix the issue. Forward fix: explicit trimming to restore join semantics. Disclaimer: always test code in a non-production environment. By applying explicit trim to both sides of the join, we neutralize differences in how the source system and Redshift handle trailing spaces, char versus varchar. This is the standard forward fix to restore join integrity during migration.
Containment and forward fix strategy.
Once join semantic drift is confirmed, containment must precede repair. 1. Identify all joins relying on migrated char or padded identifiers. 2. Normalize join keys via trimming or canonical formatting. 3. Invalidate downstream tables built on broken joins. 4. Rerun reconciliation using normalized keys. 5. Document relational invariants as mandatory migration gates. Relational correctness depends on comparison semantics, not visual equality.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Trailing spaces can silently break joins after migration. 2. Varchar equality in Redshift differs from char semantics in many sources. 3. Validation must include join correctness, not just row counts. Relational semantics must be explicitly preserved during migration.
Follow-up 1. Why didn't row count validation catch this issue?
Answer: row counts validated individual tables, not relationships. Because rows existed in both tables, validation passed even though joins silently failed.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe once downstream reports and joins consumed incomplete results. At that point, relational trust was already broken.
Follow-up 3. Curveball. Could this occur even if both sides use varchar?
Answer: yes. Trailing space handling, trimming logic, and upstream formatting can still differ. Type equality does not guarantee join equivalence.
Pro insider tip.
If two values look identical in query output but do not join, suspect invisible characters before suspecting missing data.
Real-world incident during source to Redshift migration 106. Locale and collation differences break ordering and pagination.
During an AWS Redshift migration, User-facing applications that relied on ordered query results began showing inconsistent pagination and sorting behavior. Although row counts and values matched the source system, special characters and locale-specific strings sorted differently in Redshift, leading to broken UI assumptions and incorrect page boundaries. Failure class, collation and string sensitivity incident.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system locale-aware collation with language-specific sort rules. 2. Redshift cluster default binary collation with UTF-8 byte ordering. 3. Data migration completed successfully with full row parity. 4. CDC pipeline fully caught up with no lag. 5. Applications depended on order by for pagination and ranking. 6. Declared source of truth. Redshift after cutover. 7. Authority status transferred without validating ordering semantics. Identical values do not imply identical ordering semantics.
Incident analysis and root cause.
This incident was triggered by an implicit collation assumption. 1. Triggering action cutting over order by dependent queries to Redshift. 2. Why it appeared safe data values matched exactly and validation queries passed. 3. What teams noticed first pagination gaps, duplicates, or reordered results in the UI. 4. What teams did not notice that special characters were sorted differently at the engine level. 5. How divergence accumulated. Each query execution produced a valid but semantically different order. 6. Missing invariant ordering semantics must remain stable across source and target systems.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it produces correct-looking but unstable results. Queries succeed, counts are accurate, and no errors occur. Detection latency is often high, surfacing only through user complaints or subtle business metric drift tied to ordering-dependent logic.
What exactly broke? Consistency breakdown.
Temporal and semantic consistency are broken. The same dataset yields different orderings depending on collation rules. If we roll back only data, this inconsistency remains because ordering behavior is determined by engine collation, not stored values.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Has Redshift already served ordered results to applications? Yes, UI behavior affected. 2. Is the underlying data incorrect? No, values are correct. 3. Can rollback restore source collation rules? No, engine-level behavior differs. 4. Have downstream systems relied on ordered output? Likely. 5. Can authority be re-established cleanly? No, semantics already consumed. Rollback restores rows, not sort behavior.
Decision point, rollback versus forward fix.
Rollback is not effective because any future cutover would reintroduce the same ordering issues. Forward fix must explicitly define deterministic ordering rules that do not depend on implicit collation behavior.
Rollback architecture.
A rollback would require reverting applications to the source system and invalidating any cached or paginated results. However, this does not address the core issue, as ordering semantics would diverge again upon remigration. Rollback cannot restore semantic equivalence in sorting.
Code illustration and Redshift artifacts.
In this section, we will show 1. Detection of ordering differences using order by comparisons. 2. Proof that identical values sort differently in Redshift. Execution-level evidence proves ordering drift, not data corruption. Detection, ordering differences with special characters. Disclaimer, always test code in a non-production environment. This query produces a valid, but different order than the source system when special or locale-specific characters are present. Forensic proof, inspecting character code points in Redshift. Disclaimer, always test code in a non-production environment. This function exposes the byte-level code of the leading character. In Redshift, strings are sorted by binary representation, UTF-8 code points. If your source was using a locale-aware collation like Latin 1_general, your sort order will drift after migration.
Containment and forward fix strategy.
Once collation drift is confirmed, containment must precede repair. 1. Identify all queries relying on implicit order by behavior. 2. Define explicit deterministic sort keys where possible. 3. Avoid pagination without stable, unique ordering columns. 4. Invalidate cached or paginated results built on unstable order. 5. Document ordering invariants as part of migration criteria. Sorting must be deterministic to be authoritative.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Ordering can change across databases even when data matches. 2. Locale and collation differences affect application correctness. 3. Pagination requires deterministic and explicit sort keys. Ordering semantics must be treated as part of the data contract.
Follow-up 1. Why didn't validation catch this issue?
Answer: validation focused on row counts and values, not ordering. Because order by semantics are execution-level behavior, they were never explicitly compared during validation.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe once applications and users consumed ordered results in pagination state. At that point, semantic trust was already broken.
Follow-up 3. Curveball. Can adding order by always fix this?
Answer: not necessarily. If the order by relies on locale-sensitive strings without a stable secondary key, results can still be non-deterministic across systems.
Pro insider tip.
If pagination breaks after migration, but counts match, suspect collation and ordering semantics before suspecting missing data.
Real-world incident during source to Redshift migration 107. Query result non-determinism due to missing order by on distributed queries.
During an AWS Redshift migration, applications began returning the same query results in different orders across executions. Row counts and values were correct, but result ordering changed between runs. The root cause was reliance on implicit ordering in a distributed execution engine, where Redshift makes no guarantees without an explicit order by. Failure class, collation and string sensitivity incident.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system single node or coordinator-driven execution with stable implicit ordering. 2. Redshift cluster distributed execution across slices with parallel result assembly. 3. Data migration completed with full row and column parity. 4. CDC pipeline fully caught up and stable. 5. Applications relied on consistent row order without explicit order by. 6. Declared source of truth, Redshift after cutover. 7. Authority status declared without validating ordering guarantees. Distributed engines do not preserve implicit order.
Incident analysis and root cause.
This incident was caused by an invalid execution assumption. 1. Triggering action cutting over queries that omitted order by clauses. 2. Why it appeared safe, results looked correct during spot checks and early testing. 3. What teams noticed first, pagination inconsistencies and shuffled result rows. 4. What teams did not notice that parallel slices returned rows in non-deterministic order. 5. How divergence accumulated. Each execution assembled slice outputs differently. 6. Missing invariant result ordering must be explicitly defined in distributed systems.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it produces valid but unstable answers. Queries succeed, values are correct, and no errors are raised. Detection latency is high because instability often appears only under load or across repeated executions.
What exactly broke? Consistency breakdown.
Execution and temporal consistency are broken. The same query produces different result orders across runs. If we roll back only data, this inconsistency remains because non-deterministic execution is inherent to distributed query processing without explicit ordering.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate 1. Has Redshift already served unordered results to applications? Yes, state consumed. 2. Is the underlying data incorrect? No data values are valid. 3. Can rollback enforce deterministic execution? No, query logic unchanged. 4. Have downstream systems persisted ordered results? Likely. 5. Can authority be restored cleanly? No, semantics already leaked. Rollback restores data, not execution guarantees.
Decision point, rollback versus forward fix.
Rollback is ineffective because any recut over reproduces the same non-determinism. Forward fix must enforce explicit order by clauses and stable pagination keys to restore deterministic behavior.
Rollback architecture.
A rollback would require reverting application traffic to the source and invalidating cached results. However, This only delays the failure. Without enforcing ordering invariants, any future migration reintroduces the same execution instability.
Code illustration and Redshift artifacts.
In this section, we will show 1. Detection of non-deterministic ordering across repeated executions. 2. Failure manifestation caused by distributed slice execution. 3. Why rollback cannot correct execution-level behavior. 4. How forward fix restores deterministic ordering. Execution-level evidence proves ordering instability. Detection. Same query executed multiple times without order by. Disclaimer. Always test code in a non-production environment. Executing this query repeatedly returns rows in different orders. This proves that Redshift does not guarantee row order without an explicit order by. Failure manifestation. Slice-level execution causing row shuffling. Disclaimer. Always test code in a non-production environment. This explained plan proves the failure. A simple xn sec scan without a top-level sort or merge step means Redshift is streaming rows directly from parallel slices. Because slice processing speed varies per request, the final row order is non-deterministic, which will break your application's pagination. Rollback boundary proof. Snapshot restore does not change execution behavior. Disclaimer. Always test code in a non-production environment. Row counts remain stable before and after restore, proving that rollback affects data state but not execution semantics. Forward fix. Enforcing deterministic ordering. Disclaimer. Always test code in a non-production environment. Adding an explicit order by restores deterministic results across executions, proving that correctness requires query-level invariance.
Containment and forward fix strategy.
Once non-determinism is confirmed, containment must precede repair. 1. Identify all queries relying on implicit ordering. 2. Enforce explicit order by with stable, unique keys. 3. Redesign pagination to avoid order-dependent offsets. 4. Invalidate cached results built on unstable ordering. 5. Add ordering checks to migration validation criteria. Deterministic order is a correctness requirement, not an optimization.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Distributed systems do not preserve implicit ordering. 2. Order by is required for correctness, not just presentation. 3. Rollback cannot fix execution semantics. 4. Query invariants must be validated during migration. Never rely on implicit behavior in a distributed database.
Follow-up 1. Why did this work in the source system?
Answer. The source system executed queries in a centralized or coordinator-driven manner that produced stable implicit ordering. Redshift distributes execution across slices, removing that guarantee entirely.
Follow-up 2. When did rollback stop being safe?
Answer. Rollback stopped being safe once unordered results were consumed by applications and pagination state was persisted. At that moment, semantic trust was already broken.
Follow-up 3. Curveball. Can adding order by ever hurt performance?
Answer. Yes. Order by introduces sort operations that can be expensive at scale. However, correctness must be enforced first, and performance must be addressed with proper sort keys and query design.
Pro insider tip.
If users say results change order between refreshes after migration, suspect missing order by before suspecting bad data.
Real-world incident during source to Redshift migration 108. Window functions and parallelism change execution plans, causing pagination bugs.
During an AWS Redshift migration, applications using window functions for pagination began returning inconsistent pages. The same query produced overlapping or missing rows between pages after migration. Data values were correct, but execution plans changed under parallelism, breaking assumptions about row numbering stability. Failure class, collation and string sensitivity incident.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system centralized execution with stable window function ordering. 2. Redshift cluster distributed execution with parallel window aggregation. 3. Data migration completed with full row-level correctness. 4. CDC pipeline fully caught up and stable. 5. Application logic used row_number parentheses for pagination. 6. Declared source of truth, Redshift after cut over. 7. Authority status declared without validating window function determinism. Window functions are sensitive to execution parallelism.
Incident analysis and root cause.
This incident was caused by a hidden execution semantic change. 1. Triggering action migrating window function-based pagination queries to Redshift. 2. Why it appeared safe queries returned correct row counts and values during spot checks. 3. What teams noticed first duplicate or missing rows when navigating pages. 4. What teams did not notice that parallel execution changed window frame evaluation order. 5. How divergence accumulated. Each execution assigned row numbers differently across slices. 6. Missing invariant window function ordering must be globally deterministic.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it corrupts user experience without corrupting data. No alarms fire, values are correct, and row counts match. Detection latency is high and often blamed on application bugs rather than execution semantics.
What exactly broke? Consistency breakdown.
Execution and temporal consistency are broken. Window function results are not stable across executions. If we roll back only data, this inconsistency remains because the behavior is caused by execution parallelism, not data state.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Have users consumed paginated results? Yes, state already leaked. 2. Is underlying data incorrect? No values are valid. 3. Can rollback enforce stable window execution? No, query unchanged. 4. Have pagination offsets been persisted? Likely. 5. Can authority be restored cleanly? No, semantic trust broken. Rollback restores rows, not execution order.
Decision point, rollback versus forward fix.
Rollback is ineffective because the same window function behavior reappears after recut over. Forward fix must redesign pagination to avoid reliance on unstable window ordering.
Rollback architecture.
A rollback would require reverting application reads and invalidating cached pages. However, this only postpones the issue. Without enforcing deterministic pagination logic, any future migration reproduces the failure.
Code illustration and Redshift artifacts.
In this section, we will show 1. Detection of unstable window function results. 2. Failure manifestation under parallel execution. 3. Why rollback cannot fix window semantics. 4. How forward fix restores stable pagination. Window functions expose execution-level instability. Detection, window function used for pagination. Disclaimer, always test code in a non-production environment. Repeated execution of this query produces different row number assignments, proving instability under parallel execution. Failure manifestation, distributed window function plan. Disclaimer, always test code in a non-production environment. This XN window step indicates that Redshift is calculating row numbers. In a distributed architecture, if the sort step happens across slices without a global merge node, different slices may produce overlapping or non-deterministic sequences during migration catch-up. Rollback boundary proof. Snapshot restore does not change window behavior. Disclaimer, always test code in a non-production environment. Row counts remain stable after restore, proving that rollback does not affect window function execution semantics. Forward fix, stable pagination using explicit keys. Disclaimer, always test code in a non-production environment. Using explicit ordering and key-based pagination restores deterministic page boundaries across executions.
Containment and forward fix strategy.
Once window instability is confirmed, containment must precede repair. 1. Identify all pagination queries using window functions. 2. Replace offset-based pagination with keyset pagination. 3. Enforce deterministic order by clauses. 4. Invalidate cached paginated responses. 5. Add execution plan validation to migration tests. Pagination correctness depends on execution guarantees.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Window functions are sensitive to parallel execution. 2. Row underscore number is not stable without strict ordering guarantees. 3. Rollback cannot fix execution-level semantics. 4. Pagination must be designed for distributed systems. Never paginate on unstable execution semantics.
Follow-up 1. Why did pagination work before migration?
Answer: the source system evaluated window functions in a serialized manner. Redshift evaluates them in parallel across slices, breaking implicit assumptions about row numbering stability.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe once paginated results were consumed and cached by applications. At that point, inconsistent page boundaries had already leaked into user workflows.
Follow-up 3. Curveball. Can adding order by fully fix window instability?
Answer: not always. Order by helps, but true stability often requires redesigning pagination to avoid window functions entirely, especially at scale.
Pro Insider Tip.
If pagination breaks after migration while counts stay correct, suspect window function parallelism before suspecting bad data.
Category 18 Wrap-up. When correct rows still break applications.
Collation and ordering failures demonstrate a critical lesson. Even when data is complete and counts match, execution semantics can silently break applications. At this point in the migration journey, failures are no longer about missing data, but about how and when data becomes visible and consumable.
Transition from ordering errors to visibility errors.
The next class of incidents moves beyond sorting and execution order into a more dangerous territory. Here, data appears committed and trustworthy, but consumers observe it before durability and rollback guarantees are actually satisfied.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs in a single zip file, containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, system design. Required for your data engineer interviews jobs like data quality analyst jobs, data governance analyst jobs, AWS Python data engineer jobs, AWS Redshift database administrator DBA jobs, AWS Glue ETL developer jobs, AWS data engineer jobs, cloud data engineer jobs, data architect jobs, DataOps engineer jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based questions and answers, real-world problem solving, interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section. These questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people also for your interviews. You people can download all 6 PDFs in a single zip file from below given links.
Category 19. Write-ahead logging and commit visibility drift.
These incidents occur when Redshift exposes data to readers before commit durability is fully established across the cluster. Although transactions appear committed, consumers may read data that is later rolled back or only partially persisted. This creates irreversible trust damage even when rollback is technically possible. Failure class: write-ahead logging/commit visibility drift.
Scenarios in this category.
The following incidents demonstrate how commit visibility timing breaks rollback safety. 1. BI dashboards caching uncommitted or in-flight data during copy commit windows. 2. External consumers reading data during the Redshift commit visibility window and seeing unconfirmed rows. 3. Read after write inconsistencies where queries return committed-looking data that is later rolled back. 4. Commit visibility lag, where consumers read rows before WAL fully synchronizes across nodes. Rollback restores data state, but cannot erase what consumers already observed.
Real-world incident during source to Redshift migration 109. BI dashboards cached in-flight data during copy commit window.
During an AWS Redshift migration, large copy operations were executed to load data while BI dashboards remained active. Although copy appeared to complete successfully, BI tools queried and cached data during the commit visibility window, exposing rows that were not yet fully durable. Subsequent rollback or failure invalidated those rows, but consumers had already seen and trusted the data. Failure class. Write-ahead logging / commit visibility drift.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system stable and authoritative, no direct changes during copy. 2. Redshift cluster actively running large copy operations. 3. Copy behavior rows becoming visible before full WL synchronization. 4. BI tools live dashboards querying Redshift continuously. 5. Caching layer enabled in BI tool persisting query results. 6. Declared source of truth, implicitly Redshift for analytics. 7. Authority status, temporarily assumed without commit durability guarantees. Visibility without durability creates irreversible trust leaks.
Incident analysis and root cause.
This incident resulted from incorrect assumptions about commit visibility. 1. Triggering action allowing BI dashboards to query tables during active copy operations. 2. Why it appeared safe, copy reported success and rows were queryable immediately. 3. What teams noticed first, dashboards showing new data earlier than expected. 4. What teams did not notice, that WL synchronization across nodes was still in progress. 5. How divergence accumulated, cached results preserved rows later invalidated by rollback or failure. 6. Missing invariant, consumers must never read data until durability is guaranteed cluster-wide.
Why this failure is dangerous, hidden risk.
This failure is dangerous because system health appears normal. Queries succeed, copy completes, and dashboards refresh cleanly. The corruption is temporal and trust-based. Consumers observe data that may later disappear. Detection latency is immediate in hindsight but often ignored because no errors are logged.
What exactly broke? Consistency breakdown.
Transactional and authority consistency are broken. Data becomes visible before it is durable. If we roll back only data, this inconsistency remains because consumers have already cached and acted on a state that never fully existed.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Were rows visible before WL sync completed? Yes, premature visibility. 2. Did BI tools cache results? Yes, externalized trust. 3. Can cached results be invalidated globally? No, partial reach. 4. Have decisions already been made using this data? Likely. 5. Can authority be restored cleanly? No, trust already leaked. Rollback restores tables, not memories or decisions.
Decision point, rollback versus forward fix.
Rollback remains technically possible, but is no longer sufficient. Forward fix must focus on acknowledging exposure, invalidating dashboards, and re-establishing strict read barriers during load operations.
Rollback architecture.
Rollback would require restoring the cluster to a pre-copy snapshot, invalidating all BI caches, and formally declaring that any data viewed during the commit window is untrusted. CDC and copy workflows must be halted until governance approval is obtained. This rollback is destructive, but still insufficient to restore trust already lost.
Code illustration and Redshift artifacts.
In this section, we will show 1. How copy visibility can precede full durability. 2. How BI queries observe rows during the commit window. Visibility timing, not data correctness, is the root failure. Here is Redshift SQL showing rows visible immediately after copy completes. Disclaimer: always test code in a non-production environment. This snippet proves that rows are queryable immediately after copy reports completion. Visibility alone does not guarantee that the data is fully durable or safe to consume. Here is Redshift system table, SQL showing commit timing relative to copy execution. Disclaimer: always test code in a non-production environment. This system table shows commit timing independent of data visibility. Comparing this with dashboard query times proves consumers read data before full commit synchronization.
Containment and forward fix strategy.
Once premature visibility is confirmed, containment must occur immediately. 1. Disable BI access during copy and bulk load windows. 2. Invalidate all cached dashboard results from the affected period. 3. Introduce explicit read barriers after copy completion. 4. Educate stakeholders that visibility does not equal durability. 5. Enforce governance approval before re-enabling analytics. Reads must be gated by durability, not convenience.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Redshift can expose rows before full WL synchronization completes. 2. BI tools amplify the issue by caching in-flight states. 3. Rollback restores data but cannot undo consumed truth. 4. Commit visibility must be treated as a governance boundary, not SQL guarantee. Durability, not visibility, defines authoritative data.
Follow-up 1. Why didn't Redshift prevent reads during the copy commit window?
Answer: Redshift optimizes for analytical throughput and does not block readers until full WL sync completes. From the engine's perspective, visibility is allowed, even if durability is still in progress. This design favors performance over strict read-after-write guarantees.
Follow-up 2. When exactly did Rollback stop being safe?
Answer: Rollback stopped being safe the moment BI dashboards queried and cached in-flight rows. At that point, data left the database boundary and entered human and business workflows, making Rollback insufficient to restore trust.
Follow-up 3. Curveball. Would disabling result cache alone prevent this issue?
Answer: no. Even without caching, consumers can still observe in-flight data and act on it. Caching amplifies the damage, but the root issue is uncontrolled read access during commit windows, which must be governed explicitly.
Pro insider tip.
If dashboards can see it, the business will trust it. Treat copy commit windows as a hard authority boundary, not a performance detail.
Real-world incident during source to Redshift migration 110. External consumers read unconfirmed data during commit visibility window.
During an AWS Redshift migration, external consumers accessed Redshift directly via APIs and shared connections, while large copy operations were in progress. Although the data appeared committed from a query perspective, WL synchronization had not completed across nodes. External consumers observed and acted on data that was later rolled back or invalidated. Failure class: write-ahead logging/commit visibility drift.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system stable and unchanged during bulk load. 2. Redshift cluster executing large copy operations with in-flight commits. 3. Commit behavior rose visible before full WL propagation. 4. External consumers directly querying Redshift via APIs or data shares. 5. Access controls, no read isolation during load windows. 6. Declared source of truth, implicitly Redshift for analytics and APIs. 7. Authority status, assumed durable without commit finality. External reads magnify commit visibility risk beyond internal analytics.
Incident analysis and root cause.
This failure stemmed from incorrect assumptions about consumer isolation. 1. Triggering action, allowing external consumers to read from Redshift during active copy commits. 2. Why it appeared safe, queries succeeded and returned consistent-looking results. 3. What teams noticed first, external systems reporting data that later disappeared or changed. 4. What teams did not notice, that commit visibility preceded WL durability guarantees. 5. How divergence accumulated, external systems persisted responses based on unconfirmed state. 6. Missing invariant, no consumer may read data until commit durability is guaranteed.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it extends beyond internal trust boundaries. External consumers treat API responses as authoritative and persist them independently. Even if Redshift data is corrected later, the incorrect state has already escaped the system. Detection latency is high because no internal error occurs.
What exactly broke? Consistency breakdown.
Transactional and authority consistency are broken. External systems observe a state that Redshift itself later invalidates. If we roll back only data, this inconsistency remains because external consumers have already persisted and acted on unconfirmed results.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Did external consumers read during commit window? Yes, trust escaped. 2. Can external responses be recalled or invalidated? No, out of system control. 3. Was the data later rolled back or corrected? Yes, divergence confirmed. 4. Have downstream systems persisted this state? Likely. 5. Can authority be restored cleanly? No external truth already formed. Once data crosses system boundaries, rollback loses authority.
Decision point, rollback versus forward fix.
Rollback is no longer sufficient because external consumers have already incorporated the incorrect state. Forward fix must focus on compensating actions, explicit data correction notifications, and stricter access controls during future load windows.
Rollback architecture.
A theoretical rollback would involve restoring a pre-copy snapshot and rerunning ingestion with reads fully blocked. However, this does not repair external systems that consumed unconfirmed data. Rollback is therefore structurally incomplete and insufficient to restore trust.
Code illustration and Redshift artifacts.
In this section, we will show 1. Evidence of rows visible to consumers before WAL durability. 2. Timing overlap between copy commits and external query access. External visibility during commit windows creates irreversible divergence. Here is Redshift SQL showing rows visible during copy commit window. Disclaimer: always test code in a non-production environment. This snippet proves that rows were queryable immediately after copy execution. External consumers could read these rows before durability was guaranteed. Here is Redshift system table, SQL correlating commit timing with external query access. Disclaimer: always test code in a non-production environment. This system table confirms that external queries executed during the commit window, proving consumers access data before full commit finalization.
Containment and forward fix strategy.
Once external exposure is confirmed, containment must be immediate. 1. Block all external reads during copy and bulk load operations. 2. Issue correction notices to external consumers. 3. Provide explicit reconciliation datasets where possible. 4. Introduce read isolation windows enforced at the network layer. 5. Formalize commit complete signals before exposing data externally. External consumers require stronger guarantees than internal analytics.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Redshift allows read visibility before full WAL durability. 2. External consumers treat API responses as authoritative truth. 3. Rollback cannot retract data once it leaves the system boundary. 4. Commit visibility must be governed differently for external access. Authority ends where external persistence begins.
Follow-up 1. Why is this worse than BI dashboards seeing in-flight data?
Answer: external consumers persist data independently and often trigger automated actions. Unlike BI dashboards, their outputs cannot be easily invalidated. Once external systems act on unconfirmed data, rollback loses practical authority.
Follow-up 2. When exactly did rollback stop being safe?
Answer: rollback stopped being safe the moment the first external consumer read and persisted unconfirmed data. At that instant, the system lost exclusive control over the truth, making rollback insufficient.
Follow-up 3. Curveball. Would stricter transaction isolation levels in Redshift fix this?
Answer: no. The issue is not isolation semantics but commit visibility design. Even with stricter isolation, Redshift prioritizes performance and does not provide consumer-aware durability guarees. Governance controls are required.
Pro insider tip.
If an external system can read it, assume it will act on it. Treat commit windows as a hard perimeter, not an internal optimization detail.
Real-world incident during source to Redshift migration 111. Read after write inconsistency reveals non-durable commits.
During an AWS Redshift migration, applications and analysts observed newly written rows immediately after insert and copy operations. Subsequent rollback and recovery actions revealed that some of these rows were never fully persisted across the cluster. Queries had returned data that appeared committed but was later lost, breaking the assumption that read after write implies durability. Failure class: write-ahead logging / commit visibility drift.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system stable and no longer authoritative post-cutover. 2. Redshift cluster accepting writes via copy and insert operations. 3. Transaction behavior: query is able to read newly written rows immediately. 4. Commit propagation WL synchronization incomplete across nodes. 5. Consumers, BI tools and applications issuing read-after-write queries. 6. Declared source of truth, Redshift assumed authoritative. 7. Authority status, assumed based on query visibility, not durability. Read visibility was incorrectly equated with persistence.
Incident analysis and root cause.
This incident resulted from a flawed durability assumption. 1. Triggering action, allowing applications to trust immediate read-after-write results. 2. Why it appeared safe, queries returned consistent results without errors. 3. What teams noticed first, previously visible rows disappearing after rollback or node failure. 4. What teams did not notice, that commit visibility preceded full WAL synchronization. 5. How divergence accumulated. Applications cached and acted on non-durable reads. 6. Missing invariant, read-after-write must not be treated as a durability guarantee.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it violates a deeply held transactional intuition. Engineers assume that if a query can read a row, it must be durable. In Redshift, this assumption is false under certain conditions. Detection latency is high because no errors occur until recovery exposes missing data.
What exactly broke? Consistency breakdown.
Transactional consistency and durability guarantees are broken. Reads observe state that is later invalidated by rollback or recovery. If we roll back only data, this inconsistency remains because consumers already trusted and acted on non-durable reads.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate 1. Were reads served before full WL durability? Yes, visibility precedes persistence. 2. Did consumers act on read-after-write results? Likely. 3. Can lost rows be deterministically reconstructed? No, not all writes persisted. 4. Would rollback restore consumer trust? No, observed state already contradicted. 5. Can authority be re-established cleanly? No, durability illusion exposed. Rollback cannot undo trust placed in non-durable reads.
Decision point, rollback versus forward fix.
Rollback is insufficient because it only restores storage state, not consumer assumptions. Forward fix must explicitly redefine durability guarantees, isolate readers during commit windows, and correct downstream effects of lost data.
Rollback architecture.
A rollback would involve restoring a snapshot taken before the affected writes and rerunning ingestion with strict read isolation. However, this does not repair actions taken based on non-durable reads. Rollback therefore resets data, but not authority or trust.
Code illustration and Redshift artifacts.
In this section, we will show 1. Immediate read-after-write visibility in Redshift. 2. Loss of previously visible rows after rollback or recovery. 3. System evidence that commits were not fully durable. 4. Why rollback cannot guarantee restoration of observed state. Read visibility is not a durability contract in Redshift. Here is SQL demonstrating immediate read-after-write visibility. Disclaimer: always test code in a non-production environment. This query returns the newly inserted row immediately, reinforcing the false assumption that the write is fully durable. Here is SQL showing the row missing after rollback or recovery. Disclaimer: always test code in a non-production environment. After rollback or recovery, the row is missing, proving that earlier read-after-write visibility did not imply persistence. Here is Redshift system table evidence of commit timing. Disclaimer: always test code in a non-production environment. This system table shows commit timing, illustrating how commit visibility can precede full WAL synchronization. Here is a rollback attempt that fails to restore observed state. Disclaimer: always test code in a non-production environment. This rollback only affects transactional state, not the fact that consumers already observed and trusted non-durable data.
Containment and forward fix strategy.
Once read-after-write inconsistency is confirmed, containment must proceed. 1. Block all reads during bulk writes and commit windows. 2. Invalidate caches built on non-durable reads. 3. Reconcile affected entities against a durable source where possible. 4. Redefine durability guarantees communicated to application teams. 5. Introduce explicit commit complete signaling before exposing data. Durability must be declared, not inferred.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Read after write does not equal durability in Redshift. 2. Commit visibility can precede WAL synchronization. 3. Rollback restores storage, not consumer assumptions. 4. Isolation and governance are required to preserve trust. Durability is a contract, not a side effect of visibility.
Follow-up 1. Why didn't Redshift signal an error when data was lost?
Answer: from Redshift's perspective, the system behaved as designed. Visibility and durability are decoupled for performance reasons. The failure is semantic, not operational, so no error is raised.
Follow-up 2. When exactly did Rollback stop being safe?
Answer: Rollback stopped being safe the moment consumers acted on read-after-write results. At that instant, trust was placed in a state that was never durable, and Rollback could no longer restore authority.
Follow-up 3. Curveball. Would serializable isolation prevent this issue?
Answer: no. Isolation levels govern concurrency semantics, not durability guarantees. This issue arises from commit propagation design, so isolation alone cannot prevent read-after-write visibility of non-durable data.
Pro Insider Tip.
If your system exposes data immediately after write, assume consumers will trust it. In Redshift, you must explicitly gate reads if durability actually matters.
Real-world incident during source to Redshift migration 112. Commit visibility lag exposes non-durable data to consumers.
During an AWS Redshift migration, consumers queried data immediately after transactions appeared committed. Although rows were visible and queries succeeded, commit propagation lagged across nodes. Consumers read data that was later invalidated during recovery, creating irreversible trust loss even though rollback was technically possible. Failure class: write-ahead logging / commit visibility drift.
System state before failure, very important.
At the moment the failure was introduced, the system state was: 1. Source system no longer authoritative after cutover. 2. Redshift cluster writes enabled with active copy and insert workloads. 3. Commit behavior transactions reported as committed to clients. 4. WL propagation not fully synchronized across compute nodes. 5. Consumers, BI dashboards and external readers querying immediately post-commit. 6. Declared source of truth, Redshift assumed authoritative. 7. Authority status assumed based on commit visibility alone. Commit visibility was mistaken for commit durability.
Incident analysis and root cause.
This incident resulted from a false durability assumption. 1. Triggering action allowing consumers to query immediately after commit acknowledgement. 2. Why it appeared safe, transactions completed successfully and queries returned results. 3. What teams noticed first, data discrepancies after recovery or node failure. 4. What teams did not notice, commit visibility preceded full WAL synchronization. 5. How divergence accumulated, consumers cached and acted on non-durable committed state. 6. Missing invariant, commit acknowledgement must only follow full durability.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it violates the intuitive contract of commits. Consumers reasonably assume committed data is durable. Redshift optimizes for performance, allowing visibility before full persistence. Detection latency is high because the system appears healthy until recovery exposes the gap.
What exactly broke? Consistency breakdown.
Transactional durability and authority guarantees are broken. Consumers observed data that was later invalidated. If we roll back only data, this inconsistency remains because consumers already trusted and propagated the non-durable state.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate: 1. Were consumers able to read data before full WL sync? Yes, visibility lag confirmed. 2. Did any consumer act on or cache this data? Likely. 3. Can all observed data be proven durable? No WL lag window exists. 4. Would rollback invalidate consumer decisions? Yes. 5. Can authority be re-established cleanly? No, trust already leaked. Rollback restores storage, not consumer belief.
Decision point, rollback versus forward fix.
Rollback is technically possible but unsafe because it contradicts consumer-observed reality. Forward fix must focus on redefining commit exposure rules, isolating readers, and correcting downstream usage of non-durable data.
Rollback architecture.
A rollback would involve restoring a pre-incident snapshot and replaying ingestion with strict read isolation. However, this does not undo consumer actions taken during the commit visibility lag. Rollback resets data state but not authority or trust boundaries.
Code illustration and Redshift artifacts.
In this section, we will show 1. Evidence of commit timing and visibility lag using system tables. 2. Proof that consumers could read data before full WAL durability. Commit visibility is not equivalent to commit durability. Here is Redshift SQL showing commit timing versus visibility. Disclaimer: always test code in a non-production environment. This system table exposes commit timing, showing how commits are acknowledged before full propagation across the cluster. Here is SQL proving consumers could read data during the visibility lag window. Disclaimer: always test code in a non-production environment. Rows returned here were visible to consumers immediately after commit acknowledgement, even though durability was not yet guaranteed.
Containment and forward fix strategy.
Once commit visibility lag is confirmed, containment must proceed. 1. Block consumer reads during bulk write and commit windows. 2. Invalidate dashboards and caches built during the lag window. 3. Reconcile affected data against a durable baseline. 4. Introduce explicit commit complete signaling for consumers. 5. Document durability semantics as part of migration governance. Durability must be enforced, not assumed.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Commit acknowledgement and durability are not the same in Redshift. 2. Consumers can observe data before WL propagation completes. 3. Rollback restores data state but not consumer trust. 4. Read isolation is required when durability matters. Durability is an explicit architectural contract.
Follow-up 1. Why does Redshift allow commit visibility before durability?
Answer: Redshift optimizes for analytical throughput by decoupling visibility from full WAL synchronization. This improves performance but weakens intuitive durability guarantees. The risk appears only when consumers assume transactional semantics.
Follow-up 2. When exactly did rollback stop being safe?
Answer: rollback stopped being safe the moment consumers read and acted on data during the commit visibility lag. At that instant, authority shifted from durable storage to observed state, which rollback cannot erase.
Follow-up 3. Curveball. Would synchronous WL replication eliminate this risk?
Answer: it would reduce the window but at significant performance cost. More importantly, Redshift does not expose such a control. Architects must design isolation and governance around the platform's durability model.
Pro insider tip.
If a platform acknowledges commits before full durability, treat commit time as advisory. Gate reads explicitly or assume consumers will trust data that may not survive recovery.
Category 19 wrap-up. Commit visibility drift marks the end of technical rollback.
The previous category demonstrated a critical boundary where rollback remains technically feasible, but is already meaningless. Once consumers observe and act on transient or non-durable state, trust is irreversibly damaged. From this point onward, failures are no longer about what data exists, but about what actions have already been taken based on that data.
Transition from trust leakage to repair-induced corruption.
After rollback boundaries are crossed, teams shift to forward fix and repair strategies. However, when these repair actions themselves are unsafe, the system enters a far more dangerous state. Attempts to fix corruption begin creating new corruption. This leads directly into idempotency failures.
Category 20. Reprocessing idempotency failure.
This category covers incidents where forward fix or rollback repair scripts are rerun without idempotency guarantees. In these scenarios, recovery actions amplify damage instead of containing it. Data corruption accelerates with every retry because the system cannot distinguish between original state and already applied fixes. Failure class: reprocessing idempotency failure.
Reprocessing idempotency failure scenarios.
The following incidents illustrate how unsafe reprocessing destroys recovery confidence. 113. Rerunning forward fix scripts causes data corruption, such as double inserts due to missing idempotency keys. 114. Forward fix replays executed without watermarks or guards result in duplicate rows or destructive overwrites. 115. Rollback repair scripts are accidentally reapplied, compounding divergence instead of restoring state. 116. No replay watermark is stored, making it impossible to safely resume or reprocess partial fixes. Without idempotency, every retry becomes a new failure vector.
Real-world incident during source to Redshift migration 113. Rerunning forward fix script corrupts data.
During an AWS Redshift migration incident, an emergency forward fix script was executed to repair corrupted data. Due to missing idempotency safeguards, the same script was later rerun after a partial failure. Instead of stabilizing the system, the re-execution applied the same mutations again, introducing duplicate rows and overriding previously corrected data. The repair action itself became a new source of corruption. Failure class. Reprocessing idempotency failure.
System state before failure, very important.
At the moment the corruption was amplified, the system state was 1. Source system write-enabled and continuing normal operations. 2. Redshift cluster contained partially repaired data from an earlier forward fix. 3. Repair process manual or scripted forward fix executed without idempotency checks. 4. Execution tracking, no replay watermark or execution version recorded. 5. BI/downstream systems, actively querying Redshift during and after repair. 6. Declared source of truth, implicitly Redshift for analytics. 7. Authority status, temporarily assumed, not formally re-established. A repair without idempotency guarantees is indistinguishable from corruption.
Incident analysis and root cause.
This failure emerged from unsafe assumptions about repair execution. 1. Triggering action, rerunning the same forward fix script after an initial partial or failed execution. 2. Why it appeared safe, the script was perceived as corrective and previously successful. 3. What teams noticed first, row counts increased unexpectedly or corrected values reverted. 4. What teams did not notice, that the script had no guard to prevent reapplication. 5. How divergence accumulated, each execution reapplied inserts or updates, compounding state changes. 6. Missing invariant, repair scripts must be strictly idempotent or single execution guaranteed.
Why this failure is dangerous, hidden risk.
This failure is dangerous because repair actions are trusted by default. Monitoring focuses on operational success, not semantic repetition. Detection latency is high because each execution looks valid in isolation, and corruption grows gradually with each replay.
What exactly broke? Consistency breakdown.
Transactional and domain-level consistency are broken. The same logical corrections are applied multiple times, creating duplicates or overriding valid state. If we roll back only data, this inconsistency remains because the repair executions themselves are not uniquely identifiable or reversible.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Has the forward fix been executed more than once? Yes, state mutated multiple times. 2. Is there a snapshot from before the first repair, sometimes often missing? 3. Can repair executions be uniquely identified and reversed? No execution markers. 4. Have downstream systems consumed post-repair data? Likely. 5. Can authority be restored cleanly? No. Repair history ambiguous. Repeated repairs destroy the ability to reason about system state.
Decision point, rollback versus forward fix.
Rollback becomes increasingly risky because each repair execution further diverges state. Forward fix must pause all repair activity, re-establish execution guards, and only then attempt controlled reconciliation from a known good baseline.
Rollback architecture.
Rollback requires restoring a snapshot taken before any repair execution. All CDC or repair jobs must be halted. CDC offsets must be discarded and reseeded only after restore. BI tools must be repointed and caches invalidated. Downstream consumers must be notified of invalidated data. Governance approval is required because rollback will discard all subsequent repair attempts.
Code illustration and Redshift artifacts.
In this section, we will show 1. How duplicate application from rerunning a fix is detected. 2. How lack of idempotency allows repeated corruption. 3. What rollback would require at the system level. 4. How forward fix must enforce idempotency to be safe. Repair without idempotency is equivalent to uncontrolled writes. Detection. Identifying duplicate rows caused by rerunning a forward fix. Disclaimer. Always test code in a non-production environment. This query proves that the same business entities were inserted multiple times, indicating that the forward fix was applied more than once without guards. Failure manifestation, showing lack of idempotency in repair logic. Disclaimer. Always test code in a non-production environment. This pattern lacks any idempotency key or existence check. Rerunning it applies the same changes again, directly causing corruption. Rollback boundary proof, snapshot restore requirement. Disclaimer. Always test code in a non-production environment. Because repair executions are not reversible, rollback requires a full cluster restore to a point before any repair occurred. Forward fix, enforcing idempotent repair using a guard key. Disclaimer. Always test code in a non-production environment. This guard enforces idempotency by ensuring each business entity is repaired exactly once, making re-execution safe.
Containment and forward fix strategy.
Once repeated repair is detected, containment must precede any further action. 1. Immediately halt all repair and replay scripts. 2. Declare Redshift non-authoritative until state is stabilized. 3. Restore from a known good snapshot if available. 4. Reimplement repairs with strict idempotency and execution tracking. 5. Record repair execution IDs and watermarks permanently. Repairs must be replay safe before they are allowed in production.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Forward fix scripts are writes and must obey the same safety rules as production code. 2. Lack of idempotency turns retries into corruption amplifiers. 3. Rollback becomes impossible once repair executions are not uniquely identifiable. 4. Execution tracking is as critical as data correctness during incidents. All repair actions must be replay safe by design.
Follow-up 1. Why is rerunning a repair script more dangerous than the original failure?
Answer: because the repair operates on already mutated state. Each execution compounds divergence, making it impossible to reason about what the correct state should be. The system loses a stable reference point, accelerating corruption instead of containing it.
Follow-up 2. When exactly did rollback stop being safe in this incident?
Answer: rollback stopped being safe the moment the repair script was executed without an execution marker. From that point onward, there was no reliable way to distinguish original corruption from repair-induced changes.
Follow-up 3. Curveball. What if leadership demands rerunning the fix because it worked last time?
Answer: the architect must block re-execution immediately. A fix that is not idempotent does not work. It merely mutates state. Rerunning it guarantees further corruption and permanently destroys rollback viability.
Pro insider tip.
If you cannot safely rerun a repair script multiple times, it is not a repair. It is an uncontrolled write disguised as a fix.
Real-world incident during source to Redshift migration 114. Forward fix replay without watermark causes duplicates and overwrites.
During an AWS Redshift migration recovery effort, a forward fix replay job was executed to repair corrupted or missing data. The replay logic lacked a watermark or guard condition to define what had already been processed. When the job was restarted or rerun, it reapplied changes indiscriminately, creating duplicate rows in some tables and overriding newer, correct data in others. The replay mechanism itself became destructive. Failure class: reprocessing idempotency failure.
System state before failure, very important.
At the time the replay corruption was introduced, the system state was 1. Source system write enabled and continuing to accept new transactions. 2. Redshift cluster contained partially repaired data from an earlier forward fix. 3. Forward fix replay job executed without a high watermark or process strange tracking. 4. Execution tracking, no persisted watermark or replay boundary recorded. 5. CDC pipeline, paused or running independently of the replay process. 6. BI/downstream systems, actively consuming Redshift data. 7. Authority status, assumed restored without proof of replay safety. A replay without a watermark has no concept of past or present.
Incident analysis and root cause.
This failure resulted from unsafe replay assumptions. 1. Triggering action, rerunning a forward fix replay job without defining a process boundary. 2. Why it appeared safe, the replay was believed to be corrective and deterministic. 3. What teams noticed first, duplicate rows in some tables and unexpected overwrites in others. 4. What teams did not notice, that the replay logic had no memory of prior execution. 5. How divergence accumulated, each replay reprocessed overlapping data ranges. 6. Missing invariant, every replay must be bounded by a durable, monotonic watermark.
Why this failure is dangerous, hidden risk.
This failure is dangerous because replays often look controlled and intentional. Jobs succeed operationally, logs look clean, and metrics improve. The damage is semantic. Newer correct data is overwritten and duplicates accumulate silently. Detection latency is high because corruption aligns with valid historical values.
What exactly broke? Consistency breakdown.
Temporal and domain-level consistency are broken. The system loses a stable notion of event ordering and replay scope. If we roll back only data, this inconsistency remains because the replay boundaries themselves were never recorded or enforced.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Was the replay executed more than once? Yes, overlapping application. 2. Is there a snapshot before the first replay? Sometimes often missing. 3. Is the replay range reconstructible? No, no watermark stored. 4. Have downstream systems consumed replay data? Likely. 5. Can authority be restored cleanly? No, replay scope ambiguous. Replay without boundaries destroys rollback determinism.
Decision point, rollback versus forward fix.
Rollback is only viable if a snapshot exists from before any replay execution. Without it, forward fix must halt all replays, establish explicit watermarks, and reconcile state against a trusted source using bounded reprocessing.
Rollback architecture.
Rollback requires restoring a snapshot taken prior to the first replay. All replay and CDC jobs must be stopped. CDC offsets must be discarded and reseeded only after restore. BI tools must be repointed and caches invalidated. Downstream consumers must be notified that all replayed data is invalid. Governance approval is mandatory because rollback discards all repair attempts.
Code illustration and Redshift artifacts.
In this section, we will show 1. How overlapping replays create duplicate rows. 2. How missing watermarks allow overwrites of newer data. 3. What rollback would require at the system level. 4. How a bounded replay with watermarks restores safety. Reprocessing without boundaries is indistinguishable from corruption. Detection. Identifying duplicate rows caused by replay overlap. Disclaimer. Always test code in a non-production environment. This query proves that the same business entities were applied multiple times due to overlapping replay windows. Failure manifestation. Replay overriding newer correct data. Disclaimer. Always test code in a non-production environment. This condition exposes rows where older replay data overwrote newer, correct state, proving temporal corruption. Rollback execution. Cluster-level restoration via AWS CLI. Disclaimer. Always test code in a non-production environment. This is the nuclear option. Because the migration catch-up lacked explicit replay boundaries, we cannot fix the data surgically. We are forced to use the AWS CLI to restore the entire cluster to the last known good snapshot taken before the corruption occurred. Forward fix. Bounded replay using a durable watermark. Disclaimer. Always test code in a non-production environment. This watermark enforces bounded, monotonic replay, making re-execution safe and preventing overlap.
Containment and forward fix strategy.
Once unbounded replay is detected, containment must happen immediately. 1. Stop all replay and repair jobs immediately. 2. Declare Redshift non-authoritative until reconciliation completes. 3. Restore from a pre-replay snapshot if available. 4. Implement durable replay watermarks and execution tracking. 5. Allow replays only within explicitly approved boundaries. Every replay must know exactly where it starts and ends.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Replays are writes and must be treated as production-grade mutations. 2. Watermarks are mandatory to prevent overlap in reprocessing. 3. Rollback becomes impossible when replay boundaries are unknown. 4. Bounded replay is a core data engineering invariant. All reprocessing must be bounded, monotonic, and auditable.
Follow-up 1. Why is replay without a watermark more dangerous than duplicate inserts?
Answer: because it can silently overwrite new or correct data while appearing successful. The corruption affects both correctness and ordering, making reconciliation extremely difficult and detection slow.
Follow-up 2. When exactly did Rollback stop being safe in this incident?
Answer: Rollback stopped being safe the moment the replay was executed without recording a watermark. From that point on, there was no reliable way to reconstruct what data had been legitimately applied.
Follow-up 3. Curveball. What if the replay job is idempotent but still unbounded?
Answer: idempotency alone is insufficient. Without a watermark, the system cannot distinguish old from new intent. Even idempotent logic can overwrite correct newer state if the replay window is uncontrolled.
Pro insider tip.
If a replay job cannot tell you exactly what range it processed last time, it has no place in a recovery workflow.
Real-world incident during source to Redshift migration 115. Rollback repair scripts reapplied accidentally causing state divergence.
During an AWS Redshift migration rollback, a repair script intended to correct partial corruption was accidentally re-executed multiple times. The script was not idempotent and had no execution guard or replay watermark. Each reapplication further mutated the dataset, amplifying divergence instead of restoring correctness. Failure class: reprocessing idempotency failure.
System state before failure, very important.
At the moment the rollback repair corruption was introduced, the system state was 1. Source system write-enabled or recently re-enabled after migration incident. 2. Redshift cluster partially restored from snapshot and undergoing repair actions. 3. Rollback repair scripts executed manually without execution tracking. 4. Replay controls no idempotency key guard clause or watermark enforced. 5. BI/downstream systems paused or intermittently querying Redshift. 6. Declared source of truth temporarily ambiguous during rollback window. 7. Authority status assumed restorable without proof of repair safety. A rollback script without replay protection is a second migration.
Incident analysis and root cause.
This failure resulted from unsafe rollback execution practices. 1. Triggering action, rerunning a rollback repair script after partial execution. 2. Why it appeared safe, the script was labeled as corrective and assumed to be safe to repeat. 3. What teams noticed first, data anomalies worsened after each repair attempt. 4. What teams did not notice that the script had no memory of prior execution. 5. How divergence accumulated. Each run applied mutations on already mutated state. 6. Missing invariant. All rollback and repair actions must be idempotent or single-run enforced.
Why this failure is dangerous, hidden risk.
This failure is dangerous because rollback activity is trusted by default. Scripts succeed operationally and are often rerun under pressure. The damage is logical and cumulative, with each execution drifting the system further from any known good state. Detection latency is high because changes look intentional.
What exactly broke? Consistency breakdown.
Domain level and temporal consistency are broken. The system loses a stable definition of intended state. If we roll back only data, this inconsistency remains because the repair logic itself is non-deterministic and unbounded.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate 1. Was the repair script executed more than once? Yes, state mutated repeatedly. 2. Is there a snapshot before the first repair run, sometimes often missing? 3. Can repair intent be replayed deterministically? No idempotency. 4. Have downstream systems consumed repair data? Likely. 5. Can authority be restored cleanly? No, repair history ambiguous. Rollback scripts without guards erase the concept of a baseline.
Decision point. Rollback versus forward fix.
Rollback is only viable if a snapshot exists from before any repair script execution. Without it, forward fix must halt all scripts, reconcile state against a trusted source, and re-establish authority with explicit acceptance of drift.
Rollback architecture.
Rollback requires restoring a snapshot taken prior to the first repair script execution. All repair and CDC jobs must be stopped. CDC offsets must be discarded and reseeded after restore. B. I tools must be repointed and caches invalidated. Governance approval is mandatory because rollback discards all repair attempts.
Code illustration and Redshift artifacts.
In this section, we will show 1. Evidence that the same repair logic was applied multiple times. 2. Why rollback safety collapses without idempotent repair guards. Repeated repair without guards is indistinguishable from corruption. Detection. Identifying repeated repair application via duplicate mutations. Disclaimer. Always test code in a non-production environment. This query proves that the same entities were mutated multiple times by the rollback repair script, confirming accidental reapplication.
Containment and forward fix strategy.
Once accidental reapplication is detected, containment must occur immediately. 1. Stop all rollback and repair scripts immediately. 2. Declare Redshift non-authoritative until reconciliation completes. 3. Restore from a pre-repair snapshot if available. 4. Rebuild repair logic with strict idempotency or single-run guards. 5. Require execution tracking and approval for any future repair. Repair actions must be safer than the corruption they address.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Rollback scripts are production rights and must be idempotent. 2. Rerunning repair logic without guards amplifies corruption. 3. Rollback boundaries are crossed when repair history is ambiguous. 4. Execution tracking is a core rollback invariant. All rollback and repair logic must be idempotent and auditable.
Follow-up 1. Why are rollback repair scripts more dangerous than forward fix scripts?
Answer: because they operate under the assumption of recovery and trust. When they are unsafe, they silently destroy the remaining rollback boundary while appearing corrective.
Follow-up 2. When exactly did rollback stop being safe in this incident?
Answer: rollback stopped being safe the moment the repair script was executed without idempotency or execution tracking. From that point onward, there was no reliable baseline state.
Follow-up 3. Curveball. What if the repair script is correct but executed by two teams independently?
Answer: correct logic does not guarantee safe execution. Without centralized execution control and guards, parallel or repeated runs still create irreversible divergence.
Pro insider tip.
If a repair script can be safely rerun, it is engineered. If it cannot, it is a one-time gamble disguised as recovery.
Real-world incident during source to Redshift migration 116. No replay watermark stored. Prevents safe reprocessing.
During an AWS Redshift migration recovery, partial forward fix and rollback actions were executed to correct earlier corruption. However, no replay watermark or execution boundary was stored. When teams later attempted to reprocess or resume fixes, there was no reliable way to determine what had already been applied, making safe re-execution impossible. Failure class: reprocessing idempotency failure.
System state before failure, very important.
The point replay safety was lost, the system state was 1. Source system continuing to evolve or already re-enabled post-incident. 2. Redshift cluster partially repaired with multiple corrective actions applied. 3. Repair/forward fix jobs executed without persistent execution markers. 4. Replay watermark not stored or never designed into the process. 5. BI/downstream systems resumed consumption intermittently. 6. Declared source of truth temporarily assumed after each fix attempt. 7. Authority status fragile due to inability to prove execution boundaries. If you cannot prove what ran, you cannot safely run anything again.
Incident analysis and root cause.
This failure emerged from missing replay discipline. 1. Triggering action executing repair and forward fix steps without persisting a replay watermark. 2. Why it appeared safe each individual fix completed successfully in isolation. 3. What teams noticed first, inability to determine whether fixes could be safely rerun. 4. What teams did not notice that rollback and forward fix had become non-replayable by design. 5. How divergence accumulated, subsequent fixes were either skipped or over-applied out of caution. 6. Missing invariant, every repair or replayable action must advance and persist a watermark.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it freezes recovery. The system is neither correct nor safely fixable. Any additional action risks duplication or overwrite, so teams hesitate, extending outage or inconsistency. Detection latency is immediate only to senior engineers. Tooling reports everything as healthy.
What exactly broke? Consistency breakdown.
Operational and temporal consistency are broken. There is no provable execution history, so the system cannot guarantee exactly once application of fixes. If we roll back only data, this inconsistency remains because replay boundaries were never recorded.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Is there a persisted replay watermark? No execution history unknown. 2. Can fixes be safely rerun? No risk of duplication or overwrite. 3. Is there a clean snapshot before all fixes? Often no. 4. Have downstream systems consumed partially fixed data? Likely. 5. Can authority be restored cleanly? No, state is non-reconstructible. Without a watermark, rollback and replay are indistinguishable from corruption.
Decision point, rollback versus forward fix.
Rollback is only viable if a snapshot exists from before any untracked fixes. In most cases, forward fix must stop entirely, accept partial loss, and re-establish trust through external reconciliation rather than replay.
Rollback architecture.
Rollback requires restoring a snapshot taken before any repair or forward fix execution. All CDC and repair jobs must be halted. CDC offsets must be discarded and reseeded. BI tools must be repointed and caches invalidated. Governance approval is mandatory because rollback discards undocumented fixes.
Containment and forward fix strategy.
When replay safety is lost, containment must focus on control. 1. Freeze all repair and replay actions immediately. 2. Declare the system temporarily non-authoritative. 3. Establish a new baseline via snapshot or external reconciliation. 4. Introduce mandatory replay watermarks for all future fixes. 5. Resume recovery only after replay invariants are enforced. Recovery without replay discipline is guesswork.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Replay watermarks are mandatory for safe recovery. 2. Successful execution does not imply replayability. 3. Rollback fails when execution history is not provable. 4. Recovery systems must be designed for re-execution from day one. Exactly once recovery requires explicit replay boundaries.
Follow-up 1. Why can't teams just decide to not rerun fixes?
Answer: because uncertainty itself blocks recovery. Without knowing what ran, teams cannot safely proceed or validate correctness, leaving the system in a permanent limbo state.
Follow-up 2. When did rollback stop being safe in this incident?
Answer: rollback stopped being safe the moment fixes were executed without persisting a replay watermark. From that point on, no clean execution boundary existed.
Follow-up 3. Curveball. What if engineers believe they remember what ran?
Answer: human memory is not an execution log. Recovery systems must be machine verifiable. Otherwise, rollback depends on belief, not evidence.
Pro insider tip.
If you cannot rerun a fix safely, you never truly fixed anything. You only changed state once and hoped it was correct.
Category 20 wrap-up. Reprocessing failures reveal a deeper integrity problem.
Reprocessing and idempotency failures demonstrate that even well-intentioned repair actions can permanently corrupt state when safeguards are missing. Once fixes themselves become destructive, the system is no longer drifting accidentally. It is diverging deterministically.
Transition from destructive repairs to broken relationships.
The next category moves beyond corrupted rows and focuses on something more fundamental: broken relationships between tables. Even when individual tables look correct, referential integrity can be silently destroyed across rollback and forward fix boundaries.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs in a single zip file, containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, system design. Required for your data engineer interviews jobs like data quality analyst jobs, data governance analyst jobs, AWS Python data engineer jobs, AWS Redshift Database Administrator DBA jobs, AWS Glue ETL Developer jobs, AWS Data Engineer jobs, Cloud Data Engineer jobs, Data Architect jobs, DataOps Engineer jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based questions and answers, real-world problem solving. Interview questions and answers where almost 80% of the people are failing to answer. System design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section. These questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people also for your interviews. You people can download all 6 PDFs in a single zip file from below given links.
Category 21. Cross-system referential integrity breaks.
These incidents occur when parent-child relationships, surrogate keys, or foreign key assumptions are broken across systems during rollback or partial fixes. The data may exist, counts may match, and pipelines may be green, yet joins no longer describe the same business reality.
Category 21. Scenarios.
The following scenarios illustrate how referential integrity is silently lost during migration recovery. 117. Parent table migrated or rolled back, while child table references invalid or non-existent keys. 118. Surrogate keys regenerated in one table only, breaking fact dimension joins across systems. 119. Dimension table rekeyed during forward fix, causing fact table references to point to incorrect records. 120. Foreign key drift across rollback, where the parent is restored but the child is not, leaving persistent integrity violations. Core failure, referential integrity breaks silently, especially in forward fix-only states.
Real-world incident during source to Redshift migration. 117. Parent table rolled back, while child table retained new keys.
During an AWS Redshift migration rollback, the parent dimension table was restored from a snapshot, while dependent child fact tables were not fully reverted. As a result, child records continued to reference surrogate keys that no longer existed in the restored parent table. This created silent referential integrity breakage that was not enforced or detected by Redshift. Failure class, cross-system referential integrity break.
System state before failure. Very important.
At the moment the integrity break was introduced, the system state was 1. Source system parent and child tables remained consistent prior to migration. 2. Redshift cluster parent table restored from snapshot, child table left at post-cutover state. 3. Write activity disabled during rollback but prior CDC writes persisted in child tables. 4. CDC pipeline stopped during rollback without coordinated parent-child rewind. 5. BI tools continued querying Redshift after rollback. 6. Declared source of truth assumed Redshift post-rollback. 7. Authority status fragmented across tables. Rolling back tables independently breaks referential authority.
Incident analysis and root cause.
This failure resulted from an unsafe rollback assumption. 1. Triggering action restoring only the parent table from a snapshot during rollback. 2. Why it appeared safe snapshot restore completed successfully with no errors. 3. What teams noticed first fact level joins returning fewer rows than expected. 4. What teams did not notice child rows referencing surrogate keys that no longer existed. 5. How divergence accumulated. Child tables retained newer foreign keys while parent keys were reverted. 6. Missing invariant, parent and child tables must always be rolled back atomically.
Why this failure is dangerous. Hidden risk.
This failure is dangerous because Redshift does not enforce foreign key constraints. Queries continue to run successfully, but joins silently drop orphan rows. Detection latency is high, often surfacing only through aggregate drift or unexplained metric loss.
What exactly broke? Consistency breakdown.
Referential consistency is broken. Child records reference non-existent parent keys, making analytical joins unreliable. The child table is no longer trustworthy. If we roll back only data, this inconsistency remains because key life cycles were not restored together.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate 1. Were parent and child tables rolled back together? No, integrity broken. 2. Do orphan foreign keys exist? Yes, silent join loss. 3. Can child tables be cleanly rewound? Often no, CDC already advanced. 4. Have downstream systems consumed joined results? Likely. 5. Can authority be re-established cleanly? No, partial rollback already executed. Once referential integrity is broken, rollback amplifies damage.
Decision point, rollback versus forward fix.
Rollback is no longer safe because parent-child alignment has already been violated. Restoring additional snapshots risks further fragmentation. Forward fix must focus on reconciling keys and reasserting referential authority.
Rollback architecture.
A safe rollback would have required restoring parent and child tables from the same snapshot, discarding all CDC-applied child changes, invalidating BI caches, and pausing downstream consumption. Partial table-level rollback is explicitly unsafe unless full domain isolation is provable.
Code illustration and Redshift artifacts.
In this section, we will show 1. How orphaned foreign keys are detected in Redshift. 2. Why referential breakage proves rollback was incomplete. Orphaned keys are evidence of unsafe rollback boundaries. Here is Redshift SQL showing orphaned child records after partial rollback. Disclaimer: always test code in a non-production environment. This snippet proves that child records reference parent keys that no longer exist. These orphans confirm that parent and child tables were not rolled back together, making analytical results unreliable.
Containment and forward fix strategy.
Once referential breakage is confirmed, containment must precede repair. 1. Immediately pause BI consumption of affected joins. 2. Declare Redshift non-authoritative for impacted domains. 3. Reconstruct parent keys or remap child references using source truth. 4. Rebuild fact tables only after key reconciliation is complete. 5. Revalidate joins before restoring analytical trust. You cannot repair facts until dimensions are authoritative.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. Partial rollback at table level violates referential integrity. Redshift does not enforce foreign keys, so failures are silent. Rollback must respect domain-level atomicity, not table convenience. Referential integrity requires atomic rollback boundaries.
Follow-up 1. Why didn't Redshift surface this as an error?
Answer: Redshift treats foreign keys as informational only. Because constraints are not enforced, orphaned rows do not raise errors. The system remains operational while analytical truth is silently degraded.
Follow-up 2. When did rollback stop being safe in this incident?
Answer: rollback stopped being safe the moment the parent table was restored without simultaneously restoring the child tables. From that point on, referential alignment was permanently broken.
Follow-up 3. Curveball. What if the business insists the orphan count is small?
Answer: even a single orphaned key proves authority loss. Small counts today become systemic corruption tomorrow as aggregates, joins, and downstream models amplify the inconsistency.
Pro insider tip.
If you cannot restore parent and child tables from the same snapshot, you are not performing a rollback. You are manufacturing silent data corruption.
Real-world incident during source-to-Redshift migration, 118. Surrogate keys regenerated in one table only.
During an AWS Redshift migration, a forward fix rebuild regenerated surrogate keys for a dimension table, but the corresponding fact tables were not rebuilt. As a result, fact-to-dimension joins silently broke, producing incorrect analytics despite all tables appearing structurally valid. Failure class: cross-system referential integrity break.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system write-enabled with stable surrogate keys. 2. Redshift cluster live and serving analytics queries. 3. Dimension tables rebuilt with regenerated surrogate keys. 4. Fact tables not rebuilt and still referencing old surrogate keys. 5. CDC pipeline disabled for affected domain during forward fix. 6. BI tools actively querying fact dimension join. 7. Declared source of truth, assumed Redshift postfix. 8. Authority status, fragmented across tables. Regenerating keys in isolation creates silent referential fractures.
Incident analysis and root cause.
This failure resulted from an incorrect repair assumption. 1. Triggering action, rebuilding a dimension table and regenerating surrogate keys during a forward fix. 2. Why it appeared safe, dimension rebuild completed successfully and row counts matched expectations. 3. What teams noticed first, fact tables returning fewer rows or null dimension attributes in joins. 4. What teams did not notice, that surrogate keys had changed without updating downstream references. 5. How divergence accumulated, facts continued to reference obsolete keys while dimensions exposed new ones. 6. Missing invariant, surrogate keys must remain stable or be regenerated consistently across all referencing tables.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it produces analytically plausible but incorrect results. Queries run successfully, dashboards populate, and no operational alarms fire. Detection latency is often weeks, discovered only when deep reconciliations or domain audits reveal missing or misattributed records.
What exactly broke? Consistency breakdown.
Referential and domain-level consistency are broken. Fact tables reference surrogate keys that no longer exist in the dimension table, creating orphaned facts. If we roll back only data, this inconsistency remains because the regenerated keys permanently changed identifier meaning without synchronized rollback.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Were surrogate keys regenerated? Yes, identifier meaning changed. 2. Are old dimension keys still available? No, overwritten. 3. Were fact tables rebuilt in lockstep? No, orphan references exist. 4. Have downstream systems consumed incorrect joins? Likely. 5. Can authority be re-established cleanly? No, key semantics diverged. Key regeneration breaks rollback symmetry.
Decision point, rollback versus forward fix.
Rollback is not clean because restoring dimension data alone does not realign fact references. Forward fix is required to either rebuild all dependent fact tables or remap surrogate keys explicitly, with full downstream revalidation.
Rollback architecture.
A true rollback would require restoring both dimension and fact tables from a prefix snapshot, invalidating all downstream caches and reports. Partial rollback is forbidden because it worsens referential divergence. CDC must remain disabled until full state restoration is complete, and governance approval is required before re-exposing Redshift as authoritative.
Code illustration and Redshift artifacts.
In this section, we will show 1. How orphaned fact records are detected after surrogate key regeneration. 2. How regenerated keys differ from historical references. 3. What rollback evidence would reveal at the system level. 4. How forward fix rebuild restores referential integrity. Execution-level evidence proves that key regeneration fractured joins. Here is Redshift SQL showing orphaned fact records after surrogate key regeneration. Disclaimer: always test code in a non-production environment. This snippet proves that fact records reference surrogate keys no longer present in the dimension table, exposing broken referential integrity. Here is Redshift SQL showing regenerated surrogate keys in the dimension table. Disclaimer: always test code in a non-production environment. This ordering reveals newly generated surrogate keys, which no longer align with keys referenced by existing fact tables. Here is Redshift SQL illustrating why snapshot rollback must include both fact and dimension tables. Disclaimer: always test code in a non-production environment. This confirms that fact data persists independently, proving that rolling back only dimensions would not repair broken joins. Here is Redshift SQL showing forward fix rebuild a fact table with regenerated keys. Disclaimer: always test code in a non-production environment. This join remaps facts to the regenerated surrogate keys, demonstrating the only safe forward fix to restore referential integrity.
Containment and forward fix strategy.
Once key divergence is confirmed, containment must precede repair. 1. Immediately pause analytics consumption of affected joins. 2. Declare surrogate keys unstable until rebuild completes. 3. Rebuild all dependent fact tables using deterministic joins. 4. Revalidate joins and aggregates end-to-end. 5. Re-establish Redshift authority only after reconciliation. Keys define meaning. Rebuilding them demands total consistency.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Surrogate keys are contracts, not implementation details. 2. Rebuilding a dimension without rebuilding facts breaks referential truth. 3. Row counts can pass while joins silently fail. 4. Forward fix must re-establish identifier meaning, not just reload data. Identifier stability is a non-negotiable migration invariant.
Follow-up 1. Why didn't basic validation catch this issue?
Answer: basic validation focused on row counts and load success. Because joins still executed and returned results, no errors surfaced. The failure existed at the semantic join level, not at the storage or execution level.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe the moment surrogate keys were regenerated and exposed to downstream queries. At that point, identifier meaning diverged, and restoring partial snapshots could not realign fact references.
Follow-up 3. Curveball. What if business insists on keeping the regenerated keys?
Answer: then all historical fact data must be fully rekeyed and revalidated. There is no hybrid state. Either all references move together, or analytical trust remains permanently fractured.
Pro insider tip.
If you ever rebuild a dimension during migration, assume every dependent table is now invalid. Surrogate keys are the spine of analytics, and breaking them silently breaks everything.
Real-world incident during source to Redshift migration, 119. Dimension rekey during forward fix breaks fact references.
During an AWS Redshift migration, a forward fix effort regenerated surrogate keys in a dimension table to resolve prior data issues. However, fact tables referencing the dimension were not rebuilt or remapped. As a result, fact records began pointing to incorrect dimension rows, silently corrupting analytical results. Failure class: cross-system referential integrity break.
System state before failure, very important.
At the moment the failure was introduced, the system state was: 1. Source system stable business keys with unchanged semantics. 2. Redshift cluster live and serving analytics workloads. 3. Dimension table rekeyed during forward fix using regenerated surrogate keys. 4. Fact tables retained original surrogate key references. 5. CDC pipeline disabled or bypassed for affected domain. 6. BI tools actively querying fact dimension joins. 7. Declared source of truth, Redshift assumed authoritative postfix. 8. Authority status, implicitly assumed but structurally broken. Rekeying one side of a relationship fractures meaning silently.
Incident analysis and root cause.
This failure resulted from an incomplete forward fix strategy. 1. Triggering action, regenerating surrogate keys in a dimension table during a forward fix. 2. Why it appeared safe, the dimension rebuild completed successfully and passed row-level validation. 3. What teams noticed first, metrics drifting or facts joining to unexpected dimension attributes. 4. What teams did not notice, that surrogate key meaning had changed without updating fact references. 5. How divergence accumulated, facts continued joining, but to semantically incorrect dimension rows. 6. Missing invariant, surrogate key changes must be applied consistently across all referencing tables.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it produces analytically valid-looking results that are semantically wrong. Queries return rows, dashboards populate, and no operational errors occur. Detection latency is often high, surfacing only during deep audits or business disputes over numbers.
What exactly broke? Consistency breakdown.
Referential and domain-level consistency are broken. Fact records reference valid keys, but those keys now represent different dimension entities. If we roll back only data, this inconsistency remains because the surrogate key meaning has already shifted.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate: 1. Were dimension surrogate keys regenerated? Yes, identifier meaning changed. 2. Were fact tables rebuilt or remapped? No, references incorrect. 3. Are prefix dimension snapshots available? Possibly. 4. Have downstream consumers used incorrect joins? Likely. 5. Can authority be restored without full rebuild? No. Rekeying breaks rollback symmetry across tables.
Decision point, rollback versus forward fix.
Rollback is not clean because restoring only dimension data does not realign fact references. A safe outcome requires either a full snapshot restore of all related tables or a controlled forward fix that remaps every fact deterministically.
Rollback architecture.
A valid rollback would require restoring both fact and dimension tables from the same snapshot, invalidating downstream caches, and repointing BI systems. Partial rollback is explicitly unsafe because it preserves broken key relationships. Governance approval is required before restoring authority.
Code illustration and Redshift artifacts.
In this section, we will show 1. How fact records join to incorrect dimension rows after rekey. 2. How mismatched surrogate keys can be detected with minimal evidence. Minimal proof is sufficient to expose semantic join corruption. Here is Redshift SQL showing facts joining to unexpected dimension records. Disclaimer: always test code in a non-production environment. This condition exposes fact records whose surrogate keys no longer resolve to valid dimension attributes, proving semantic breakage. Here is Redshift SQL comparing business keys to detect rekey mismatch. Disclaimer: always test code in a non-production environment. This comparison proves that facts are now associated with the wrong dimension entities, even though joins still succeed.
Containment and forward fix strategy.
Once semantic drift is confirmed, containment must precede repair. 1. Immediately suspend analytics using affected joins. 2. Declare surrogate keys unstable until reconciliation completes. 3. Rebuild or remap all fact tables using deterministic business keys. 4. Revalidate joins and aggregates end-to-end. 5. Re-establish Redshift authority only after consistency is restored. Key meaning must be rebuilt, not patched.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Surrogate keys encode meaning, not just identity. 2. Rekeying one table without rekeying dependence corrupts joins silently. 3. Row counts and query success do not imply correctness. 4. Forward fix must realign meaning across the entire model. Identifier meaning must be globally consistent.
Follow-up 1. Why didn't monitoring detect this issue?
Answer: monitoring focused on query success and system health. Because joins still returned results, no alerts fired. The failure existed at the semantic level, not the operational level.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe once the regenerated keys were exposed to downstream queries. At that point, restoring partial state could not realign identifier meaning across tables.
Follow-up 3. Curveball. Could this ever be fixed without rebuilding facts?
Answer: only if a complete and deterministic key mapping exists. Without that, rebuilding fact tables is the only way to restore referential and semantic integrity.
Pro insider tip.
If surrogate keys change, assume every dependent table is wrong until proven otherwise. Referential integrity failures are silent, but their impact is absolute.
Real-world incident during source to Redshift migration 120. Parent restored, but child not. Referential integrity drift after rollback.
During an AWS Redshift migration rollback, a parent table was restored from a clean snapshot to recover from upstream corruption. However, dependent child tables were not rolled back due to perceived isolation. This created silent foreign key drift, where child rows reference parent keys that no longer existed or now represented different entities. Failure class: cross-system referential integrity break.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system stable and unchanged during rollback window. 2. Redshift cluster partially restored from snapshot. 3. Parent table restored to pre-incident snapshot state. 4. Child tables left untouched with post-incident data. 5. CDC pipeline disabled during rollback execution. 6. BI tools re-enabled after parent restore. 7. Declared source of truth, Redshift assumed authoritative. 8. Authority status fragmented across restored and non-restored domains. Partial rollback fractures relational truth.
Incident analysis and root cause.
This failure resulted from an invalid rollback scope assumption. 1. Triggering action, restoring only the parent table from snapshot during rollback. 2. Why it appeared safe, the corruption was believed to exist only in the parent domain. 3. What teams noticed first, missing or inconsistent joins between parent and child tables. 4. What teams did not notice that child rows now referenced keys that no longer existed. 5. How divergence accumulated. Queries continued executing while silently dropping or misjoining records. 6. Missing invariant. Rollback scope must preserve referential integrity across all dependent tables.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it produces plausible but incomplete results. Joins execute successfully, aggregates compute, and dashboards render without errors. Detection latency is high and often occurs only when business users question unexplained drops or shifts in metrics.
What exactly broke? Consistency breakdown.
Referential and domain-level consistency are broken. Child records reference parent keys that no longer exist or now map to different entities. If we roll back only data, this inconsistency remains because parent and child tables no longer share a common historical state.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Were all dependent tables included in rollback? No partial restore. 2. Do child tables reference restored keys? No orphan rows exist. 3. Is a full snapshot available for all domains? Possibly. 4. Have downstream systems consumed broken joins? Likely. 5. Can authority be restored without full domain rollback? No. Partial rollback breaks relational guarantees.
Decision point, rollback versus forward fix.
Rollback is no longer safe unless all related tables are restored from the same snapshot. Forward fix may be required if downstream usage has already occurred, but it must explicitly reconcile and rebuild broken relationships.
Rollback architecture.
A correct rollback would require restoring parent and all dependent child tables from the same snapshot, invalidating BI caches, and rerunning validation across joins. Partial rollback is explicitly unsafe and must be treated as a rollback failure, not a mitigation.
Code illustration and Redshift artifacts.
In this section, we will show 1. How orphan child rows can be detected after partial rollback. 2. How referential drift proves rollback scope was invalid. Minimal evidence is sufficient to expose broken rollback boundaries. Here is Redshift SQL, detecting orphan child rows after partial rollback. Disclaimer: always test code in a non-production environment. This condition exposes child records whose parent references no longer exist after the parent table rollback.
Containment and forward fix strategy.
Once referential drift is confirmed, containment must precede repair. 1. Immediately suspend analytics relying on affected joins. 2. Declare referential integrity compromised. 3. Choose between full domain rollback or deterministic remapping. 4. Rebuild child tables against restored parent state if possible. 5. Revalidate all joins before re-establishing authority. Integrity must be restored globally, not selectively.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Rollback scope must align with referential boundaries. 2. Partial restores create silent data corruption. 3. Referential integrity is an invariant, not an optimization. 4. Rollback success requires relational completeness. Rollback must preserve relationships, not just tables.
Follow-up 1. Why didn't this fail loudly after rollback?
Answer: because SQL joins are permissive by default. Missing parents do not raise errors. They simply drop rows, allowing the system to appear healthy while returning incomplete results.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe the moment only a subset of relational tables was restored. At that point, no single snapshot represented a consistent system state.
Follow-up 3. Curveball. Could foreign key constraints have prevented this?
Answer: only partially. Redshift does not enforce foreign keys. Even if declared, they serve documentation purposes only and cannot prevent this class of rollback-induced corruption.
Pro insider tip.
If a rollback plan does not list dependent tables explicitly, it is not a rollback plan. It is a controlled corruption event.
Category 21 wrap-up. Why referential integrity failures are so hard to undo.
Cross-system referential integrity failures are especially dangerous because they often survive both rollback and forward fix attempts. Even when parent or dimension data is restored correctly, broken foreign keys, regenerated surrogates, or misaligned references silently persist, leaving analytics logically corrupted without obvious errors.
Transition from structural breakage to human intervention.
When engineers encounter broken referential integrity under pressure, the next failure mode is rarely automated. Teams often resort to manual fixes in production to stop the bleeding. This marks the transition from system-induced failures to human-initiated ones, where auditability and rollback confidence collapse entirely.
Category 22. Human-initiated emergency fixes.
This category covers incidents where engineers apply manual or ad hoc fixes during migration or rollback windows. These actions are usually well-intentioned, but they bypass governance, destroy lineage, and make it impossible to reconstruct or safely roll back system state.
Category 22. Human-initiated emergency fixes.
These incidents occur when manual intervention replaces controlled rollback or forward fix processes. 121. Manual update applied during freeze to target diverges from source. 122. Hotfix scripts run on Redshift only, not source to untracked divergence. 123. Emergency backfill with no lineage to audit trail lost. 124. Ad hoc SQL fixes not version to rollback confidence destroyed. Once humans patch data manually, rollback stops being a technical problem and becomes a trust problem.
Real-world incident during source to Redshift migration. 121. Manual update applied during freeze caused target divergence.
During an AWS Redshift migration freeze, engineers executed manual update statements directly on Redshift to correct perceived data issues. The source system remained unchanged. This introduced an irreversible divergence between source and target during a period when state was assumed to be immutable. Failure class: human-initiated emergency fixes.
System state before failure, very important.
At the time the failure was introduced, the system state was 1. Source system write-enabled but logically frozen for migration consistency. 2. Redshift cluster accessible to engineers for validation and emergency fixes. 3. CDC pipeline paused or lagging during freeze window. 4. BI tools temporarily disabled or limited to validation users. 5. Declared source of truth assumed unchanged source system. 6. Authority status implicitly source but violated by manual target rights. A freeze assumes immutability. Manual rights violate that assumption instantly.
Incident analysis and root cause.
This failure resulted from procedural breakdown under pressure. 1. Triggering action: engineers executed manual update statements on Redshift during a declared freeze window. 2. Why it appeared safe: changes were small, targeted, and intended to unblock validation quickly. 3. What teams noticed first: source and Redshift values no longer matched for specific records. 4. What teams did not notice: that freeze invariants had already been violated beyond recovery. 5. How divergence accumulated: subsequent validations assumed Redshift reflected source state, compounding trust errors. 6. Missing invariant: no data mutation is allowed on the target during a migration freeze.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it feels corrective rather than destructive. Manual fixes often succeed locally, pass spot checks, and relieve immediate pressure. Detection latency is high, and the true impact surfaces later when rollback or reconciliation is attempted and no clean baseline exists.
What exactly broke? Consistency breakdown.
Authoritative and procedural consistency are broken. Redshift now contains data that never existed in the source system. If we roll back only data, this inconsistency remains because the source and target timelines can no longer be reconciled deterministically.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate: 1. Were manual rights applied to Redshift during freeze? Yes, authority violated. 2. Do those changes exist in source logs? No, source unaware. 3. Can changes be programmatically identified and reversed? Uncertain, human intent lost. 4. Have validations consumed the modified data? Likely. 5. Can authority be restored cleanly? no baseline compromised. Once humans patch data during a freeze, rollback becomes ambiguous by definition.
Decision point, rollback versus forward fix.
Rollback is no longer clean because restoring snapshots cannot account for undocumented manual mutations. Forward fix must focus on declaring divergence, revalidating against source, and re-establishing authority explicitly.
Rollback architecture, if executed.
Rollback would require discarding the Redshift cluster state entirely and restoring from a pre-freeze snapshot, followed by CDC reseeding. However, because manual changes are undocumented and source state continued independently, this rollback cannot guarantee restored trust or correctness and is typically rejected.
Code illustration and Redshift artifacts.
In this section, we will show 1. How source versus target comparisons expose manual divergence. 2. Why this evidence proves freeze invariants were violated. Detection proves divergence but cannot recover lost authority. Here is Redshift SQL showing divergence caused by manual updates during freeze. Disclaimer: always test code in a non-production environment. This predicate isolates records where Redshift diverged from the source. In a freeze window, any difference is evidence of unauthorized mutation, proving rollback boundaries were crossed.
Containment and forward fix strategy.
Once manual divergence is confirmed, containment must precede repair. 1. Immediately halt all manual data access to Redshift. 2. Declare Redshift non-authoritative until reconciliation completes. 3. Reconstruct intended fixes from tickets or communications, not data. 4. Realign Redshift strictly from source via controlled reload. 5. Reintroduce freezes only with enforced write barriers. Manual fixes must be replaced with governed recovery.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. A migration freeze is a contract, not a suggestion. Manual target writes instantly violate rollback assumptions. Procedural failures can be more destructive than technical ones. Freeze invariants must be enforced, not trusted.
Follow-up 1. Why is a manual update during freeze worse than a CDC error?
Answer: a CDC error is at least traceable and bounded by tooling state. A manual update bypasses lineage, logging, and intent. The system can no longer explain why data looks the way it does, which destroys rollback confidence.
Follow-up 2. When did rollback stop being safe in this scenario?
Answer: rollback stopped being safe the moment the first manual update was committed on Redshift during the freeze. From that point on, no snapshot could represent a known good authoritative state.
Follow-up 3. Curveball. What if the manual fix was actually correct?
Answer: correctness is irrelevant without authority. Even a correct fix breaks governance if it is undocumented and unilateral. Migration safety depends on traceability, not individual accuracy.
Pro insider tip.
If someone suggests a quick manual update during a freeze, treat it as a rollback killer, not a shortcut.
Real-world incident during source to Redshift migration 122. Hotfix scripts executed only on Redshift create untracked divergence.
During an AWS Redshift migration incident, teams executed emergency hotfix scripts directly on Redshift to address data issues, while the source system was left untouched. These fixes were not versioned, logged, or replayed on the source, creating silent divergence that permanently weakened rollback guarantees. Failure class: human-initiated emergency fixes.
System state before failure, very important.
At the time the failure was introduced, the system state was 1. Source system write-enabled and unchanged by emergency fixes. 2. Redshift cluster directly modified via ad hoc hotfix scripts. 3. CDC pipeline running or paused unaware of manual target changes. 4. BI tools reading from Redshift and validating post-hotfix data. 5. Declared source of truth assumed to remain the source system. 6. Authority status implicitly broken by unilateral target fixes. Fixes applied to only one side immediately fracture authority.
Incident analysis and root cause.
This failure was driven by emergency response without governance. 1. Triggering action executing hotfix SQL scripts directly on Redshift only. 2. Why it appeared safe the fixes resolved visible symptoms in reports. 3. What teams noticed first Redshift data appeared corrected and stable. 4. What teams did not notice the source system no longer matched Redshift. 5. How divergence accumulated. Subsequent CDC applied changes on top of an altered target baseline. 6. Missing invariant. All corrective data changes must be applied symmetrically and tracked across systems.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it creates the illusion of successful recovery. Reports stabilize, alarms quiet down, and confidence returns. Detection latency is high because the divergence is logical rather than operational, surfacing only when rollback or deep reconciliation is attempted.
What exactly broke? Consistency breakdown.
Authoritative and procedural consistency are broken. Redshift now represents a state that never existed in the source. If we roll back only data, this inconsistency remains because the source and target histories have permanently diverged without a shared change log.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Were hotfixes applied only to Redshift? Yes, authority fractured. 2. Are the fixes reproducible on the source? No, scripts not tracked. 3. Can CDC replay reconcile the difference? No, baseline altered. 4. Have downstream systems consumed fixed data? Likely. 5. Can a clean authoritative baseline be restored? No, provenance lost. Rollback fails when fixes are not replayable.
Decision point, rollback versus forward fix.
Rollback is no longer clean because restoring any snapshot will either reintroduce the original issue or erase undocumented fixes. Forward fix must focus on re-establishing authority, replaying fixes correctly, and restoring governance controls.
Rollback architecture, if executed.
Rollback would require discarding the current Redshift state and restoring from a pre-hotfix snapshot, followed by a controlled reapplication of all fixes from a verified source. Because the fixes were not versioned or replayable, this rollback cannot guarantee correctness and is typically rejected by governance.
Code illustration and Redshift artifacts.
In this section, we will show 1. How source versus target comparisons expose untracked hotfix divergence. Detection proves asymmetry, not recoverability. Here is Redshift SQL showing divergence caused by hotfix scripts, applied only on target. Disclaimer: always test code in a non-production environment. This predicate isolates records where Redshift differs from the source. When fixes were applied only to the target, these mismatches prove that rollback baselines no longer align.
Containment and forward fix strategy.
Once asymmetric hotfixes are confirmed, containment must precede repair. 1. Immediately block ad hoc write access to Redshift. 2. Inventory all emergency scripts from tickets and chat logs. 3. Replay fixes deterministically on the source or rebaseline from source. 4. Reload Redshift from a clean, authoritative snapshot. 5. Enforce change management for all future fixes. Hotfixes without lineage are rollback killers.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. Fixes must be replayable, not just effective. Unilateral target changes destroy rollback guarantees. Governance failures often outweigh technical ones. All fixes must preserve authority symmetry.
Follow-up 1. Why is a one-sided hotfix worse than a failed migration step?
Answer: a failed migration step is at least logged and bounded. A one-sided hotfix silently rewrites history on one system only. This removes any deterministic way to reason about state or safely rollback.
Follow-up 2. When did rollback stop being safe in this scenario?
Answer: rollback stopped being safe the moment the first hotfix script was committed on Redshift without an equivalent source-side change. From that point forward, no snapshot represented a shared authoritative truth.
Follow-up 3. Curveball. What if the hotfix fixed a real production bug?
Answer: even correct fixes are unsafe if they are not traceable and replayable. Migration safety depends on provenance and authority, not on whether an individual fix was logically correct.
Pro insider tip.
If a fix cannot be replayed from source logs, treat it as permanent divergence, not recovery.
Real-world incident during source to Redshift migration 123. Emergency backfill executed without lineage or audit trail.
During an AWS Redshift migration incident, teams executed an emergency backfill directly into Redshift to address missing or incorrect data. The backfill was performed outside the migration pipeline, without lineage metadata, versioning, or reconciliation against the source system. This permanently destroyed rollback confidence because the origin, timing, and correctness of the injected data could not be reconstructed. Failure class, human-initiated emergency fixes.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system write-enabled and continuing normal operations. 2. Redshift cluster manually modified via emergency backfill. 3. CDC pipeline running or paused unaware of injected data. 4. Backfill process executed outside migration tooling with no lineage. 5. BI tools reading corrected-looking data from Redshift. 6. Declared source of truth, implicitly violated by manual injection. 7. Authority status, broken due to unverifiable data origin. Data without lineage cannot be trusted or rolled back.
Incident analysis and root cause.
This failure resulted from bypassing migration invariants under pressure. 1. Triggering action, performing an emergency backfill directly into Redshift. 2. Why it appeared safe, the backfill corrected visible gaps in reports. 3. What teams noticed first, metrics appeared to normalize after the backfill. 4. What teams did not notice, no record existed tying injected data back to source truth. 5. How divergence accumulated, subsequent CDC changes layered on top of unverifiable data. 6. Missing invariant, all data entering Redshift must be traceable to a deterministic source.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it creates false finality. The data looks correct, pipelines are green, and business pressure subsides. Detection latency is extremely high because the corruption is epistemic. No one can prove whether the data is correct or reconstruct how it arrived.
What exactly broke? Consistency breakdown.
Authoritative and historical consistency are broken. Redshift now contains data that cannot be traced to any authoritative event or snapshot. If we roll back only data, this inconsistency remains because the lineage required to validate or replay the backfill no longer exists.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate 1. Was the backfill source from a verified snapshot? No, origin unknown. 2. Is there lineage metadata for injected rows? No, untraceable. 3. Can the backfill be deterministically replayed? No, one-off execution. 4. Have downstream systems consumed this data? Likely. 5. Can authority be restored cleanly? No, provenance destroyed. Rollback fails when data history cannot be reconstructed.
Decision point, rollback versus forward fix.
Rollback is no longer viable because no snapshot represents a fully authoritative state. Forward fix must explicitly acknowledge the unverifiable backfill, constrain further propagation, and re-establish governance controls to prevent recurrence.
Rollback architecture, if executed.
Any rollback would require discarding the current Redshift state and restoring a pre-backfill snapshot. Because the injected data cannot be replayed or validated, such a rollback would knowingly reintroduce known gaps and is typically rejected by business and governance stakeholders.
Containment and forward fix strategy.
Once untracked backfill is confirmed, containment must precede repair. 1. Immediately freeze manual data modification paths. 2. Document the affected tables and time ranges explicitly. 3. Communicate uncertainty to downstream consumers. 4. Rebaseline analytics to exclude unverifiable data where possible. 5. Mandate lineage and replayability for all future backfills. Transparency is the only substitute for lost lineage.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. Data without lineage is indistinguishable from corruption. Emergency backfills must preserve replayability. Rollback depends on history, not intent. Lineage is a first-class migration invariant.
Follow-up 1. Why is missing lineage worse than incorrect data?
Answer: incorrect data can be corrected if its origin is known. Missing lineage removes the ability to validate, replay, or reason about correctness at all. This makes both rollback and forward fix unsafe.
Follow-up 2. When did rollback stop being safe in this scenario?
Answer: rollback stopped being safe the moment the emergency backfill completed without lineage. From that point on, no snapshot could be asserted as authoritative with confidence.
Follow-up 3. Curveball. What if the backfill used data exported from the source?
Answer: without a deterministic replay mechanism and audit trail, Even source-derived data is unsafe. Provenance requires repeatability and verification, not just good intentions.
Pro insider tip.
If you cannot prove where a row came from, assume it will eventually invalidate rollback.
Real-world incident during source to Redshift migration 124. Ad hoc SQL fixes executed without versioning or approval.
During an AWS Redshift migration incident, engineers executed ad hoc SQL fixes directly against production Redshift tables to address urgent data issues. These changes were not versioned, peer-reviewed, logged, or tied to any migration artifact. As a result, the system entered an untraceable state where rollback confidence was permanently destroyed. Failure class: human-initiated emergency fixes.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system continuing to accept writes under assumed authority. 2. Redshift cluster live and manually modified via ad hoc SQL. 3. CDC pipeline running or paused unaware of manual mutations. 4. Change control bypassed with no versioning or approval trail. 5. BI tools reading corrected looking but unverifiable data. 6. Declared source of truth implicitly violated by manual intervention. 7. Authority status broken due to untracked state mutation. Unversioned fixes destroy state reproducibility.
Incident analysis and root cause.
This failure resulted from bypassing governance under time pressure. 1. Triggering action executing ad hoc SQL fixes directly in Redshift. 2. Why it appeared safe, immediate query results appeared correct. 3. What teams noticed first, dashboard stabilized after the fixes. 4. What teams did not notice, no record existed of what was changed, when or why. 5. How divergence accumulated, subsequent CDC and queries built on undocumented state. 6. Missing invariant, all production data changes must be versioned, reviewable, and replayable.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it creates an illusion of resolution. The system appears stable, but no one can assert correctness or reconstruct state. Detection latency is effectively infinite because there is no reference point to compare against.
What exactly broke? Consistency breakdown.
Authoritative and historical consistency are broken. Redshift contains data mutations that cannot be tied to any source event or approved change. If we roll back only data, this inconsistency remains because the mutations cannot be identified or selectively reversed.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Are all production changes versioned? No ad hoc SQL executed. 2. Can manual fixes be replayed deterministically? No one-off execution. 3. Is there a clean snapshot before the fixes? Uncertain. 4. Have downstream systems consumed this state? Likely. 5. Can authority be re-established cleanly? No state provenance lost. Rollback requires knowing what to undo.
Decision point, rollback versus forward fix.
Rollback is unsafe because no authoritative prefix state can be asserted with confidence. Forward fix must focus on freezing further manual changes, documenting current state as a new baseline, and restoring governance controls.
Rollback architecture, if executed.
Any rollback would require restoring a snapshot taken before the ad hoc fixes. Because the fixes cannot be enumerated or replayed, rollback would knowingly discard undocumented changes and reintroduce unknown gaps, making it unacceptable in most production environments.
Containment and forward fix strategy.
Once ad hoc fixes are confirmed, containment must precede repair. 1. Immediately revoke direct write access to production tables. 2. Establish a strict change control and versioning process. 3. Document current state as an explicit audited baseline. 4. Rederive critical data from source where possible. 5. Enforce replayable migration and fix workflows going forward. Governance restores trust when rollback cannot.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. Unversioned fixes destroy rollback confidence. Correct-looking data is not authoritative data. Governance failures outlive technical incidents. Every production change must be replayable.
Follow-up 1. Why are ad hoc SQL fixes more dangerous than bad code?
Answer: bad code can be reverted through version control and deployment history. Ad hoc SQL leaves no such trail, making it impossible to reconstruct or safely reverse changes.
Follow-up 2. When did rollback stop being safe here?
Answer: rollback stopped being safe the moment unversioned SQL was executed in production. From that point on, no snapshot could be asserted as fully authoritative.
Follow-up 3. Curveball. What if the engineer remembers what they changed?
Answer: human memory is not an audit trail. Without verifiable, replayable records, the system state cannot be trusted or reconstructed.
Pro insider tip.
If a fix cannot be replayed automatically, assume it permanently damages rollback.
Category 22 wrap-up. Why human fixes permanently damage rollback confidence.
Human-initiated emergency fixes represent a critical inflection point in any migration. Once manual changes bypass governance, logging, and replayability, the system loses its ability to assert historical truth. From this point forward, rollback becomes a theoretical concept rather than an executable option.
Transition from data corruption to security drift.
The next class of incidents goes one step further. Even when data rollback succeeds, migrations often fail because security and access state do not roll back with the data. These failures are subtle, operationally destructive, and frequently misdiagnosed as infrastructure bugs.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs in a single zip file, containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, system design. Required for your data engineer interviews jobs like data quality analyst jobs, data governance analyst jobs, AWS Python data engineer jobs, AWS Redshift Database Administrator DBA jobs, AWS Glue ETL Developer jobs, AWS Data Engineer jobs, Cloud Data Engineer jobs, Data Architect jobs, DataOps Engineer jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based questions and answers, real-world problem-solving, interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people also for your interviews. You people can download all 6 PDFs in a single zip file from below given links.
Category 23. Security and access rollback drift incidents.
Security and access rollback drift incidents occur when IAM roles, permissions, encryption grants, or access controls are modified during migration but not restored during rollback. The data may be correct, but users, services, or consumers experience outages, unauthorized access, or compliance violations because security state no longer matches data state.
Security and access rollback drift scenarios.
The following incidents illustrate how security state divergence breaks rollback safety. 125. Role permissions widen during migration and not reverted, leaving unauthorized access active after rollback. 126. Cross-account Redshift data share permissions persist after rollback, causing consumers to lose access or see inconsistent state. 127. KMS grants altered during migration, allowing source restore but blocking consumers due to key mismatches. 128. Security boundary drift where grants or row-level security change mid-cutover, restoring data but not access controls. Core failure, rollback restores data, but security and access state remain altered, causing phantom outages or compliance violations.
Real-world incident during source to Redshift migration. 125. Role permissions widened during migration, not reverted on rollback.
During an AWS Redshift migration, IAM roles and database grants were temporarily widened to accelerate validation and troubleshooting. After a rollback restored the original data state, the expanded permissions were never reverted. As a result, Users and services retained access that should not have existed, creating a silent security and compliance breach. Failure class, security and access rollback drift.
System state before failure, very important.
At the moment the access drift was introduced, the system state was 1. Source system restored to pre-cutover state after rollback. 2. Redshift cluster snapshot restored successfully with historical data. 3. IAM roles temporarily broadened during migration activities. 4. Database grants expanded to multiple roles for validation. 5. BI and downstream tools reconnected post-rollback using existing credentials. 6. Declared source of truth source system for writes, Redshift for analytics. 7. Authority status assumed restored after rollback, not revalidated for access. Rollback restored data, but access authority was never re-established.
Incident analysis and root cause.
This incident resulted from an incomplete rollback scope. 1. Triggering action, widening IAM and Redshift permissions during migration to unblocked teams. 2. Why it appeared safe, permissions were considered temporary and outside the rollback checklist. 3. What teams noticed first, nothing, queries continued to work normally post-rollback. 4. What teams did not notice, unauthorized roles still had access to sensitive schemas. 5. How divergence accumulated, new consumers and jobs began relying on the widened access. 6. Missing invariant, rollback must restore security and access state, not just data.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it creates silent compliance and security violations. Data appears correct, dashboards work, and rollback is declared successful. Detection latency is often months, surfacing only during audits or incident reviews.
What exactly broke? Consistency breakdown.
Authority and security consistency are broken. The data state reflects a rolled back system, but the access state reflects a post-migration system. Redshift can no longer be trusted as a compliant analytical environment. If we roll back only data, this inconsistency remains because permission state is orthogonal to data snapshots.
Rollback viability checklist, go or no go.
Before rollback is considered complete, the architect must evaluate 1. Were IAM roles modified during migration? Yes, drift introduced. 2. Were Redshift grants reverted explicitly? No, permissions persist. 3. Can snapshot restore revert IAM state? No, out of scope. 4. Have unauthorized consumers access data possible? 5. Can security authority be reasserted cleanly? Yes, with manual intervention. Rollback without access revalidation creates phantom compliance.
Decision point, rollback versus forward fix.
Data rollback alone is insufficient. Forward fix is required to explicitly re-establish least privilege access, revoke unintended permissions, and re-audit all roles and consumers.
Rollback architecture.
Rollback cannot revert IAM or database grant changes automatically. A complete rollback architecture must include explicit permission baselining, revocation scripts, BI credential rotation, cache invalidation, and formal security approval before declaring the system restored.
Code illustration and Redshift artifacts.
In this section, we will show 1. How widened permissions are detected via Redshift system views. 2. How IAM role drift is proven post-rollback. Access drift proves rollback was incomplete, not unsuccessful. Detection. Inspecting active Redshift grants post-rollback. Disclaimer. Always test code in a non-production environment. This query exposes all active table-level privileges. Comparing this output against the pre-migration baseline proves that access was widened and never reverted during rollback. Detection. Inspecting IAM role policies still attached post-rollback. Disclaimer. Always test code in a non-production environment. This policy snippet proves overly broad permissions remain attached to roles after rollback. Snapshot restore does not modify IAM state, confirming security drift.
Containment and forward fix strategy.
Once access drift is confirmed, containment must precede trust restoration. 1. Immediately revoke non-baseline IAM and Redshift privileges. 2. Rotate credentials for BI tools and service accounts. 3. Rerun access audits against pre-migration baselines. 4. Invalidate cache sessions and query results. 5. Require security sign-off before resuming analytics. Security state is part of system truth, not an afterthought.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. Rollback restores data, not IAM or database permissions. Security state must be versioned and reverted explicitly. Silent access drift is more dangerous than data loss. A rollback is incomplete until authority is revalidated. Rollback must restore authority, not just bytes.
Follow-up 1. Why didn't the rollback revert permissions automatically?
Answer: because Redshift snapshots only capture data and metadata inside the cluster. IAM roles and many grant changes live outside snapshot scope. Without explicit reversal steps, access state persists silently across rollback boundaries.
Follow-up 2. When exactly did rollback stop being safe here?
Answer: rollback stopped being safe the moment widened permissions were used by additional consumers. At that point, unauthorized access occurred, and restoring data alone could not undo the compliance breach or trust loss.
Follow-up 3. Curveball. What if data is correct but auditors flag access violations?
Answer: then the system has already failed. Correct data does not compensate for broken security boundaries. The only valid response is access revocation, re-audit, and potential disclosure, regardless of data accuracy.
Pro insider tip.
Always treat IAM roles and database grants as first-class rollback artifacts. If you do not snapshot and revert access state explicitly, your rollback is only cosmetic.
Real-world incident during source-to-Redshift migration 126. Cross-account Redshift data share permissions persist post-rollback.
During an AWS Redshift migration, data sharing was enabled to allow downstream consumer clusters to validate data early. After a rollback restored the producer cluster to its pre-cutover state, the cross-account data share permissions were never revoked or resynchronized. Consumer clusters continued querying stale or inaccessible objects, causing silent access failures and broken analytics. Failure class: security and access rollback drift.
System state before failure, very important.
At the time the access inconsistency was introduced, the system state was: 1. Producer Redshift cluster rolled back via snapshot restore. 2. Consumer Redshift cluster still attached to pre-rollback datashare. 3. Redshift data share objects not reverted or revalidated. 4. IAM trust relationships unchanged across rollback. 5. BI tools on consumer side continued querying shared schemas. 6. Declared source of truth, assumed producer cluster post-rollback. 7. Authority status, split between producer restore state and consumer access state. Data rollback does not propagate across data share boundaries.
Incident analysis and root cause.
This incident resulted from an incorrect rollback scope assumption. 1. Triggering action, rolling back the producer cluster without coordinating data share state. 2. Why it appeared safe, snapshot restore completed successfully with no cluster-level errors. 3. What teams noticed first, consumer queries failing or returning inconsistent results. 4. What teams did not notice, data share metadata still pointed to pre-rollback objects. 5. How divergence accumulated, consumer clusters cached and depended on invalid shared schemas. 6. Missing invariant, rollback must include all dependent consumer access paths.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it creates a false sense of rollback completeness. The producer cluster appears healthy, but consumers experience partial outages or stale reads. Detection latency is often delayed until downstream teams report failures.
What exactly broke? Consistency breakdown.
Authority and access consistency are broken. The producer cluster reflects a rolled-back truth, while consumer clusters operate against an invalid or outdated contract. If we roll back only data, this inconsistency remains because data share permissions and metadata are not versioned with snapshots.
Rollback viability checklist, go or no go.
Before declaring rollback complete, the architect must evaluate: 1. Were data shares active before rollback? Yes, external dependency exists. 2. Were data shares recreated or revoked? No, drift persists. 3. Do consumer clusters rely on shared objects? Yes. 4. Can snapshot restore affect consumer clusters? No. 5. Can authority be restored cleanly? Yes, with coordinated data share reset. Uncoordinated rollback fractures, producer-consumer contracts.
Decision point. Rollback versus forward fix.
Rollback of the producer cluster alone is insufficient. Forward fix requires explicit teardown and recreation of data shares, consumer coordination, and contract revalidation before analytics can resume.
Rollback architecture.
A complete rollback architecture must treat data shares as first-class dependencies. This includes revoking and recreating data shares, invalidating consumer caches, coordinating consumer downtime, and obtaining cross-account governance approval.
Code illustration and Redshift artifacts.
In this section, we will show 1. How active data shares are inspected on the producer cluster. 2. How consumer-side access failures prove post-rollback drift. Data share state exists outside snapshot rollback boundaries. Detection, listing active data shares on the producer cluster. Disclaimer, always test code in a non-production environment. This query lists all active data shares. Presence of shares that predate the rollback proves that access contracts were not reverted. Detection, consumer-side failure querying shared objects. Disclaimer, always test code in a non-production environment. Query failures or inconsistent results on the consumer cluster prove that shared metadata no longer aligns with the producer rollback state.
Containment and forward fix strategy.
Once data share drift is confirmed, containment must precede recovery. 1. Immediately disable affected data shares. 2. Coordinate downtime with all consumer clusters. 3. Recreate data shares from the restored producer state. 4. Force consumer metadata refresh and cache invalidation. 5. Revalidate access contracts before resuming queries. Producer rollback without consumer coordination is incomplete.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. Redshift snapshots do not version data share state. Producer rollback must include consumer contract resets. Data sharing introduces external rollback dependencies. Rollback authority must span all consuming systems. Rollback authority must extend beyond the cluster boundary.
Follow-up 1. Why didn't Snapshot Restore fix the consumer failures?
Answer, because snapshots restore only the producer cluster state. Data shares and consumer metadata live outside that boundary. Without explicit coordination, consumers continue operating on invalid assumptions.
Follow-up 2. When did rollback stop being safe in this incident?
Answer, rollback stopped being safe when consumer clusters continued querying shared objects after the producer restore. At that point, producer and consumer truths diverged irreversibly without coordinated reset.
Follow-up 3. Curveball. What if consumers cached correct results before rollback?
Answer, cached correctness does not preserve authority. Once the producer state changes, any cached consumer result becomes suspect. All caches must be invalidated to re-establish trust.
Pro insider tip.
Treat Redshift data shares like external APIs. If you would not roll back an API without notifying consumers, you cannot roll back a data share without coordination.
Real-world incident during source to Redshift migration 127. KMS grants altered during migration, causing post-rollback access failures.
During an AWS Redshift migration, KMS key grants were modified to support encrypted snapshots and temporary cross-account access. After a rollback restored the Redshift cluster successfully, downstream consumers began failing with decryption and permission errors because KMS grants were never reverted. Data existed and was correct, but could not be accessed. Failure class, security and access rollback drift.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Redshift cluster restored from encrypted snapshot. 2. KMS key modified during migration to add temporary grants. 3. KMS grants not reverted post-rollback. 4. Downstream consumers using roles without updated grants. 5. BI tools querying Redshift through IAM-authenticated roles. 6. Declared source of truth Redshift cluster post-rollback. 7. Authority status. Data authoritative but access authority broken. Encryption rollback without key rollback creates invisible outages.
Incident analysis and root cause.
This incident resulted from treating encryption as data local. 1. Triggering action updating KMS grants during migration to support encryption changes. 2. Why it appeared safe snapshot restore completed successfully with no Redshift errors. 3. What teams noticed first permission denied and decryption errors from consumers. 4. What teams did not notice, KMS grants are not versioned with snapshots. 5. How divergence accumulated. Access paths silently broke after rollback. 6. Missing invariant security state must be rolled back with data state.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it masquerades as a data outage while the data itself is intact. Operators focus on Redshift health while the real failure sits in KMS. Detection latency is often hours to days, depending on who reports access failures.
What exactly broke? Consistency breakdown.
Access and authority consistency are broken. Data exists and is correct, but authorized consumers cannot read it. If we roll back only data, this inconsistency remains because KMS grants are external to Redshift snapshots.
Rollback viability checklist, go or no go.
Before declaring rollback complete, the architect must evaluate. 1. Was encryption enabled or modified during migration? Yes, external dependency. 2. Are KMS grants versioned with snapshots? No. 3. Are all consumer roles authorized on the restored key? No. 4. Does Redshift show data integrity issues? No, data intact. 5. Can authority be restored cleanly? Yes, with explicit KMS remediation. Encryption state can invalidate an otherwise perfect rollback.
Decision point, rollback versus forward fix.
Rolling back the cluster again does not help. Forward fix requires restoring correct KMS grants, validating consumer roles, and reasserting access authority before declaring recovery.
Rollback architecture.
Rollback architecture must explicitly include encryption state. This means snapshot restore plus KMS grant reconciliation, IAM role validation, consumer testing, and security sign-off before reopening access.
Code illustration and Redshift artifacts.
In this section, we will show 1. How KMS grant state is inspected to prove post-rollback drift. 2. How Redshift access failures confirm encryption level inconsistency. Snapshots restore data blocks, not encryption contracts. Detection. Inspecting KMS grants associated with the Redshift encryption key. Disclaimer. Always test code in a non-production environment. This command exposes which principles can decrypt data. Missing consumer roles prove why access failed after rollback. Detection. Redshift query failing due to missing KMS permissions. Disclaimer. Always test code in a non-production environment. Permission or decryption errors on this query. Confirm that data exists, but encryption authority is broken.
Containment and forward fix strategy.
Once KMS drift is confirmed, containment must precede recovery. 1. Freeze all consumer access to prevent partial recovery attempts. 2. Restore correct KMS grants for all authorized roles. 3. Validate decryption access using controlled test queries. 4. Rerun security audits before reopening BI tools. 5. Document encryption state as part of rollback runbooks. Security state is part of data authority.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. Redshift snapshots do not include KMS grant state. Encryption is an external dependency, not a data attribute. Rollback must include security and access layers. Access failures can mask as data outages. Data authority without access authority is meaningless.
Follow-up 1. Why did the rollback appear successful initially?
Answer: because Redshift restored data blocks correctly. The failure existed outside the cluster in KMS. Until consumers queried the data, the access break remained invisible.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe when KMS grants were modified during migration without a reversion plan. From that moment, snapshot restore alone could never guarantee access recovery.
Follow-up 3. Curveball. What if data was never queried post-rollback?
Answer: lack of queries does not restore trust. Until access paths are validated end-to-end, the system cannot be declared recovered, regardless of apparent quiet.
Pro insider tip.
If encryption changes during migration are not tracked like schema changes, rollback success is an illusion.
Real-world incident during source to Redshift migration, 128. Security boundary drift during cut over leaves access controls, inconsistent after rollback.
During an AWS Redshift migration, row-level security (RLS) policies and grant statements were modified to support phased access and validation. When a rollback restored the Redshift cluster to a prior snapshot, the data state reverted but security policies did not. Users experienced unexpected access loss or overexposure depending on role, creating phantom outages and compliance risk. Failure class, security and access rollback drift.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Redshift cluster restored successfully from snapshot. 2. Security policies grant and RLS changes applied during migration window. 3. Rollback scope data only snapshot restore. 4. Downstream users accessing via role-based permissions. 5. BI tools reconnected automatically post-rollback. 6. Declared source of truth Redshift data post-rollback. 7. Authority status, data authority restored, security authority divergent. Security state is not snapshot aware unless explicitly managed.
Incident analysis and root cause.
This incident was caused by an incomplete rollback model. 1. Triggering action modifying grant and RLS policies during partial cutover. 2. Why it appeared safe snapshot rollback completed without Redshift errors. 3. What teams noticed first users reported missing access or unexpected visibility. 4. What teams did not notice security changes are not reverted by snapshot restore. 5. How divergence accumulated. Access controls drifted independently of data state. 6. Missing invariant, security boundaries must be versioned and rolled back with data.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it produces silent compliance violations or hidden outages. Data looks correct, queries succeed for some users, and dashboards partially load. Detection latency is high because symptoms vary by role rather than system health.
What exactly broke? Consistency breakdown.
Authority and access consistency are broken. The same data presents different truths depending on user role. If we roll back only data, this inconsistency remains because grant and RLS state live outside snapshot restoration.
Rollback viability checklist, go or no go.
Before declaring rollback complete, the architect must evaluate. 1. Were grant or RLS policies changed during migration? Yes, external state drift. 2. Are security policies captured in snapshots? No. 3. Do all roles have expected access post-rollback? No. 4. Has any unauthorized access occurred? Unknown compliance risk. 5. Can authority be restored cleanly? Yes, with explicit policy reconciliation. Rollback that ignores security state is incomplete by definition.
Decision point, rollback versus forward fix.
Repeating rollback does not resolve the issue. Forward fix requires auditing all security changes, reapplying correct grant and RLS policies, and revalidating access before declaring recovery.
Rollback architecture.
Rollback architecture must explicitly include security state. This requires exporting grant and RLS definitions before migration, replaying them post-rollback, validating role-based access, and obtaining governance sign-off before reopening systems.
Code illustration and Redshift artifacts.
In this section, we will show 1. How grant and RLS definitions differ post-rollback. 2. How role-based query results expose security drift. Security drift manifests through selective visibility, not data loss. Detection, inspecting grant state after rollback. Disclaimer, always test code in a non-production environment. This query exposes mismatched privileges after rollback, proving that access controls did not revert with data. Detection, role-based visibility difference caused by RLS drift. Disclaimer, always test code in a non-production environment. Different results or permission errors for the same query under different roles. Confirm row-level security inconsistency.
Containment and forward fix strategy.
Once security drift is confirmed, containment must precede recovery. 1. Freeze all access to prevent further compliance exposure. 2. Audit all grant and RLS changes made during migration. 3. Reapply approved security policies explicitly. 4. Validate access per role using controlled queries. 5. Document security state as part of rollback runbooks. Access control is part of system truth.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. Snapshots restore data, not security policies. RLS and grant are external rollback dependencies. Access drift can create both outages and compliance breaches. Rollback success must include authorization validation. Security boundaries must be versioned like schemas.
Follow-up 1. Why did monitoring not catch this immediately?
Answer: because system health and data integrity remained green. The failure existed at the authorization layer and only manifested when specific roles queried restricted data.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe the moment security policies were modified without a rollback plan. From that point onward, snapshot restore alone could not guarantee correct access semantics.
Follow-up 3. Curveball. What if access drift benefits some users?
Answer: temporary benefit does not restore trust. Any unauthorized visibility or hidden restriction invalidates system authority until security state is fully reconciled.
Pro insider tip.
If you do not export and version grant and RLS policies before migration, you have already lost rollback fidelity.
Category 23 wrap-up. When rollback restores data but not safety.
The previous category demonstrated a critical but often overlooked truth. Rollback is not complete unless security, access, and trust boundaries are restored alongside data. Once permissions, roles, or encryption state drift, the system may appear healthy while silently violating compliance or denying access. At this point, rollback becomes a partial illusion rather than a true recovery.
Transition from security drift to platform-level illusions.
We now move beyond human error and governance gaps into a more dangerous territory: failures introduced by modern, managed Redshift architectures themselves. These incidents occur even when teams follow best practices, because the underlying platform abstracts state in ways that break traditional rollback and recovery assumptions.
Category 24. Modern Redshift architecture and native integration failures.
This category focuses on failures unique to modern Redshift deployments, including zero-ETL integrations, cross-cluster data sharing, result caching, and Array3 or serverless snapshot behavior. These systems create hidden state outside tables and schemas. When that state becomes inconsistent, rollback restores data but not behavior, correctness, or trust. Failure class: modern Redshift architecture and native integration failures.
Scenarios in this category.
The following incidents illustrate how native Redshift integrations introduce new, non-obvious rollback killers. 1. Zero-ETL sync collapse. Upstream Aurora schema change breaks replication, leaving Redshift stuck in a needs resync state with no safe resume. 2. Cross-cluster data share poisoning. Producer cluster rolls back, but consumer cluster continues operating on corrupted shared data. 3. Result cache poisoning. Underlying data is fixed, but stale or incorrect results continue to be served from the leader node cache. 4. Table-level versus cluster-level restore asymmetry. A single table corruption forces a full cluster restore because Array3 snapshots are monolithic. Core failure. Modern Redshift abstractions create state that rollback cannot fully rewind.
Real-world incident during source-to-Redshift migration 129. Zero-ETL sync collapse after upstream schema change.
During an AWS Redshift zero-ETL integration from Aurora, an upstream schema change was deployed in the source database during an active synchronization window. Redshift continued to show the integration as configured, but replication entered a degraded state requiring full resynchronization. There was no safe resume path, and previously replicated data could no longer be trusted. Failure class: modern Redshift architecture and native integration failures.
System state before failure, very important.
At the moment the failure was introduced, the system state was: 1. Source system Aurora write-enabled with active schema evolution. 2. Redshift cluster consuming data via zero-ETL managed integration. 3. Integration state enabled and previously healthy. 4. Schema governance no freeze enforced during migration window. 5. BI tools reading from Redshift and publishing analytics. 6. Declared source of truth implicitly Redshift for analytics. 7. Authority status assumed stable due to managed integration. Managed integrations still require schema discipline.
Incident analysis and root cause.
This failure resulted from an invalid assumption about managed durability. 1. Triggering action, deploying an incompatible schema change in Aurora during active zero-ETL replication. 2. Why it appeared safe. Zero-ETL is marketed as managed and resilient with minimal operational visibility. 3. What teams noticed first? Replication status degraded to a non-progressing state requiring resync. 4. What teams did not notice? Previously replicated data was already inconsistent with the new schema. 5. How divergence accumulated. Redshift retained partial state while the source advanced structurally. 6. Missing invariant schema compatibility must remain stable for the lifetime of a 0ETL sync.
Why this failure is dangerous, hidden risk.
This failure is dangerous because the integration does not fail loudly. Redshift continues serving previously replicated data while the sync is stalled. Validation may pass for historical ranges, and dashboards appear stable. Detection latency is often days, discovered only when fresh data stops appearing or schema-dependent queries fail.
What exactly broke? Consistency breakdown.
Contractual and temporal consistency are broken. Redshift contains data derived from an earlier schema contract, while the source has moved on. If we roll back only data, this inconsistency remains because the integration contract itself is no longer valid and cannot be resumed incrementally.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Can the 0ETL integration resume incrementally? No, full resync required. 2. Is the pre-change schema still authoritative? No, source already evolved. 3. Can Redshift discard partial integration states safely? Only via destructive reset. 4. Have downstream systems consumed Redshift data? Likely. 5. Can authority be restored without re-ingestion? No. 0ETL collapse removes incremental recovery paths.
Decision point, rollback versus forward fix.
Rollback is not clean because there is no incremental rewind for 0ETL integrations. The only viable path is a destructive reset followed by a full resynchronization after schema alignment. Forward fix focuses on rebaselining trust, not preserving partial history.
Rollback architecture, if executed.
Rollback requires fully disabling the 0ETL integration, discarding all replicated state in Redshift, and reinitializing the integration after schema contracts are re-established. BI tools must be repointed or disabled during resync, and downstream consumers must invalidate any derived artifacts. This rollback is fully destructive by necessity. Partial rollback is not supported by the integration model.
Code illustration and Redshift artifacts.
In this section, we will show 1. How 0ETL integration status exposes a forced resync state. 2. Why schema incompatibility makes incremental resume impossible. Managed sync status is the only visibility into 0ETL failure boundaries. Here is Redshift system, view SQL, showing a 0ETL integration, stuck in resync required state. Disclaimer, always test code in a non-production environment. This field reveals that the integration is no longer progressing and requires a full resynchronization. This proves there is no safe incremental rollback or resume path.
Containment and forward fix strategy.
Once 0ETL collapse is confirmed, containment must proceed repair. 1. Disable the 0ETL integration immediately. 2. Declare Redshift analytically non-authoritative until resync completes. 3. Align source and target schema contracts explicitly. 4. Reinitialize 0ETL with a full backfill. 5. Revalidate all downstream artifacts post-resync. 0ETL recovery is re-ingestion, not rewind.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. 0ETL removes operational burden, not architectural responsibility. 2. Schema compatibility is a hard invariant for managed integrations. 3. Once 0ETL requires resync, partial history is no longer trustworthy. 4. Rollback becomes destructive because incremental state cannot be preserved. Managed replication still enforces strict contract boundaries.
Follow-up 1. Why can't 0ETL resume after schema change?
Answer: 0ETL relies on a fixed contract between source and target. Once that contract is broken, Redshift cannot safely interpret ongoing changes. The system correctly forces a resync, but it does not protect previously replicated data from semantic drift.
Follow-up 2. When did rollback stop being safe here?
Answer: rollback stopped being safe the moment the source schema changed, while Redshift retained earlier state. From that point onward, no snapshot or resume could reconcile old data with the new contract.
Follow-up 3, curveball. What if the integration shows needs resync but data still looks correct?
Answer: that is the most dangerous state. Visual correctness only reflects historical slices. The integration is explicitly signaling that future correctness is impossible without re-ingestion, and continuing to trust the data compounds downstream risk.
Pro insider tip.
Zero ETL failures are not data bugs. They are contract violations. If you see a forced resync, assume all previously replicated data is suspect until proven otherwise.
Real-world incident during source to Redshift migration 130. Cross-cluster data share poisoning after producer rollback.
During an AWS Redshift migration, a producer cluster exposed data to a consumer cluster using Redshift data sharing. When a rollback was later executed on the producer due to migration failure, the consumer cluster retained and continued building analytics on the pre-rollback data. This created a permanent divergence where the consumer operated on poison state that no longer existed on the producer. Failure class, modern Redshift architecture, and native integration failures.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Producer Redshift cluster acting as data share provider during migration. 2. Consumer Redshift cluster actively querying and materializing shared data. 3. Data share mechanism live share without snapshot isolation. 4. Rollback action executed only on producer cluster. 5. BI tools connected to consumer cluster for downstream analytics. 6. Declared source of truth. Implicitly assumed producer rollback was authoritative. 7. Authority status split across clusters without revocation mechanism. Data shares propagate data, not rollback intent.
Incident analysis and root cause.
This failure occurred due to an incorrect rollback scope assumption. 1. Triggering action, rolling back the producer cluster without revoking or invalidating active data shares. 2. Why it appeared safe, producer state was restored successfully and validated in isolation. 3. What teams noticed first, consumer reports diverged from producer after rollback. 4. What teams did not notice, consumer had already persisted and transformed shared data. 5. How divergence accumulated, consumer continued operating on pre-rollback state indefinitely. 6. Missing invariant, rollback must include all data share consumers to preserve authority.
Why this failure is dangerous, hidden risk.
This failure is dangerous because rollback gives a false sense of safety. The producer appears clean, but consumers continue amplifying corrupted history. Detection latency is high because consumers are operationally healthy and queries succeed without errors.
What exactly broke? Consistency breakdown.
Authoritative and referential consistency are broken. Two clusters now answer the same business questions differently. If we roll back only data on the producer, this inconsistency remains because consumer clusters retain independent materialized state.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Are there active data share consumers? Yes, independent state exists. 2. Can consumer state be invalidated automatically? No manual intervention required. 3. Have consumers materialized shared data? Likely. 4. Is there a global rollback coordination mechanism? No. 5. Can authority be re-established cleanly? Only with destructive consumer reset. Producer rollback does not propagate across data shares.
Decision point, rollback versus forward fix.
Rollback is incomplete unless all consumer clusters are also reset or invalidated. Forward fix typically requires declaring the consumer data poisoned, rebuilding downstream artifacts, and enforcing stricter data share governance.
Rollback architecture, if executed.
A valid rollback requires revoking data shares, coordinating downtime across all consumers, discarding consumer-side materializations, and resharing only after producer integrity is restored. Partial rollback is forbidden because it guarantees split-brain analytics.
Code illustration and Redshift artifacts.
In this section, we will show 1. How active data share consumers can be identified from the producer. 2. Why consumer state persists independently of producer rollback. Data sharing breaks rollback locality. Here is Redshift SQL showing active data share consumers attached to a producer cluster. Disclaimer: Always test code in a non-production environment. This system view proves that consumer clusters remain attached even after producer rollback, confirming that rollback does not revoke shared state.
Containment and forward fix strategy.
Once data share poisoning is confirmed, containment must precede repair. 1. Revoke all active data shares immediately. 2. Declare consumer-derived data non-authoritative. 3. Invalidate or drop consumer-side materializations. 4. Reshare data only after producer state is fully validated. 5. Introduce rollback-aware governance for future data shares. Data sharing requires shared rollback boundaries.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Redshift data sharing propagates data, not rollback semantics. 2. Producer rollback does not invalidate consumer state automatically. 3. Consumers can permanently poison analytics if not coordinated. 4. Rollback must be treated as a multi-cluster operation. Rollback authority must span all consumers, not just producers.
Follow-up 1. Why doesn't producer rollback clean consumer data?
Answer: data sharing exposes live data, but does not enforce lifecycle coupling. Once consumers materialize or query shared data, they own that state independently. Rollback on the producer has no mechanism to retract what consumers already saw.
Follow-up 2. When did rollback stop being safe in this incident?
Answer: rollback stopped being safe the moment consumer clusters queried and persisted shared data. From that point on, producer state alone was no longer authoritative for analytics.
Follow-up 3. Curveball. What if consumers only ran select queries and stored nothing?
Answer: even pure reads leak truth. Dashboards, exports, and human decisions all persist beyond queries. Without explicit consumer invalidation, rollback still fails at the trust boundary.
Pro insider tip.
If you enable Redshift data sharing during migration, assume rollback is no longer local. Every consumer becomes part of your rollback blast radius.
Real-world incident during source to Redshift migration, 131. Result: cache poisoning after data repair.
During an AWS Redshift migration, incorrect data was identified and repaired using rollback or forward fix operations. Although underlying tables were corrected, BI dashboards continued showing stale and corrupted results because the Redshift leader node served cached query results computed before the fix. This created a false impression that rollback or repair had failed. Failure class: modern Redshift architecture and native integration failures.
System state before failure, very important.
At the moment the failure manifested, the system state was: 1. Redshift cluster data corrected via rollback or forward fix. 2. Leader node serving cached query results. 3. Result cache enabled and populated during the corrupted state. 4. BI tools rerunning identical queries after data repair. 5. Downstream consumers observing unchanged results post-fix. 6. Declared source of truth assumed Redshift after repair. 7. Authority status: correct at storage layer, misleading at query layer. Query results can outlive the data they were computed from.
Incident analysis and root cause.
This failure was caused by an execution layer assumption. 1. Triggering action rerunning identical BI queries immediately after data repair. 2. Why it appeared safe tables were validated and row-level checks passed. 3. What teams noticed first dashboards still showed prefix values. 4. What teams did not notice results were served entirely from cache. 5. How divergence accumulated cached results masked repaired data. 6. Missing invariant. Query cache must be invalidated after any corrective action.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it undermines confidence in corrective actions. Engineers believe rollback or forward fix failed, while in reality the storage layer is correct. Detection latency is high because query execution appears successful and fast.
What exactly broke? Consistency breakdown.
Execution time consistency is broken. The system presents results that no longer correspond to underlying data. If we roll back only data, this inconsistency remains because cached results bypass storage entirely.
Rollback viability checklist, go or no go.
Before rollback or repair validation, the architect must evaluate. 1. Was result cache populated during the failure window? Yes, cached corruption. 2. Were identical queries rerun post-fix? Yes, cache reused. 3. Is cache invalidation automatic? No, session and query dependent. 4. Can consumers distinguish cached versus fresh results? No. 5. Can authority be re-established without cache reset? No. Rollback validation fails if execution artifacts are ignored.
Decision point, rollback versus forward fix.
Rollback or forward fix may already be correct at the data layer. The real decision is whether to invalidate execution artifacts globally or continue debugging a problem that no longer exists in storage.
Rollback architecture, if executed.
Rollback architecture must include execution layer reset. This requires terminating active sessions, disabling or bypassing result cache, invalidating BI tool caches, and rerunning validation queries under guaranteed fresh execution conditions.
Code illustration and Redshift artifacts.
In this section, we will show 1. How result cache usage can be detected at query level. 2. How disabling result cache forces fresh execution. Correct data does not guarantee correct answers. Here is Redshift SQL showing detection of result cache usage. Disclaimer: always test code in a non-production environment. This column proves that query results were served from cache. A value of true confirms that storage-level fixes were bypassed during validation. Here is Redshift SQL forcing fresh execution by disabling result cache. Disclaimer: always test code in a non-production environment. Disabling the result cache forces Redshift to recompute query results from underlying tables, allowing accurate validation of rollback or forward fix.
Containment and forward fix strategy.
Once cache poisoning is identified, containment must be immediate. 1. Invalidate or bypass result cache for all validation sessions. 2. Force BI tools to refresh and drop cached query plans. 3. Rerun validation queries with cache explicitly disabled. 4. Document cache behavior as part of rollback runbooks. 5. Educate stakeholders that fast results can be wrong results. Execution artifacts must be treated as part of system state.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Redshift result cache conserves stale results after data repair. 2. Rollback validation must include execution layer checks. 3. Cached correctness illusions are common in analytics systems. 4. Disabling cache is sometimes the only way to prove truth. Correctness spans storage, execution, and consumption layers.
Follow-up 1. Why didn't fixing the data fix the dashboards?
Answer: because dashboards often rerun identical queries that are satisfied from result cache. The storage layer was correct, but execution reused stale results, masking the repair.
Follow-up 2. When did rollback stop appearing safe in this incident?
Answer: rollback appeared unsafe the moment cached results were trusted as validation output. From that point, engineers were debugging execution artifacts instead of actual data state.
Follow-up 3. Curveball. What if cache is disabled but BI still shows old numbers?
Answer: then the cache is outside Redshift. BI tools, middleware, or API layers may also cache results. Rollback validation must clear all consumer-side caches to restore trust.
Pro insider tip.
If rollback validation is fast, be suspicious. In Redshift, correctness often requires slower queries because fresh execution is the only truth.
Real-world incident during source to Redshift migration, 132. Table-level corruption forces full cluster restore.
During an AWS Redshift migration, corruption was detected in a single high-value table due to partial rollback and CDC inconsistencies. Engineers attempted a targeted restore, but because RA3 snapshots are cluster-level and monolithic, Redshift could not restore a single table in isolation. The incident escalated into a full cluster restore decision. Failure class: modern Redshift architecture and native integration failures.
System state before failure, very important.
At the moment the limitation was discovered, the system state was 1. Redshift cluster RA3 based with automated snapshots enabled. 2. Affected scope single corrupted table within an otherwise healthy cluster. 3. Snapshots available only at cluster granularity. 4. CDC pipeline already stopped to prevent further corruption. 5. BI tools actively querying unaffected tables. 6. Declared source of truth. Redshift for most domains. 7. Authority status partially valid, partially broken. Array-3 snapshots restore clusters, not tables.
Incident analysis and root cause.
This incident resulted from a restore granularity mismatch. 1. Triggering action attempting to roll back a single corrupted table. 2. Why it appeared safe, engineers assumed table-level restore parity with traditional databases. 3. What teams noticed first, no supported path to restore only one table. 4. What teams did not notice, snapshot architecture enforces cluster-level atomicity. 5. How divergence accumulated, healthy tables were forced into rollback consideration. 6. Missing invariant, restore granularity must match snapshot granularity.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it turns localized corruption into ecosystem-wide impact. A single table issue can trigger full cluster downtime, data loss in unaffected domains, and widespread trust erosion. Detection latency is low, but blast radius is extreme.
What exactly broke? Consistency breakdown.
Operational and authority consistency are broken. The system cannot isolate damage. If we roll back only data, this inconsistency remains because restore mechanics are coarser than the corruption scope.
Rollback viability checklist, go or no go.
Before any rollback decision, the architect must evaluate. 1. Is corruption limited to a single table? Yes. 2. Can Redshift restore that table alone? No. 3. Would cluster restore impact healthy domains? Yes. 4. Have downstream systems consumed healthy data? Yes. 5. Can authority be preserved post-restore? Unlikely. Granularity mismatch makes rollback destructive.
Decision point, rollback versus forward fix.
Rollback is technically possible but operationally catastrophic. Forward fix, involving table rebuilds and reconciliation, becomes the only viable path to preserve authority and limit blast radius.
Rollback architecture, if executed.
Rollback requires full cluster snapshot restore. This includes discarding all post-snapshot changes, repointing BI systems, invalidating downstream caches, reseeding CDC, and obtaining explicit governance approval due to cross-domain data loss.
Containment and forward fix strategy.
To avoid full cluster rollback, containment focuses on isolation. 1. Quarantine the corrupted table immediately. 2. Rebuild the table from source or trusted snapshots. 3. Validate joins and downstream dependencies explicitly. 4. Avoid snapshot restore unless corruption spreads. 5. Update runbooks to reflect restore granularity limits. Restore mechanics define blast radius, not data volume.
Interview framing, extremely important.
How would you explain this in an interview? Here are the key talking points. 1. Array-3 snapshots operate at cluster level only. 2. Single table corruption can force full restore decisions. 3. Rollback granularity must be designed, not assumed. 4. Forward fix often preserves more trust than rollback. Restore granularity is an architectural constraint.
Follow-up 1. Why couldn't you just restore one table?
Answer: because Array-3 snapshots capture the entire cluster state. Redshift does not support table-level snapshot restore, so isolation is impossible at restore time.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe once healthy domains were actively used post-snapshot. A full restore would invalidate trusted data unrelated to the failure.
Follow-up 3. Curveball. What if the business insists on rollback anyway?
Answer: then the decision is no longer technical. Engineers must document blast radius, data loss scope, and authority impact, and obtain explicit executive sign-off.
Pro insider tip.
In RA3, snapshot granularity is destiny. Design rollback strategy around restore mechanics, not around where corruption appears.
Category 24 wrap-up. When the platform itself becomes the failure boundary.
This category exposes a critical reality of modern Redshift architectures. Failures increasingly originate not from SQL or data modeling, but from managed integrations, hidden state, and platform-level abstractions. Zero ETL, data sharing, result cache, and Array-3 snapshot mechanics introduce opaque behaviors where rollback semantics no longer align with user expectations. In these scenarios, engineers lose fine-grained control, and correctness depends on understanding what the platform can and cannot rewind. Once these boundaries are crossed, recovery shifts from data repair to trust and authority management.
Final series conclusion. Rollback is an authority problem, not a data problem.
Across all categories in this series, a single pattern repeats. Migrations fail not because data moves incorrectly, but because authority, invariance, and system boundaries are misunderstood. Rollback is rarely a SQL operation. It is a system-wide reset that must restore data, meaning, and trust simultaneously. When any one of those is lost, rollback becomes unsafe or irrelevant. The real skill of a migration architect is not knowing how to copy data, but knowing exactly when rollback stops being possible, and having the discipline to act before that moment is crossed.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs in a single zip file, containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, system design. Required for your data engineer interviews jobs like data quality analyst jobs, data governance analyst jobs, AWS Python data engineer jobs, AWS Redshift database administrator DBA jobs, AWS Glue ETL developer jobs, AWS data engineer jobs, cloud data engineer jobs, data architect jobs, DataOps engineer jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based questions and answers, real-world problem solving, interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people also for your interviews. You people can download all 6 PDFs in a single zip file from below given links.
For more exciting tips, tricks, and more importantly, for valuable insights of interviews, please share, like, and subscribe to my channel. It has a lot of valuable information about various insights of interviews. It has a wide range of real-world portfolio projects of various technologies for interviews, and it has wide range of most asked interview questions and answers of various technologies like data science, SAP, AWS, DevOps, and full-stack web development, and more. That will be useful during interviews. It has a wide range of most asked interview questions and answers and real-world portfolio projects of various technologies for freshers, for 2 to 3 years, experienced candidates, and for 5 or above years, experienced candidates to test their skills by knowing most asked interview questions and make themselves ready for interviews.